The growth of biological thought. Diversity, evolution, and inheritance. Ernst Mayr. For Gretel. Much of modern biology, particularly the various controversies between different schools of thought, cannot be fully understood without a knowledge of the historical background of the problems. Whenever I made this point to my students, they would ask me in what book they could read up on these matters. To my embarrassment, I had to admit that none of the published volumes filled this need. To be sure, there is much literature on the lives of biologists and their discoveries, but these writings are invariably inadequate as far as an analysis of the major problems of biology are concerned or as a history of concepts and ideas in biology. While some of the histories of individual biological disciplines, like genetics and physiology, are indeed histories of ideas, there is nothing available that covers biology as a whole. To fill this gap in the literature is the object of this work. This volume is not, and this must be stressed, a history of biology, and it is not intended to displace existing histories of biology, such as that of Nordenskjöld. The emphasis is on the background and the development of the ideas dominating modern biology. In other words, it is a developmental, not a purely descriptive, history. Such a treatment justifies, indeed necessitates, the neglect of certain temporary developments in biology that left no impact on the subsequent history of ideas. When I first conceived the plan to write a history of ideas in biology, the goal seemed impossibly remote. The first years, 1970-1975, were devoted to reading, note-taking, and the preparation of a first draft. Soon it became obvious that the subject was too vast for a single volume, and I decided to prepare first a volume on the biology of ultimate, evolutionary, causations. But even this limited objective is a hopelessly vast undertaking. If I have been successful at all, it is because I have myself done a considerable amount of research in most areas covered by this volume. This means that I was already reasonably familiar with the problems and some of the literature of the areas involved. I hope to deal with the biology of proximate, functional, causations in a later volume that will cover physiology in all of its aspects, developmental biology and neurobiology. When a biological discipline, for instance genetics, deals both with ultimate and proximate causations, only the ultimate causations are treated in the present volume. There are two areas of biology that might have been, at least in part, but were not included in this volume, the conceptual history of ecology and that of behavioral biology, particularly ethology. Fortunately, this omission will not be quite as painful as it might otherwise be, because several volumes by other authors dealing with the history of ecology and ethology are now in active preparation. The professional historian is not likely to learn much from chapters 1 and 3, in fact he may consider them somewhat amateurish. I have added these two chapters for the benefit of non-historians, believing that it will help them to see the purely scientific developments of the other chapters with a deepened perception. I owe an immense debt of gratitude to numerous individuals and institutions. Peter Ashlock, F. J. Ayala, John Beatty, Walter Bach, Robert Brandon, Arthur Kane, Fred Churchill, Bill Coleman, Lindley Darden, Max Stilbriak, Michael Gazellin, John Green, Carl Gustav Hempel, Sandra Herbert, John Hodge, David Hull, David Laser, E. B. Lewis, Robert Merton, J. A. Moore, Ron Munson, Edward Reed, Philip Sloan, Frank Soloway, Mary Williams, and others have read drafts of various chapters, have pointed out errors and omissions, and have made numerous constructive suggestions. I did not always follow their advice and am thus solely responsible for remaining errors and deficiencies. To P. Axe, Muriel Blaisdell, and B. Werner I am indebted for useful factual information. Gillian Brown, Cheryl Bergdorf, Sally Loth, Agnes I. Martin, Maureen Sepkowski, and Charlotte Ward have typed innumerable drafts and helped with the bibliography. Walter Borowski not only typed preliminary versions but also the entire final copy of the manuscript and of the bibliography and prepared the manuscript of the index. Randy Bird contributed to filling gaps in the references. Susan Wallace edited the entire manuscript and in the process eliminated numerous inconsistencies, redundancies, and stylistic infelicities. All of these people materially contributed to the quality of the final product. It is obvious how great a debt of gratitude I owe to them. The Museum of Comparative Zoology, through the courtesy of its director, Professor A. W. Crompton, has provided office space, secretarial help, and library facilities, even after my retirement. Research periods at the Institute for Advanced Study, Princeton, Spring 1970, at the Library of the Max Planck Institute of Biology, Tübingen, 1970, a senior fellowship of the Alexander von Humboldt Foundation, Würzburg, 1977, a fellowship awarded by the Rockefeller Foundation, Villa Serbelloni, Bellagio, 1977, and a grant, No. GS 32176, by the National Science Foundation have greatly facilitated my work. Whenever secretarial help was not available, my wife took over, transcribed dictations, excerpted literature, and aided the work on the manuscript in countless ways. It is impossible to acknowledge appropriately her inestimable contributions to this volume. Ernst Mayr. Museum of Comparative Zoology. Harvard University. Contents. 1. Introduction, How to Write History of Biology Subjectivity and Bias. 9. Why Study the History of Biology. 18. 2. The Place of Biology in the Sciences and its Conceptual Structure. The Nature of Science. 21. Method in Science. 25. The Position of Biology within the Sciences. 32. How and why is biology different? 36. Special characteristics of living organisms. 51. Reduction and biology. 59. Emergence. 63. The conceptual structure of biology. 67. A new philosophy of biology. 73. 3. The changing intellectual milieu of biology. Antiquity. 84. The Christian world picture. 91. The Renaissance. 94. The discovery of diversity. 99. Biology in the Enlightenment. 107. The rise of science from the 17th to the 19th century. 109. Divisive developments in the 19th century. 112. Biology in the 20th century. 120. Major periods in the history of biology. 125. Biology and philosophy. 128. Biology today. 131. Part I. Diversity of life. 4. Macrotaxonomy. The science of classifying. Aristotle. 149. The classification of plants by the ancients and the herbalists. 154. Downward classification by logical division. 158. Pre-Linnaean zoologists. 166. Carl Linnaeus. 171. Buffon. 180. A new start in animal classification. 182. Taxonomic characters. 185. Upward classification by empirical grouping. 190. Transition period, 1758 to 1859, 195. Hierarchical classifications. 205. 5. Grouping according to common ancestry. The decline of macrotaxonomic research. 217. Numerical phonetics. 221. Cladistics. 226. The traditional or evolutionary methodology. 233. New taxonomic characters. 235. Facilitation of contents. Information retrieval. 239. The study of diversity. 245. 6. Microtaxonomy. The science of species. Early species concepts. 254. The essentialist species concept. 256. The nominalistic species concept. 263. Darwin's species concept. 265. The rise of the biological species concept. 270. Applying the biological species concept to multidimensional species taxa. 286. The significance of species in biology. 295. 2. Evolution. 7. Origins without evolution. The coming of evolutionism. 309. The French Enlightenment. 322. 8. Evolution before Darwin. Lamarck. 343. Cuvier. 363. England. 371. Lyell and Uniformitarian. 375. Germany. 387. 9 Charles Darwin Darwin and Evolution 400 Alfred Russel Wallace 417 The publication of The Origin 423 Darwin's Evidence for Evolution and Common Descent and the Natural System 436 Common Descent and Geographical Distribution 439 Morphology as Evidence for Evolution and Common Descent 455 Embryology as Evidence for Evolution and Common Descent 469 The Causation of Evolution. Natural selection The major components of the theory of natural selection 481 The origin of the concept of natural selection 488 The impact of the Darwinian revolution 501 The resistance to natural selection 510 Alternate evolutionary theories 525 Diversity and synthesis of evolutionary thought The growing split among the evolutionists 540 Advances in evolutionary genetics 550 Advances in evolutionary systematics 559 The evolutionary synthesis 566 Post-synthesis developments Molecular biology 574 Natural selection 585 Unresolved issues in natural selection 591 Modes of speciation 600 Macroevolution 607 The evolution of man 620 Evolution in modern thought 626 Part 3 Variation and its inheritance 14 Early theories and breeding experiments Theories of inheritance among the ancients 635 Mendel's forerunners 641 15 Germ cells, vehicles of heredity The Schwann-Leiden cell theory 655 The meaning of sex and fertilization 658 Chromosomes and their role 673 16 The nature of inheritance Darwin and variation 681 August Weismann 698 Hugo de Vries 707 Gregor Mendel 710 17 The flowering of Mendelian genetics The rediscoverers of Mendel 727 The classical period of Mendelian genetics 731 The origin of new variation, mutation, 738 The emergence of modern genetics 744 The Sutton-Boveri chromosome theory 747 Sex determination 750 Morgan and the fly room 752 Meiosis 761 Morgan and the chromosome theory 769 18 Theories of the gene Competing theories of inheritance 784 The Mendelian explanation of continuous variation 790 19 The chemical basis of inheritance The discovery of the double helix 821 Genetics in modern thought 826 20 Epilogue Tour de Science of Science Scientists and the Scientific Milieu 830 The maturation of theories and concepts 839 Impediments to the maturation of theories and concepts 843 The sciences and the external milieu 848 Progress in science 856 1 Introduction, How to write history of biology. Anything that changes in time has, by definition, a history the universe, countries, dynasties, art, and philosophy, and ideas. Science also, ever since its emergence from myths and early philosophies, has experienced a steady historical change and is thus a legitimate subject for the historian. Because the essence of science is the continuing process of problem solving in the quest for an understanding of the world in which we live, a history of science is first a history of the problems of science and their solution or attempted solutions. But it is also a history of the development of the principles that form the conceptual framework of science. Because the great controversies of the past often reach into modern science, many current arguments cannot be fully understood unless one understands their history. Written histories, like science itself, are constantly in need of revision. Erroneous interpretations of an earlier author eventually become myths, accepted without question and carried forward from generation to generation. A particular endeavor of mine has been to expose and eliminate as many of these myths as possible without, I hope, creating too many new ones. The main reason, however, why histories are in constant need of revision is that at any given time they merely reflect the present state of undering they depend on how the author interpreted the current zeitgeist of biology and on his own conceptual framework and background. Thus, by necessity the writing of history is subjective and ephemeral. When we compare published histories of science, it becomes at once apparent that different historians have quite different concepts of science and also of history writing. Ultimately all of them attempt to portray the increase in scientific knowledge and the changes in interpretive concepts. But not all historians of science have attempted to answer the 6 principal questions that must be addressed by anyone who wants to describe the progress of science critically and comprehensively: who, when, where, what, how, and why. On the basis of the author's selection from among these questions, most of the histories known to me can be classified as follows: cf. Passmore, 1965, 857-861, though it must be recognized that nearly all histories are a combination of the various approaches or strategies. Lexicographic histories. These are more or less descriptive histories with a strong emphasis on the questions what, when, and where. What were the principal scientific activities at any given past period? What were the centers of science where the leading scientists were working, and how did they shift in the course of time? No one will argue about the value of such histories. A correct presentation of the true facts is indispensable because much of the traditional history of science, and its standard texts, is encrusted with myths and spurious anecdotes. Yet, a purely descriptive history provides only part of the story. Chronological histories. A consideration of time sequences is crucial to any kind of history writing. Indeed, one can even make chronology the primary organizing criterion, and some authors have done so. They have asked, for instance, what happened in biology between 1749 and 1789, or between 1789 and 1830. Chronological histories present a sequence of cross-sections through the entirety of developments in all branches of biology. This is not only a legitimate but indeed a most revealing approach. It creates a feeling for the zeitgeist and the totality of contemporary influences. It permits one to investigate how developments in other branches of science have influenced biology, and how even within biology advances made by the experimentalists have affected the thinking of the naturalists, and vice versa. The understanding of many problems in the development of biology is greatly facilitated by this chronological approach. However, it suffers from the drawback that each major scientific problem is atomized. Biographical histories. The endeavor in these volumes is to portray the progress of science through the lives of leading scientists. This approach is also legitimate, since science is made by people and the impact of individual scientists like Newton, Darwin, and Mendel has often been of quasi-revolutionary nature. However, this approach shares with the purely chronological approach one very serious weakness: it atomizes each major scientific problem. The species problem, for example, will have to be discussed under Plato, Aristotle, Caesalpino, and the herbalists, Buffon, Linnaeus, Cuvier, Darwin, Weismann, Nageli, De Vries, Jordan, Morgan, Huxley, Mayr, Simpson, and so on. All of these discussions of the same problem are separated from each other by many pages, if not chapters. Cultural and sociological histories. This approach stresses the point that science is a form of human endeavor and is therefore inseparable from the intellectual and institutional milieu of the period. This view is particularly fascinating to those who come to the history of science from the field of general history. They might ask such questions as why was British science from 1700 to 1850 so strongly experimental and mechanical while contemporary French science tended to be mathematical and rationalistic? Why did natural theology dominate science for 75 years longer in Britain than on the continent? To what extent was Darwin's theory of natural selection a child of the Industrial Revolution? Even if the historian of biology chooses not to adopt this approach, he must carefully study the cultural and intellectual milieu of a scientist if he wants to determine the causes for the rise of new concepts. This is of evident importance in the present work, since one of the major objectives of my treatment is to investigate the reasons for the changes in biological theories. What enabled one investigator to make a discovery that has escaped his contemporaries? Why did he reject the traditional interpretations and advance a new one? From where did he get the inspiration for his new approach? These are the kind of questions that need to be asked. Most early histories of science, particularly those of special scientific disciplines, were written by working scientists, who took it for granted that the intellectual impetus for scientific change came from within the field itself, internal influences. Later on, when the history of science became more professionalized and historians and sociologists began to analyze the progress of scientific thought, they tended to stress the influence of the general intellectual, cultural, and social milieu of the period, external influences. No one would want to doubt that both kinds of influences exist, but there is a great deal of disagreement on their relative importance, particularly with reference to specific developments, such as Darwin's theory of natural selection. Often it is rather difficult even to distinguish external from internal factors. The great chain of being, scala naturae, was a philosophical concept which clearly had an impact on concept formation in the case of Lamarck and other early evolutionists. Yet, Aristotle had developed this concept on the basis of empirical observations of organisms. On the other hand, universally adopted ideologies are among the most uncontroversial of external factors. The Christian dogma of creationism and the argument from design coming from natural theology dominated biological thinking for centuries. Essentialism, from Plato, is another all-powerful ideology. Interestingly, its displacement by Darwin was largely due to the observations of animal breeders and taxonomists, that is, to internal factors. External factors do not necessarily originate in religion, philosophy, cultural life, or politics, but as far as biology is concerned they may originate in a different science. The extreme physicalism, including determinism and extreme reductionism, that was prevalent in Western thinking after the scientific revolution strongly influenced theory formation in biology for several centuries, often quite adversely, as is now evident. Scholastic logic, to cite another example, dominated taxonomic method from Caesalpino to Linnaeus. These examples, to which many others could be added, document without doubt the importance of external influences on theory formation in biology. They will be analyzed in full detail in the relevant chapters. It is important to realize that external factors influence science in two entirely different ways. They may either affect the overall level of scientific activity at a given place at a given time, or they may affect or even give rise to a particular scientific theory. All too often in the past these two aspects have been lumped together, resulting in much controversy over the relative importance of external versus internal factors. The effect of environmental conditions on the level of scientific activities has been appreciated as long as there has been a history of science. It has been speculated endlessly as to why the Greeks had such an interest in scientific questions and why there was a revival of science during the Renaissance. What was the effect of Protestantism on science? Merton, 1938. Why did science during the 19th century flourish to such an extent in Germany? Sometimes important external factors can be specified. For instance, as Mayr, 1896–1914, has pointed out, the replacement in 1694 of Latin by German at Halle University, and the founding in 1737 of a university at Göttingen in which Wissenschaft played an important role. Institutional changes of all sorts, including the founding of the Royal Society, political events such as wars and the launching of Sputnik, as well as technological needs have had either a stimulating or a depressing effect on the level of scientific activity. Yet, this still leaves open the highly controversial question of to what extent such external factors have favored or inhibited specific scientific theories. In recent years, Marxist historiographers in particular have voiced the thesis that social ideologies influence the ideas of a scientist, and that the history of science as practiced until now has totally neglected the social context. The result, they believe, has been a bourgeois history of science, which is quite different from what a proletarian history of science would be. What is needed instead, they say, is radical history. This demand ultimately goes back to Marx's claim that ruling ideas cannot be separated from ruling classes. Therefore, bourgeois history of science will be quite different from proletarian history of science. However, the thesis that there is a proletarian way to write the history of science is in conflict with three sets of facts. First, the masses do not establish scientific theories that are different from those of the scientific class. If there is any difference, it is that the common man often retains ideas long after they have been discarded by scientists. Second, there is high social mobility among scientists, with from 1/4 to 1/3 of each new crop of scientists coming from the lower socio-economic classes. Third, birth order within a social class tends to be far more important in determining those who originate rebellious new ideas than does membership in a particular class. Soloway, M.S. All of this is in conflict with the thesis that the socio-economic environment has a dominant impact on the birth of particular new scientific ideas and concepts. The burden of proof is clearly on those who make such claims, and so far they have failed to supply any concrete evidence whatsoever. See Chapter 11. Of course no one lives in a vacuum, and anyone who reads voraciously, as for example Darwin did after his return from the voyage of the Beagle, is bound to be influenced by his reading. Schweber, 1977. Darwin's notebooks are ample evidence for the correctness of this inference. But, as Hodge, 1974, points out, this by itself does not prove the thesis of the Marxists that Darwin and Wallace were extending the laissez-faire capitalist ethos from society to all nature. Up to now it appears that the influence of social factors on the development of specific biological advances has been negligible. The reverse, of course, is not true. But the study of the impact of science on social theory, social institutions, and politics belongs to the domains of history, sociology, and political science, and not to that of the history of science. I agree with Alexander Coir, 1965, 856, that it is futile to deduce the existence of certain scientists and sciences from their environment. Athens does not explain Plato any more than Syracuse explains Archimedes or Florence Galileo. To look for explanations along these lines is an entirely futile enterprise, as futile as trying to predict the future evolution of science or of the sciences as a function of the structure of the social context. Thomas Kuhn, 1971, 280, has likewise observed that the historian seems invariably to give excessive emphasis to the role of the surrounding climate of extra-scientific ideas. See also Passmore, 1965. Problematic histories. More than 100 years ago Lord Acton advised historians, study problems, not periods. This advice is particularly appropriate for the history of biology, which is characterized by the longevity of its scientific problems. Most of the great controversies of the 19th and early 20th centuries relate to problems already known to Aristotle. Such controversies endure from generation to generation, and from century to century. They are processes, not events, and can be fully understood only through a historical treatment. As R.G. Collingwood said of history, 1939, 98, it is concerned not with events but with processes. Processes are things which do not begin and end but turn into one another. This must be stressed particularly in the face of the static views of the logical positivists who thought that logical structure was the real problem of science. The philosophy of science is conceived by them primarily as a careful and detailed analysis of the logical structure and the conceptual problems of contemporary science. Lawton, 1968. Actually, most scientific problems are far better understood by studying their history than their logic. However, it must be remembered that problematic history does not replace chronological history. The two approaches are complementary. In the problematic approach, the chief emphasis is placed on the history of attempts to solve problems, for instance, the nature of fertilization or the direction-giving factor in evolution. The history not only of the successful but also of the unsuccessful attempts to solve these problems is presented. In the treatment of the major controversies in the field, an endeavor is made to analyze the ideologies, or dogmas, as well as the particular evidence by which the adversaries supported their opposing theories. In problematic history, the emphasis is on the working scientist and his conceptual world. What were the scientific problems of his time? What were the conceptual and technical tools available to him in his quest for a solution? What were the methods he could employ? What prevalent ideas of his period directed his research and influenced his decisions? Questions of this nature dominate the approach in problematic history. I have chosen this approach for the present book. The reader should be aware of the fact that this is not a traditional history of science. Owing to its concentration on the history of scientific problems and concepts, it slights by necessity the biographical and sociological aspects of the history of biology. It should therefore be used in conjunction with a general history of biology, like Nordensk-Schold, 1926, with the Dictionary of Scientific Biography, and with available histories of special areas of biology. Since I am a biologist, I am better qualified to write a history of the problems and concepts of biology than a biographical or sociological history. It is the essence of problematic history to ask why. Why was it in England that the theory of natural selection was developed, in fact independently 4 times? Why did genuine population genetics arise in Russia? Why were Battison's explanatory attempts in genetics almost uniformly wrong? Why did Correns get distracted into all sorts of peripheral problems and therefore contributed so little to major advances in genetics after 1900? Why did the Morgan School devote their efforts for so many years to reinforcing the already well-established chromosome theory of inheritance, instead of opening up new frontiers? Why were De Vries and Johansen so much less successful in the evolutionary application of their findings than in their straight genetic work? Attempts to answer such questions require the collecting and scrutiny of much evidence, and this almost invariably leads to new insights even if the respective question turns out to have been invalid. Answers to why questions are inevitably somewhat speculative and subjective, but they force one into the ordering of observations and into the constant testing of one's conclusions consistent with the hypothetico-deductive method. Now that the legitimacy of why questions has been established even for scientific research, particularly in evolutionary biology, there should be even less question about the legitimacy of such questions in the writing of history. At the worst, the detailed analysis necessitated by such a question may establish that the assumptions underlying the question were wrong. Even this would advance our understanding. Throughout this volume I have endeavored to carry the analysis of each problem as far as possible and to dissect heterogeneous theories and concepts into their individual components. Not all historians have been aware how complex many biological concepts are in fact, how complex the structure of biology as a whole is. As a consequence, some exceedingly confused accounts of the history of biology have been published by authors who did not understand that there are 2 biologies, that of functional and that of evolutionary causations. Similarly, anyone who writes about Darwin's theory of evolution in the singular, without segregating the theories of gradual evolution, common descent, speciation, and the mechanism of natural selection, will be quite unable to discuss the subject competently. Most major theories of biology were, when first proposed, such composites. Their history and their impact cannot be understood unless the various components are separated and studied independently. They often belong to very different conceptual lineages. It is my conviction that one cannot understand the growth of biological thought unless one understands the thought structure of biology. For this reason I have attempted to present the insights and concepts of biology in considerable detail. This was particularly necessary in the treatment of diversity, Part I, because no other adequate treatment or conceptual framework of the science of diversity is available. I am aware of the danger that some critic might exclaim, but this is a textbook of biology, historically arranged. Perhaps this is what a problematical history of biology ought to be. Perhaps the greatest difficulty any conceptual history of biology must cope with is the longevity of the controversies. Many of the current controversies had their origin generations or even centuries ago, some indeed going all the way back to the Greeks. A more or less timeless presentation of the issues is more constructive in such cases than a chronological one. I have tried to make each of the major sections of this volume, diversity, evolution, inheritance, a self-contained unit. A similar separation is attempted for each separate problem within these three major areas. This leads to a certain amount of overlap and redundancy because there are numerous cross-connections between different topics, and each topical strand will pass through the same sequence of time-dependent intellectual milieus. I have made a special effort to strike a balance between a certain amount of unavoidable duplication and convenient cross-references to other chapters. Subjectivity and bias. A well-known Soviet theoretician of Marxism has once referred to my writings as pure dialectical materialism. I am not a Marxist and I do not know the latest definition of dialectical materialism, but I do admit that I share some of Engels' anti-reductionist views, as stated in his Anti-Die-Ring, and that I am greatly attracted by Hegel's scheme of thesis-antithesis-synthesis. Furthermore, I believe that an antithesis is most easily provoked by a categorical statement of a thesis, and that the issue is most readily resolved by such a confrontation of an uncompromising thesis and antithesis, and that the ultimate synthesis is thus most quickly achieved. Many examples for this can be found in the history of biology. This view has dominated my presentation. Whenever possible, I have attempted a synthesis of opposing viewpoints, unless one of them is clearly in error. Where the situation is quite unresolved, I have described the opposing viewpoints in categorical, sometimes almost one-sided, terms in order to provoke a rejoinder, if such is justified. Because I hate beating around the bush, I have sometimes been called dogmatic. I think this is the wrong epithet for my attitude. A dogmatic person insists on being right, regardless of opposing evidence. This has never been my attitude and, indeed, I pride myself on having changed my mind on frequent occasions. However, it is true that my tactic is to make sweeping categorical statements. Whether or not this is a fault, in the free world of the interchange of scientific ideas, is debatable. My own feeling is that it leads more quickly to the ultimate solution of scientific problems than a cautious sitting on the fence. Indeed, I agree with Passmore, 1965, that histories should even be polemical. Such histories will arouse contradiction and they will challenge the reader to come up with a refutation. By a dialectical process this will speed up a synthesis of perspective. The unambiguous adoption of a definite viewpoint should not be confused with subjectivity. The traditional admonition to historians has always been to be strictly objective. This ideal was well expressed by the great historian Leopold von Ranke when he said the historian should show how it really was. History was envisioned by him as the accurate reconstruction of a series of past events. Such objectivity is entirely appropriate when one attempts to answer who, what, when, and where, although it must be pointed out that even in presenting facts the historian is subjective because he uses value judgments when sorting the facts and is selective when deciding which ones to accept and how to relate them to one another. Subjectivity enters at every stage of history writing, especially when one is seeking explanations and asks why, as is necessary in problematic history. One cannot arrive at explanations without using one's own personal judgment, and this is inevitably subjective. A subjective treatment is usually far more stimulating than a coldly objective one because it has a greater heuristic value. To what extent is subjectivity permissible and where does it become bias? Roddy, 1907-08, for instance, had such a strong anti-Darwinian bias that he was not even able to present the Darwinian theory adequately. This clearly went too far. Subjectivity is apt to become bias whenever the evaluation of scientists of former periods is involved. Here historians tend to go either to one or to the other extreme. Either they adopt a strictly retrospective approach in which the past is evaluated entirely in the light of present knowledge and understanding, or else they suppress hindsight completely and describe past events strictly in terms of the thinking at that period. It seems to me that neither approach is entirely satisfactory. A better procedure would be to combine the best aspects of both approaches. This would first attempt to reconstruct the intellectual milieu of the period as faithfully as possible. But it would not be satisfactory to treat past controversies strictly in terms of the information available at the time. This would leave such controversies as unresolved and opaque as they were when they took place. Instead, modern knowledge should be used whenever this helps in the understanding of past difficulties. Only such an approach will enable us to determine the reasons for the controversy and for the failure to resolve it. Was it a semantic difficulty, for example, the use of the same word in different meanings, or a conceptual disagreement, such as essentialist versus population thinking, or an outright error, like the confusion of ultimate and proximate causes? A study of past controversies is particularly illuminating when the arguments and opposing viewpoints are analyzed in terms of our present knowledge. Semantic problems are particularly bothersome because they are so often undiscovered. The Greeks, for instance, had a very limited technical vocabulary and often used the same term for rather different things or concepts. Both Plato and Aristotle used the term eidos, and Aristotle at least used it in several senses, but the major meaning of the term is totally different in the two authors. Plato was an essentialist, but Aristotle was essentialist only to a very limited extent. Baum, 1980. Aristotle used the term genus occasionally as a collective noun, corresponding to the taxonomist's genus, but far more often in the sense of species. When Aristotle was rediscovered in the late Middle Ages and translated into Latin and Western European languages, his terms were translated in equivalent terms available in medieval dictionaries. These misleading translations have had an unfortunate influence on our understanding of Aristotle's thought. Some modern authors have had the courage to use modern terms to reveal Aristotle's thought, terms he would have quite likely used if he were living today. I am thinking of Delbriac's use of genetic program to make clear Aristotle's intention when using eidos in the description of individual development. Likewise, one should use teleonomy, instead of teleology, when Aristotle discusses goal-directedness controlled by an eidos program. This is not anachronistic but simply a way of making clear what an ancient author thought, by using a terminology that is unambiguous for a modern reader. It would, however, be quite inappropriate to use modern hindsight for value judgments. Lamarck, for instance, was not nearly as wrong as he seems to those familiar with selectionism and Mendelian genetics, when judged in terms of the facts known to him and of the ideas prevailing at his period. The phrase Whig interpretation of history was introduced by the historian Herbert T. Butterfield, 1931, to characterize the habit of some English constitutional historians to see their subject as a progressive broadening of human rights, in which good forward-looking liberals were continuously struggling with the backward-looking conservatives. Butterfield later, 1957, applied the term Whiggish to that kind of history of science in which every scientist is judged by the extent of his contribution toward the establishment of our current interpretation of science. Instead of evaluating a scientist in terms of the intellectual milieu in which he was active, he is evaluated strictly in terms of current concepts. The complete context of problems and concepts in which the earlier scientists had worked is ignored in this approach. The history of biology is rich in such biased Whig interpretations. Whenever there is a scientific controversy, the views of the losing side are almost invariably later misrepresented by the victors. Examples are the treatment of Buffon by the Linnaeans, of Lamarck by the Cuverians, of Linnaeus by the Darwinians, of the biometricians by the Mendelians, and so forth. The historian of biology must attempt to present a better balanced account. Many, now rejected theories, like the inheritance of acquired characters espoused by Lamarck, seemed formerly so consistent with the known facts that authors should not be criticized for having adopted such prevailing theories even if they have since been shown to be wrong. Almost always those who held an erroneous theory had seemingly valid reasons for doing so. They were trying to emphasize something that was neglected by their opponents. The preformationists, for instance, attempted to stress something which was later resurrected as the genetic program. The biometric Ians upheld Darwin's views of gradual evolution against the saltationism of the Mendelians. In both instances, correct ideas were lumped together with erroneous ones and went down together with the errors. In my case, I tend to pay special attention to underdogs, both persons and theories, because in the past they have often been treated unfairly or at least inadequately. The path of science is never straight. There are always competing theories, and most of the attention of a period may be directed toward a side issue which eventually turns out to be a dead end. These developments often illuminate the zeitgeist of a period more successfully than the straightforward advances of science. Regrettably, lack of space precludes an adequate treatment of many of these developments. No history can afford to deal with every lost cause and every deviation. There are, however, exceptions. Some of the failures or errors of the past very suitably reveal aspects of contemporary thinking which we might otherwise miss. Maclay's and Swainson's Quinarianism, for instance, which was totally eclipsed by The Origin of Species, represented a sincere endeavor to reconcile the seeming chaotic diversity of nature with the then prevailing conviction that there had to be some higher order in nature. It also reveals the still powerful hold of the old myth that all order in the world is ultimately numerical. As ill-conceived and ephemeral as the theory of Quinarianism was, it nevertheless contributes to our understanding of the thinking of its period. The same can be said of almost any theory or school of the past that is no longer considered valid. The interests of a historian necessarily influence his decision as to which subjects to treat in detail and which others in a more cursory fashion. I tend to agree with Schuster, who said in The Progress of Physics, 1911, "I prefer to be frankly subjective, and warn you beforehand that my account will be fragmentary, and to a great extent reminiscent of those aspects which have come under my own personal view." Historians versus scientists. Two groups of scholars with entirely different viewpoints and backgrounds. Historians and scientists have claimed the history of science as their own. Their respective contributions are somewhat different, dictated by differences in their interests and competence. A scientist tends to select for analysis and discussion rather different problems from a historian or sociologist. For instance, in recent accounts of evolution by various evolutionists, H. Spencer has hardly received any attention. There are good reasons for this neglect. Not only was Spencer vague and confused, but the ideas he championed were those of others and already obsolete when taken up by Spencer. That Spencer's borrowed ideas were quite popular and influential, as far as the general public was concerned, is without question true, but it is not the task of the scientist-historian to trespass in the domain of the sociologist. Biologists usually lack the competence to deal with social history. On the other hand, it would be just as ridiculous to demand that a social historian present a competent analysis of the scientific issues. The history of science derives inspiration, information, and methodological assistance both from science and from history and, in turn, contributes by its findings to both fields. There are valid reasons for the interest of both historians and scientists in the history of science. The Greeks had no science, as we now define it, and whatever science they had was practiced by philosophers and physicians. After the Middle Ages there was a continuing trend of emancipation of science from philosophy and from the general zeitgeist. In the Renaissance period and during the 18th century, scientific beliefs were strongly influenced by the scientist's attitude toward religion and philosophy. A Cartesian, an Orthodox Christian, or a deist would inevitably have different ideas on cosmology, generation, and all aspects of the interpretation of life, matter, and origins. Nothing signaled the emancipation of science from religion and philosophy more definitely than the Darwinian revolution. Since that time it has become quite impossible to say by looking at an author's scientific publications whether he was a devout Christian or an atheist. Except for a few fundamentalists, this is true even for the writings of biologists on the subject of evolution. This trend toward the emancipation of science had a considerable effect on the writing of the history of science. The farther back we go in time, the less important becomes the store of scientific knowledge of the period and the more important the general intellectual atmosphere. As far as biology is concerned, it is not until after about 1740 that the scientific problems begin to separate themselves from the general intellectual controversies of the period. There is no question that historians are particularly well qualified to deal with the earlier time span in the history of biology. However, the 19th and 20th centuries' history of special biological disciplines was entirely dominated by scientists, until its rather recent professionalization. This is well illustrated by such recent histories of special areas in biology, as those of Dunn, Stubb, and Sturtevant in genetics, of Fruton, Edsel, and Lester in biochemistry, of Needham and Oppenheimer in embryology, of Baker and Hughes in cytology, of Stresemann in ornithology, to mention only a few names in the extensive literature. They demonstrate the qualification of scientists for historical research. The bias of the physical scientists. Most general histories of science have been written by historians of physics who have never quite gotten over the parochial attitude that anything that is not applicable to physics is not science. Physical scientists tend to rate biologists on a scale of values depending on the extent to which each biologist has used laws, measurements, experiments, and other aspects of scientific research that are rated highly in the physical sciences. As a result, the judgments on fields of biology made by certain historians of the physical sciences that one may find in that literature are so ludicrous that one can only smile. For example, knowing that Darwin developed his theory of evolution largely on the basis of his observations as a naturalist, one can only marvel at this statement, made by a well-known historian of Newton: the naturalist is indeed a trained observer, but his observations differ from those of a gamekeeper only in degree, not in kind. His sole esoteric qualification is familiarity with systematic nomenclature. This kind of biased physicalist thinking is entirely out of place in the study of evolutionary biology, as we shall see in Chapter 2. Theory formation and its history in evolutionary and systematic biology require a radically different approach, an approach which is in some ways more similar to that adopted by a historian of archaeology or by an interpreter of modern world history. Other biases. Not just the physicist but every specialist, quite naturally, considers his particular field of research to be the most interesting and its methods to be the most productive. As a result, often an invidious kind of chauvinism exists among fields, and even within a field such as biology. It is chauvinism, for instance, when Hartmann, 1947, allotted 98% of his large general biology to physiological biology and only 2% to evolutionary biology. It is chauvinism when certain historians ascribe the occurrence of the evolutionary synthesis entirely to the findings of genetics, completely ignoring the contribution made by systematics, paleontology, and other branches of evolutionary biology. Mayr and Provini, 1980. There is sometimes also a national chauvinism within a field which tends to exaggerate or even to misrepresent the importance of the scientists from the writer's own country and to belittle or ignore scientists of other nations. This is not necessarily due to misplaced patriotism but is often the result of an inability to read the languages in which important contributions by scientists of other countries have been published. In my own work I am keenly aware of the probability of bias introduced by my inability to read Slavic languages and Japanese. Pitfalls and difficulties. The greatest difficulty in the endeavor to identify the vast number of problems of biology and to reconstruct the development of its conceptual framework is the vast amount of material to be studied. This consists, in principle, of the entire store of knowledge of biology, including all books and periodical aides published by biologists, their letters and biographies, information on the institutions with which they were associated, contemporary social history, and much else. Not even the most conscientious historian would be able to cover even 0.1% of all this material. The situation is aggravated by the exponential acceleration in the rate of current scientific output. In an amazingly short span of years more papers, and pages, are now published than in the whole preceding history of science. Even specialists complain that they can no longer keep up with the avalanche of research output in their own held. Curiously, exactly the same is true for history writing. In the United States there are now perhaps 5 times as many historians of biology as there were only 25 years ago. Even though I have valiantly attempted to read the most important publications, I know that every specialist will discover numerous omissions in my treatment and presumably not infrequent errors. The first draft of most of the manuscript was written from 1970 to 1976, and the more recently published literature is not always as adequately incorporated as would have been desirable. My task would have been altogether impossible if it had not been for the richness and excellence of the modern secondary literature. The older literature was often rather superficial, and author after author would copy the same myths or errors, as one discovered when one consulted the original publications. Obviously, in a volume such as this one, which may contain more than 20,000 individual items of information, it is impossible to verify each item in the original source. Since my work is not a lexicographic history, an occasional factual error is not fatal. My major objective has been to synthesize an enormous literature with a consistent emphasis on interpretation and the analysis of causation. Timeliness. A criticism often raised against historians of science, and not without justification, is that they are preoccupied too exclusively with the prehistory of science, that is, with periods the events of which are largely irrelevant for modern science. To avoid this complaint, I have tried to bring the story as close to the present as is possible for a non-specialist. In some cases, for instance the discovery in the last 5 to 10 years in molecular biology of numerous families of DNA, the conceptual consequences, for instance on evolution, are still too uncertain to be dealt with. I disagree with the statement of a recent historian that the object of the history of science is investigation and disputes that have been concluded rather than issues that are presently alive. This is quite in error. Most scientific controversies extend over far longer periods of time than is generally conceived. Even today's controversies have a root that usually goes far back in time. It is precisely the historical study of such controversies that often contributes materially to a conceptual clarification and thus makes the ultimate solution possible. Analogous to the field of world history, where current history is recognized as a legitimate field, there is current history in the history of science. Nothing would be more misleading than to assume that the history of science deals only with dead issues. On the contrary, one might even go so far as to consider as prehistory the accounts of long-dead issues of earlier centuries and millennia. Simplification. A historian who covers such a vast area as is dealt with in this volume is forced to present a highly streamlined account. The reader is warned that the seeming simplicity of many of the developments is quite deceiving. Detailed accounts that concentrate on special developments or short periods must be consulted if one is to appreciate the full flavor of the many cross-currents, false starts, and unsuccessful hypotheses that prevailed at any given period. Developments virtually never were as straightforward and logical as they appear to be in a simplified retrospective account. It is particularly difficult to emphasize adequately the often quite paralyzing power of entrenched conceptualizations when confronted by new discoveries or new concepts. Inaccuracy is also introduced by labeling certain authors as vitalists, preformationists, teleologists, saltationists, or neo-Darwinians, as if these labels would refer to homogeneous types. Actually, these categories consist of individuals no two of whom had exactly the same views. This is particularly true for the epithets Lamarckians and Neo-Lamarckians, some of whom had nothing in common with each other except a belief in an inheritance of acquired characters. Silent assumptions. A further difficulty for the historian is posed by most scientists' unawareness of their own framework of ideas. They rarely articulate, if they think about it at all, what truths or concepts they accept without question and what others they totally reject. In many cases the historian can piece this together only by reconstructing the total intellectual milieu of the period. And yet an understanding of these silent assumptions may be necessary in order to answer previously puzzling questions. In science one always deals with priorities and value systems. They determine the direction of new research after a previous piece of research has been completed. They determine which theories the investigator is most anxious either to confirm or to refute. they also determine whether or not he considers an area of research exhausted. And yet a study of the factors that determine such priorities or value systems has been greatly neglected until now. The historian must attempt to find out what went on in the mind of a worker when he gave a new interpretation to a long familiar set of facts. It is perhaps legitimate to say that the truly crucial events in the history of science always take place in the mind of a scientist. One must, so to speak, attempt to think as the scientist thought when he performed the work one is trying to analyze. Most scientists tend to concentrate in their publications on new facts, or rather on new discoveries, and in particular on anything that is spectacular. At the same time, they usually fail to record important ongoing changes of concepts or emphasis. They may even fail to recognize such changes, or may consider them as negligible even when they are aware of them. When the modern historian attempts to reconstruct such changes in past centuries, he cannot help but project into history the interests and scale of values of the present. This danger of interpretation can be minimized only if the historian is fully aware of what he is doing. Why study the history of biology? My own interest in the history of science was aroused by reading A. O. Lovejoy's The Great Sham of Being, where the attempt is made, and it was eminently successful, to trace the life history, so to speak, of a single idea, or a cohesive complex of ideas, from the ancients to the end of the 18th century. I have learned more from this one volume than from almost anything else I have read. Others who have attempted a similar approach are Ernst Cassirer and Alexander Koyer. They have provided entirely new standards for scientific historiography. In the case of the history of science, the focal points are problems rather than ideas, but the approach of the historian of science is not much different from that of a historian of ideas such as Lovejoy. Like Lovejoy, he attempts to trace the problem back to its beginning and to follow up its fate and its ramifications from such a beginning either to its solution or to the present time. It is the principal objective of this volume to discover for each branch of biology and for each period what the open problems were and what proposals were made to solve them, the nature of the dominant concepts, their changes, and the causes for their modification and for the development of new concepts, and finally, what effect prevailing or newly arising concepts had in delaying or accelerating the solution of the open problems of the period. At its best, this approach would portray the complete life history of each problem of biology. Preoccupation with this sort of conceptual history of science is sometimes belittled as a hobby of retired scientists. Such an attitude ignores the manifold contributions which this branch of scholarship makes. The history of science, as has been pointed out frequently, is particularly suitable as a first introduction to science. It helps to bridge the gap between general beliefs and the actual findings of science, since it shows in what manner and for what reason science has advanced beyond the beliefs of folklore. To illustrate this for a single branch of biology, in the history of genetics it can be shown by what discoveries and arguments rather widely held erroneous beliefs were refuted, as for instance that there is an inheritance of acquired characters, that the genetic materials of the parents blend, that the blood of a female is tainted so that she can never again produce pure offspring once she has been inseminated, even if only a single time, that a single egg is simultaneously fertilized by the sperm of several males, or that accidents of a pregnant mother can lead to the production of heritable characters. Similar erroneous beliefs, derived from folklore, myths, religious documents, or from early philosophies, had originally been held in many fields of biology. The historical demonstration of the gradual replacement of these prescientific or early scientific beliefs by better-based scientific theories and concepts greatly assists in explaining the current framework of biological theories. The layperson often excuses his ignorance of science with the comment that he finds science too technical or too mathematical. Let me assure the prospective reader of this volume that he will hardly find any mathematics in its pages, and that it is not technical to the extent that a layperson would have difficulty with the exposition. It is a major advantage of the history of ideas in biology that one can study it without a background knowledge of the name of a single species of animal or plant or of the major taxonomic groups and their classification. However, a student of the History of ideas must acquire some knowledge of the dominant concepts in biology, like inheritance, program, population, variation, emergence, or organismic. It is the objective of Chapter 2 to provide an introduction into the world of major biological concepts. Many of these concepts, and the terms that go with them, have now also been incorporated into various branches of the humanities, and it has simply become a matter of education to be acquainted with them. All of these concepts are indispensable for an understanding of man and the world in which he lives. Any endeavor to elucidate the origin and nature of man must be based on a thorough understanding of the concepts and theories of biology. Finally, it is helpful to become familiar with a very small repertory of technical terms like gamete, zygote, species, gene, chromosome, and so on, terms that are defined in the glossary. Yet, the total vocabulary of such technical terms is far smaller than what a student in any field of the humanities has to learn, whether it be music, literature, or current history. It is not only the layperson whose horizon will be greatly extended by the study of the history of ideas in biology. Advances in many areas of biology are so precipitous at the present time that specialists can no longer keep up with developments in areas of biology outside their own. The broad survey of biology and its dominant concepts that is presented in this volume will help in filling some of the gaps. My survey is also directed toward those who have entered biology in recent years from the outside, that is, from chemistry, physics, mathematics, or other adjacent fields. The technical sophistication of these neo-biologists is, unfortunately, rarely matched by an equivalent conceptual sophistication. Indeed, those who know organisms in nature and understand the ways of evolution are often appalled by the naivete of some of the generalizations made in some papers in molecular biology. Admittedly, there is no quick and easy way to compensate for this deficiency. Like Conant, I feel that the study of the history of a field is the best way of acquiring an understanding of its concepts. Only by going over the hard way by which these concepts were worked out, by learning all the earlier wrong assumptions that had to be refuted one by one, in other words by learning all past mistakes, can one hope to acquire a really thorough and sound understanding. In science one learns not only by one's own mistakes but by the history of the mistakes of others. 2. The place of biology in the sciences and its conceptual structure. It is quite impossible to try to understand the development of any particular concept or problem in the history of biology unless one has first answered for oneself these questions: what is science? What is the place of biology among the sciences? And what is the conceptual structure of biology? Entirely misleading answers have been given to all three of these questions, particularly by philosophers and other non-biologists, and this has greatly impeded an understanding of the growth of biological thought. To try to answer these basic questions correctly, then, is the first task of my analysis. It will provide a secure basis for the study of the history of specific concepts. The nature of science. From the earliest times on, man has asked questions about the origin and the meaning of the world, and frequently about its purpose. His tentative answers can be found in the myths characteristic of every culture, even the most primitive ones. He has advanced beyond these simple beginnings in two rather different directions. In one, his ideas became formalized in religions, which proclaimed a set of dogmas, usually based on revelation. The Western world, for instance, at the end of the Middle Ages was completely dominated by an implicit trust in the teachings of the Bible, and beyond that, by a universal belief in the supernatural. Philosophy, and later science, is the alternative way of dealing with the mysteries of the world, although science was not strictly separated from religion in its early history. Science confronts these mysteries with questions, with doubts, with curiosity, and with explanatory endeavors, thus with a rather different attitude from religion. The pre-Socratic, Ionian, philosophers initiated this different approach by searching for natural explanations, in terms of observable forces of nature, like fire, water, and air, see chap. Ter 3. This endeavor to understand the causation of natural phenomena was the beginning of science. For many centuries after the fall of Rome, this tradition was virtually forgotten, but it was revived again in the late Middle Ages and during the Scientific Revolution. The belief grew that the divine truth was revealed to us not only in Scripture but also in God's creation. Galileo's statement of this opinion is well known. I think that in the discussion of natural problems we ought not to begin at the authority of places of Scripture, but at sensible experiments and necessary demonstrations. For, from the divine word the sacred Scripture and nature did both alike proceed. He continued that God equally admirably reveals himself to us in nature's actions as in the Scripture's sacred dictions. He thought that a God who governs the world with the help of eternal laws inspires trust and faith at least as much as one who forever intervenes in the course of events. It was this thought which gave rise to the birth of science as we now understand it. Science for Galileo was not an alternative to religion but an inseparable part of it. Likewise, many great philosophers from the 17th to the 19th centuries, for instance, Kant, included God in their explanatory schemes. So-called natural theology was, in spite of its name, as much science as it was theology. The conflict between science and theology developed only later when science explained more and more processes and phenomena of nature by natural laws which previously had been considered inexplicable except by the intervention of the Creator or by special laws ordained by Him. A fundamental difference between religion and science, then, is that religion usually consists of a set of dogmas, often revealed dogmas, to which there is no alternative nor much leeway in interpretation. In science, by contrast, there is virtually a premium on alternative explanations and a readiness to replace one theory by another. The discovery of an alternate explanatory scheme is often the source of great elation. The goodness of a scientific idea is judged only to a minor degree by criteria extrinsic to science because it is on the whole judged entirely by its efficacy in explanation and, sometimes, prediction. Scientists, curiously, have been rather inarticulate about stating what science is all about. In the heyday of empiricism and inductionism, the objective of science was most often described as the accumulation of new knowledge. By contrast, when one reads the writings of philosophers of science, one gets the impression that for them science is a methodology. Even though no one will want to question the indispensability of method, the almost exclusive preoccupation of some philosophers of science with method has deflected attention from the more basic purpose of science, which is to increase our understanding of the world in which we live, and of ourselves. Science has a number of objectives. Ayala, 1968, describes them this way: 1. Science seeks to organize knowledge in a systematic way, endeavoring to discover patterns of relationship among phenomena and processes. 2. Science strives to provide explanations for the occurrence of events. 3. Science proposes explanatory hypotheses that must be testable, that is, accessible to the possibility of rejection. More broadly, science attempts to subsume the vast diversity of the phenomena and processes of nature under a much smaller number of explanatory principles. Discovery of new facts or development of new concepts. Discoveries are the symbol of science in the public mind. The discovery of a new fact is usually easily reportable, and thus the news media also see science in terms of new discoveries. When Alfred Nobel wrote out the conditions for Nobel Prizes, he thought entirely in terms of new discoveries, particularly those useful to mankind. Yet to think of science merely as an accumulation of facts is very misleading. In biological science, and this is perhaps rather more true for evolutionary than for functional biology, most major progress was made by the introduction of new concepts, or the improvement of existing concepts. Our understanding of the world is achieved more effectively by conceptual improvements than by the discovery of new facts, even though the two are not mutually exclusive. Let me illustrate this by one or two examples. Ratios of 3:1 had been discovered by plant breeders many times before Mendel. Even Darwin had obtained a number of such ratios in his plant breeding work. Nevertheless, all this was meaningless until Mendel introduced the appropriate concepts and until Weismann introduced additional concepts that made Mendelian segregation more meaningful. Similarly, the phenomena that are now explained by natural selection were widely known long before Darwin but made no sense until the concept of populations consisting of unique individuals was introduced. Then natural selection acquired great explanatory power. The concepts of population thinking and geographic variation, together with that of isolation, were, in turn, the prerequisites for the development of the theory of geographic speciation. That the acquisition of reproductive isolation is a crucial component in the process of speciation was not fully realized until the concept of isolating mechanisms had been clarified. The true role of isolating mechanisms was not understood as long as geographical barriers were included among the isolating mechanisms, as was still done by Dobbs-Hansky, 1937. One can take almost any advance, either in evolutionary biology or in systematics, and show that it did not depend as much on discoveries as on the introduction of improved concepts. Historians of science have long known this, but this fact is unfortunately far too little understood among non-scientists. To be sure, discoveries are an essential component of scientific advance, and some current bottlenecks in biology, such as the problem of the origin of life and of the organization of the central nervous system, are primarily due to a deficiency of certain basic facts. Nevertheless, the contribution made by new concepts or by the more or less radical transformation of old concepts is equally and often more important than facts and their discovery. In evolutionary biology, concepts like evolution, common descent, geographic speciation, isolating mechanisms, or natural selection have led to a drastic reorientation in a previously confusing area of biology and to new theory formation and countless new investigations. Those are not far wrong who insist that the progress of science consists principally in the progress of scientific concepts. The use of concepts is, of course, not confined to science, since there are concepts in art, in history, and other areas of the humanities, in philosophy, and indeed in any activity of the human mind. What criteria, then, beyond the use of concepts, can be used for the demarcation between science and these other human endeavors? The answer to this question is not as simple as one might expect, as is documented by asking to what extent the social sciences are sciences. Tentatively one might suggest that what characterizes science is the rigor of its methodology, the possibility of testing or falsifying its conclusions, and of establishing non-contradictory paradigms, systems of theories. Method, even if it is not all of science, is one of its important aspects, particularly since it differs somewhat in different scientific disciplines. Method in science. The Greeks always looked for rational explanations in the world of phenomena. The school of Hippocrates, for example, when trying to determine the cause of a disease, did not look for it in a divine influence but attributed it to natural causes such as climate or nutrition. The Ionian philosophers, likewise, attempted to give rational explanations for the phenomena of the inanimate and living world. Aristotle, unquestionably the father of scientific methodology, gives in his Posterior Analytics such a remarkable account of how one ought to go about a scientific explanation, McKeon, 1947, Foley, 1953, Vogel, 1952, that almost up to the 19th century, says Lawton, 1977, 13, in a somewhat extreme statement, philosophers of science were still working largely within the confines of the methodological problems discussed by Aristotle and his commentators. The Greek philosophers, including Aristotle, were primarily rationalists. They thought Empedocles being a typical example that they could solve scientific problems simply by sharp reasoning, involving ordinarily what we would now call deduction. The undoubted success which these ancient physicians and philosophers had in their explanations led to an overrating of a purely rational approach, which reached its climax in Descartes. Even though he did some empirical research, dissections, for example, many statements of this philosopher read as though he had believed that everything could be solved simply by concentrated thinking. The ensuing attacks on Cartesianism by inductivists and experimentalists made it very clear that method was considered of great importance in science. This is as true today as it was in the 17th century. All too many philosophers, unfortunately, continued to believe until far into the 19th century that they could solve the riddles of the universe simply by reasoning or philosophizing. When their conclusions were in conflict with the findings of science, some of them insisted that they were right and science was wrong. It was this attitude which induced Helmholtz to complain bitterly about the arrogance of the philosophers. The reaction of philosophers to natural selection, relativity, and quantum mechanics shows that this attitude has by no means been entirely overcome. Descartes endeavored to present only such conclusions and theories as had the certainty of a mathematical proof. Although there have always been some dissenters, the belief that a scientist had to supply absolute proof for all of his findings and theories prevailed until modern times. It dominated not only the physical sciences, where proof of the nature of a mathematical proof is often possible, but also the biological sciences. Even here, inferences are often so conclusive that they can be accepted as proof, as for instance the claim that the blood circulates or that a particular kind of caterpillar is the larval stage of a particular species of butterfly. The fact that the most minute exploration of the face of the earth has failed to reveal the presence of dinosaurs can be accepted as proof that they have become extinct. So far I have referred to facts, and to prove whether or not an assertion corresponds to a fact can usually be done. In many cases, however, and perhaps in the majority of the conclusions of the biologists, it is impossible to supply proof of such certainty. Hume, 1738. How are we to prove that natural selection is the directing agent guiding the evolution of organisms? Eventually the physicists also realized that they could not always give absolute proof, Lakatos, 1976, and the new theory of science no longer demands it. Instead, scientists are satisfied to consider as true either that which appears most probable on the basis of the available evidence, or that which is consistent with more, or more compelling, facts than competing hypotheses. Realizing the impossibility of supplying absolute proof for many scientific conclusions, the philosopher Karl Popper has proposed that falsifiability be made the test of their validity instead. The burden of the argument thus is shifted to the opponent of a scientific theory. Accordingly, that theory is accepted which has withstood successfully the greatest number and variety of attempts to refute it. Popper's claim also allows one rather neatly to delimit science from non-science. Any claim which in principle cannot be falsified is outside the realm of science. Thus, the assertion that there are men on the Andromeda Nebula is not a scientific hypothesis. Falsification, however, is sometimes as difficult to provide as positive proof. It is therefore not considered the only measure for obtaining scientific acceptability. As the history of science demonstrates, when scientific theories were rejected, it was often not because they had been clearly refuted but rather because an alternative new theory seemed more probable, simpler, or more elegant. Furthermore, rejected theories are often tenaciously adhered to by a minority of followers, in spite of a series of seemingly successful refutations. The new theory of science, based on a probabilistic interpretation of scientific conclusions, makes it inappropriate to speak of truth or proof as something absolute. This is of greater consequence for some branches of biology than for others. Every evolutionist who has had a discussion with lay people has been asked, has evolution been proven, or how do you prove that man descended from apes? He is then obliged first to discuss the nature of scientific proof. The working scientist, by contrast, has always been pragmatic. He was always reasonably happy with a theory until a better one was proposed. Factors that were inaccessible to explanation were treated as a black box, as was done by Darwin with the source of genetic variability, one of the chief components of his theory of natural selection. It did not and does not bother a scientist unduly that many of his generalizations are only probabilistic and that there is a remarkably high stochastic component in many, if not most, natural processes. Accepting great flexibility as one of the attributes of scientific theories, the scientist is willing to test numerous theories, to combine elements of different theories, and sometimes even to consider several alternate theories, multiple working hypotheses, simultaneously, while in search for evidence that would permit him to adopt one in preference to the others, Chamberlain, 1890. It should not be concealed, however, that the open-mindedness of scientists is not without limitations. When theories are strange or alien to the current intellectual milieu, they tend to be ignored or silenced. As we shall see, this is true, for instance, for the concepts of emergentism and of level specificity properties of hierarchies. Interestingly, Darwin's approach was completely in line with modern theory. He realized he could never demonstrate evolutionary conclusions with the certainty of a mathematical proof. Instead, in about 20 different parts of the origin he asks, is this particular bending whether a pattern of distribution or an anatomical structure more easily explained by special creation or by evolutionary opportunism? Invariably he insists that the second alternative is the more probable one. Darwin anticipated many of the most important tenets of the current philosophy of science. Although scientists have now universally adopted the probabilistic interpretation of scientific truth and indeed the complete impossibility of supplying demonstrations of the certainty of mathematical proof for most of their conclusions, this new insight is still not yet appreciated by many non-scientists. It would be desirable if this new concept of scientific truth were made part of scientific instruction to a much greater extent. There are indications, however, that the importance attributed to the choice of method has been exaggerated. In this I agree with Mayr, 1965, who opined that abstract methodology is of relatively little importance for the concrete development of scientific thought. Goodfield, 1974, could discover no difference in scientific success and theory formation between reductionists and anti-reductionists among physiologists. Kuhn and others have likewise minimized the importance of choice of method. Scientists in their actual research often go back and forth between a phase in which they collect material or conduct purely descriptive or classificatory research and another phase of concept formation or testing of theories. Induction. For centuries there have been arguments as to the respective merits of the inductive versus the deductive method, Mayr, 1967. It is now clear that this is a relatively irrelevant argument. Inductivism claims that a scientist can arrive at objective, unbiased conclusions only by simply recording, measuring, and describing what he encounters without having any prior hypotheses or preconceived expectations. Francis Bacon, 1561–1626, was the chief promoter of inductivism, though he never applied this method consistently in his own work. Darwin, who boasted that he was following the true Baconian method, was anything but an inductivist. Indeed, he made fun of this method, saying that if one did believe in this method, one might as well go into a gravel pit and count the pebbles and describe the colors. Yet, in the philosophical literature Darwin has often been classified as an inductivist. Inductivism had a great vogue in the 18th and early 19th centuries, but it is now clear that a purely inductive approach is quite sterile. This is illustrated by the plant breeder Gärtner, who patiently made and recorded tens of thousands of crosses without arriving at any generalizations. Liebig, 1863, was the first prominent scientist to repudiate Baconian inductivism, arguing convincingly that no scientist ever had or ever could follow the methods described in the Novum Organum. Liebig's incisive critique brought the reign of inductivism to an end. Lawton, 1968. Hypothetico-deductive method. Inductivism was replaced more and more consciously by the so-called hypothetico-deductive method. According to this method, the first step is to speculate, as Darwin called it, that is, to generate a hypothesis. The second step is to conduct experiments or gather observations permitting the testing of this hypothesis. Darwin's employment of this method has been excellently described by Gazellin, 1969, Hull, 1973a, and Roos, 1975b. There is a strong common sense element in this method, and one can argue that it is already implicit in the Aristotelian method and certainly in much of the so-called deductivism of Descartes and his followers. Although temporarily eclipsed during the 18th century vogue of inductivism, it became the prevailing method in the 19th century. The reason why the hypothetico-deductive method has been so widely adopted is that it has two great advantages. First, it fits right in with the growing conviction that there is no absolute truth and that our conclusions and theories should continually be tested. And second, connected with this new relativism, it encourages the continuous establishment of new theories and the search for new observations and new experiments that either confirm or refute the new hypotheses. It makes science more flexible and more enterprising, and has made some scientific controversies less acrimonious, since victory in the battle for ultimate truth is no longer involved. To what extent scientists actually employ the hypothetico-deductive approach is arguable. Collingwood, 1939, has stated quite correctly that a hypothesis is always a tentative answer to a question and that the posing of a question is really the first step on the path toward a theory. The history of science knows scores of instances where an investigator was in the possession of all the important facts for a new theory but simply failed to ask the right question. Accepting the importance of questions, however, immediately leads to new doubts. Why, in the first place, was the question raised? The answer must be because a scientist observed something which he did not understand or something the origin of which puzzled him, or because he encountered some seemingly contradictory phenomena from which he wanted to remove the contradiction. In other words, observations of facts gave rise to the questions. The anti-inductivists are, of course, entirely right in claiming that such facts by themselves never lead to a theory. They acquire significance only when an inquiring mind asks an important question. The creative mind is able, as Schopenhauer has stated it, to think something that nobody has thought yet, while looking at something that everybody sees. Imagination, thus, is ultimately the most important prerequisite of scientific progress. The hypothetico-deductive method is, in essence, the modern scientific method of discovery, although the establishment of a tentative hypothesis is invariably preceded by observations and the posing of questions. Experiment versus comparison. The difference between physical and biological research is not, as is often claimed, a difference of methodology. Experimentation is not restricted to the physical sciences but is a major method of biology, particularly of functional biology, see below. Observation and classification are clearly more important in the biological than in the physical sciences, yet it is evident that these are the dominant methods in such physical sciences as geology, meteorology, and astronomy. Analysis is of equal importance in the physical and in the biological sciences, as we will see. In philosophies of science written by physical scientists, the experiment is often referred to as the method of science. 3. This is not true, because other strictly scientific methods are of major importance in sciences like evolutionary biology and oceanography. Each science demands its own appropriate methods. For Galileo, the student of mechanics, measurement, and quantification were of paramount importance. For Aristotle, the student of living systems and of organic diversity, the analysis of what we now call teleonomic processes and the establishment of categories were favored approaches. In physiology and other functional sciences, the experimental method is not only appropriate but almost the only approach leading to results. Most historians of the physical sciences display an extraordinary ignorance when discussing methods other than the experimental one. Morgan, 1926, well documents the arrogance of the experimentalist. He denied to the paleontologist any competence in theory formation. My good friend the paleontologist he was, no doubt, referring to H. F. Osborn, is in greater danger than he realizes, when he leaves descriptions and attempts explanation. He has no way to check up his speculations. And when looking at the gaps in the fossil record, the geneticist says to the paleontologist, since you do not know, and from the nature of your case can never know, whether your differences are due to one change, a single mutation, or to 1,000, you cannot with certainty tell us anything about the hereditary units which have made the process of evolution. As if the paleontologist could not draw quite valid inferences from his material, inferences that can be tested in numerous ways. To imply that experimental work is never descriptive is also misleading. When reporting the results of their experiments, the practitioners of the experimental method are as descriptive as the naturalists when reporting their observations. The alternate to experiment, clearly, is observation. Progress in many branches of science depends on observations made in order to answer carefully posed questions. Modern evolutionary, behavioral, and ecological biology have demonstrated conclusively that these largely observational sciences are anything but descriptive. Actually, many papers based on experiments made without adequate Phlogiston, alas, there are far too many, are more descriptive than most non-experimental publications in evolutionary biology. Mere observation, however, is not sufficient. It was not until late in the 18th century that a method was first seriously employed which is peculiarly suitable for the study of diversity. It is the comparative method. Although he had some forerunners, Cuvier without question was the first great champion of the comparative method, see Chapter 4. It is frequently overlooked that the application of the comparative method must be preceded by a classification of the items to be compared. Indeed, the success of the comparative analysis depends to a large extent on the goodness of the preceding classification. At the same time, discrepancies revealed by the comparison often lead to an improved classification of the phenomena. Such a back and forth between two methods characterizes many branches of science and is not in the least circular. Hull, 1967. The difference between the experimental and the comparative method is not as great as it may appear at first. In both of them data are gathered and in both of them observation plays a crucial role, though the experimentalist usually does not mention the fact that his results are due to the observation of the conducted experiments. In the so-called observational sciences, the observer studies experiments of nature. The principal difference between the two sets of observations is that in the artificial experiment one can choose the conditions and is thus able to test the factors that determine the outcome of the experiment. In an experiment of nature, whether it is an earthquake or the production of an insular fauna, it is our main task to infer or reconstruct the conditions under which this experiment of nature had taken place. By searching for the right constellation of factors, it is sometimes almost possible in a controlled observation to reach the reliability of a controlled experiment. As Panton, 1968, 17, has stated, in astronomy, in geology, and in biology, observation of natural events at chosen times and places can sometimes provide information as wholly sufficient for a conclusion to be drawn as that which can be obtained by experiment. It is important to emphasize the scientific legitimacy of the observational comparative method because the experimental method is inapplicable to many scientific problems. Yet, contrary to the claims of some physicists, the branches of science which depend on the comparative method are not inferior. As a wise scientist, E.B. Wilson, expressed a long time ago, the experiments performed in our laboratories but supplement those that have taken place and are always taking place in nature, and their results must be wrought into the same fabric. Wilson opposed consistently those who claimed that progress in biology could be achieved by experiment alone. Observation led to the discovery of foreign faunas and floras and became the basis of biogeography. Observation revealed the diversity of organic nature and led to the establishment of the Linnaean hierarchy and to the theory of common descent. Observation led to the foundations of ethology and ecology. Observation in biology has probably produced more insights than all experiments combined. The position of biology within the sciences. When confronted by mythology or religion, science offers a unified front. All sciences, in spite of manifold differences, have in common that they are devoted to the endeavor to understand the world. Science wants to explain, it wants to generalize, and it wants to determine the causation of things, events, and processes. To that extent, at least, there is a unity of science. Causey, 1977. From this observation the conclusion is often drawn that what is true for one science, let us say physics, must be equally true for all sciences. To give illustration, I must have some 6 or 7 volumes on my shelves which claim to deal with the philosophy of science, but all of them actually deal only with the philosophy of the physical sciences. Philosophers of science, most of them with a background in physics, have unfortunately based their treatment of the philosophy and methodology of science almost exclusively on the physical sciences. Such treatments are very incomplete because they fail to cover the rich domain of phenomena and processes found in the world of living organisms. Philosophers and humanists, when they describe or criticize science, almost invariably have only the physical sciences, or even technology, in mind. When historians speak of the scientific revolution, which was primarily a revolution of the mechanical sciences, they silently imply all too often that this was a revolution pertaining equally to the biological sciences. That there are important differences between biology and the physical sciences is often entirely ignored. Most physicists seem to take it for granted that physics is the paradigm of science and that once one understands physics, one can understand any other science, including biology. The arrogance of the physicists, Hull, 1973, has become proverbial among scientists. The physicist Ernst Rutherford, for example, referred to biology as postage stamp collecting. Even V. Weisskopf, normally quite free of the usual hubris of the physicists, forgot himself recently sufficiently to claim that the scientific worldview is based upon the great discoveries of the 19th century concerning the nature of electricity and heat and the existence of atoms and molecules, 1977, 405, as if Darwin, Bernard, Mendel, and Freud, not to mention hundreds of other biologists, had not made a tremendous contribution to our scientific worldview, indeed, perhaps a greater one than the physicists. To counterbalance this attitude, it is sometimes beneficial or even necessary to stress the plurality of science. Too often Newton and the natural laws are considered as coextensive with science. Yet, if one looks at the intellectual scene during the 16th, 17th, and 18th centuries, one finds that simultaneously there were several other traditions which had virtually nothing to do with each other or with mechanics. The botany of the herbalists, the magnificent plates in the anatomy of Vesalius, the ubiquitous natural history cabinets, the scientific voyages, the Jardins de Plantes, the menageries. What did all of this have to do with Newton? And yet this other science is what inspired Rousseau's Romanticism and the dogma of the noble savage. It has become apparent only in recent years how naive and misleading the assumption of the sameness of physical and biological sciences is. The physicist C. F. von Weizsäcker, 1971, admits that the conventional physical explanation and the abstract mathematical form in which it is dressed, does not satisfy our need for a real understanding of nature. Moreover, a common worldview no longer unites the great groups of sciences. The physicist finds an autonomous biology. A study of biological phenomena, thus, leads to the legitimate question, to what extent are methodology and conceptual framework of the physical sciences appropriate models for the biological sciences? This question pertains not merely to such somewhat exceptional problems as that of consciousness or mind but to any biological phenomenon or concept, such as population, species, adaptation, digestion, selection, competition, and the like. Are these biological phenomena and concepts without equivalent in the physical sciences? Nowhere is the difference between different sciences more conspicuous than in their philosophical applications. Many philosophers have pointed out that there is no conceivable connection between the physical sciences and ethics. Yet, it is equally evident that there is a seeming potential for a connection between biological sciences and ethics. Social Spencerism is one example, eugenics is another one. There is some validity to the physicist's claim that there is no connection between the physical sciences and ethics, but think of nuclear physics. However, if he proclaims, as so many physicists have done, that there is no connection between science and ethics, he displays parochial narrowness. Political ideologies have always shown far more interest in the biological than in the physical sciences. Lysenkoism and the tabula rasa teaching of behaviorism, and its Marxist followers, are just some examples. For all these reasons it is wrong to speak of philosophy of science when one means the philosophy of the physical sciences. The conviction of many physical scientists that all the insights of biology can be reduced to the laws of physics has led many biologists, in self-defense, to assert the autonomy of biology. Although this emancipation movement of the biologists has, quite naturally, encountered considerable resistance, not only among physical scientists but also among essentialism-committed philosophers, it has continued to gain in strength in recent decades. A dispassionate discussion of the question whether the principles, theories, and laws of the physical sciences explain everything in the biological sciences, or whether biology is, at least in part, an autonomous science has been made very difficult by a conspicuous rivalry, even mutual hostility among the sciences, both within physical and biological sciences and between these two camps. Numerous have been the attempts, for example, that of Kant, to rank the sciences, with mathematics, or geometry in particular, appointed the queen of the sciences. The rivalry becomes apparent in the competition for honors such as Nobel Prizes, budgets within universities and governments, positions, and general prestige vis-a-vis non-scientists. For the preceding discussion might convey the impression that I too am pleading for a complete autonomy of the biological sciences, in other words, that I want to abandon radically the concept of the unity of science and replace it by the concept of two separate sciences, the physical and the biological sciences. This is not my position. All I wish to assert is that the physical sciences are not an appropriate yardstick of science. Physics is quite unsuited for this role because, as the physicist Eugene Wigner has stated very correctly, present-day physics deals with a limiting case. To use an analogy, physics corresponds to Euclidean geometry, which is the limiting case of all geometries, including non-Euclidean geometry. No one has described this situation better than G. Simpson, 1964 b. 106-107. Insistence that the study of organisms requires principles additional to those of the physical sciences does not imply a dualistic or vitalistic view of nature. Life is not thereby necessarily considered as non-physical or non-material. It is just that living things have been affected for billions of years by historical processes. The results of those processes are systems different in kind from any non-living systems and almost incomparably more complicated. They are not for that reason necessarily any less material or less physical in nature. The point is that all known material processes and explanatory principles apply to organisms, while only a limited number of them apply to non-living systems. Biology, then, is the science that stands at the center of all science. And it is here, in the field where all the principles of all the sciences are embodied, that science can truly become unified. The recognition that in the biological sciences we deal with phenomena unknown for inanimate objects is by no means new. The history of science, from Aristotle on, has been a history of endeavors to assert the autonomy of biology, and of attempts to stem the tide of facile mechanistic quantitative explanations. However, when naturalists and other biologists as well as some philosophers stressed the importance of quality, uniqueness, and history in biology, their efforts were often ridiculed and simply brushed aside as bad science. This fate happened even to Kant, who argued rather convincingly in his Kritik der Urteilskraft, 1790, that biology is different from the physical sciences and that living organisms are different from inanimate objects. Regrettably, often such endeavors were labeled as vitalism and hence as outside the boundary of science. Claims for the autonomy of biology have begun to be taken seriously only within the last generation or so, that is, after the final extinction of any genuine vitalism. It is becoming quite evident that one will never be able to make universally valid statements about science in general until one has first compared the various sciences with each other, and has determined what they have in common and what distinguishes them. How and why is biology different? The word biology is a child of the 19th century. Prior to that date, there was no such science. When Bacon, Descartes, Leibniz, and Kant wrote about science and its methodology, biology as such did not exist, only medicine, including anatomy and physiology, natural history, and botany, somewhat of a mixture. Anatomy, the dissection of the human body, was until far into the 18th century a branch of medicine, and botany likewise was practiced primarily by physicians interested in medicinal herbs. The natural history of animals was studied mainly as part of natural theology, in order to bolster the argument from design. The scientific revolution in the physical sciences had left the biological sciences virtually untouched. The major innovations in biological thinking did not take place until the 19th and 20th centuries. It is not surprising, therefore, that the philosophy of science, when it developed in the 17th and 18th centuries, was based exclusively on the physical sciences, and that it has been very difficult, subsequently, to revise it in such a way as to encompass also the biological sciences. It is only in recent decades that several philosophers, such as Scriven, Beckner, Hull, and Campbell, have attempted to characterize the differences between biology and the physical sciences, Ayala 1968. Thought about this problem is still so new that one can only make tentative statements. The object of the following discussion is more to delineate the nature of the problems than to provide definite solutions. Laws in the physical and biological sciences. Laws play an important explanatory role in the physical sciences. A particular happening is considered to be explained when it can be shown to be due to particular causal factors that are consistent with general laws. Some philosophers have designated the establishment of laws as the diagnostic criterion of science. Such laws are believed to be strictly deterministic and thus to permit precise predictions. The question has been raised in recent years whether or not laws are as important in biology as they seem to be in the physical sciences. Some philosophers, like Smart, 1963, 1968, have gone so far as to deny that there are any universal laws in biology such as characterize physics. Other philosophers, like Roos, 1973, and to a lesser extent Hull, 1974, have emphatically defended the existence of biological laws. Biologists have paid virtually no attention to the argument, implying that this question is of little relevance for the working biologist. If one looks back over the history of biology, one finds that 19th-century authors like Lamarck, Agassiz, Darwin, Haeckel, Cope, and most of their contemporaries referred frequently to laws. If one looks at a modern textbook of almost any branch of biology, one may not encounter the term law even a single time. This does not mean that regularities do not occur in biology, it simply means that they are either too obvious to be mentioned, or too trivial. This is well illustrated by the 100 evolutionary laws listed by Ranch, 1968, 109 to 114. They all refer to adaptive trends affected by natural selection. Most of them have occasional or frequent exceptions and are only rules, not universal laws. They are explanatory as far as past events are concerned, but not predictive, except in a statistical, probabilistic sense. When I say, a territory-holding male songbird has a 98.7%, or whatever the correct figure may be, chance to be victorious over an intruder, I can hardly claim to have established a law. When they say that proteins do not translate information back into the nucleic acids, molecular biologists consider this a fact rather than a law. Generalizations in biology are almost invariably of a probabilistic nature. As one wit has formulated it, there is only one universal law in biology, all biological laws have exceptions. This probabilistic conceptualization contrasts strikingly with the view during the early period of the scientific revolution that causation in nature is regulated by laws that can be stated in mathematical terms. Actually, this idea occurred apparently first to Pythagoras. It has remained a dominant idea, particularly in the physical sciences, up to the present day. Again and again it was made the basis of some comprehensive philosophy, but taking very different forms in the hands of various authors. With Plato it gave rise to essentialism, with Galileo to a mechanistic world picture, and with Descartes to the deductive method. All three philosophies had a fundamental impact on biology. Plato's thinking was that of a student of geometry, a triangle, no matter what combination of angles it has, always has the form of a triangle, and is thus discontinuously different from a quadrangle or any other polygon. For Plato, the variable world of phenomena in an analogous manner was nothing but the reflection of a limited number of fixed and unchanging forms, ida, as Plato called them, or essences as they were called by the Thomists in the Middle Ages. These essences are what is real and important in this world. As ideas they can exist independent of any objects. Constancy and discontinuity are the points of special emphasis for the essentialists. Variation is attributed to the imperfect manifestation of the underlying essences. This conceptualization was the basis not only of the realism of the Thomists but also of so-called idealism or of the positivism of later philosophers, up to the 20th century. Whitehead, who was a peculiar mixture of a mathematician and a mystic, perhaps one should call him a Pythagorean, once stated, "The safest general characterization of the European philosophical tradition is that it consists in a series of footnotes to Plato." No doubt, this was meant as praise, but it really was a condemnation, so far as it was true at all. What it really says is that European philosophy through all the centuries was unable to free itself from the straitjacket of Plato's essentialism. Essentialism, with its emphasis on discontinuity, constancy, and typical values, typology, dominated the thinking of the Western world to a degree that is still not yet fully appreciated by the historians of ideas. Darwin, one of the first thinkers to reject essentialism, at least in part, was not at all understood by the contemporary philosophers, all of whom were essentialists, and his concept of evolution through natural selection was therefore found unacceptable. Genuine change, according to essentialism, is possible only through the saltational origin of new essences. Because evolution as explained by Darwin is by necessity gradual, it is quite incompatible with essentialism. However, the philosophy of essentialism fitted well with the thinking of the physical scientists, whose classes consist of identical entities, be they sodium atoms, protons, or pi mesons. For Galileo, likewise, geometry was the key to the laws of nature. But he applied it in a far more mathematical manner than Plato. Philosophy is written in this grand book, the universe, which stands continually open to our gaze. But the book cannot be understood unless one first learns to comprehend the language and read the letters in which it is composed. It is written in the language of mathematics, and its characters are triangles, circles, and other geometric figures without which it is humanly impossible to understand a single word of it. Without these, one wanders about in a dark labyrinth. The Assayer, 1623, as quoted by Carney, 1964. It was, however, not only geometry that was considered basic by him, but all aspects of mathematics and particularly any kind of quantification of measurement. The mechanization of the world picture, the belief in a highly orderly world such as one would expect if the world was designed by the Creator to obey a limited set of eternal laws. Mayr, 1938, Dijksterhuis, 1961, made rapid progress in the ensuing centuries and achieved its greatest triumph in Newton's unification of terrestrial and celestial mechanics. These splendid successes led to an almost unlimited prestige of mathematics. It resulted in Kant's famous or infamous dictum that only so much genuine science can be found in any branch of the natural sciences as it contains mathematics. If this were true, where would the origin of species stand as a work of science? Not surprisingly, Darwin had a rather low opinion of mathematics. Hull, 1973, 12. The blind faith in the magic of numbers and quantities perhaps reached its climax in the middle of the 19th century. Even so perceptive a thinker as Mayr, 1896, 30, stated, "Modern science defines the method, not the aim of its work. It is based upon numbering and calculating, in short, upon mathematical processes, and the progress of science depends as much upon introducing mathematical notions into subjects which are apparently not mathematical, as upon the extension of mathematical methods and conceptions themselves." In spite of rather devastating subsequent refutations, Gazellin, 1969, 21, philosophers with a background in mathematics or physics continue to cling to the myth of mathematics as the queen of the sciences. For instance, the mathematician Jacob Bronowski, 1960, p. 218, stated that to this day, our confidence in any science is roughly proportional to the amount of mathematics it employs. We feel that physics is truly a science, but that there somehow clings to chemistry the less formal odor, and odium, of the cookbook. And as we proceed further to biology, then to economics, and last to social studies, we know that we are fast slipping down a slope away from science. These misconceptions concerning qualitative and historical sciences, or sciences dealing with systems too complex to be expressed in mathematical formulas, culminated in the arrogant claim that biology is an inferior science. This has led to facile and thoroughly misleading mathematical explanations in various areas of biology. No one was more impressed by the importance of mathematics than Descartes, but the consequences of this admiration on his thinking were quite different from that on Galileo or Newton. Descartes was impressed by the rigor of mathematical proofs and by the certainty by which conclusions issued from definite statements, going so far as to claim that the laws of mathematics had been legislated by God in the same manner as a king ordains laws in his realm. Descartes developed a logic in which the methods of mathematics were used, in a strictly deductive manner, to acquire rational knowledge. It was the structure of thought that was mathematical rather than a language of equations or mathematical formulas. Nevertheless, it favored strictly deterministic explanations and essentialistic thinking. Leibniz, who followed Descartes' methodology, was the founder of mathematical logic. As overwhelming as the dominance of mathematics over the sciences was for several centuries, there were voices of dissent almost from the beginning. Pierre Bell, 1647–1706, was apparently the first to deny the claim that mathematical knowledge was the only kind of knowledge attainable by the scientific method. He asserted, for instance, that historical certainty was not inferior but simply different from mathematical certainty. Facts of history, such as that the Roman Empire once existed, were as certain as anything in mathematics. A biologist would likewise insist that the former existence of dinosaurs and trilobites was as certain as any mathematical theorem. Another author to launch a devastating attack on the mathematical geometrical interpretations of the world by Descartes was Guillaume Battista Vico. He asserted that the methods of observation, classification, and hypothesis were indeed able to give one a genuine though modest outside knowledge of the material world. Natural history was a second source of rebellion against Galileo's mathematical ideal of science. It was particularly promoted by Buffon, who asserted emphatically, over philosophy, 26, that some subjects are far too complicated for a useful employment of mathematics, among these subjects being all parts of natural history. Here observation and comparison were the appropriate methods. Buffon's Histoire naturelle in turn decisively influenced Herder and through him the Romantics and Nature philosophy. Even Kant, by 1790, had abandoned his subservience to mathematics. If the invalidity of the mathematical ideal of science had not been obvious before, it certainly became so with the publication of The Origin of Species. It might be mentioned, incidentally, how misleading it is to refer to mathematics as the queen of the sciences. Mathematics, of course, is as little a science as grammar is a language, comparable to Latin or Russian. Mathematics is a language relating to all sciences or to none, although to highly varying degrees. There are some sciences, like the physical sciences and much of functional biology, in which quantification and other mathematical approaches have a high explanatory or heuristic value. There are other sciences, like systematics and much of evolutionary biology, in which the contributions of mathematics are very minor. In fact, an ill-advised application of mathematics in these branches of biology has sometimes led to typological thinking, and thus to misconceptions. The geneticist Johansen, for instance, fell prey to this temptation and simplified genetically variable populations to pure lines, thereby losing the very meaning of population and drawing erroneous conclusions concerning the importance of natural selection. The founders of mathematical population genetics, likewise, for the sake of mathematical tractability, oversimplified the factors entering their formulas. This led to a stress on absolute fitness values of genes, to an overvaluation of additive gene effects, and to the assumption that genes, rather than individuals, are the target of natural selection. This invariably led to unrealistic results. When Darwin calculated that the Earth must be more than 1,000 million years old in order to account for the phenomena of geology and phylogeny, Lord Kelvin pronounced him emphatically wrong on the basis of calculations of the heat loss of a globe of the size of the Sun. 24 million years was the maximum he could allow. Birchfield, 1975. It is rather amusing with what assurance Kelvin assumed the correctness of his own and the error of the naturalists' age determinations. Since biology was an inferior science, there could be no question where the error was. Kelvin never allowed for the possibility of the existence of an unknown physical factor that would eventually validate the calculations of the biologists. In this intellectual climate, biologists went out of their way to interpret their findings in terms of simple physics. Weissmann, in his early work, ascribed inheritance as due to molecular movements and Bateson as due to the movement of vortices, explanations that simply retarded scientific progress. The situation has changed rather dramatically during the last 50 years. The indeterminacy of most strictly biological processes no longer stands in sharp contrast to a strict determinacy in physical processes. The study of the effects of turbulence in galaxies and nebulae, as well as in the oceans and weather systems, has shown how frequent and powerful are stochastic processes in inanimate nature. This conclusion has not been acceptable to some physicists, leading Einstein, for example, to exclaim, "God does not play dice." Yet, stochastic processes occur at every hierarchical level from the atomic nucleus up to the systems produced by the Big Bang. And stochastic processes, even though making predictions probabilistic, or impossible, rather than absolute, are just as causal as deterministic processes. Only absolute predictions are impossible owing to the complexity of the hierarchical systems, the high number of possible options at each step, and the numerous interactions of simultaneously occurring processes. Weather systems and cosmic nebulae are, in that respect, not in principle different from living systems. The number of potentially possible interactions in such highly complex systems is far too large to permit prediction as to which one will actually take place. The students of natural selection and of other evolutionary processes, of quantum mechanics, and of astrophysics reached this conclusion at different times and more or less independently. For all of these reasons, physics is no longer the yardstick of science. Particularly where the study of man is concerned, it is biology that provides methodology and conceptualization. The President of France has recently formulated this conviction in these words: "There is no doubt that mathematics, physics, and other sciences rather ill-advisedly referred to as exact will continue to afford surprising discoveries, yet, I cannot help feeling that the real scientific revolution of the future must come from biology." Concepts in the biological sciences. Instead of formulating laws, biologists usually organize their generalizations into a framework of concepts. The claim has been made that laws versus concepts is only a formal difference, since every concept can be translated into one or several laws. Even if this were formally true, of which I am not at all sure, such a translation would not be helpful in the actual performance of biological research. Laws lack the flexibility and heuristic usefulness of concepts. Progress in biological science is, perhaps, largely a matter of the development of these concepts or principles. The progress of systematics was characterized by the crystallization and refinement of such concepts as classification, species, category, taxon, and so on, evolutionary science by such concepts as descent, selection, and fitness. Similar key concepts could be listed for every branch of biology. 5. Scientific progress consists in the development of new concepts, like selection, or biological species, and the repeated refinement of definitions by which these concepts are articulated. Particularly important is the occasional recognition that a more or less technical term, previously believed to characterize or designate a certain concept, was in reality used for a mixture of two or more concepts, like isolation for geographical and reproductive isolation, or variety, as used, for instance, by Darwin, for individuals and populations, or teleological for four different phenomena. It is strange how little attention the philosophy of science has paid to the overwhelming importance of concepts. For this reason, it is not yet possible to describe in detail the processes of discovery and maturation of concepts. This much is evident, however, that the major contribution of the leaders of biological thought has been the development and refinement of concepts and occasionally the elimination of erroneous ones. Evolutionary biology owes a remarkably large portion of its concepts to Charles Darwin, and ethology to Konrad Lorenz. The history of concepts, so neglected up to now, is full of surprises. Affinity or relationship, as used in pre-evolutionary systematics to designate not much more than simple similarity, was transferred after 1859 to proximity of descent without causing any confusion or difficulty. On the other hand, the attempt by Hennig to transfer the term monophyletic from a characterization of a taxonomic group to a characterization of a pathway of descent caused painful upheavals in taxonomy. The study of concepts sometimes reveals serious terminological deficiencies in certain languages. The term resource, for instance, so important for ecology, partitioning of, competition for, and so on, had no equivalent in German, until the English word was Germanicized to Ressourcen. There are concepts of the most diverse kind. Biology, for instance, has greatly benefited from a refinement of quasi-philosophical or methodological concepts, like proximate and evolutionary causation, or the clear demarcation of the comparative from the experimental method. The recognition of the existence of a comparative approach constituted the introduction of a new concept into biology. The difficulties within a science are particularly great when a truly new concept is introduced. This occurred, for instance, through the introduction of population thinking as the replacement of Plato's essence concept, or the introduction of concepts like selection or like genetic, closed, or open programs. This is what Kuhn, in part, was talking about when he spoke of scientific revolutions. Sometimes simply the introduction of a new term, like isolating mechanisms, taxon, or teleonomic, has greatly helped to clarify a previously confused conceptual situation. More often the conceptual morass had to be eliminated first, before the introduction of a new terminology could do any good. This was true for Johansson's terms genotype and phenotype, even though Johansson himself was somewhat confused, see Roll Hansen, 1978a. One further difficulty is posed by the fact that the same term may be used for different concepts in different sciences, or even disciplines of the same science. The term evolution meant something very different for embryologists from the 18th century, Bonnet, or for Louis Agassiz, 1874, than it meant for the Darwinians. Likewise, it meant something very different for most anthropologists, at least those directly or indirectly influenced by Herbert Spencer, than for selectionists. Many celebrated controversies in the history of science were caused almost entirely because the opponents referred to very different concepts by the same term. In the history of biology, the phrasing of definitions has often proven rather difficult, and most definitions have been modified repeatedly. This is not surprising since definitions are temporary verbalizations of concepts, and concepts, particularly difficult concepts, are usually revised repeatedly as our knowledge and understanding grows. This is well illustrated by the definitions of such concepts as species, mutation, territory, gene, individual, adaptation, and fitness. One very important methodological aspect of science is frequently misunderstood and has been a major cause of controversy over such concepts as homology or classification. It is the relation between a definition and the evidence that the definition is met in a particular instance. Simpson, 1961, 68-70. This is best illustrated by an example. The term homologous existed already prior to 1859, but it acquired its currently accepted meaning only when Darwin established the theory of common descent. Under this theory, the biologically most meaningful definition of homologous is, a feature in two or more taxa is homologous when it is derived from the same, or a corresponding, feature of their common ancestor. What is the nature of the evidence that can be used to demonstrate probable homology in a given case? There is a whole set of such criteria, like the position of a structure in relation to others, but it is completely misleading to include such evidence in the definition of homologous, as has been done by some authors. The same relation between definition and the evidence that the definition is met exists in the definition of virtually all terms used in biology. For instance, an author may attempt a phylogenetic classification but may rely entirely on morphological evidence to infer relationship. This does not make it a morphological classification. The currently most widely accepted species definition includes the criterion of the reproductive community, interbreeding. A paleontologist cannot test interbreeding in his fossil material, but he can usually bring together various other kinds of evidence, association, similarity, and so on, to strengthen the probability of conspecificity. A definition articulates a concept, but it does not need to include the evidence that the definition is met. Let me now discuss some of the concepts of particular importance in biology. Population thinking versus essentialism. Western thinking for more than 2,000 years after Plato was dominated by essentialism. It was not until the 19th century that a new and different way of thinking about nature began to spread, so-called population thinking. What is population thinking and how does it differ from essentialism? Population thinkers stress the uniqueness of everything in the organic world. What is important for them is the individual, not the type. They emphasize that every individual in sexually reproducing species is uniquely different from all others, with much individuality even existing in uniparentally reproducing ones. There is no typical individual, and mean values are abstractions. Much of what in the past has been designated in biology as classes are populations consisting of unique individuals. Gazelin, 1974b, Hull, 1976. There was a potential for population thinking in Leibniz's theory of monads, for Leibniz postulated that each monad was individualistically different from every other monad, a major departure from essentialism. But essentialism had such a strong hold in Germany that Leibniz's suggestion did not result in any population thinking. When it finally developed elsewhere, it had two roots. One consisted of the British animal breeders, Bakewell, Sprite, and many others, who had come to realize that every individual in their herds had different heritable characteristics, on the basis of which they selected the sires and dams of the next generation. The other route was systematics. All practicing naturalists were struck by the observation that when collecting a series of specimens of a single species they found that no two specimens were ever completely alike. Not only did Darwin stress this in his Barnacle work, but even Darwin's critics concurred on this point. Wollaston, 1860, for instance, wrote, "Amongst the millions of people who have been born into the world, we are certain that no two have ever been precisely alike in every respect, and in a similar manner it is not too much to affirm the same of all living creatures, however alike some of them may seem to our uneducated eyes, that have ever existed." Similar statements were made by many mid-19th century taxonomists. This uniqueness is true not only for individuals but even for stages in the life cycle of any individual, and for aggregations of individuals whether they be demes, species, or plant and animal associations. Considering the large number of genes that are either turned on or turned off in a given cell, it is quite possible that not even any two cells in the body are completely identical. This uniqueness of biological individuals means that we must approach groups of biological entities in a very different spirit from the way we deal with groups of identical inorganic entities. This is the basic meaning of population thinking. The differences between biological individuals are real, while the mean values which we may calculate in the comparison of groups of individuals, species, for example, are man-made inferences. This fundamental difference between the classes of the physical scientists and the populations of the biologists has various consequences. For instance, he who does not understand the uniqueness of individuals is unable to understand the working of natural selection. 6. The statistics of the essentialist are quite different from those of the populationist. When we measure a physical constant, for instance, the speed of light, we know that under equivalent circumstances it is constant and that any variation in the observational results is due to inaccuracy of measurement, the statistics simply indicating the degree of reliability of our results. The early statistics from Petty and Gruntuk Vitellit, Hiltz, 1973, was essentialistic statistics, attempting to arrive at true values in order to overcome the confusing effects of variation. Vitellit, a follower of Laplace, was interested in deterministic laws. He hoped by his method to be able to calculate the characteristics of the average man, that is, to discover the essence of man. Variation was nothing but errors around the mean values. Francis Gabon was perhaps the first to realize fully that the mean value of variable biological populations is a construct. Differences in height among a group of people are real and not the result of inaccuracies of measurement. The most interesting parameter in the statistics of natural populations is the actual variation, its amount, and its nature. The amount of variation is different from character to character and from species to species. Darwin could not have arrived at a theory of natural selection if he had not adopted populational thinking. The sweeping statements in the racist literature, on the other hand, are almost invariably based on essentialistic, typological, thinking. As important as the introduction of new concepts like population thinking was the elimination or revision of erroneous concepts. This is well illustrated by the concept of teleology. The problem of teleology. From Plato, Aristotle, and the Stoics on, a belief was prevalent, opposed by the Epicureans, that there is a purpose, a predetermined end, in nature and its processes. Those with this view in the 17th and 18th centuries, the teleologists, saw the clear expression of a purpose not only in the scala naturae, culminating in man, but also in the total unity and harmony of nature and its manifold adaptations. Opposed to the teleologists were the strict mechanists, who viewed the universe as a mechanism functioning according to natural laws. The seeming purposefulness of the universe, of the goal-directed processes in the development of individuals, and of the adaptations of organs was too conspicuous for the mechanist to ignore, however. How could a mechanism have all these properties purely as the result of laws, without recourse to final causes? No one perhaps was more keenly aware of this dilemma than Kant. To be for or against teleology remained a battle cry throughout the 19th century and right up to modern times. Only within the last 25 years or so has the solution become evident. It is now clear that seemingly goal-directed processes exist in nature which are not in any way in conflict with a strictly physico-chemical explanation. The solution, as so often in the history of science, was achieved by dissecting a complex problem and partitioning it into its components. It became obvious, Mayr, 1974d, that the term teleological had been applied to 4 different concepts or processes. 1. Teleonomic activities. The discovery of the existence of genetic programs has provided a mechanistic explanation of one class of teleological phenomena. A physiological process or a behavior that owes its goal-directedness to the operation of a program can be designated as teleonomic, Pittendry, 1958. All the processes of individual development, ontogeny, as well as all seemingly goal-directed behaviors of individuals fall in this category, and are characterized by 2 components: they are guided by a program, and they depend on the existence of some endpoint or goal which is foreseen in the program regulating the behavior. The endpoint might be a structure, a physiological function or steady state, the attainment of a new geographical position, or a consummatory behavioral act. Each particular program is the result of natural selection and is constantly adjusted by the selective value of the achieved endpoint, Mayr, 1974d. Aristotle called these causes the for the sake of which causes, Gothelf, 1976. From the point of view of causation, it is important to state that the program as well as the stimuli which elicit the goal-seeking behavior precede in time the seemingly purposive behavior. There are usually manifold feedback devices which improve the precision of the teleonomic process, but the truly characteristic aspect of teleonomic behavior is that mechanisms exist which initiate or cause this goal-seeking behavior. Teleonomic processes are particularly important in ontogeny, physiology, and behavior. They belong to the area of proximate causation, even though the programs were acquired during evolutionary history. It is the endpoints that produce the selection pressure which cause the historical construction of the genetic program. 2. Teleomatic processes. Any process, particularly one relating to inanimate objects, in which a definite end is reached strictly as a consequence of physical laws may be designated as teleomatic. Mayr, 1974d. When a falling rock reaches its endpoint, the ground, no goal-seeking or intentional or programmed behavior is involved, but simply conformance to the law of gravitation. So it is with the river inexorably flowing toward the ocean. When a red-hot piece of iron reaches an end state where its temperature and that of its environment are equal, the reaching of this endpoint is, again, due to strict compliance with a physical law, the first law of thermodynamics. The entire process of cosmic evolution, from the first Big Bang to the present time, is strictly due to a sequence of teleomatic processes on which stochastic perturbations are superimposed. The laws of gravitation and of thermodynamics are among the natural laws which most frequently govern teleomatic processes. Already Aristotle was aware of the separate existence of this class of processes, referring to them as caused by necessity. 3. Adapted systems. The natural theologians were particularly impressed by the design of all the structures responsible for physiological functions: the heart that is built to pump the blood through the body, the kidneys that are built to eliminate the byproducts of protein metabolism, the intestinal tract that performs digestion and makes nutritional material available to the body, and so on. It was one of the most decisive achievements of Darwin to have shown that the origin and gradual improvements of these organs could be explained through natural selection. It is therefore advisable not to use the term teleological, end-directed, to designate organs which owe their adaptedness to a past selectionist process. Adaptational or selectionist language is here more appropriate. Munson, 1971, Wimsatt, 1972, than teleological language, which may imply the existence of orthogenetic forces as responsible for the origin of these organs. One studies adapted systems by asking why questions. Why are there valves in the veins? Sherrington, 1906, 235, stressed this very appropriately for the reflex: we cannot obtain due profit from the study of any particular type reflex unless we can discuss its immediate purpose as an adapted act. The purpose of a reflex seems as legitimate and urgent an object for natural inquiry as the purpose of the coloring of an insect or blossom. And the importance to physiology is, that the reflex cannot be really intelligible to the physiologist until he knows its aim. 4. Cosmic teleology. Although Aristotle had developed his concept of teleology on the basis of the study of individual development, where it is entirely legitimate, he eventually applied it also to the universe as a whole. This being 2000 years before the proposal of the theory of natural selection, Aristotle could think of only two alternatives when encountering instances of adaptation: coincidence, chance, or purpose. Since it cannot be coincidence that the grinding molars are always flat and the cutting teeth, incisors, sharp-edged, the difference must be ascribed to purpose. There is purpose, then, in what is, and in what happens in nature. Indeed, so much in the universe reflects seeming purpose that final causation must be postulated. 7. In due time this concept of cosmic teleology, particularly when combined with Christian dogma, became the prevailing concept of teleology. It is this teleology which modern science rejects without reservation. there is and never was any program on the basis of which either cosmic or biological evolution has occurred. If there is a seeming aspect of progression in biological evolution, from the prokaryotes of 2 or 3 billion years ago to the higher animals and plants, this can be explained entirely as the result of selection forces generated by competition among individuals and species and by the colonization of new adaptive zones. Until natural selection was fully understood, many evolutionists, from Lamarck to H. F. Osborn and Teilhard de Chardin, postulated the existence of a non-physical, perhaps even non-material, force which drove the living world upward toward ever greater perfection, orthogenesis. It was not too difficult for materialistic biologists to show that there is no evidence for such a force, that evolution rarely produces perfection, and that the seeming progress toward greater perfection can be explained quite well by natural selection. The rectilinearity of many evolutionary trends is due to the many constraints which the genotype and the epigenetic system impose on the response to selection pressures. The theory of orthogenesis has recently been revived by hard-nosed physical scientists. Huygens, 1971, in his theory of hypercycles is convinced that the evolution of life must be considered an inevitable process despite its indeterminate course. Monod, 1974a, 22, refers to Huygens, and Prigogine, as animists, owing to their efforts to show first, that life could not have failed to start on Earth, and secondly that evolution could not have failed to occur. Biologists, of course, would reject the deterministic aspects of Huygens' theory, but rather similar conclusions can be based on stochastic processes constantly ordered by natural selection. Monod, in his theorizing, curiously failed to give due weight to natural selection. The partitioning, under 4 headings, of the aggregate of concepts lumped under the term teleological should eliminate teleology as a source of argument. One would wish, however, that these recent advances were more widely known among non-biologists. For instance, many psychologists in their discussion of goal-directed behavior still operate with such undefinable terms as intentions and consciousness which make an objective analysis impossible. Since we have no way of determining which of the animals, and plants, have intentions or consciousness, the use of these terms adds nothing to the analysis, indeed, it only obfuscates it. Progress in the solution of these psychological problems depends on a reconceptualization of intention or consciousness in terms of our new evolutionary insights. Special characteristics of living organisms. The question why some objects of nature are inanimate while others are alive, and what the special characteristics of living organisms are, already occupied the thoughts of the ancients. From the days of the Epicureans and Aristotle up to the early decades of this century there have always been 2 opposing interpretations of the phenomena of life. According to one school, the mechanists, organisms are nothing but machines, the workings of which can be explained by the laws of mechanics, physics, and chemistry. Many of the mechanists of the 17th and 18th centuries could not see that there was any significant difference between a rock and a living organism. Did not both share the same characteristics: gravity, inertia, temperature, and so on, and obey the same physical forces? When Newton proposed his law of gravitation in purely mathematical terms, many of his followers postulated an invisible but strictly materialistic gravitational force to explain the planetary motions as well as terrestrial gravity. By assumed analogy, some biologists invoked an equally materialistic and equally invisible force vis viva, to explain living processes. Later authors, however, believed that such a vital force was outside the realm of the chemico-physical laws. They thus continued a tradition started by Aristotle and other ancient philosophers. This vitalistic school opposed the mechanists, believing that there are processes in living organisms which do not obey the laws of physics and chemistry. Vitalism had representatives well into the 20th century, one of the last being the embryologist Hans Driesch. However, by the 1920s or 1930s biologists had almost universally rejected vitalism, primarily for 2 reasons. First, because it virtually leaves the realm of science by falling back on an unknown and presumably unknowable factor, and second, because it became eventually possible to explain in physico-chemical terms all the phenomena which according to the vitalists demanded a vitalistic explanation. It is fair to say that for biologists vitalism has been a dead issue for more than 50 years. Curiously, during that period it has still been defended by a number of physicists and philosophers. This rejection of vitalism was made possible by the simultaneous rejection of a crude animals are nothing but machines conceptualization. Like Kant in his later years, most biologists realized that organisms are different from inanimate matter and that the difference had to be explained not by postulating a vital force but by modifying rather drastically the mechanistic theory. Such a theory begins by granting that there is nothing in the processes, functions, and activities of living organisms that is in conflict with or outside of any of the laws of physics and chemistry. All biologists are thoroughgoing materialists in the sense that they recognize no supernatural or immaterial forces, but only such that are physico-chemical. But they do not accept the naive mechanistic explanation of the 17th century and disagree with the statement that animals are nothing but machines. Organismic biologists stress the fact that organisms have many characteristics that are without parallel in the world of inanimate objects. The explanatory equipment of the physical sciences is insufficient to explain complex living systems and, in particular, the interplay between historically acquired information and the responses of these genetic programs to the physical world. The phenomena of life have a much broader scope than the relatively simple phenomena dealt with by physics and chemistry. This is why it is just as impossible to include biology in physics as it is to include physics in geometry. Attempts have been made again and again to define life. These endeavors are rather futile since it is now quite clear that there is no special substance, object, or force that can be identified with life. The process of living, however, can be defined. There is no doubt that living organisms possess certain attributes that are not or not in the same manner found in inanimate objects. Different authors have stressed different characteristics, but I have been unable to find in the literature an adequate listing of such features. The list which I herewith present is presumably both incomplete and somewhat redundant. It may serve, however, for the want of a better tabulation, to illustrate the kinds of characteristics by which living organisms differ from inanimate matter. Complexity and organization. Complexity per se is not a fundamental difference between organic and inorganic systems. There are some highly complex inanimate systems, the air masses of the world weather system or any galaxy, and there are quite a few relatively simple organic systems like many macromolecules. Systems may have any degree of complexity, but, on the average, systems in the world of organisms are infinitely more complex than those of inanimate objects. Simon, 1962, has defined complex systems as those in which the whole is more than the sum of the parts, not in an ultimate, metaphysical sense but in the important pragmatic sense that, given the properties of the parts and the laws of their interaction, it is not a trivial matter to infer the properties of the whole. I accept this definition, except that we may continue to consider some relatively simple systems, such as the solar system, as complex even after we have succeeded in explaining their complexity. Complexity in living systems exists at every level from the nucleus, with its DNA program, to the cell, to any organ system, like kidney, liver, or brain, to the individual, the ecosystem, or the society. Living systems are invariably characterized by elaborate feedback mechanisms unknown in their precision and complexity in any inanimate system. They have the capacity to respond to external stimuli, the capacity for metabolism, binding or release of energy, and the capacity to grow and to differentiate. Living systems do not have a random complexity but are highly organized. Most structures of an organism are meaningless. Without the rest of the organism, wings, legs, heads, kidneys cannot live by themselves but only as parts of the ensemble. Consequently, all parts have an adaptive significance and may be able to perform teleonomic activities. Such mutual adaptation of parts is unknown in the inanimate world. This co-adapted function of parts was already recognized by Aristotle when he said, as every instrument and every bodily member subserves some partial end, that is to say, some specialization, so the whole body must be destined to minister to some plenary sphere of action. De partibus 1.5.645 al 0-15. Chemical uniqueness. Living organisms are composed of macromolecules with the most extraordinary characteristics. For instance, there are nucleic acids that can be translated into polypeptides, enzymes that serve as catalysts in metabolic processes, phosphates that permit energy transfer, and lipids that can build membranes. Many of these molecules are so specific and so uniquely capable of carrying out one particular function, like rhodopsin in the process of photoreception, that they occur in the animal and plant kingdoms whenever there is a need for that particular function. These organic macromolecules do not differ in principle from other molecules. They are, however, far more complex than the low molecular weight molecules that are the regular constituents of inanimate nature. The larger organic macromolecules are not normally found in inanimate matter. Quality. The physical world is a world of quantification, Newton's movements and forces, and of mass actions. By contrast, the world of life can be designated as a world of qualities. Individual differences, communication systems, stored information, properties of the macromolecules, interactions in ecosystems, and many other aspects of living organisms are prevailingly qualitative in nature. One can translate these qualitative aspects into quantitative ones, but one loses thereby the real significance of the respective biological phenomena, exactly as if one would describe a painting of Rembrandt in terms of the wavelengths of the prevailing color reflected by each square millimeter of the painting. In a like manner, many times in the history of biology, brave efforts to translate qualitative biological phenomena into mathematical terms have ultimately proved complete failures because they lost touch with reality. Early efforts to emphasize the importance of quality, like those of Galen, Paracelsus, and van Helmont, were likewise failures owing to the choice of wrong parameters, but they were the first steps in the right direction. The champions of quantification tend to consider the recognition of quality as something unscientific or at best as something purely descriptive and classificatory. They reveal by this bias how little they understand the nature of biological phenomena. Quantification is important in many fields of biology, but not to the exclusion of all qualitative aspects. These are particularly important in relational phenomena, which are precisely the phenomena that dominate living nature. Species, classification, ecosystems, communicatory behavior, regulation, and just about every other biological process deals with relational properties. These can be expressed, in most cases, only qualitatively, not quantitatively. Uniqueness and variability. In biology, one rarely deals with classes of identical entities, but nearly always studies populations consisting of unique individuals. This is true for every level of the hierarchy, from cells to ecosystems. Many biological phenomena, particularly population phenomena, are characterized by extremely high variances. Rates of evolution or rates of speciation may differ from each other by 3 to 5 orders of magnitude, a degree of variability rarely if ever recorded for physical phenomena. While entities in the physical sciences, let us say atoms or elementary particles, have constant characteristics, biological entities are characterized by their changeability. Cells, for instance, continuously change their properties, and so do individuals. Every individual undergoes a drastic change from birth to death, that is, from the original zygote, through adolescence, adulthood, senescence, to death. Again, there is nothing like it in inanimate nature, except for radioactive decay, the behavior of highly complex systems, such as the Gulf Stream and weather systems, and some vague analogies in astrophysics. Possession of a genetic program. All organisms possess a historically evolved genetic program, coded in the DNA of the nucleus of the zygote, or in RNA in some viruses. Nothing comparable to it exists in the inanimate world, except for man-made computers. The presence of this program gives organisms a peculiar duality, consisting of a phenotype and a genotype, See Chapter 16. Two aspects of this program must be specially emphasized. The first is that it is the result of a history that goes back to the origin of life and thus incorporates the experiences of all ancestors. Delbriac, 1949. The second is that it endows organisms with the capacity for teleonomic processes and activities, a capacity totally absent in the inanimate world. Except for the twilight zone of the origin of life, the possession of a genetic program provides for an absolute difference between organisms and inanimate matter. One of the properties of the genetic program is that it can supervise its own precise replication and that of other living systems such as organelles, cells, and whole organisms. There is nothing exactly equivalent in inorganic nature. An occasional error may occur during replication, let us say one error in 10,000 or 100,000 replications. Once such a mutation has taken place, it becomes a constant feature of the genetic program. Mutation is the primary source of all genetic variation. The full understanding of the nature of the genetic program was achieved by molecular biology only in the 1950s after the elucidation of the structure of DNA. Yet, it was already felt by the ancients that there had to be something that ordered the raw material into the patterned systems of living beings. As Delbriac, 1971, pointed out quite correctly, Aristotle's eidos, even though considered immaterial, because invisible, was conceptually virtually identical with the ontogenetic program of the developmental physiologist. Buffon's moule interior was a similar ordering device. Yet, it required the rise of computer science before the concept of such a program became reputable. What is particularly important is that the genetic program itself remains unchanged while it sends out its instructions to the body. The whole concept of program is so novel that it is still resisted by many philosophers. Historical nature. One result of having an inherited genetic program is that classes of living organisms are not primarily assembled or recognized by similarity but by common descent, that is, by a set of joint properties due to a common history. Hence, many of the attributes of classes recognized by logicians are not at all appropriate characteristics of species or higher taxa. This is even true for cell lineages in ontogeny. In other words, the classes of the biologist often are not equivalent to the classes of the logician. This must be remembered in many definitional arguments, but in none more than the one whether species taxa are individuals or classes. Natural selection. Natural selection, the differential reproduction of individuals that differ uniquely in their adaptive superiority, is a process without exact equivalent among processes of change in the inanimate world. Considering how often natural selection is still being misunderstood, it is worth quoting Sewell Wright's perceptive remark, 1967a. The Darwinian process of continuous interplay of a random and a selective process is not intermediate between pure chance and pure determinism, but in its consequences qualitatively utterly different from either. This process, at least in sexually reproducing species, is further characterized by the fact that, by recombination, a new gene pool is organized in each generation, and hence a new and unpredictable start is made for the selection procedure of the next generation. Indeterminacy. There has long been argument among biologists and philosophers whether physical and biological processes differ in determinacy and predictability. Unfortunately, epistemological and ontological aspects have been consistently confused and this has beclouded the issue. The word prediction is being used in two entirely different senses. When the philosopher of science speaks of prediction, he means logical prediction, that is, conformance of individual observations with a theory or a scientific law. Darwin's theory of common descent, for instance, permitted Haeckel the prediction that missing links between apes and humans would be found in the fossil record. Theories are tested by the predictions which they permit. Since the physical sciences are a system of theories to a far greater extent than biology, prediction plays in them a much greater role than in biology. Prediction, in daily usage, is an inference from the present to the future, it deals with a sequence of events, it is temporal prediction. In strictly deterministic physical laws absolute temporal predictions are often possible, such as predictions of the occurrence of eclipses. Temporal predictions are much more rarely possible in the biological sciences. The sex of the next child in a family cannot be predicted. No one would have predicted at the beginning of the Cretaceous that the flourishing group of the dinosaurs would become extinct by the end of this era. Predictions in biology are, on the average, far more probabilistic than in the physical sciences. The existence of the two kinds of predictions must be kept in mind in the discussion of causation and explanation. G. Bergman defines a causal explanation as one which, owing to a law of nature, permits to make predictions about future states of a system when its state at the present time is known. Essentially, this is only a rewording of the notorious boast of Laplace. Such claims have been rejected by Scriven, 1959, 477, who asserts that temporal prediction is not part of causality and that one cannot regard explanations as unsatisfactory when they are not such as to enable the event in question to have been predicted. In biology, and particularly in evolutionary biology, explanations ordinarily concern historical narratives. As far back as 1909, Baldwin specified two reasons why biological events are so often unpredictable: the great complexity of biological systems and the frequency at which unexpected novelties emerge at higher hierarchical levels. I can think of several others. Some of these might be considered ontological, others epistemological, indeterminacies. These factors do not weaken the principle of causality, conceived in a postdictive sense. 8. Randomness of an event with respect to its significance. Spontaneous mutation caused by an error in DNA replication illustrates this cause for indeterminacy very well. There is no connection between the molecular event and its potential significance. The same is true for such events as crossing over, chromosomal segregation, gametic selection, mate selection, and for much in survival. Neither the underlying molecular phenomena nor the mechanical motions involved in some of these processes are related to their biological effects. Uniqueness. The properties of a unique event or newly produced unique entity cannot be predicted, see above. Magnitude of stochastic perturbations. Let me illustrate the effect of this factor by an example. Let us say a species consists of 1 million uniquely different individuals. Each individual has a chance to be killed by an enemy, to succumb to a pathogen, to encounter a weather catastrophe, to suffer from malnutrition, to fail to find a mate, or to lose its offspring before they can reproduce. These are some of the numerous factors determining reproductive success. Which of these factors will become active depends on highly variable environmental constellations which are unique and unpredictable. We have, therefore, two highly variable systems, unique individuals and unique environmental constellations, interacting with each other. Chance determines to a large extent how they mesh together. Complexity. Each organic system is so rich in feedbacks, homeostatic devices, and potential multiple pathways that a complete description is quite impossible. Hence, a prediction of its productions is also impossible. Furthermore, the analysis of such a system would require its destruction and thus preclude the completion of the analysis. Emergence of new and unpredictable qualities at hierarchical levels, this will be discussed in more detail below. The stated 8 characteristics, together with additional ones to be mentioned below under the discussion of reductionism, make it clear that a living system is something quite different from any inanimate object. At the same time, not one of these characteristics is in conflict with a strictly mechanistic interpretation of the world. Reduction and biology. The claim of an autonomy of the science of living organisms, as manifested in the 8 unique or special characters of life listed above, has been rather unpopular with many physical scientists and philosophers of the physical sciences. They have reacted by asserting that the seeming autonomy of the world of life does not really exist, but that all theories of biology can, at least in principle, be reduced to theories of physics. This, they claim, restores the unity of science. The claim that reductionism is the only justifiable approach is often reinforced by the additional claim that its alternative is vitalism. This is not true. Even though some anti-reductionists have indeed been vitalists, virtually all recent anti-reductionists have emphatically rejected vitalism. Actually, it would be difficult to find a more ambiguous word than the word reduce. When one studies the reductionist literature, one finds that the term reduction has been used in at least 3 different meanings: Dobbs-Hansky and Ayala, 1974, Hull, 1973b, Schaffner, 1969, Nagel, 1961. Constitutive reductionism. It asserts that the material composition of organisms is exactly the same as that found in the inorganic world. Furthermore, it posits that none of the events and processes encountered in the world of living organisms is in any conflict with the physico-chemical phenomena at the level of atoms and molecules. These claims are accepted by modern biologists. The difference between inorganic matter and living organisms does not consist in the substance of which they are composed but in the organization of biological systems. Constitutive reductionism is therefore not controversial. Virtually all biologists accept the assertions of constitutive reductionism, and have done so, except the vitalists, for the last 200 years or more. Authors who accept constitutive reduction but reject other forms of reduction are not vitalists, the claims of some philosophers notwithstanding. Explanatory reductionism. This type of reductionism claims that one cannot understand a whole until one has dissected it into its components, and again these components into theirs, down to the lowest hierarchical level of integration. In biological phenomena it would mean reducing the study of all phenomena to the molecular level, that is, molecular biology is all of biology. Indeed, it is true that such explanatory reduction is sometimes illuminating. The functioning of genes was not understood until Watson and Crick had figured out the structure of DNA. In physiology, likewise, the functioning of an organ is usually not fully understood until the molecular processes at the cellular level are clarified. There are, however, a number of severe limitations to such explanatory reduction. One is that the processes at the higher hierarchical level are often largely independent of those of the lower levels. The units of the lower levels may be integrated so completely that they operate as units at the higher levels. The functioning of an articulation, for example, can be explained without a knowledge of the chemical composition of cartilage. Furthermore, replacing the articulating surface by a plastic, as is done in modern surgery, may completely restore the normal functioning of an articulation. There are probably as many cases where a dissection of a functional system into its components is unhelpful or at least irrelevant as there are cases where this is of explanatory value. A facile application of explanatory reduction in the history of biology has often done more harm than good. Examples are the early cell theory, which interpreted the organism as an aggregate of cells, or early population genetics, which considered the genotype an aggregate of independent genes with constant fitness values. Extreme analytical reductionism is a failure because it cannot give proper weight to the interaction of components of a complex system. An isolated component almost invariably has characteristics that are different from those of the same component when it is part of its ensemble, and does not reveal, when isolated, its contribution to the interactions. René Dubos, 1965, 337, has well stated the reasons why the atomized approach is singularly unproductive when applied to complex systems. In the most common and probably the most important phenomena of life, the constituent parts are so interdependent that they lose their character, their meaning, and indeed their very existence, when dissected from the functional whole. In order to deal with problems of organized complexity, it is therefore essential to investigate situations in which several interrelated systems function in an integrated manner. The most important conclusions one can draw from a critical study of explanatory reductionism is that the lower levels in hierarchies or systems supply only a limited amount of information on the characteristics and processes of the higher levels. As the physicist P. W. Anderson said, 1972, 393 to 396, the more the elementary particle physicists tell us about the nature of the fundamental laws, the less relevance they seem to have to the very real problems of the rest of science. much less of society. Furthermore, it is rather misleading to apply the term reduction to an analytical method. There are numerous other ways in which analysis of complex biological systems can be facilitated. The genetics of animals, for instance, was originally studied in horses, cattle, dogs, and other large mammals. Geneticists later shifted to fowl and various species of rodents. To get more numerous generations per year and perhaps simpler genetic systems, rodents were replaced after 1910 in most genetic labs by Drosophila melanogaster and other species of Drosophila. This was followed by a shift in the 1930s to Neurospora and other species of fungi, yeasts. Finally, most molecular genetics was done with bacteria, for example, Escherichia coli, and various viruses. In addition to a more rapid sequence of generations, the endeavor was to find ever simpler genetic systems and extrapolate from them to the more complex systems. By and large, this hope was fulfilled, except that it was shown eventually that the genetic system of prokaryotes, bacteria, and of viruses is not quite comparable to that of eukaryotes, where the genetic material is organized in complex chromosomes. Simplification, thus, must be undertaken with care. There is always the danger that one shifts to a system that, in its simplicity, is sufficiently different to be no longer comparable. Theory reductionism. This type of reductionism postulates that the theories and laws formulated in one held of science, usually a more complex held or one higher in the hierarchy, can be shown to be special cases of theories and laws formulated in some other branch of science. If this is done successfully, one branch of science has been reduced to the other one, in the quaint language of certain philosophers of science. To take a specie case, biology is considered to be reduced to physics when the terms of biology are denned in terms of physics and the laws of biology are deduced from the laws of physics. Such theory reduction was repeatedly attempted within the physical sciences, but never, according to Popper, 1974, with complete success. I am not aware of any biological theory that has ever been reduced to a physico-chemical theory. The claim that genetics has been reduced to chemistry after the discovery of the structure of DNA, RNA, and certain enzymes cannot be justified. To be sure, the chemical nature of a number of black boxes in the classical genetic theory was filled in, but this did not affect in any way the nature of the theory of transmission genetics. As gratifying as it is to be able to supplement the classical genetic theory by a chemical analysis, this does not in the least reduce genetics to chemistry. The essential concepts of genetics, like gene, genotype, mutation, diploidy, heterozygosity, segregation, recombination, and so on, are not chemical concepts at all, and one would look for them in vain in a textbook on chemistry. Theory reductionism is a fallacy because it confuses processes and concepts. As Beckner, 1974, has pointed out, such biological processes as meiosis, gastrulation, and predation are also chemical and physical processes, but they are only biological concepts and cannot be reduced to physico-chemical concepts. Furthermore, any adapted structure is the result of selection, but this again is a concept which cannot be expressed in strictly physico-chemical terms. It is a fallacy because it fails to consider the fact that the same event may have entirely different meanings in several different conceptual schemes. The courtship of a male, for instance, can be described entirely in the language and conceptual framework of the physical sciences, locomotion, energy turnover, metabolic processes, and so on, but it can also be described in the framework of behavioral or reproductive biology. The same is true for many other events, properties, relations, and processes relating to living organisms. Species, competition, territory, migration, and hibernation are examples of organismic phenomena for which a purely physical description is at best incomplete and usually biologically irrelevant. This discussion of reductionism can be summarized by saying that the analysis of systems is a valuable method, but that attempts at a reduction of purely biological phenomena or concepts to laws of the physical sciences has rarely, if ever, led to any advance in our understanding. Reduction is at best a vacuous, but more often a thoroughly misleading and futile, approach. This futility is particularly well illustrated by the phenomenon of emergence. Emergence. Systems almost always have the peculiarity that the characteristics of the whole cannot, not even in theory, be deduced from the most complete knowledge of the components, taken separately or in other partial combinations. This appearance of new characteristics in wholes has been designated as emergence. Emergence has often been invoked in attempts to explain such difficult phenomena as life, mind, and consciousness. Actually, emergence is equally characteristic of inorganic systems. As far back as 1868, T.H. Huxley asserted that the peculiar properties of water, its aquosity, could not be deduced from our understanding of the properties of hydrogen and oxygen. The person, however, who was more responsible than anyone else for the recognition of the importance of emergence was Lloyd Morgan, 1894. There is no question, he said, that at various grades of organization, material configurations display new and unexpected phenomena, and that these include the most striking features of adaptive machinery. Such emergence is quite universal and, as Popper said, we live in a universe of emergent novelty, 1974, 281. Emergence is a descriptive notion which, particularly in more complex systems, seems to resist analysis. Simply to say, as has been done, that emergence is due to complexity is, of course, not an explanation. Perhaps the two most interesting characteristics of new wholes are, 1, that they, in turn, can become parts of still higher level systems, and, 2, that wholes can affect properties of components at lower levels. The latter phenomenon is sometimes referred to as downward causation, Campbell, 1974, 182. Emergentism is a thoroughly materialistic philosophy. Those who deny it, like Wrench, 1971, 1974, are forced to adopt panpsychic or hylozoic theories of matter. Two false claims against emergentism must be rejected. The first is that emergentists are vitalists. This claim, indeed, was valid for some of the 19th century and early 20th century emergentists, but it is not valid for modern emergentists, who accept constitutive reduction without reservation and are therefore, by definition, non-vitalists. The second is the assertion that it is part of emergentism to believe that organisms can only be studied as wholes, and that any further analysis is to be rejected. Perhaps there have been some holists who have made such a claim, but this view is certainly alien to 99% of all emergentists. All they claim is that explanatory reduction is incomplete, since new and previously unpredictable characters emerge at higher levels of complexity in hierarchical systems. Hence, complex systems must be studied at every level, because each level has properties not shown at lower levels. Some recent authors have rejected the term emergence as tainted with an unwanted metaphysical flavor. Simpson, 1964b, has referred to it as the compositional method, Lawrence, 1973, as fulguration. So many authors, however, have now adopted the term emergence and, like the term selection, it has been purified by this frequent usage to such an extent, through the elimination of vitalistic and finalistic connotations, that I see no reason for not adopting it. The hierarchical structure of living systems. Complex systems very often have a hierarchical structure, Simon, 1962, the entities of one level being compounded into new entities at the next higher level, like cells into tissues, tissues into organs, and organs into functional systems. Hierarchical organization is also present in the inanimate world, such as, for instance, elementary particles, atoms, molecules, crystals, and so on, but it is in living systems that hierarchical structure is of special significance. Patty, 1973, asserts that all problems of biology, particularly those relating to emergence, see below, are ultimately problems of hierarchical organization. In spite of the widespread interest in hierarchies, we are still rather uncertain about the classification of hierarchies and about the special attributes of different kinds of hierarchies. In biology, one deals apparently with two kinds of hierarchies. One is represented by constitutive hierarchies, like the series macromolecule, cellular organelle, cell, tissue, organ, and so forth. In such a hierarchy, the members of a lower level, let us say tissues, are combined into new units, organs, that have unitary functions and emergent properties. The formation of constitutive hierarchies is one of the most characteristic properties of living organisms. At each level there are different problems, different questions to be asked, and different theories to be formulated. Each of these levels has given rise to a separate branch of biology, molecules to molecular biology, cells to cytology, tissues to histology, and so forth, up to biogeography and the study of ecosystems. Traditionally, the recognition of these hierarchical levels has been one of the ways of subdividing biology into fields. To which particular level an investigator will turn, depends on his interests. A molecular biologist is simply not interested in the problems studied by the functional morphologist or the zoogeographer, and vice versa. The problems and findings at other levels are usually largely irrelevant for those working at a given hierarchical level. For a full understanding of living phenomena, every level must be studied, but, as was pointed out above, the findings made at lower levels usually add very little towards solving the problems posed at the higher levels. When a well-known Nobel laureate in biochemistry said, "There is only one biology, and it is molecular biology," he simply revealed his ignorance and lack of understanding of biology. With so many components contributing to the functioning of a biological system, it is for the working scientist a matter of strategy and interest to decide the study of which level would make the greatest contribution toward the full understanding of the system under present circumstances. This includes the decision to leave certain black boxes unopened. An altogether different kind of hierarchy may be designated as an aggregational hierarchy. The best known paradigm for it is the Linnean hierarchy of taxonomic categories, from the species through genus and family up to phylum and kingdom. It is strictly an arrangement of convenience. The units at the lower level, for example, the species of a genus, or the genera of a family, are not compounded by any interaction into emerging new higher level units as a whole. Instead, groups of taxa are ranked in ever higher categories by the taxonomist. The validity of this statement is not weakened by the fact that the members of a natural, higher taxon are descendants of a common ancestor. Such hierarchies produced by rank assignments to categories are essentially only classificatory devices. It is unknown to me to what extent there might be still other kinds of hierarchies. Holism, organicism. Perceptive biologists, all the way back to Aristotle, have been dissatisfied with a purely atomistic reductionist approach to the problems of biology. Most biologists simply stressed wholeness, that is, the integration of systems. Others sidestepped scientific explanation by invoking metaphysical forces. Vitalism was the favorite explanation right into the 20th century. When Smuts, 1926, introduced the convenient term holism to express that the whole is more than the sum of its parts, he combined it with vitalistic ideas which unfortunately tainted the otherwise suitable term holism from its very beginning. The terms organismal and organicism were apparently introduced by Ritter, 1919, and are now rather widely used, for instance by Beckner, 1974, 163. Bertalanffy, 1952, listed some 30 authors who had declared their sympathy for a holistic organismic approach. This list is, however, very incomplete, not even including the names of Lloyd Morgan, Jan Smuts, and J. S. Haldane. François Jacobs, 1970, concept of the integrone is a particularly well-argued endorsement of organismic thinking. In contrast to the earlier holistic proposals, which usually were more or less vitalistic, the newer ones are strictly materialistic. They stress that the units at higher hierarchical levels are more than the sums of their parts and, hence, that a dissection into parts always leaves an unresolved residue. In other words, that explanatory reduction is unsuccessful. More importantly, they stress the autonomous problems and theories of each level and ultimately the autonomy of biology as a whole. The philosophy of science can no longer afford to ignore the organismic concept of biology as being vitalistic and hence belonging to metaphysics. A philosophy of science restricted to that which can be observed in inanimate objects is deplorably incomplete. There are many scientists who concentrate on the study of isolated objects and processes. They deal with them as if they exist in a vacuum. Perhaps the most important aspect of holism is that it emphasizes relationships. I myself have always felt that relationships are not given sufficient weight. This is why I have called the species concept a relational concept, and why my work on genetic revolution, 1954, and on the cohesion of the genotype, 1975, both deal with relational phenomena. My attack on beanbag genetics, 1959d, springs from the same source, see Chapter 13. Others have felt the same way. The painter Georges Braque, 1882–1963, declared, "I do not believe in things, I believe only in their relationships." Einstein, of course, based his entire relativity theory on the consideration of relationship. And when discussing changing selective values of genes in different genetic environments, I have called this concept, somewhat jokingly, the relativity theory of genes. The conceptual structure of biology. When comparing biology with the physical sciences, I have, up to now, treated biology as if it were a homogeneous science. This is not correct. Actually, biology is diversified and heterogeneous in several important ways. For thousands of years biological phenomena were subsumed under two labels, medicine, physiology, and natural history. This was actually a remarkably perceptive division, far more penetrating than such later labels of convenience as zoology, botany, mycology, cytology, or genetics. For biology can be divided into the study of proximate causes, the subject of the physiological sciences, broadly conceived, and into the study of ultimate, evolutionary, causes, the subject matter of natural history, Mayr, 1961. What proximate and evolutionary causes are is best made clear by a concrete example. Why does a certain warbler individual in temperate North America start its southward migration in the night of August 25? The proximate causes are that the bird, belonging to a migratory species responding to photoperiodicity, had become physiologically ready to migrate at that date since the numbers of hours of daylight had dropped to a certain threshold and since weather conditions, wind, temperature, barometric pressure, favored departure during that night. Yet a screech owl and a nuthatch living in the same piece of woodlands and exposed to the same decrease in daylight and to the same weather conditions did not depart southward. In fact, these other species remained in the same area throughout the year because they lacked the migratory urge. Obviously, then, there has to be an entirely different second set of causal factors to account for the differences between the migratory and the sedentary species. It consists in a genotype acquired through natural selection during thousands and millions of years of evolution which determines whether or not a population or species is migratory. An insect-eating warbler or flycatcher will have been selected to migrate because it otherwise would starve to death during the winter. Other species which can find their food throughout the winter will have been selected to avoid the perilous and, for them, unnecessary migration. To give another example, the proximate causation of sexual dimorphism might be hormonal or some genetic growth factors, while sexual selection or a selective advantage of differential utilization of the food niche might be the ultimate causation. Any biological phenomenon is due to these two independent kinds of causations. There is considerable uncertainty concerning the origin of the terminology proximate ultimate. Herbert Spencer and George Romanes have used these terms rather vaguely, but John Baker was apparently the first author to distinguish clearly between ultimate causes responsible for the evolution of a given genetic program, selection, and proximate causes responsible, so to speak, for the release of the stored genetic information in response to current environmental stimuli, thus abundance of insect food for the young at certain months might be the ultimate, and length of day the proximate cause of a breeding season. Baker, 1938, 162. The two biologies that are concerned with the two kinds of causations are remarkably self-contained. Proximate causes relate to the functions of an organism and its parts as well as its development, from functional morphology down to biochemistry. Evolutionary, historical, or ultimate causes, on the other hand, attempt to explain why an organism is the way it is. Organisms, in contrast to inanimate objects, have two different sets of causes because organisms have a genetic program. Proximate causes have to do with the decoding of the program of a given individual, evolutionary causes have to do with the changes of genetic programs through time, and with the reasons for these changes. The functional biologist is vitally concerned with the operation and interaction of structural elements, from molecules up to organs and whole individuals. His ever-repeated question is how. How does something operate? How does it function? The functional anatomist who studies an articulation shares this method and approach with the molecular biologist who studies the function of DNA molecules in the transfer of genetic information. The functional biologist attempts to isolate the particular component he studies, and in any given study he usually deals with a single individual, a single organ, a single cell, or a single part of a cell. He attempts to eliminate and control all variables, and he repeats his experiments under constant or varying conditions until he believes he has clarified the function of the element he studies. The chief technique of the functional biologist is the experiment, and his approach is essentially the same as that of the physicist and the chemist. Indeed, by isolating the studied phenomenon sufficiently from the complexities of the organism, he may achieve the ideal of a purely physical or chemical experiment. In spite of certain limitations of this method, one must agree with the functional biologist that such a simplified approach is an absolute necessity for achieving his particular objectives. The spectacular success of biochemical and biophysical research justifies this direct, although distinctly simplistic, approach. Mayr, 1961. There is little argument about the methodology and the achievements of functional biology from William Harvey to Claude Bernard and to molecular biology. Every organism, whether an individual or a species, is the product of a long history, a history that dates back more than 3,000 million years. As Max Delbrück, 1949, 173, has said, a mature physicist, acquainting himself for the first time with the problems of biology, is puzzled by the circumstance that there are no absolute phenomena in biology. Everything is time-bound and space-bound. The animal or plant or microorganism he is working with is but a link in an evolutionary chain of changing forms, none of which has any permanent validity. There is hardly any structure or function in an organism that can be fully understood unless it is studied against this historical background. To find the causes for the existing characteristics, and particularly adaptations, of organisms is the main preoccupation of the evolutionary biologist. He is impressed by the enormous diversity as well as the pathway by which it has been achieved. He studies the forces that bring about changes in faunas and floras, as in part documented by paleontology, and he studies the steps by which have evolved the miraculous adaptations so characteristic of every aspect of the organic world. In evolutionary biology, almost all phenomena and processes are explained through inferences based on comparative studies. These, in turn, are made possible by very careful and detailed descriptive studies. It is sometimes overlooked how essential a component in the methodology of evolutionary biology the underlying descriptive work is. The conceptual breakthroughs of Darwin, Weismann, Jordan, Rensch, Simpson, and Whitman would have been quite impossible without the sound foundation of descriptive research on which they could erect their conceptual framework. Lawrence, 1973. Natural history, by necessity, was strictly descriptive in its early history, and so was early anatomy. The endeavors of the systematists of the 18th and early 19th centuries to classify the diversity of nature rose more and more above simple description. After 1859, the autonomy of evolutionary biology as a legitimate biological discipline was no longer in question. Functional biology has often been designated as quantitative. By contrast, it is in many cases quite legitimate to refer to evolutionary biology as qualitative. The term qualitative was a pejorative designation during the anti-Aristotelian period of the scientific revolution. In spite of the efforts of Leibniz and other perceptive authors, it remained that way until the Darwinian Revolution. Under its liberating impact, a change in the intellectual climate occurred that made the development of evolutionary biology possible. This revolution was not successful instantaneously. Many physical scientists and functional biologists have consistently failed to understand the special nature of evolutionary biology. Driesch, in his autobiography, written in the 1930s, comments with considerable satisfaction that biological professorships are nowadays awarded only to experimentalists. Systematic problems have receded entirely to the background. He totally ignored the existence of evolutionary biology. This attitude was widespread among experimental biologists. Haeckel, 1877, was perhaps the first biologist to object vigorously to the notion that all science had to be like the physical sciences or to be based on mathematics. Evolutionary biology, he insisted, is a historical science. Particularly the studies of embryology, paleontology, and phytogeny are historical, he said. Instead of historical, we would perhaps now say regulated by historically acquired genetic programs and their changes in historical time. Alas, this viewpoint made only very slow progress. When Baldwin in 1909 pointed out how much the acceptance of Darwinism had changed the thinking of biologists, he concluded that the reign of physical science and of mechanical law over the scientific and philosophical mind is over now, at the opening of the 20th century. In this optimism he was mistaken. There are still many philosophers who write as if Darwin had never existed and as if evolutionary biology were not part of science. Historical narratives and evolutionary biology. Philosophy of science, when first developed, was firmly grounded in physics, and more specifically in mechanics, where processes and events can be explained as the consequences of specific laws, with prediction symmetrical to causation. History-bound scientific phenomena, by contrast, do not fit well into this conceptualization. As the physicist Hermann Bondi, 1977, 6, stated correctly, any theory of the origin of the solar system, of the origin of life on Earth, of the origin of the universe is of an exceptional nature as compared to conventional theories of physics in that it tries to describe an event in some sense unique. Uniqueness, indeed, is the outstanding characteristic of any event in evolutionary history. Several philosophers of science have, therefore, argued that explanations in evolutionary biology are not provided by theories but by historical narratives. As T. A. Gouch, 1961, 65-79, has stated, narrative explanations enter into evolutionary theory at points where singular events of major importance for the history of life are being discussed. Narrative explanations are constructed without mentioning any general laws. Whenever a narrative explanation of an event in evolution is called for, the event is not an instance of a kind class, but is a singular occurrence, something which has happened just once and which cannot recur in the same way. Historical explanations form an essential part of evolutionary theory. Morton White, 1963, has developed these ideas further. The notion of central subjects is crucial to the logical structure of historical narratives. Any phyletic line, any fauna, in zoogeography, or any higher taxon is a central subject in terms of the historical narrative theory and has continuity through time. Sciences in which historical narratives play an important role include cosmogony, geology, paleontology, phylogeny, and biogeography. Historical narratives have explanatory value because earlier events in a historical sequence usually make a causal contribution to later events. For instance, the extinction of the dinosaurs at the end of the Cretaceous vacated a large number of ecological niches and thus set the stage for the spectacular radiation of mammals during the Paleocene and Eocene. One of the objects of a historical narrative, thus, is to discover causes responsible for ensuing events. Philosophers trained in the axioms of essentialistic logic seem to have great difficulty in understanding the peculiar nature of uniqueness and of historical sequences of events. Their attempts to deny the importance of historical narratives or to axiomatize them in terms of covering laws fail to convince. The most characteristic aspect of evolutionary biology are the questions it asks. Instead of concentrating on what and how, as does the biology of proximate causes, it asks why. Why are certain organisms very similar to each other, while others are utterly different? Why are there two sexes in most species of organisms? Why is there such a diversity of animal and plant life? Why are the faunas of some areas rich in species and those of others poor? If an organism has certain characteristics, they must have been derived from those of an ancestor or have been acquired because they were of selective advantage. The question why, in the sense of what for, is meaningless in the world of inanimate objects. One can ask, why is the sun hot, but only in the sense of how come. By contrast, in the living world the question what for, has a powerful heuristic value. The question, why are there valves in the veins, contributed to Harvey's discovery of the circulation of blood. By asking, why do the nuclei in cells undergo the complex process of reorganization during mitosis, instead of simply dividing in half, Roux, 1883, gave the first correct interpretation of cell division. He fully understood that the question concerning the significance of a biological process can be asked in two ways. First with reference to its function for the biological structure in which it occurs, but secondly one can also ask for the causes responsible for the origin and progress of this process. Therefore the evolutionary biologist must always ask why questions when he attempts to analyze evolutionary causations. All biological processes have both a proximate cause and an evolutionary cause. Much confusion in the history of biology has resulted when authors concentrated exclusively either on proximate or on evolutionary causation. For instance, let us consider the question, what is the reason for sexual dimorphism? Th. Morgan, 1932, castigated the evolutionists for speculating about this question when, as he said, the answer is so simple, male and female tissues during ontogeny respond to different hormonal influences. He never considered the evolutionary question why the hormonal systems of males and females are different. The role of sexual dimorphism in courtship and other behavioral and ecological contexts was of no interest to him. Or to take another example, what is the meaning of fertilization? Several functional biologists, when considering this question, were impressed by the fact that the unfertilized egg is quiescent while development, indicated by the first cleavage division, begins almost immediately after the spermatozoon had entered the egg. Fertilization, therefore, it was stated by some functional biologists, has as its objective the initiation of development. The evolutionary biologist, by contrast, pointed out that fertilization was not needed in parthenogenetic species in order to initiate development, and he concluded therefore that the true objective of fertilization is the achievement of a recombination of paternal and maternal genes, such recombination producing the genetic variability required as material for natural selection. Weismann, 1886. It is evident from these case histories that no biological problem is fully solved until both the proximate and the evolutionary causation has been elucidated. Furthermore, the study of evolutionary causes is as legitimate a part of biology as is the study of the usually physico-chemical proximate causes. The biology of the origin of genetic programs and their changes through evolutionary history is as important as the biology of the translating, decoding, of genetic programs, that is, the study of proximate causes. The assumption of Julius von Sachs, Jacques Loeb, and other naive mechanists that biology consists entirely of a study of proximate causations is demonstrably wrong. A new philosophy of biology. It is now clear that a new philosophy of biology is needed. This will include and combine the cybernetic functional organizational ideas of functional biology with the populational historical program uniqueness adaptedness concepts of evolutionary biology. Although obvious in its essential outlines, this new philosophy of biology is, at the present time, more of a manifesto of something to be achieved than the statement of a mature conceptual system. It is most explicit in its criticism of logical positivism, essentialism, physicalism, and reductionism, but is still rather hesitant and inchoate in its major theses. The various authors who have written on the subject in recent years, like Simpson, Wrench, Mayr, the contributors to the Ayala and Dobbs-Hansky volume, 1974, and the authors of Philosophies of Biology, Beckner, Campbell, Hull, Munson, and so on, still differ widely from one another not only in emphasis but even in some basic tenets, for instance, acceptance or rejection of emergentism. There is, however, one very encouraging development. All of the more perceptive writers on the subject reject the extreme views of the past, not a single one of them accepts vitalism in any form whatsoever. Nor does any of them endorse any kind of atomistic or explanatory reductionism. With the borderlines of a new philosophy of biology clearly staked out, there is every hope for a true synthesis in the not-too-distant future. Philosophers of science, when dealing with the subject of biology, have devoted a good deal of time and attention to the problems of mind, consciousness, and life. I feel that they have created for themselves unnecessary difficulties. As far as consciousness is concerned, it is impossible to define it. Various criteria indicate that even lower invertebrates have consciousness, possibly even protozoans in their avoidance reactions. Whether one wants to pursue this down to the prokaryotes, for example, magnetic bacteria, is a matter of taste. At any rate, the concept of consciousness cannot even approximately be defined, and therefore detailed discussion is impossible. As far as the words life and mind are concerned, they merely refer to reifications of activities and have no separate existence as entities. Mind refers not to an object but to mental activity, and since mental activities occur throughout much of the animal kingdom, depending on how we define mental, one can say that mind occurs whenever organisms are found that can be shown to have mental processes. Life, likewise, is simply the reification of the processes of living. Criteria for living can be stated and adopted, but there is no such thing as an independent life in a living organism. The danger is too great that a separate existence is assigned to such life analogous to that of a soul. Blandino, 1969. The avoidance of nouns that are nothing but reify cations of processes greatly facilitates the analysis of the phenomena that are characteristic for biology. The gradual emergence of an autonomous philosophy of biology has been a long, drawn-out, and painful process. Early attempts were doomed to failure owing to a lack of knowledge of the facts of biology and the prevalence of unsuitable or erroneous concepts. This is well illustrated by Kant's philosophy of biology. What Kant did not realize was that the subject matter of biology first had to be straightened out by the biologists themselves, by science. For instance, that it was the task of the systematists to explain causally the Linnaean hierarchy, done by Darwin in his theory of common descent, or that it was the task of the evolutionist to explain the origin of adaptation without invoking supernatural forces, done by Darwin and Wallace through their theory of natural selection. Once these explanations had become available, the philosophers again could have joined the enterprise. They did so, but alas, on the whole by fighting Darwin and by endorsing biologically unsound theories. This has continued into modern times, to wit, the publications of authors like Marjorie Green, Hans Jonas, and so on. I think it is fair to state that biologists like Wrench, Waddington, Simpson, Bertalanffy, Medower, Ayala, Mayr, and Gazellin have made a far greater contribution to a philosophy of biology than the whole older generation of philosophers, including Cassirer, Popper, Russell, Bloch, Bungay, Hempel, and Nagel. It is only the generation of the youngest philosophers, Beckner, Hull, Munson, Wimsatt, Beatty, Brandon, who are finally able to get away from the obsolete biological theories of vitalism, orthogenesis, macrogenesis, and dualism, or the positivist reductionist theories of the older philosophers. 101 needs only to read what such an otherwise so brilliant philosopher as Ernst Cassirer says about Kant's critique of judgment to realize how difficult it is for a traditional philosopher to understand the problems of biology. To their excuse, it must be stated that the guilt is shared by the biologists, who have failed to present a clear analysis of the conceptual problems of biology. They were unable to see the forest for the trees. What principles or concepts would form a good basis on which to found a philosophy of biology? I shall not even attempt to be exhaustive, but from the preceding discussion it should be evident, 1. That a full understanding of organisms cannot be secured through the theories of physics and chemistry alone. 2. That the historical nature of organisms must be fully considered, in particular their possession of an historically acquired genetic program. 3. That individuals at most hierarchical levels, from the cell up, are unique and form populations, the variance of which is one of their major characteristics. 4. That there are two biologies, functional biology, which asks proximate questions, and evolutionary biology, which asks ultimate questions. 5. That the history of biology has been dominated by the establishment of concepts and by their maturation, modification, and occasionally their rejection. 6. That the patterned complexity of living systems is hierarchically organized and that higher levels in the hierarchy are characterized by the emergence of novelties. 7. That observation and comparison are methods in biological research that are fully as scientific and heuristic as the experiment. 8. That an insistence on the autonomy of biology does not mean an endorsement of vitalism, orthogenesis, or any other theory that is in conflict with the laws of chemistry or physics. A philosophy of biology must include a consideration of all major specifically biological concepts, not only those of molecular biology, physiology, and development but also those of evolutionary biology, such as natural selection, inclusive fitness, adaptation, progress, descent, systematics, species, category, classification, behavioral biology and ecology, competition, resource utilization, ecosystem. I might even add a few don'ts. For instance, a philosophy of biology should not waste any time on a futile attempt at theory reduction. It should not take one of the existing philosophies of physics as a starting point. It is depressing to discover how little some prestigious volumes in this field have to do with the actual practices in scientific research, at least in biology. It should not focus most of its attention on laws, considering what small role laws actually play in much of biological theory. In other words, what is needed is an uncommitted philosophy of biology which stays equally far away from vitalism and other unscientific ideologies and from a physicalist reductionism that is unable to do justice to specifically biological phenomena and systems. Biology and Human Thought. C.P. Snow in a well-known essay, 1959, claimed that there is an unbridgeable gap between the cultures of science and the humanities. He is right about the communication gap between physicists and humanists, but there is almost as great a gap between, let us say, physicists and naturalists. Also, there is even a rather pronounced failure of communication between representatives of functional biology and evolutionary biology. Furthermore, functional biology shares with the physical sciences an interest in laws, prediction, all aspects of quantity and quantification and the functional aspects of processes, while in evolutionary biology questions like quality, historicity, information, and selective value are of special interest, questions that are also of concern in the behavioral and social sciences but not in physics. It is not at all unreasonable, therefore, to consider evolutionary biology as something of a bridge between the physical sciences on one hand and the social sciences and the humanities on the other. In a comparison of history and the sciences, Carr, 1961-62, states that history is believed to differ from all the sciences in 5 respects. 1. History deals exclusively with the unique, science with the general. 2. History teaches no lessons. 3. History is unable to predict. 4. History is necessarily subjective. And 5. History, unlike science, involves issues of religion and morality. These differences are valid only for the physical sciences. Statements 1, 3, 4, and 5 are largely true also for evolutionary biology and, as Carr admits, some of these claims, statement 2, for instance, are not even strictly true for history. In other words, the sharp break between science and the non-sciences does not exist. The nature of the impact which science has had on man and his thinking has been controversial. That Copernicus, Darwin, and Freud have profoundly altered man's thinking can hardly be questioned. The impact of the physical sciences in the last few hundred years has been primarily via technology. Kuhn, 1971, claims that for a scientist to exert a real influence on human thinking, he must be read by lay people. No matter how distinguished certain mathematical physicists, including Einstein and Bohr, were, none of them, as far as I can see, has had more than the most tenuous and indirect impact upon the development of extra-scientific thought. Whether or not Kuhn is right, one can certainly claim that some scientists have more influence on the thinking of the intelligent layman than others. Quite likely it depends on the degree with which the scientist's subject matter is of immediate concern to the layperson. Hence, biology, psychology, anthropology, and related sciences naturally have a much greater impact on human thought than the physical sciences. Prior to the rise of science, it was the philosophers who were, so to speak, charged with the task of furthering the understanding of this world. Since the 19th century, philosophy has more and more retreated into the study of the logic and methodology of science, largely abandoning vast areas such as metaphysics, ontology, epistemology that used to be the major concern of philosophy. Much of this area, unfortunately, has been left a virtual no man's land because most scientists are entirely satisfied to pursue their special researches, not at all concerned how the general conclusions derivable from these studies might affect basic issues of human concern and of general epistemology. Philosophers, on the other hand, find it difficult if not impossible to keep up with the rapid advances of science, and as a result turn to trivial or esoteric problems. Opportunities of joint approaches by philosophers and scientists, as profitable as they would be, are all too rarely taken. Biology and human values. It is sometimes stated that, in contrast to religious interpretations, science has the great advantage of being impersonal, detached, unemotional, and thus completely objective. This may well be true for most explanations in the physical sciences, but it is not at all true for much of explanation in the biological sciences. The findings and theories of the biologist are quite often in conflict with traditional values of our society. For instance, Darwin's teacher Adam Sedgwick vigorously rejected the theory of natural selection because it implied the refutation of the argument from design and would thus permit a materialistic explanation of the world, that is, as he saw it, an elimination of God from the explanation of order and adaptation in the world. Biological theory very often is, indeed, very value-laden. As examples one might mention Darwin's theory of common descent, which deprived man of his unique place in the universe. More recently, the argument as to whether and to what extent IQ is genetically determined, particularly when joined to the race problem, and the arguments about sociobiology are apt illustrations. In all these cases, conflicts arose between certain scientific findings or interpretations and certain traditional value systems. No matter how objective scientific research might be, its findings often lead to conclusions that are value-laden. Literary critics have long been aware of the impact which the writings of some scientists have had on novelists and essayists and through them on the public at large. The reports of the happiness and innocence of primitive natives of exotic countries brought home by 18th-century explorers, as erroneous as they were, greatly affected 18th and 19th century writers and, ultimately, political ideologies. It was a tragedy both for biology and for mankind that the currently prevailing framework of our social and political ideals developed and was adopted when the thinking of Western man was largely dominated by the ideas of the scientific revolution, that is, by a set of ideas based on the principles of the physical sciences. This included essentialistic thinking and, as a correlate, a belief in the essential identity of members of a class. Even though the ideological revolution of the 18th century was, to a large extent, a rebellion against feudalism and class privileges, it cannot be denied that the ideals of democracy were in part derived from the stated principles of physicalism. As a consequence, democracy can be interpreted to assert not only equality before the law but also essentialistic identity in all respects. This is expressed in the claim, all men are created equal, which is something very different from the statement, all men have equal rights and are equal before the law. Anyone who believes in the genetic uniqueness of every individual thereby believes in the conclusion, no two individuals are created equal. When evolutionary biology developed in the 19th century, it demonstrated the inapplicability of these physical principles to unique biological individuals, to heterogeneous populations, and to evolutionary systems. Nevertheless, the fused ideology of physicalism and anti-feudalism, usually called democracy, no two people have exactly the same concept of democracy, has taken over in the Western world to such an extent that even the slightest implied criticism, as in these lines, is usually rejected with complete intolerance. Democratic ideology and evolutionary thinking share a high regard for the individual but differ on many other aspects of our value system. The recent controversy over sociobiology is a sad illustration of the intolerance displayed by a segment of our society when statements of a scientist come into conflict with political doctrines. Orwell, 1972, has well described this. At any given moment there is an orthodoxy, a body of ideas, which it is assumed that all right-thinking people will accept without question. It is not exactly forbidden to state this or that or the other, but it is not done so to say. Anyone who challenges the prevailing orthodoxy finds himself silenced with surprising effectiveness. A genuinely unfashionable opinion is almost never given a fair hearing, either in the popular press or in the highbrow periodicals. Scientists, I am afraid, are not entirely innocent of such intolerance. All social reformers from Helvetius, Rousseau, and Robert Owen to certain Marxists, but not Karl Marx himself, have accepted Locke's claim that man at birth is a tabula rasa on which any characteristics can be stamped. Hence, by providing the proper environment and education, one can make anything out of any individual, considering that all of them are potentially identical. This led Robert Owen, 1813, to the claim that by judicious training, the infants of any one class in the world may be readily formed into men of any other class. Since classes were defined socio-economically, at least by implication, Owen's statement had considerable validity. When extended to individuals and stated in a somewhat more extreme form, as was done by the behaviorist John B. Watson in 1924, it becomes very questionable. No wonder that those who hold such optimistic views are dismayed by the claims of those who have investigated the genetics of human characteristics in twin and adoption studies. The demonstration by systematics, physical anthropology, genetics, and behavioral biology that no two individuals in any species, including the human one, are identical has created deep concern among all those who are sincere believers in the principle of human equality. As Haldane and Dobbs-Hansky have pointed out, the dilemma can be escaped by giving a definition of equality which is consonant with modern biological findings. All individuals should be equal before the law and be entitled to equal opportunities. However, considering their biological inequalities, they must be given a diverse environment, for example, diverse educational opportunities, in order to assure equal opportunities. Paradoxically, identicism that ignores biological non-identity is democracy's worst enemy when it comes to implementing the ideals of equal opportunity. biology has an awesome responsibility. It can hardly be denied that it has helped to undermine traditional beliefs and value systems. Many of the most optimistic ideas of the Enlightenment, including equality and the possibility of a perfect society, were ultimately, although very subconsciously, part of physico-theology. It was God who had made this near-perfect world. A belief in such a world was bound to collapse when the belief in God as designer was undermined. Hence Sedgwick's justified anguish. Losing a belief in God led to an existential vacuum and an unsword question as to the meaning of life. Leading thinkers, from the Enlightenment on, felt strongly that biology should not be merely a destroyer of traditional values but also the creator of new value systems. Virtually all biologists are religious, in the deeper sense of this word, even though it may be a religion without revelation, as it was called by Julian Huxley. The unknown and maybe unknowable instills in us a sense of humility and awe, but most of those who tried to replace a belief in God by a belief in man took the wrong path. They defined man as the self, the personal ego, and promoted an ideology of self-concern and egotism which not only fails to bring happiness but is conspicuously destructive in the long run. It would, of course, be equally simple-minded and dangerous to treat man simply as a biological creature, that is, as if he were nothing but an animal. Man, owing to his many unique features, has the capability to develop culture and to transmit acquired information, as well as value systems and ethical norms, to later generations. One would, therefore, get a very one-sided and indeed misleading concept of man, if one were to base one's evaluation of man entirely on the study of subhuman creatures. And yet, the study of animals has given us some of the most significant insights on the nature of man, even where these studies have revealed nothing more but how different man is in some characteristics from his nearest simian relatives. If, instead of defining man as the personal ego or merely a biological creature, one defines man as mankind, an entirely different ethics and ideology is possible. It would be an ideology that is quite compatible with the traditional social value of wanting to better mankind and yet which is compatible with any of the new findings of biology. If this approach is chosen, there will be no conflict between science and the most profound human values. Campbell, 1974, 183-185, Wrench, 1971. Such an approach, at first sight, would seem to be in conflict with the principle of inclusive fitness. This, however, is not necessarily so, for two reasons. First, in the anonymous mass society of modern mankind, it might well contribute to one's own inclusive fitness to work for the improvement of society as a whole. Second, man is a unique species, in that a large amount of cultural inheritance has been added to biological inheritance, and that the nature of this cultural inheritance can affect Darwinian fitness. This interaction has, so far, not been sufficiently considered by those who were interested in the effect of Darwinism on human evolution. It is my personal conviction that the seeming conflicts between inclusive fitness, cultural inheritance, and a sound ethics can be resolved. 82. 3. The changing intellectual milieu of biology. Writing a history of ideas requires that the science of a given historical period be divided into its major problems and that the development of each problem be traced in time. Such a strictly topical treatment has its advantages, but it isolates each problem from its connections with other contemporary problems in science as well as from the total cultural and intellectual milieu of the period. In order to compensate for this grave deficiency, I am providing in this chapter a brief history of biology as a whole and an attempt to relate it to the intellectual milieu of the time. The more specialized treatment of individual biological problems presented in the later chapters should be read against this overview. This introductory chapter will also establish a few connections with areas of functional biology, anatomy, physiology, embryology, behavior, which are not covered elsewhere in this volume. Each age has its own mood or conceptual framework which, though far from being uniform, somehow affects most thought and action. The Athenian culture of the 5th and 4th centuries BC, the otherworldliness of much of the Middle Ages, or the scientific revolution of the 17th century are examples of strikingly differing intellectual milieus. However, it is wrong to assume that any era is always dominated by one mode of thinking, that is, by one explanatory framework or ideology, to be replaced eventually by a new and often very different conceptual framework. In the 18th century, for example, the intellectual framework of Linnaeus differed in just about every respect from that of his contemporary Buffon. Two very different research traditions may coexist, with the adherents of each working in intellectual isolation. For instance, the positivism of the physicists in the second half of the 19th century, resting on an essentialist foundation, coexisted with the Darwinism of the naturalists, which was based on population thinking and asked adaptational questions that were quite meaningless to a positivist physicist. Antiquity. All primitive men are keen naturalists, not surprisingly since their survival depends on a knowledge of nature. They must know potential enemies and sources of livelihood, they are interested in life and death, in illness and birth, in the mind and the differences between man and other living beings. Almost universal among primitive peoples of the world is a belief that all of nature is alive, that even rocks, mountains, and sky are inhabited by spirits, souls, or gods. The powers of the gods are part of nature, and nature herself is active and creative. All religions prior to Judaism were more or less animistic, and their attitude toward the divine was altogether different from the monotheism of Judaism. The interpretation of the world by early man was a direct consequence of his animistic beliefs. Sarton, Thorndike. There are reasons to believe that the science of early civilizations advanced considerably beyond this primitive state, but except for some medical lore, we have next to no information about the biological knowledge of the Sumerians, Babylonians, Egyptians, and other civilizations preceding that of the Greeks. There is no evidence that attempts were made to devise explanatory schemes for whatever facts had been accumulated. The great Greek epics of Homer and Hesiod vividly portray the polytheism of the early Greeks, which contrasted so strikingly with the monotheism of Judaism, Christianity, and Islam. It seems that this polytheism permitted the development of philosophy and early science. For the Greeks there was no powerful single god with a revealed book that would make it a sacrilege to think about natural causes. Nor was there a powerful priesthood, as in Babylon, Egypt, and Israel, to claim a monopoly on thought about the natural and the supernatural. Nothing, therefore, prevented different thinkers in Greece from coming to different conclusions. As far as Greek biology is concerned, we can distinguish three great traditions. The first is a natural history tradition, based on the knowledge of local plants and animals, a tradition going back to our pre-human ancestors. This knowledge was handed by word of mouth from generation to generation, and it is rather certain that the little we know of it through Aristotle's Historia Animalium and the writings of Theophrastus on plants provides only a glimpse at a vastly greater store of knowledge. The information about wild animals was valuably supplemented in many cultures by experience with domestic animals. Individual behavior, birth, growth, nutrition, sickness, death, and many other phenomena of biological significance are far more easily observed in domestic than in wild animals. Since most of these manifestations of life in animals are the same as in man, they encouraged comparative studies. In due time this made an important contribution to the development of research in anatomy and medical science. The second Greek tradition, that of philosophy, originated with the Ionian philosophers Thales, Anaximander, Anaximenes, and their followers, who started a radically new approach. 3. They related natural phenomena to natural causes and natural origins, not to spirits, gods, or other supernatural agents. In their search for a unifying concept that would account for many different phenomena, they often postulated an ultimate cause or element from which all else originated, such as water, air, earth, or nondescript matter. Apparently, these Ionian philosophers had considerable knowledge of the achievements of the Babylonian and other Near Eastern cultures and adopted some of their interpretations, primarily those relating to inanimate nature. The speculations of the Ionians on the origin of living beings had no lasting influence. Of a little more significance were their thoughts about human physiology. The real importance of the Ionian school is that it signifies the beginnings of science, that is, they sought natural causes for natural phenomena. The center of philosophical thinking shifted later, in the 6th and in the 5th century BC, to the Greek colonies in Sicily and southern Italy, where the key figures were Pythagoras, Xenophanes, Parmenides, and Empedocles. Pythagoras, with his emphasis on numbers and quantities, started a powerful tradition affecting not only the physical sciences but also biology. Empedocles seems to have thought more about biological matters than any of his predecessors, but little of his teaching is preserved. He is now best known for his postulation of the existence of 4 elements: fire, air, water, and earth. The entire material world, according to him, is composed of varying combinations of these 4 elements, either leading to greater homogeneity or else to greater mixing. A belief in these 4 elements continued for more than 2,000 years. A concern with heterogeneity versus homogeneity appears again in the writings of the 19th century zoologist K. E. von Baer and in those of the philosopher Herbert Spencer. The ensuing decades saw the establishment of 2 great philosophical traditions, that of Heraclitus, who stressed change, everything is in flux, and that of Democritus, the founder of atomism, who by contrast stressed the unchanging constancy of the atoms, the ultimate components of everything. Democritus seems to have written a great deal about biological matters, though little survives, and some of Aristotle's ideas are believed to have been derived from him. Apparently he was the first to have posed a problem that has split philosophers ever since: does organization of phenomena, particularly in the world of life, result purely from chance, or is it necessary, owing to the structure of the elementary components, the atoms? Chance or necessity has ever since been the theme of controversies among philosophers. For it provided Monod, 1970, with the title of his well-known book. It was Darwin, more than 2,200 years later, who showed that chance and necessity are not the only 2 options, and that the 2-step process of natural selection avoids Democritus's dilemma. These early Greek philosophers recognized that such familiar physiological phenomena as locomotion, nutrition, perception, and reproduction require explanation. What strikes the modern student as strange is the fact that they thought they could provide such explanation merely by concentrated thinking about the respective problem. Admittedly, at the time in which they lived, this was perhaps the only conceivable approach to these problems. The situation slowly changed, particularly when experimental science began to emancipate itself from philosophy during the late Middle Ages and in the Renaissance. The lingering tradition of providing scientific explanation by mere philosophizing had an increasingly deleterious effect on scientific research in the 18th and 19th centuries, leading to Helmholtz's bitter complaint about the arrogance of the philosophers who rejected his experimental findings because these were in conflict with their deductions. The objections of essentialistic philosophers to Darwinism is another illustration of this attitude. In ancient Greece, however, the deductive philosophical approach helped to raise questions which no one had asked before. It led to an ever more precise formulation of these questions, and it thereby set the stage for a purely scientific approach which ultimately replaced philosophizing. The third great ancient tradition, coexisting with natural history and the philosophical tradition, was the biomedical tradition of the school of Hippocrates, about 450 to 377 BC, which developed an extensive corpus of anatomical and physiological knowledge and theory. This body of knowledge, further developed by the Alexandrians, Herophilus and Erasistratus, and by Galen and his school, formed the basis of the revival of anatomy and physiology in the Renaissance, particularly in the Italian schools. Research in human anatomy and physiology was the main interest of biology from the post-Aristotelian period until the 18th century. For science as a whole, however, indeed for the entire Western thinking, developments in philosophy were far more important than concrete discoveries in anatomy and physiology. 2 Greek philosophers, Plato and Aristotle, had a greater influence on the subsequent development of science than any others. Plato, ca. 427 to 347 BC, had a special interest in geometry which powerfully affected his thinking. His observation that a triangle, no matter what combination of angles it has, is always a triangle, discontinuously different from a quadrangle or any other polygon, became the basis for his essentialism, a philosophy quite unsuitable for biology. It took more than 2,000 years for biology, under the influence of Darwin, to escape the paralyzing grip of essentialism. Plato's influence was equally unfortunate in matters more strictly biological. With the roots of his thinking in geometry, it is not surprising that he had little use for natural history observations. Indeed, in the Timaeus he expressly states that no true knowledge can be acquired through the observations of the senses, but only a pleasure to the eye. His emphasis on the soul and on the architect, demiurge, of the cosmos permitted, through the Neoplatonists, a connection with Christian dogma which dominated the thinking of Western man up to the 17th century. Without questioning the importance of Plato for the history of philosophy, I must say that for biology he was a disaster. His inappropriate concepts influenced biology adversely for centuries. The rise of modern biological thought is, in part, the emancipation from Platonic thinking. With Aristotle, the story is different. Aristotle. No one prior to Darwin has made a greater contribution to our understanding of the living world than Aristotle, 384–322 BC. 6. His knowledge of biological matters was vast and had diverse sources. In his youth he was educated by Asclepiadic physicians, later he spent 3 years of his life on the island of Lesbos, where he evidently devoted much time to the study of marine organisms. In almost any portion of the history of biology one has to start with Aristotle. He was the first to distinguish various of the disciplines of biology and to devote to them monographic treatments, De Partibus Animalium, De Generatione Animalium, and so forth. He was the first to discover the great heuristic value of comparison and is rightly celebrated as the founder of the comparative method. He was the first to give detailed life histories of a large number of species of animals. He devoted an entire book to reproductive biology and life histories, Edgerton, 1975. He was intensely interested in the phenomenon of organic diversity, as well as in the meaning of the differences among animals and plants. Although he did not propose a formal classification, he classified animals according to certain criteria, and his arrangement of the invertebrates was superior to that of Linnaeus 2,000 years later. Perhaps the least distinguished part of his biological corpus is his physiology, where he largely adopted traditional ideas. Far more than his predecessors, he was an empiricist. His speculations always go back to observations he had made. At one time, De Generatione Animalium 760b28, he states rather clearly that the information one receives from one's senses has primacy over what reason tells one. In that respect he was a world apart from the so-called Aristotelians among the scholastics, who reasoned out all problems. Aristotle's outstanding characteristic was that he searched for causes. He was not satisfied merely to ask how questions, but was amazingly modern by asking also why questions. Why does an organism grow from a fertilized egg to the perfect adult form? Why is the world of living organisms so rich in end-directed activities and behaviors? He clearly saw that raw matter lacks the capacity to develop the complex form of an organism. Something additional had to be present, for which he used the word eidos, a term which he defined entirely differently from Plato. Aristotle's eidos is a teleonomic principle which performed in Aristotle's thinking precisely what the genetic program of the modern biologist performs. In contrast to Plato, who posited an outside force to explain the regularity of nature and especially its tendency toward reaching complexity and goals, Aristotle taught that natural substances act according to their own properties, and that all phenomena of nature are processes or the manifestations of processes. And since all processes have an end, he considered the study of ends as an essential component of the study of nature. Consequently, for Aristotle all structures and biological activities have a biological meaning or, as we would now say, an adaptive significance. One of Aristotle's major aims was to elucidate such meanings. Aristotelian why questions have played an important heuristic role in the history of biology. Why is the most important question the evolutionary biologist asks in all of his researches. There are four ways of conceiving the origin and the nature of the world. 1. A static world of short duration, the Judeo-Christian created world. 2. A static world of unlimited duration, Aristotle's worldview. 3. A cyclical change in the state of the world in which periods of golden ages alternate with periods of decay and rebirth. And 4. A gradually evolving world, Lamarck, Darwin. Aristotle's belief in an essentially perfect world precluded any belief in evolution. Aristotle has received full recognition for his pioneering thoughts only within recent decades. The bad reputation he had in past centuries had several causes. One is that the Thomists adopted him as their authoritative philosopher, and when scholasticism came into disrepute, Aristotle automatically shared in the eclipse. Even more important is the fact that during the scientific revolution of the 16th and 17th centuries, almost the entire emphasis was on the physical sciences. Aristotle, who developed a remarkable philosophy of biology, unfortunately simultaneously believed that one could deal with macrocosm and microcosm in the same way, and applied his biological thinking to physics and cosmology. The results were rather unfortunate, as Francis Bacon, Descartes, and many other authors of the 16th, 17th, and 18th centuries never tired of pointing out. The scorn heaped on Aristotle by these authors is difficult to understand considering the excellence and originality of most of his work. The renewed appreciation in modern times of Aristotle's importance grew to the degree that the biological sciences emancipated themselves from the physical sciences. Only when the dual nature of living organisms was fully understood in our time was it realized that the blueprint of development and activity, the genetic program, represents the formative principle which Aristotle had postulated. As a result, we are beginning to be more tolerant of Aristotle. The world of philosophers and physicists was for hundreds of years completely deaf to the assertion of naturalists such as Aristotle that something more than the laws of physics was needed to produce a frog from a frog egg and a chicken from a chicken egg. Mayr, 1976. Nor does this require any ella vital, nisus formativus, entelechy, or living spirit. All it requires is the recognition that complex biological systems are the product of genetic programs that have a history of more than 3,000 million years. Nothing has caused more time-consuming and adrenaline-producing controversies than the myth that macrocosm and microcosm obey exactly the same laws. There is little indication that this insight has yet reached most philosophers, but it is beginning to be understood among biologists. After Aristotle there was a continuation of the three Greek biological traditions. Natural history, particularly the description and classification of plants, reached a height in the writings of Theophrastus and Dioscorides, while Pliny, AD 2379, whose interests were zoological, was an encyclopedic compiler. The biomedical tradition reached its height in Galen, AD 131–200, whose influence endured until the 19th century. In post-Aristotelian philosophy, a polarity developed between the Epicureans and the Stoics. Epicurus, 342–271 BC, building on the foundation laid by Democritus, believed everything is made of unchanging atoms which whirl about and collide at random. He established a well-thought-out materialistic explanation of the inanimate and living world, all things happening through natural causes. Life was viewed by him as due to the motions of lifeless matter. His explanation as to how manifestations of life originate through the assembly of appropriate configurations of atoms was remarkably modern. His follower Lucretius, 99–55 BC, was an equally uncompromising atomistic materialist. Both of them rejected Aristotle's teleological ideas, Lucretius presenting a well-reasoned argument against the concept of design. He states many of the arguments that were raised again in the 18th and 19th centuries. Yet, Aristotle was entirely justified in his criticism of those atomists who, through a purely accidental interaction of water and fire, produced lions and oak trees. Galen agreed with him. The argument of the Epicureans was mainly directed against the Stoics, who supported pantheistic ideas and believed in a designed world created for the benefit of man. According to them, it is the object of philosophy to understand the order of the world. Later, natural theology was derived from Stoic thought. The Stoics rejected chance as a factor in the world, everything is teleological and deterministic. Their attitude was strictly anthropocentric. Stressing the differences between intelligent man and instinct-guided animals, Pollens, 1948. Nothing of any real consequence happened in biology after Lucretius and Galen until the Renaissance. The Arabs, so far as I can determine, made no important contributions to biology. This is even true for two Arab scholars, Avicenna, 980-1037, and Averroes, Ibn Rosh, 1120-1198, who showed a particular interest in biological matters. It was, however, through Arab translations that Aristotle again became known to the Western world. This was perhaps the greatest contribution the Arabs made to the history of biology. Another of their contributions was more indirect. The Greeks were great thinkers but experimented only to a limited extent, Regenbogen, 1931. By contrast, the Arabs were great experimenters, and one can go so far as saying that they laid the foundation on which experimental science later arose. The pathway to this ultimate goal was quite tortuous, with alchemy being the most important intermediate step. The Christian world picture. When Christianity conquered the West, the Greek concept of an eternal, essentially static world was replaced by an entirely new one. Christian theology is dominated by the concept of creation. The world according to the Bible is a recently created one, all knowledge of which is contained in the revealed word. This dogma precluded the need, indeed the possibility, of asking any why questions or of harboring any thought of evolution. The world, having been created by God, was, as later expressed by Leibniz, the best of all possible worlds. Man's attitude toward nature was governed by God's command to be fruitful and multiply, and fill the earth and subdue it, and have dominion over the fish of the sea, and over the birds of the air, and over every living thing that moves upon the earth. Genesis 1:28. Nature was subservient to man. There was nothing in the Hebrew or Christian dogma of that oneness with nature felt by the animists or reflected in many Buddhist beliefs. The recent reverence for the environment was alien to the great monotheistic religions of the Near East. White, 1967. No other development in Christianity was as important to biology as the worldview known as natural theology. In the writings of the Church Fathers, nature is sometimes compared to a book, a natural analog to the revealed book of the Christian religion, the Bible. The equivalence of the two books suggests that a study of the book of nature, God's creation, would allow the development of a natural theology, supplementing the revealed theology of the Bible. Christian natural theology was not a new concept. The harmony of the world, and the seeming perfection of the adaptations of the world of life, had impressed observers again and again, long before the rise of Christianity. As far back as the Old Kingdom of Egypt, Memphis, 2,000 years before the Greeks and Hebrews, a creative intelligence had been postulated that had designed the phenomena of nature. More definite teleological statements can be found in Herodotus and Xenophon. Plato saw the world as the creation of an intelligent, good, reasoning, and divine artisan. The idea that the earth is a designed and fit environment for life was further cultivated and enriched by the Stoics. Galen strongly endorsed the concept of design, the work of a wise and powerful creator. But no one was more important for the development of natural theology than St. Thomas Aquinas. A teleological worldview became dominant in Western thinking through his writings. In his Summa Theologia, the fifth argument proving the existence of God is based on the order and harmony of the world, which requires that there must be an intelligent being directing all natural things to their end. Despite the teachings of natural theology, the scholastic age was not favorable for the development of the natural sciences. The scholastics were rationalists. It was their endeavor to determine the truth by logic, not by observation or experiment. Hence their interminable disputations. Teaching and the search for truth, as they exercised it, was the privilege of the clerics. The study of natural things, indeed any empirical approach, was on the whole despised. The dominant philosophy of scholasticism was the Thomistic one, believed by Aquinas to have been mainly derived from Aristotle. This philosophy is known under the strangely misleading name of realism. Its most characteristic aspect, as it appears to a modern biologist, is its total support of essentialism. Nominalism, the only other powerful school of scholastic philosophy, stressed that only individuals exist, bracketed together into classes by names. Nominalism had no influence on biology during the Middle Ages, and it is still not at all clear whether and to what extent nominalism contributed to the eventual rise of empiricism and population thinking. The concept of the Christian Church that the revealed word had overriding authority was, curiously, extended in medieval times to other writings, particularly to Aristotle's work and even to the writings of Arab scholars like Avicenna. When an argument arose as to how many teeth the horse has, one looked it up in Aristotle rather than in the mouth of a horse. The inner-directed world of medieval Christianity paid little attention to nature. This began to change somewhat in the 12th and 13th centuries. Hildegard of Bingen, 1098–1179, and Albertus Magnus, 1193–1280, wrote on natural history, but their work is not in the same class with that of the splendid observer Frederick II, 1194–1250, whose superb art of falconry, De Arte Venandi, was many centuries ahead of its time in its interest in the morphology and biology of birds. Frederick's genuine understanding of the living animal, so obviously based on personal experience, loomed large above the level of other contemporary natural history writings, exemplified by the uncritical compilations of Acantempré or Beauvais, Stresemann, 1975. Frederick's influence was manifold. He had some of Aristotle's writings translated into Latin and was a patron of the medical school of Salerno, founded 1150, where human bodies were dissected for the first time in more than 1,000 years. Beginning with Salerno, universities were founded in various parts of Europe, particularly in Italy, Bologna, Padova, France, Paris, Montpellier, and England, Oxford and Cambridge. They had exceedingly different backgrounds, some originating as medical schools or law schools, others, like the Sorbonne, founded around 1200, as schools of theology. Most of them soon became centers of scholasticism, and it has been argued whether their existence had a beneficial or detrimental effect on Western learning. In some areas, anatomy, for instance, they eventually became the centers of progressive scholarship. As far as biology as a whole is concerned, it was not until the late 18th and early 19th century that the universities became centers of biological research. Logic, cosmology, and physics, Crombie, 1952, had a remarkable renaissance in the later Middle Ages, the high intellectual level of which has been appreciated only in the last generation. By comparison, biology continued to be dormant. The only aspects of living nature that received attention were problems of medicine and human biology. One looks in vain for any attempt to grapple with the deeper problems of life so fascinating to later centuries and to the modern mind. One has the feeling that this lack of interest was somehow connected with the extreme piety of the period, which did not allow questions about God's creation, but then one wonders why this taboo did not extend to physics and cosmology. Was it that the prestige of mathematics and its theological neutrality led automatically to physics and cosmology, while there was no such entering wedge for biology? Natural theology eventually provided such an opening, but effectively not until the 17th century. Was it the discovery of exotic countries, where the same heavenly bodies occurred and the same laws of physics held as in Europe, but where entirely different faunas and floras were found? Was it that the phenomena of life require asking far more sophisticated questions than those raised by the study of falling bodies? Who knows? We still lack an adequate analysis for the lag between the awakening in the mechanical sciences and the post-medieval revival of biology. The Renaissance. During the Renaissance, a new interest developed in natural history and anatomy. Both, in a way, were parts of medicine, and the most active investigators in these fields were usually professors of medicine or practicing physicians. The study of medicinal plants was popular throughout the later Middle Ages, as reflected in the number of herbals, particularly after the works of Theophrastus and Dioscorides had again become available. But it was the plant books of Brunfels, Bach, and Fuchs which heralded a new back-to-nature movement in the study of plants, see Chapter 4. The liberating influence of travel eventually made itself felt as well. It began with the Crusades, continued with the travels of the Venetian merchants, such as Marco Polo's visit to China, and the voyages of the Portuguese seafarers, and culminated in the discovery of the New World by Columbus, 1492. One of the decisive consequences of these travels was the sudden recognition of the immense diversity of animal and plant life in all parts of the globe. This realization led to the publication of several encyclopedic natural histories by Wotton, Gessner, and Aldrovandi, and to more specialized ones by Bellin on birds and by Rondelet on marine organisms. Anatomy was taught in medieval medical schools, particularly in Italy and France, but in a peculiarly literary way. The professor of medicine would recite Galen, while an assistant surgeon dissected the corresponding parts of the body. This was poorly done, and the oratory and the disputations of the professors, all of them merely interpreting Galen, were considered to be far more important than the dissection. It was Andreas Vesalius, 1514–1564, more than anyone else, who changed all this. He himself actively participated in the dissections, invented new dissecting instruments, and finally published an anatomical work with magnificent illustrations, De Humani Corporis Fabrica, 1543. In this he corrected a number of errors of Galen, but he himself made only a rather limited number of discoveries and retained the Aristotelian framework of physiological explanation. Nevertheless, a new era in anatomy started with Vesalius, in which the scholastic reliance on the traditional texts was replaced by personal observations. Vesalius' successors, including Fallopio, Fabricius of Aquapendente, Eustachi, Caesalpino, and Severino, not only made important discoveries in human anatomy but several of them also made important contributions to comparative anatomy and to embryology. The particular importance of this development is that it provided the basis for the new start in physiology. Applied science, that is, technology and the engineering arts, prepared the ground during the Renaissance for an entirely new way of looking at things. The mechanization of the world picture which resulted from this movement reached a first culmination in the thought of Galileo Galilei, 1564–1642, and in that of his students and associates. Nature for them was a law-bound system of matter in motion. Motion was the gist of everything and everything had to have a mechanical cause. His stress on quantification was expressed in the admonition to measure what can be measured and to make measurable what cannot be measured. This led to the development and use of instruments in order to determine quantities, to the calculation of regularities which led to the establishment of general laws, and to a dependence on observation and experiment rather than on the word of authority. This meant in particular a rejection of certain aspects of Aristotelianism which had become so authoritative through the influence of the Thomists. The attacks on Aristotle came not only from the physicists but also from philosophy. Francis Bacon, who was particularly scathing in his anti-Aristotelianism, became the prophet of the method of induction, though his own biological theories were entirely deductive constructions. Bacon's great merit, however, was his unceasing questioning of authority and his emphasis on the incompleteness of our knowledge, in contrast to the medieval belief that knowledge was complete. The most positive contributions of the scientific revolution, as far as biology is concerned, was the development of a new attitude toward investigation. It consisted in a complete rejection of sterile scholasticism, which endeavored to find the truth merely by logic. There was greater emphasis on experiment and observation, that is, on the collecting of facts. This favored the explanation of regularities in the phenomena of the world by natural laws, which it became the task of the scientist to discover. The actual number of concrete contributions to biology made by a mechanistic approach is very small. It includes Harvey's measurements of blood volume, which were an important link in the chain of his argument in favor of a circulation of blood, and the studies of some anatomists, particularly Giovanni Alfonso Borelli, 1608–1679, on locomotion. Indeed, no other branch of physiology is as suitable for a mechanical analysis as the movement of extremities, articulations, and muscles. The publication of Newton's Principia in 1687, which proposed a mechanization of the entire inanimate world on a mathematical basis, greatly reinforced the mechanistic approach to physiology. More than ever, it now became fashionable to explain everything in physical terms of forces and motion, as inappropriate as such an explanation was for most biological phenomena. The explanation of warm-bloodedness in mammals and birds as due to friction of the blood in the blood vessels, for instance, was accepted for about 150 years, even though this would have been refuted by a few simple experiments or by the observation of blood circulation in cold-blooded amphibians and fish of the same body size as mice or birds. Facile physicalist explanations were a great impediment of biological research during the 17th and 18th centuries, and sometimes even later. As Roddy, 1913, 8, pointed out long ago, the triumph of the physical sciences during the scientific revolution was, in many ways, a defeat for biology, and for all those specifically biological modes of thinking that did not receive recognition again until the 19th and 20th centuries. Teleonomy, maligned as the search for final causes, systems thinking, the study of qualitative and emergent properties and of historical developments. All this was neglected, if not actively opposed and ridiculed. The response of the life scientists to the attacks of the physical scientists was either a futile attempt to express biological processes in the quite unsuitable terms of the physicists, movements and forces, or an equally futile escape into vitalism or supernatural explanations. It is embarrassingly recent that biologists have had the intellectual strength to develop an explanatory paradigm that fully takes into consideration the unique properties of the world of life and yet is fully consistent with the laws of chemistry and physics. See Chapter 1. Descartes. No one perhaps contributed more to the spread of the mechanistic world picture than the philosopher René Descartes, 1596–1650. As with Plato, his thought was greatly influenced by mathematics, his most brilliant contribution probably being the invention of analytical geometry. His attacks on Aristotelian cosmology were legitimate and constructive, even though ultimately his own proposals did not prevail either. However, his proposal to reduce organisms to a class of automata had the unfortunate consequence of offending every biologist who had even the slightest understanding of organisms. Descartes' crass mechanism encountered, therefore, violent opposition. This expressed itself usually in an equally absurd teleological vitalism. It is presumably no coincidence that France, the country with the most extreme mechanists from Descartes to La Mettrie and Holbach, was perhaps also the most active center of vitalism. Descartes claims that organisms are merely automata, that the human species differs from them by having a soul, that all science must be based on mathematics, and many other of his sweepingly dogmatic statements, since proven to be quite erroneous, created a millstone around the neck of biology, the effects of which, in the mechanism-vitalism controversy, have carried through to the end of the 19th century. One of the weakest components of Descartes' thinking concerned origins. He thought that organisms were formed by the fortuitous coming together of particles. Ultimately, this meant explaining nature as the result of blind accident. This thesis, however, was clearly contradicted by the order of nature and the remarkable adaptations of all creatures, as demonstrated by the naturalists. What is most astounding about Descartes is that, his own protestations notwithstanding, much of the framework of his reasoning is Thomistic. His way of thinking is well illustrated by his conclusions concerning his own existence. I concluded that I was a substance whose whole essence or nature consists in thinking, and whose existence depends neither on its location in space nor on any material thing. Thus the self, or rather the soul, by which I am what I am, is entirely distinct from the body, is indeed easier to know than the body, and would not cease to be what it is, even if there were no body. Discourse on Method, p. 4. Most of his physiological conclusions were arrived at by deduction rather than by observation or experiment. Like Plato before him, Descartes demonstrated by the failure of his method that one cannot solve biological problems through mathematical reasoning. Much still remains to be done in the investigation of Descartes' influence on the subsequent development of biology, particularly in France. This includes the question how far Cartesianism was responsible for the cool reception of evolutionary thinking, for example, of Lamarck, in France in later centuries. What is particularly remarkable, in hindsight, is the naivete with which purely physical explanations of the most simplistic form were accepted by Descartes and some of his followers. Buffon, for instance, concluded that a single force, namely gravitational attraction, is the cause of all phenomena of brute matter, and this force, combined with that of heat, produces the living molecules on which depend all the effects of organized bodies. Over. Philosophy, 41. Perhaps biology had to go through a phase in which the sterile physicalism of Descartes was adopted. Aristotle's perfectly sound demonstration that biological form could not be understood in terms of mere inanimate matter had unfortunately been vulgarized by the scholastics, who replaced Aristotle's psyche by the soul of Christian dogma. Aristotelian Galenic physiology had indeed become scientifically unacceptable when interpreted in terms of the Christian soul. Under these circumstances Descartes had two options. He could either go back to the Aristotelian form and redefine it, as does the modern biologist in his genetic program, or he could entirely throw out the Christian soul, as far as animals are concerned, without replacing it by anything, leaving the organism a piece of inanimate matter like all other inanimate things. The latter was the option he adopted, an option obviously unacceptable to any biologist who knew that an organism is more than just inanimate matter. Not being much of a biologist, Descartes did not think so. It was only when he contemplated man that Descartes realized that his thesis would not do. He then adopted the dualism between body and soul, a dualism, not new with Descartes, which has plagued us ever since. The dominance of the mechanical worldview was not complete. Indeed, the claims of the Galilean mechanists and of the Cartesians were so extreme that they elicited a number of countermovements almost at once. Two among these are of particular interest in the history of biology: the rise of a qualitative chemical tradition and the study of diversity. Both movements were, in part, rooted in the scientific revolution. A novel movement in 16th-century physiology concentrated on quality and chemical constituents instead of on movement and forces. This approach was by no means antiphysicalist in principle, because it utilized concepts, laws, and mechanisms in the explanation of living processes that had first been developed to explain processes in the inanimate world. I refer to Paracelsus, 1493 to 1541, and his followers, to the alchemists, and to the school usually referred to as the iatrochemists. As unpromising as this new movement was at first, and as wrong in particulars, in the long run it had a far longer lasting impact on the explanation of biological processes than the strictly mechanistic ones. Paracelsus, part genius and part charlatan, a believer in magic and occult forces, rejected the importance of the traditional four elements of the Greeks, replacing them by actual chemicals, particularly sulfur, mercury, and salt. His concept of life processes as chemical processes started an entirely new tradition which, through J. H. van Helmont, 1577 to 1644, was the beginning of a new phase in the history of physiology. In Van Helmont's writings we find a peculiar mixture of superstition, vitalism, and extraordinarily perceptive observations. He coined the term gas and did significant research on CCB. He recognized the acidity of the stomach and the alkalinity of the small intestines, thereby initiating a whole new field of research in nutritional biology. The chemicalization of physiology continued through his followers such as Stahl. The discovery of diversity. One of the objectives of attempts to provide a mechanistic explanation of all phenomena was to further the unity of science. It became the ambition of physical scientists to reduce the phenomena of the universe to a minimal number of laws. Owing to the discovery of the almost unlimited diversity of animals and plants, an almost diametrically opposite tendency developed in the study of living organisms. The herbalists and encyclopedists had revived the tradition of Theophrastus and Aristotle, discovering and describing with loving detail diverse kinds of organisms. More and more naturalists devoted themselves to the study of nature's diversity and discovered that the world of creation is far richer than anyone had imagined. And the glory of God could be studied in any of his creatures, from the lowliest ones up to the rhinoceroses and elephants admired by Dyer or Gessner. The scientific revolution coincidentally made a major contribution to the interest in diversity. The development of all sorts of 100 new instruments was one of the products of the spirit of mechanization, the most important among them for the biologist being the microscope. Microscopy opened up a new world for the biologist. Even though the earliest microscopes permitted only a tenfold magnification, this was sufficient to reveal the existence of an entirely unexpected living microcosmos, particularly of aquatic organisms invisible to the naked eye. The two outstanding early practitioners of microscopy were Anton van Leeuwenhoek, 1632–1723, and Marcello Malpighi, 1628–1694. They provided descriptions of animal and plant tissues, the birth of histology, and they discovered freshwater plankton, blood cells, and even the spermatozoon. The work of these early microscopists is characterized by the pleasure of discovery. Without a goal, they looked at almost any magnifiable object and described what they saw. One finds very little biological theory in their writings. Incidentally, the earliest applications of electron microscopy, 300 years later, were characterized by a similar attitude. It was also in this period that the insects were discovered to be a proper subject for scientific study. Francesco Redi in 1668 showed that insects are not the results of spontaneous generation but develop from eggs laid by fertilized females. Jan Swammerdam, 1637–1680, did superb anatomical work on the honey bee and other insects. Pierre Lyonnais, Ferk Alt de Riamour, de Serres, Leonard Frisch, and Roezel von Rosenhoff were other naturalists of the 17th and 18th centuries who made major contributions to the knowledge of insects. Most of them were motivated by the sheer joy of describing what they discovered, even if it was nothing more than the 4041 muscles of a caterpillar. Lyonnais, 1762, see Chapter 4. The enthusiasm over the extraordinary diversity of the living world was fired still further by the success of voyages and individual explorers bringing back exotic plants and animals from all continents. Captain Cook had the Forsters, father and son, as naturalists on one of his voyages. The younger Forster inspired Alexander von Humboldt, who in turn inspired the young Charles Darwin. The era of overseas travel and explorations resulted in a veritable obsession with exotic organisms and led to the establishment of vast collections, as illustrated by those of the patrons of Linnaeus in the Netherlands, of Banks and his competitors in London, and of the Jardin du Roi in Paris, which was directed by Buffon. The exponential growth of the collections produced the foremost need of the period, classification. Beginning with Cisalpino, 1583, Tournefort, and John Ray, whose work is analyzed in Chapter 4, the age of classification reached its climax with Carl Linnaeus, 1707–1778. His importance was exalted in his lifetime beyond that of any naturalist since Aristotle. Yet 100 years later Linnaeus was denigrated as a pedantic throwback to the scholastic period. We now see him as a child of his time, outstanding in some ways and blind in others. As a local naturalist, like John Ray before him, he observed the clear-cut discontinuity between species and assumed the impossibility of one species changing into another one. His insistence on the constancy and sharp delimitation of species, at least in his earlier writings, set the stage for the subsequent development of an evolutionary theory. It is only in recent years that one has remembered again Linnaeus's contribution to phytogeography and ecology. Most of his followers unfortunately lacked Linnaeus's flair and found ample satisfaction in describing new species. Not all naturalists of the period succumbed to the craze of species description. J. G. Kallreuter, 1733–1806, for instance, although starting out from a rather traditional interest in the nature of species, made pioneering contributions to genetics, fertilization, and flower biology in plants. These studies were extended by C. K. Sprengel, 1750–1816, through copious experiments on fertilization in plants. The work of these two investigators, although virtually ignored in their lifetime, was part of the foundation on which Darwin later based his experimental research on fertilization, and fertility, in plants. A tradition in natural history very different from that of Linnaeus was initiated by Buffon, whose Histoire naturelle, L. 749 ff., was read by practically every educated European. With its emphasis on living animals and their life history, this work had a tremendous impact on natural history studies, an impact that did not come 101. 102. To full fruition until the modern age of ethology and ecology. The study of natural history in the 18th and early 19th centuries was almost completely in the hands of amateurs, particularly country parsons such as Zorn, White, Vicar of Selborne, and C. L. Bram. Buffon, as brilliant as he was as a popularizer, exerted perhaps his greatest influence through his stimulating, often daringly novel, ideas. He had an enormously liberating influence on contemporary thinking, in such divergent fields as cosmology, embryonic development, the species, the natural system, and the history of the Earth. He never quite advanced to a theory of evolution, but unquestionably he prepared the ground for Lamarck, see Chapter 7. I entirely agree with Nordenskjöld's evaluation of Buffon, 1928, 229. In the purely theoretical sphere he was the foremost biologist of the 18th century, the one who possessed the greatest wealth of ideas, of real benefit to subsequent ages and exerting an influence stretching far into the future. Diversity, of course, is a phenomenon that does not seem to fit at all the Newtonian paradigm of physical laws. Yet, since laws were evidence for the existence of a law-giving creator, the discovery of laws regulating diversity became a challenge for students of diversity from Mayr to the Quinnerians and to Louis Agassiz. These endeavors, largely against the intention of their authors, provided much evidence for evolution. Linnaeus, for all intents and purposes, founded the science of systematics, and Buffon made the study of natural history everybody's pastime. Physiology reached new heights with Haller and embryology with Bonnet and Wolff. As a consequence, biology's degree, greatly eclipsed by the physical sciences in the 17th century, began to come into its own in the middle of the 18th century. The dominant interest of the century, clearly, was the description, comparison, and classification of organisms. Anatomy, which had been primarily a method of physiological research since its very beginning, now became increasingly comparative. It developed into another method of studying diversity. The comparative method, one of the two great methods of science, experimentation being the other one, had its real beginning in the second half of the 18th century. To be sure, comparative studies had been conducted since the 16th century by Bellin, Fabrizio, and Severino, but they became a systematic research method only in the hands of Camper, Hunter, Pallas, Daubenton, and particularly Wieck d'Azur. The new tradition, thus established, reached a first peak in the work of Cuvier, who in a series of methodical studies, with particular emphasis on the invertebrates, demonstrated the absence of any intermediates between the major phyla of animals, thus completely refuting the existence of a scala naturae. After 1859, comparative anatomical studies, of course, provided some of the most convincing evidence in favor of Darwin's theory of common descent. Natural theology. It is difficult for a modern person to appreciate the unity of science and Christian religion that existed at the time of the Renaissance and far into the 18th century. The reason why there was no conflict between science and theology was that the two had been synthesized as natural theology, physico-theology, the science of the day. The natural theologian studied the works of the Creator for the sake of theology. Nature for him was convincing proof for the existence of a supreme being, for how else could one explain the harmony and purposiveness of the creation? This justified the study of nature, an activity about which many of the devout were rather a little self-conscious, particularly in the 17th century. The spirit of natural theology still dominated authors as late as Leibniz, Linnaeus, and Herder, and British science up to the middle of the 19th century. The total domination of all scientific activities and thinking by the concepts of natural theology has long been understood by the historians of science, and we have a large number of perceptive treatments. The mechanization of the world picture caused a serious dilemma for the devout. If he followed the claims of the physical scientist, he had to assume that the world had been created at a single time and that at the same time natural laws, secondary causes, had been established which required only a minimal amount of divine intervention in subsequent periods. The task of the natural philosopher was to study the proximate causes by which these divine laws manifested themselves. This interpretation fitted the phenomena of the physical world reasonably well, but was completely contradicted by the phenomena of the living world. Here such a diversity of individual actions and interactions is observed that it becomes inconceivable to explain it by a limited number of basic laws. Everything in the living world seemed to be 104. So unpredictable, so special, and so unique that the observing naturalist found it necessary to invoke the Creator, his thought, and his activity in every detail of the life of every individual of every kind of organism. This, however, seemed likewise unthinkable because, as one of the commentators said, a ruler supervises his workers but does not himself perform all the tasks of a working man. Thus neither alternative seemed acceptable. The next 200 years were filled with endeavors to escape this dilemma, but there was no escape within the framework of creationist dogma. Consequently, the two schools of thought continued. The physical scientists saw in God the power who had instituted, at the time of creation, the laws governing the processes of this world. By contrast, the devout naturalists who studied living nature concluded that the basic laws of Galileo and Newton were meaningless as far as the diversity and adaptation of the living world is concerned. Rather, they saw the hand of God even in the smallest aspect of adaptation or diversity. John Ray's The Wisdom of God manifested in the works of the creation, 1691, is not only a powerful argument from design but also very sound natural history, indeed, one might say one of the earliest works of ecology. The excellence of observations on which the writings of the naturalist theologians were based gave them a wide circulation and greatly contributed to the spread of the study of natural history. Natural theology was a necessary development because design was really the only possible explanation for adaptation in a static created world. Any new finding in this early age of natural history was grist on the mill of natural theology. The supposedly idyllic life of the inhabitants of the tropics, in particular, was seen as evidence for the providential design by the Creator. The discovery of infuser eons and zoophytes seemed to confirm the great chain of being, leading up to man. But the hour of triumph of natural theology was short. It was implicitly questioned in much of Buffon's writings and quite explicitly criticized in Hume's Dialogues, 1779, concerning natural religion, and in Kant's Critique of Judgment, 1790. Evolutionary biology greatly benefited from natural theology. This sounds like a rather paradoxical claim, considering that evolution received hardly any attention prior to 1859, and yet it is true, although in an indirect sense. What natural theology did was to ask questions concerning the wisdom of the Creator and the ingenious way in which He had adapted all organisms to each other and to their environment. This led to the seminal studies of R.E.I. Maris and Kirby on animal instincts, and to C.K. Sprengel's discovery of the adaptations of flowers for insect pollination and the corresponding adaptations of the pollinators. From Ray and Derham, to Paley, to the authors of the Bridgewater treatises, and to numerous of their contemporaries, all natural theologians described what we would now call adaptations. When the hand of the Creator was replaced in the explanatory scheme by natural selection, it permitted incorporating most of the natural theology literature on living organisms almost unchanged into evolutionary biology. No one can question that natural theology laid a remarkably rich and solid foundation for evolutionary biology, and that it was not until far into the Darwinian period that studies in adaptation were again pursued as eagerly as it had been done by natural theology. Natural theology represents an intensely optimistic worldview. Yet much happened in the second half of the 18th century to destroy this unbounded optimism, beginning with the earthquake of Lisbon, the horrors of the French Revolution, and the realization of the intensity of the struggle for existence. The hold of natural theology on the thinking of Western man ended in France and Germany before the end of the 18th century. Curiously, it had a new flowering in England in the first half of the 19th century. Paley's Natural Theology, 1803, and the Bridgewater treatises, 1832 to 1840, once more advanced quite emphatically the argument from design. The leading English paleontologists and biologists of the day were natural theologians, including Charles Lyell and other of Darwin's friends. This fact explains much of the intellectual structure of The Origin of Species, see Chapter 9. Life and Generation. Except for natural history, the study of living organisms from the Renaissance to the 19th century was largely in the hands of the medical profession. Even the great botanists, with the exception of Ray, had been educated as medical doctors. Their main interest was, of course, the functioning of the healthy or sick body, and second, the problem of generation, that is, the origin of new organisms. By the beginning of the 18th century it became the task of physiology to find a compromise between the ever more radical mechanistic and opposing vitalistic extremes. It was Albrecht von Haller, 1707 to 1777, who gave physiology a new 105 direction. He returned to the empirical tradition of Harvey and of the vivisectionists and attempted to determine the function of various organs by innumerable animal experiments. Even though he found no evidence for a soul directing physiological activities, his experiments convinced him that the structures of the living body have certain properties, like irritability, which are not found in inanimate nature. In spite of Haller's balanced conclusions, the pendulum continued to swing back and forth right up to the first quarter of the 20th century. Vitalism and mechanism continued to battle each other. Vitalism, for instance, was defended by the Montpellier school, Bourdieu, Barthet, by the German Naturphilosophien, by Bichat and Claude Bernard, and by Driesch, while an uncompromising mechanism was preached by Ludwig, Dubois-Reymond, Julius Sachs, and Jacques Loeb. It is perhaps legitimate to say that this controversy was not totally eliminated until it was recognized that all manifestations of development and life are controlled by genetic programs. To go back to the 17th and 18th centuries, the second great controversy concerned the nature of development. The question to be answered was, how can the amorphous egg of a frog develop into an adult frog and a fish egg into a fish? The defenders of preformation thought that there was something preformed in the egg which was responsible for turning the egg of a grass frog into a grass frog and that of a trout into a trout. Unfortunately, the extreme representatives of the preformationist school postulated pre-existence, that is, that a miniaturized adult, homunculus, was somehow encapsulated in the egg, or in the spermatozoon, an assumption the absurdity of which was rather easily demonstrated. Their opponents who upheld the thesis of epigenesis, that is the gradual differentiation of an entirely amorphous egg into the organs of the adult, were hardly more convincing, since they were quite unable to account for the species specificity of this process, and thus they had to invoke vital forces. They were the leaders of vitalism. As so often in the history of biology, neither of the opposing theories prevailed in the end, but rather their eclectic fusion. The epigenesists were correct in stating that the egg at its beginning is essentially undifferentiated, and the preformationists were correct that its development is controlled by something preformed, now recognized as the genetic program. Among the participants in this controversy, in addition to Haller, one might mention Bonnet, Spallanzani, and C.F. Wolf, Rowe, 1981. Biology in the Enlightenment. As indicated by the term Enlightenment, the 18th century, from Buffon, Voltaire, and Rousseau to Diderot, Condillac, Helvetius, and Condorcet, was an intellectually liberating period. The predominant form of religion was deism. Even though admitting the existence of God, the enlightened deist could find no evidence that God had created the world for the benefit of man. His God was the supreme intelligence, the creator of the world and its universal order, the promulgator of general and immutable laws. His was a God remote from man, with whom he is little concerned. It was not a very large step from deism through agnosticism to outright atheism. Many thinkers took the step. The Enlightenment was a time when any previously held dogma, whether theological, philosophical or scientific, was critically questioned. The persecutions of the philosophers by the French government, the king, should warn us, however, that many of the teachings of the philosophers were considered as political as they were philosophical. Condorcet's egalitarianism, for instance, was a rebellion against class privileges, feudalism, completely ignoring any possible biological aspects. He recognized only three kinds of inequality, relating to wealth, social status, and education, but not allowing for any differences in native endowment. Total equality could be established, he thought, as soon as wealth, status, and education were equalized. A concept like natural selection, or even evolution, would make no sense to one committed to such uncompromising egalitarianism. One must remember, however, that the Enlightenment was not a homogeneous movement. Almost as many views were represented as there were different philosophers. Paris from Buffon to Cuvier. The history of biology is rich in episodes of a meteoric rise of some center of research. The North Italian universities in the 16th and 17th century are one example. The German universities in the second half of the 19th century are an 107. 108. Other one, and Paris from Buffon, 1749, to Cuvier, 1832, is a third one. The specific contributions of the principal figures in the galaxy of Parisian stars will be discussed in the respective chapters, but at this time it is important to single out one name, that of Lamarck, 1744 to 1829, because his proposal of evolutionism, first articulated in the Discours of 1800, was such a radical departure from tradition. It is often said that only young people have revolutionary new inspirations, but Lamarck was more than 50 years old when he developed his heterodox ideas. His geological studies had convinced him that the Earth was very old and that conditions on it were constantly changing. Fully understanding that organisms are adapted to their environment, he was forced to the conclusion that they must change in order to maintain their adaptation to the ever-changing world. His comparison of fossil mollusks through the Tertiary strata to the present confirmed this conclusion. This led Lamarck to propose a theory of transformation, 1809, which postulated an intrinsic tendency of organisms to strive toward perfection and an ability to adjust to the demands of the environment. Virtually all of his explanatory endeavors were unsuccessful, largely because he depended on conventional beliefs such as an inheritance of acquired characters. Even though Lamarck was viciously attacked by Cuvier, he nevertheless impressed many of his readers, including Chambers, the author of Vestiges, 1844. Opposing protestations notwithstanding, he clearly prepared the ground for Darwin. Even without his evolutionary theory, Lamarck would be an honored name in the history of science owing to his manifold contributions to botany and to the knowledge of the biology and classification of the invertebrates. Lamarck is sometimes credited for having ushered in a new era of biology by his theory of evolution, 1809, and by his coining the word biology in 1802, independently proposed also by Burdake in 1800 and by Treviranus in 1802. A broad look at the biological sciences does not substantiate this claim. Lamarck's evolutionary theory had exceedingly little impact, and the coining of the word biology did not create a science of biology. In the early 1800s there was really no biology yet, regardless of Lamarck's grandiose scheme, Gros, 1940, and the work of some of the Naturphilosophien in Germany. These were only prospectuses of a to-be-created biology. What existed was natural history and medical physiology. The unification of biology had to wait for the changing intellectual milieu of biology. Establishment of evolutionary biology and for the development of such disciplines as cytology. Lamarck's great opponent was Cuvier, 1769 to 1832, whose contributions to science are almost too extensive to be listed. He clearly established the science of paleontology, and his analysis of the vertebrate faunas of the Paris Basin were as important a contribution to stratigraphy as was the work of William Smith in England. I have already mentioned Cuvier's important studies in comparative anatomy and his destruction of the Scala Naturae. When Geoffroy Saint-Hilaire attempted once more to revive the concept of unity of plan in the entire animal world, Cuvier refuted these claims devastatingly. The so-called Academy dispute, 1831, with Geoffroy Saint-Hilaire was not a debate about evolution, as is sometimes claimed, but about whether or not the structural plans of all animals can be reduced to a single archetype. Cuvier had an enormous impact on his age, an impact that was both good and bad. He inspired research in comparative anatomy, perhaps more in Germany than in France, and in paleontology, but he also impressed his conservative frame of mind on generations of French biologists. As a result, evolution, in spite of the priority of Lamarck, had a tougher time getting accepted in France than in any other scientifically active European nation. Cuvier played a remarkably paradoxical role in the history of evolution. He opposed it in its foremost representative, Lamarck, with all the power of his knowledge and logic, and yet his own researches in comparative anatomy, systematics, and paleontology supplied some of the best evidence for those who subsequently embraced evolutionism. The rise of science from the 17th to the 19th century. Much happened in these 3 centuries, but it is often impossible to say what is cause and what is effect. The movement of Latin-speaking scholars from country to country, so characteristic of the late Middle Ages and the Renaissance, declined strikingly, and with it the popularity of the Latin language. As a result, nationalism in science grew, aided and abetted by the use of national languages in the scholarly literature. Work published in the Foreign Litera. Ls. 110. Tour was ever more rarely referred to. This parochialism reached its height in the 19th century, with the result that each country had its own intellectual and spiritual milieu. There was perhaps no other era in Western history when national moods were as different as in the period from 1790 to 1860. In Britain empiricism was dominant. It rested on a nominalistic tradition going back to William of Ockham, was primarily developed by John Locke, and was adopted by the 18th century chemists Hales, Black, Cavendish, and Priestley. In France there was first the ferocity of rebellion and then an extraordinary reaction after the restoration of the monarchy. Even though neither natural theology nor the Church played a role, there was a spirit of great conservatism through Cuvier. The mood was entirely different in Germany. Here a country was finding itself after the extreme trials and deprivations of the 17th and 18th centuries, and the new spirit expressed itself in great enthusiasms, first for classical antiquity, then for various Romantic movements, culminating in nature philosophy, as developed by Schelling, Oken, Carus. As in France, physico-theology played no role after about 1780. England represented a complete contrast. Here natural theology was completely dominant. Science, particularly biological science, was rather neglected, being almost entirely in the hand of amateurs, if not dilettantes. This was the background against which the rise of Darwinism must be considered. Professionalization in science developed in France after the Revolution of 1789 and at about the same time in Germany. I know of no thorough analysis, see Mendelssohn, 1964, but in Britain it was delayed until about the middle of the 19th century. The now generally accepted concept of science and its pursuit largely developed at the German universities. It is here that the first teaching laboratories were established in the 1830s, those of Purkinje, Liebig, Lückert. The German universities of the 19th century were devoted to research and scholarship to a higher degree than those of any other country. No one saw a conflict between pure science and useful knowledge. There was a remarkable similarity in Germany between the university system and the apprentice system in the crafts. It strongly encouraged excellence and achievement. When science began to prosper in the United States and graduate schools were established at the universities, it was the system of the German university that was most widely adopted. Again, a massive movement of scholars between countries began to develop in the later decades of the 19th century, a movement in which the Marine Biological Station at Naples played an important role. Science once more became truly international, a fact which has strongly affected the development of experimental biology in the United States. Allen, 1960. One further word on the geographic situation. Nearly all the major contributions to biological advance from the 15th to the end of the 19th century were made by only 6 or 7 countries. The center was first Italy, but then it shifted to Switzerland, France, and the Netherlands, later to Sweden, and finally 111 to Germany and England. There was always a free movement of scholars and it was primarily for economic or sociological reasons that either one or the other country temporarily held the hegemony. One of the reasons, for instance, for the primacy of Germany in biology in the 19th century was the early establishment of chairs of zoology, botany, and physiology at the German universities. At a time when Richard Owen was about the only professional biologist in Britain, all teaching was done either by divines or by M.D.S. Zoology and botany had already been professionalized in Germany. The nature of scientific publication. Up to well into the 19th century, science was progressing at quite a leisurely pace. In many disciplines and subdisciplines there was only a single specialist at any one time. So few people were working in the different branches of biology that Darwin thought he could afford to wait 20 years before publishing his theory of natural selection. He was quite thunderstruck when somebody else, A.R. Wallace, had the same idea. When the professionalization of biology began with the establishment of chairs for diverse branches of biology at many universities and when each professor began educating numerous young specialists, an exponential acceleration in the rate of scientific production occurred. The numerical increase of specialists brought about an important change in the nature of biological publication. This, as Julius Sachs pointed out in his History of Botany, took place in the first half of the 19th century. The great books which had characterized the 18th century, like Buffon's Histone Naturelle or Linnaeus Systema Naturae, began to be supplemented not only by shorter monographs, but more significantly by short 112 journal papers. This caused a need for many new journals. Up to 1830 there had only been the publications of the Royal Society, of the French and other academies, as well as such general publications as the Göttinger Wissenschaft like Nachrichten. Now, special societies like the Zoological Society, the Linnean Society, and the Geological Society of London began publishing independent journals, such as Annals and Magazine, American Journal of Science, Zeitschrift für Wissenschaftliche Zoologie, and Jahrbücher für Wissenschaftliche Botanik, made their appearance. We still lack a history of the biological journals, but that they had an important impact on the development of biology is without question. As biology became more and more specialized in modern times, chromosoma, evolution, ecology, and the Zeitschrift für Tierpsychologie, again only a few random samples, became the rallying points of newly developing subdisciplines. It has now reached the point where more papers, and pages, are published in the course of a few decades than in the whole antecedent history of biology. This broadens and deepens biology immensely, but if we should attempt to list the 10 most basic problems of biology, we would probably discover that most of these problems had already been posed at least 50 or 100 years ago. Even if the historian cannot follow every problem or controversy into the 1980s, he can certainly lay a foundation that facilitates the understanding of the current activities. Divisive developments in the 19th century. The development of the comparative approach around the turn of the 19th century provided for the first time an excellent opportunity for the unification of biology, that is, the formation of a bridge between the naturalists and the anatomists physiologists. Cuvier's emphasis on function strengthened this bond. But only few biologists took advantage of this opportunity, no one more so than Johannes Müller, 1801 to 1858, who switched in the 1830s from pure physiology to comparative embryology and invertebrate morphology. But Müller's own students aggravated the split in biology by their aggressive promotion of a physicalist reductionist approach toward the study of life, quite unsuited for the study of the phenomena the naturalists were interested in. From the 1840s on, more than ever, there was a lack of communication between the naturalists and the physiologists, or as it was possible to frame it after 1859, between the students of evolutionary, ultimate, and those of physiological, proximate, causations. In some ways this polarity was nothing but a continuation of the old contrast between the herbalist naturalists and the physician physiologists of the 16th century, but the conflicts and differences of interests were now much more precisely defined, particularly after 1859. Two well-defined biologies, evolutionary and functional, were now coexisting side by side. They competed with each other for talent and resources. They engaged in one controversy after the other, engendered by the difficulty of understanding the opposing viewpoints. Some historians of science like to distinguish different periods, each with a single dominant paradigm, Kuhn, episteme, Foucault, or research tradition. This interpretation does not fit the situation in biology. Ever since the later 17th century, one finds more and more often that even within a given biological discipline or specialization, two seemingly incompatible paradigms may exist side by side, like preformation and epigenesis, mechanism and vitalism, iatrophysics and iatrochemistry, deism and natural theology, or catastrophism and uniformitarian, to mention only a few of the numerous polarities. This creates formidable difficulties of interpretation. How can it be explained, on the basis of the total intellectual, cultural, and spiritual context, that is, the zeitgeist of the period, that two diametrically opposed interpretations could have originated and been maintained? Two additional problems exist for the historiographer. The various controversies, a sample of which I have just listed, do not coincide with each other, and their terminations, by whatever means, fall in separate periods. Worse than that, as I have already described, the sequence of events in different countries is often very different. Nature philosophy was largely confined to Germany, exceptions e.g. Geoffroy Saint-Hilaire, Quinarianism, Richard Owen. Natural theology dominated British science in the first half of the 19th century but had played out in the 18th century in France and Germany. Foucault's ideal, to paint the progress of science, and its milieu, as a series of consecutive epistemes, is clearly not encountered in the real world. What we find instead are two sets of phenomena. First, a gradual change of the structure, institutionalization, and normative aspects of that which we now call science, and secondly, some definite periods in individual branches of science. Therefore, the 113, 114. Best I can do is to present a regrettably disjunct set of thumbnail sketches of advances in various biological disciplines. Further study will unquestionably succeed in establishing whether and to what extent connections between the events in the various branches of biology have existed, and also what the connections, if any, are between the scientific advances and the general intellectual and social milieu. The establishment of such connections is regrettably slighted in my own account. The two branches of biology that were best defined in the middle of the 19th century were physiological biology and evolutionary biology. I shall deal with them first, before taking up later developments. Physiology comes of age. In no other area of biology has the pendulum between opposing viewpoints swung back and forth as frequently and as violently as in physiology. Extreme mechanistic interpretations, considering organisms as nothing but machines to be explained in terms of movements and forces, and extreme vitalism, considering organisms as being completely controlled by a sensitive if not thinking soul, were opposing each other from the time of Descartes and Galileo virtually to the end of the 19th century. The physicalist movement was greatly strengthened by the popular philosophical publications of three natural scientists, Karl Voigt, Jacob Moleschott, and Ludwig Buchner, generally referred to as the German scientific materialists, Gregory, 1977. In spite of their name, they were sincere idealists, but equally sincere atheists. By their unswerving opposition to vitalism, supernaturalism, and any other kind of non-materialistic explanation, they served as watchdogs, so to speak, of physiology, attacking relentlessly any interpretation that was not physico-chemical. There were two reasons for the rise of an almost rampant reductionist physicalism in mid-19th century physiology. One was that the still widespread power of vitalism evoked a justifiable opposition. The other reason was the enormous current prestige of the physical sciences, which physiologists were able to extend to themselves by adopting uncompromising physicalism and mechanical explanations. Helmholtz was one of the leaders in this endeavor and proposed in 1869 at the Innsbruck meeting of the German naturalists the motto, "NZL der Naturwissenschaften ist, die Alien anderen Veränderungen bewie. Gungen und deren Triebkraft zu finden, also sie in Mechanik aufzulösen." The ultimate objective of the natural sciences is to reduce all processes in nature to the movements that underlie them and to find their driving forces, that is, to reduce them to mechanics. Such a reduction is, indeed, often possible in those areas of biology that deal with proximate causes, and attempts of such an analysis are usually heuristic even where they are unsuccessful. The high prestige of this reduction, however, resulted in its application to many biological problems, particularly in evolutionary biology, where this approach is entirely unsuitable. Helmholtz, for example, went back and forth between the physical and biological sciences, a movement which was facilitated by the fact that all physiological processes are, indeed, ultimately chemical or physical processes. But his fashionable concept was readily applied also to branches of biology where it is inappropriate. Haeckel, 1866, in the preface of his Generelle Morphologic, gives himself the task of lifting the science of organisms durch mechanisch-causale Begründung to the level of the inorganic sciences. Nageli calls his great treatise of evolution the Mechanisch-Physiologische Theorie der Abstammungslehre, 1884, and, at about the same time, recasts embryology into Entwicklungsmechanik. There were two great weaknesses in these endeavors. First, mechanistic or mechanical was rarely clearly defined, sometimes meaning mechanical quite literally, as in studies of functional morphology, sometimes, however, meaning simply the opposite of supernatural. The second weakness is that the prophets of mechanicism never made any distinction between proximate and ultimate causations, failing to see that the mechanistic approach, although quite indispensable in the study of proximate causations, is usually quite meaningless in the analysis of evolutionary causations. The methodology of physiology underwent drastic changes in the 19th century, including a much more refined application of physical methods, particularly by Helmholtz and Ludwig, and, even more so, an increasing application of chemical methods. Each bodily process and the function of each organ and each gland were studied separately by a large army of medical, zoological, and chemical physiologists. Human physiology was, on the whole, conducted in separate laboratories from animal or plant physiology, although the human physiologists made extensive use of an 7/5 animal experimentation, including vivisection. The publication in 1859 of The Origin of Species caused hardly a ripple, since explanation in physiology was explanation of proximate causation. Darwinism did not perish with the death of Lamarck in 1829. It remained a popular thought in Germany with the Naturphilosophien and with a few other zoologists and botanists such as 116 Schaffhausen and Unger. In England it was revived by Chambers in his Vestiges, 1844, a plea for evolutionism that was highly popular in spite of the violent criticism of the professionals. Yet, natural theology and the argument from design continued to be dominant, supported by virtually all the leading scientists of the era, including Charles Lyell. This was the background against which Darwin in 1859 proposed his new theory. Evolution consists in changes of adaptation and in diversity. Lamarck in his theory had virtually ignored diversity, assuming that new kinds of organisms originate continuously by spontaneous generation. As a result of reading Lyell's principles and of his studies of the fauna of the Galapagos Islands and of South America, Darwin's attention centered on the origin of diversity, that is, on the origin of new species. His evolutionary theory was one of common descent, ultimately deriving all organisms from a few original ancestors or possibly from a single first life. Man thereby was inexorably made part of the total evolutionary stream and was demoted from the exalted position given to him by the Stoics, by the Christian dogma, and by the philosophy of Descartes. This theory of common descent can be designated as the first Darwinian revolution. Darwin was equally revolutionary in his theory of the causation of evolution. First of all, he rejected the saltational theories of the essentialists and insisted on completely gradual evolution. He likewise rejected the Lamarckian notion of evolution by an automatic intrinsic drive toward perfection, proposing instead a strict and separate causation of every single evolutionary change. This causation for Darwin was a two-step phenomenon, the first step being the continuous production of an inexhaustible supply of genetic variation. Here, Darwin was not embarrassed to admit that he did not understand at all how such variation was produced. He treated it as a black box. The second step was the differential survival and reproduction, selection, among the oversupply of individuals produced in every generation. This natural selection was not a chance phenomenon, as Darwin was so often accused of having adopted, but strictly caused, although in a probabilistic sense, by the interaction between genetic endowment and environmental circumstances. This theory of evolutionary causation was Darwin's second revolution. He explained design, the harmony of the living world, in a strictly materialistic fashion, and so, according to his opponents, he had dethroned God. The first Darwinian revolution, that is, the theory of common descent, was soon adopted by nearly all knowledgeable biologists, though some of his original opponents, such as Sedgwick and Agassiz, resisted it to their death. The second Darwinian revolution, the acceptance by biologists of natural selection as the only direction-giving factor in evolution, was not completed until the period of the evolutionary synthesis, about 1936 to 1947. Darwin's theory of common descent was one of the most heuristic theories ever proposed. It put a whole army of zoologists, anatomists, and embryologists to work to determine relationships and the probable characteristics of the inferred common ancestors. This was an almost endless task, not at all completed even at the present day, since there is still great uncertainty about the nearest relatives and the presumptive common ancestor of many of the major groups of plants and animals. Curiously, comparative anatomy limited itself almost entirely to the application of Darwin's theory of common descent and was, it cannot be denied, an unconscious continuation of the tradition of idealistic morphology. Hardly anyone asked direct questions concerning the causes of the structural changes in phylogeny. It was not until the 1950s that comparative morphology consciously became evolutionary morphology, by establishing contact with ecology and behavioral biology and consistently asking why questions. Haeckel's theory of recapitulation, that is, the theory that an organism during its ontogeny passes through the morphological stages of its ancestors, resulted in an enormous stimulation of comparative embryology. Kovalevsky's discovery that the ascidians are near relatives of the vertebrates, both belonging to the phylum Chordata, was a typical achievement of this type of research. Comparative embryology asked almost exclusively the questions of evolutionary biology and was thus quite unsatisfactory to the representatives of functional biology. Goethe, His, and Roux eventually rebelled against this one-sidedness and sought to establish 117. 118. Lycian embryology devoted to the study of proximate causations, a purely mechanistic embryology, not one solely of speculation and history. This new embryology, characteristically designated by Roux as Entwicklungsmechanik, dominated embryology from the 1880s to the 1930s. However, it soon ran into difficulties when it was found that two perfect embryos could develop from an egg separated into two after the first cleavage division. What machine, if cut in half, could function normally? This unexpected amount of self-regulation induced Driesch, who had performed this experiment, to embrace a rather extreme form of vitalism and to postulate a non-mechanical Entleche. Even those embryologists who did not follow Driesch tended to adopt interpretations that were tinted with vitalism, such as Spamann's organizer. Interestingly, though not anti-evolutionists, embryologists were virtually unanimously opposed to Darwinism. But then, so were most biologists of the time. A minor reorientation in European biology occurred around 1870. This is when the students of J. Muller's successors took over, when the impact of Darwin's origin gathered momentum, when microscopy truly came of age, when the gradual professionalization of British science began to be noticeable, Thistleton Dyer, Michael Foster, and when France began to emancipate itself from Cuvier's influence. Progress, however, was very uneven in the different areas of biology. As a result of rapid technological advances in microscopes and in fixing and staining methods, no area was more successful in the 1870s, 80s, and 90s than the study of cells and their nuclei. In this period the process of fertilization was finally understood. Weismann, Hertwig, Strasburger, and Kolliker concluded in 1884 that the nucleus contained the genetic material. Darwin's theory of pangenesis was proposed before this information on cells was available. The subsequent research on cells led to the establishment of rather elaborate genetic theories, culminating in the detailed analysis and synthesis by Weismann, 1892. With exception of Nageli, 1884, and O. Hertwig, all these authors postulated particulate inheritance, and with the exception of De Vries, 1889, they all concentrated on the developmental aspect of inheritance. With the benefit of modern hindsight, we can see that they made two major assumptions that proved to be incorrect. First, they assumed in order to explain differentiation and quantitative inheritance that the determinants for a character could be represented in a nucleus by multiple identical particles that could be distributed unequally during cell division, and second, they thought that these determinants converted directly into the structures of the developing organism. The first of these assumptions was refuted by Mendel, the second by Avery and molecular biology. In the year 1900 De Vries and Correns rediscovered Mendel's rules, demonstrating that each parent contributes to each segregating character only one genetic unit, later called a gene, see chapters 16 and 17. Within 2 decades most of the principles of transmission genetics were worked out by a whole army of geneticists, under the leadership of Bateson, Punnett, Knaut, Correns, Johansen, Castle, East, Bauer, and Th. Morgan. All the evidence they brought together indicated that the genetic material was unchanging, that is, inheritance is hard. Changes in the genetic material are discontinuous and were designated mutations. Unfortunately, De Vries and Bateson used the discovery of Mendelian inheritance as the basis for a new saltational theory of evolution, rejecting Darwin's concept of gradual evolution and more or less ignoring his theory of natural selection. This interpretation of evolution was altogether unacceptable to the naturalists, whose understanding of the nature of species and of geographic variation had made immense progress during the preceding 50 years. Most importantly, they had begun to understand the nature of populations and had developed population thinking, according to which each individual is unique in its characteristics. Their evidence completely confirmed Darwin's conclusion that evolution is gradual, except in cases of polyploidy, and that speciation is normally geographic speciation. The literature of the taxonomists, ultimately culminating in the new systematics, was as regrettably ignored by the experimental biologists as was much of the post-1910 genetic literature by the naturalists. The result was a deplorable communication gap between these two camps of biologists. The difficulties and misunderstandings were finally resolved during the period between 1936 to 1947, resulting in a unified evolutionary theory often referred to as the evolutionary synthesis, Mayr and Provini, 1980. Dobbs-Hansky, Wrench, Mayr, Huxley, Simpson, and Stebbins, among others, showed that the major evolutionary phenomena such as speciation, evolutionary trends, the origin of evolutionary novelties, and the entire systematic hierarchy could be explained in terms of the genetic theory as Ma. 119. 120. Toured during the 1920s and 30s. Except for shifts in emphasis and for a far more precise analysis of all the various mechanisms, the synthetic theory of evolution is the paradigm of today. Biology in the 20th century. In the same period during which the evolutionary theory was refined, whole new fields of biology emerged. Of particular importance have been the fields of ethology, the comparative study of animal behavior, of ecology, and of molecular biology. Ethology and ecology. After the pioneering, but largely ignored, work of Darwin, 1872, Whitman, 1898, and O. Heinroth, 1910, the field of ethology owes its real development to Konrad Lorenz, 1927 ff., and subsequently to Nico Tinbergen. While the previous schools of animal psychologists had devoted most of their attention to the study of proximate causes of behavior, generally working with a single species and concentrating on learning processes, the ethologists focused on the interaction between the genetic program and subsequent experience. They were most successful in the study of species-specific behaviors, particularly courtship behavior, behavior that is largely controlled by closed programs. The arguments between Lorenz and von Holst on one side and authors like Schneerlaw and Lehrman on the other side about the size of the genetic contribution to behavior were in some ways a replay of similar arguments that had gone on all the way back to the 18th century, Riemarus versus Kondelik, and 19th century, Altum versus Abraham. The controversies of the 1940s and 50s in this field are now a matter of the past. There is little difference of principle among students of animal behavior, and what differences remain are largely a matter of emphasis. The study of behavior is now expanding primarily in two directions. On one hand, it is merging with neurophysiology and sensory physiology, and on the other hand with ecology. Species-specific behavior is studied from the point of view of its selective significance within the niche of the respective species. Finally, much of behavior consists of the exchange of signals, most frequently among conspecific individuals. The science of signals and messages, semiotics, and the role that communication plays in the social structure of species are now particularly active areas of research. The 20th century is also usually credited with having given birth to ecology. It is true that the importance of the study of the environment had never before been appreciated quite so keenly as since the 1960s, but ecological thought goes back to the ancients. Glackon, 1970. It is prominent in the writings of Buffon and Linnaeus, and played an important role in the travelogues of the great explorers of the 18th and 19th centuries, the Forsters and Humboldt, for example. For these travelers the ultimate goal was no longer collecting and describing species but understanding the interaction of organisms and their environment. Alexander von Humboldt became the father of ecological plant geography, but his interests later turned almost entirely to geophysics. Many of Darwin's discussions and considerations would be quite appropriate for a textbook of ecology. The term ecology was proposed in 1866 by Haeckel as the science dealing with the household of nature. Semper, 1880, provided a first general text on the subject. In the ensuing years, there was little contact among various groups that studied the conditions of life or associations of various kinds of organisms. Mobius, 1877, published his classical study of an oysterbank. Henson and others concentrated on marine ecology, Warming on plant ecology, and still others founded limnology, the science, mostly ecological, of fresh waters. Ecology long remained rather static and descriptive, literally thousands of papers dealing with the number of species and individuals within a certain measured area. Various authors competed with each other in proposing fancy nomenclatures for any and all terms being used in the held. Even the spade with which plants were dug out was renamed geotome. A revitalization of the held was due to three developments. One was the calculations of Lotka-Volterra dealing with the cyclic changes of populations owing to predator-prey relations, and more broadly with various other aspects of the growth, decline, and cycling of populations. The second development was a greater emphasis on competition. It led to the establishment of the principle of competitive exclusion and its experimental testing by Gauss. In due time the study of the competitive relationships of species became one of the major subdivisions of ecology under the leadership of David Lack and Robert MacArthur. The subject occupies the border area between ecology and evolutionary biology since 121. 122. These competitive relationships not only determine the presence and absence of species, their relative frequency, and the total species diversity but also the adaptive changes of these species in the course of evolution. A third development leading to the vitalization of ecology was attention to energy turnover problems, particularly in fresh water and in the ocean. The question of how much computer-based modeling is contributing to the understanding of interactions in ecosystems is still controversial. Since many ecological factors are ultimately behavioral characteristics, such as predator thwarting, feeding strategies, niche selection, niche recognition, all evaluations of aspects of the environment, and many others, one can perhaps even go so far as saying that, at least in animals, the greater part of ecological research is now concerned with behavioral problems. Furthermore, all work in plant as well as animal ecology ultimately deals with natural selection. The emergence of molecular biology. As the analysis of physiological and developmental processes became more detailed and more sophisticated, it became evident that ultimately many of these processes can be reduced to the action of biological molecules. The study of such molecules at first was strictly the domain of chemistry and biochemistry. The early roots of biochemistry go far back into the 19th century, but originally there was no clear delimitation from organic chemistry, and biochemical research was usually conducted in chemical institutions. Indeed, much early biochemistry had little to do with biology, being merely the chemistry of compounds extracted from organisms or, at best, compounds of importance in biological processes. To the present day, some biochemistry is still of this complexion. A second pathway leading to molecular biology branched off from physiology. Florkin, 1972 ff., Fruton, 1972, Lester, 1974. Some of the achievements of biochemistry are of particular significance for the biologist. One is the elucidation, step by step, of certain metabolic pathways, for instance the citric acid cycle, as well as the eventual demonstration that each step is normally controlled by a specific gene. Such work is no longer simply biochemistry, and it became customary and quite legitimate to refer to it as molecular biology. Indeed, one deals here with the biology of molecules, their modifications, interactions, and even their evolutionary history. Another important development was the realization that the assumptions of colloid chemistry were unrealistic and that many biologically important materials consisted of polymers of high molecular weight. This development, particularly connected with the name of Staudinger in the 1920s, greatly facilitated the eventual understanding of collagen, muscle protein, and most importantly, DNA and RNA. Polymerized organic molecules have some of the properties of crystals, and it was discovered that their complex three-dimensional structure could be elucidated with X-ray crystallography, as demonstrated by Bragg, Peretz, Wilkins, and others. Through these studies it became clear that the three-dimensional structure of macromolecules, that is, their morphology, is the basis of their functioning. Although most biological macromolecules are ultimately aggregates of the same limited number of atoms, mainly carbon, hydrogen, oxygen, sulfur, phosphorus, and nitrogen, they all have extraordinarily specific and often totally unique properties. The study of the three-dimensional configuration of these macromolecules greatly added to our understanding of these properties. Molecular biologists have worked out the structure of literally thousands of biological compounds and clarified the pathways in which they are involved, but few of their researches created as much excitement as those clarifying the chemical nature of the genetic material. As far back as 1869, Mayr had discovered that a high proportion of the nuclear material consisted of nucleic acids. For a while, 1880s and 90s, it was postulated that nucleic acid, was the genetic material, but this hypothesis eventually lost in popularity. Chapter 19. It was not until Avery and his associates demonstrated in 1944 that the transforming substance of the pneumococcus was DNA that a reorientation occurred. Although several biologists were at once fully aware of the importance of Avery's discovery, they did not have the technical know-how for a detailed study of this fascinating molecule. The problem was quite obvious. How could this seemingly simple molecule, believed at that time to be simple compared to most proteins, carry the entire information in the nucleus of the fertilized egg to control the species-specific development of the resulting organism? One needed to know the exact structure of DNA before one could begin to speculate how it could perform its unique function. A hot race to achieve this goal developed among a number of laboratories, with Watson and Crick of the Cavendish Laboratory in Cambridge, England, emerging in 1953 as victors. If 123, 124, they had not been successful, somebody else would have been a few months or years later. Everybody has heard of the story of the double helix, but not everybody fully understands the significance of this discovery. It turned out that the DNA does not participate directly in development or in the physiological functions of the body, but simply supplies a set of instructions, a genetic program, which is translated into the appropriate proteins. DNA is a blueprint, identical in every cell of the body, which through fertilization is handed on from generation to generation. The crucial component of the DNA molecules are 4 base pairs, always one purine and one pyrimidine. A sequence of 3 base pairs, a triplet, functions like a letter in a code and controls the translation into a specific amino acid. The sequence of such triplets determines the particular peptide that is formed. The discovery that it is triplets of DNA that are translated into amino acids was made by M. Nierenberg in 1961. The sequence of the bases in the triplet is the code. The discovery of the double helix of DNA and of its code was a breakthrough of the first order. It clarified once and for all some of the most confused areas of biology and led to the posing of clear-cut new questions, some of which are now among the current frontiers of biology. It showed why organisms are fundamentally different from any kind of non-living material. There is nothing in the inanimate world that has a genetic program which stores information with a history of 3,000 million years. At the same time, this purely materialistic explanation elucidates many of the phenomena which the vitalists had claimed could not be explained chemically or physically. To be sure, it still is a physicalist explanation, but one infinitely more sophisticated than the gross mechanistic explanations of earlier centuries. Simultaneously with the purely chemical developments of molecular biology occurred others of a different nature. The invention of the electron microscope in the 1930s, for instance, permitted an entirely new understanding of cell structure. What the 19th century investigators had called protoplasm and had considered to be the basic substance of life turned out to be a highly complex system of intracellular organelles with various functions. Most of them are membrane systems which serve as the habitat of specific macromolecules. Molecular biology is advancing at far more frontiers than can here be mentioned, many of them of considerable medical importance. Major periods in the history of biology. It is traditional in historiography to distinguish periods. Western world history, for instance, has been divided into three periods: ancient, medieval, and modern. The break between medieval and modern is usually placed around 1500, or to be more precise between 1447 and 1517. Within this period, it was said, all those decisive events occurred or movements started that gave the New West its characteristic tone: the invention of printing with movable type, 1447, the Renaissance, supposed to have started with the fall of Constantinople in 1453, the discovery of the New World, 1492, and the Reformation, 1517. These events signify rather drastic changes, even though one may question the legitimacy of postulating a clear-cut division between medieval and modern. After all, there were also numerous notable developments in the 200 years before 1447. Historians of science have attempted similarly to distinguish well-defined eras in science. Much has been made of the fact that the chief works of Copernicus and Vesalius were both published in 1543. More importantly, the events of the period from Galileo, 1564 to 1642, to Newton, 1642 to 1727, have been designated as the Scientific Revolution, Hall, 1954. As significant as the advances were that occurred in the physical sciences during this period and also in philosophy, with Bacon and Descartes, no world-shaking changes happened simultaneously in biology. And for one who is critical, the Fabnka of Vesalius is, except for the artistic superiority of its illustrations, hardly a revolutionary treatise. It cannot in any way be compared in importance with De Revolutionibus of Copernicus. See also Roddy, 1913, 99-107. The 16th century was a difficult and often contradictory period, a period of rapid changes of mood. It saw the height of humanism, as exemplified in the work of Erasmus of Rotterdam, Luther's Reformation, 1517, but also a vigorous beginning of the Counter-Reformation, with the founding of the Jesuit order, and the beginning of the scientific revolution. The rediscovery of the real Aristotle, as distinct from that of the scholastics, had a clear impact on biology in the work of Cézanne and Harvey. Although in no way comparable with the flowering of the mechanical sciences, both physiology and natural history showed definite signs of increasing activity toward the end of the 16th and early 17th century. 125. 126. All the indications are that there is little congruence between what happened in the physical and in the life sciences. Nor can one delimit well-defined ideological periods in biology, as has been pointed out quite rightly by John Green, 1967, in a thoughtful review of Foucault's Les mots et les choses. Jacob's Logic of Life, 1970, is written in the Foucault tradition even though Jacob likewise does not accept Foucault's periods. Holmes, 1977, in turn, has questioned whether Jacob's delimitation of periods is any better. None of these authors has quite faced up to the question why the partitioning of the history of biology leads to such different results when done by different authors. Could it be that perhaps such periods are purely imaginary and hence can be established only by arbitrary divisions that will be made in different ways by different authors? It is rather unlikely that this suggestion is correct. Many of the periods recognized by certain historians are far too real. It seems to me that the answer is a different one. It is, that these periods are not universal. They differ to some extent in different countries, and they differ quite decidedly in different sciences and in different parts of biology, and in particular between functional biology and evolutionary biology. The correlation between changes in these two branches of biology is not at all close. The biological sciences lack the unity of the physical sciences, and, as I have mentioned, each of the various disciplines has had its own chronology of birth and flowering. Until the 17th century or thereabouts, biological science, as we would now call it, consisted of two fields, connected only in the most tenuous manner, natural history and medicine. Then, during the 17th and 18th centuries, natural history rather definitely separated into zoology and botany, although many of the practitioners, up to Linnaeus and Lamarck, moved freely from one to the other. In medicine, at the same time, anatomy, physiology, surgery, and clinical medicine became increasingly segregated. Fields that became dominant in the 20th century, like genetics, biochemistry, ecology, and evolutionary biology, simply did not exist prior to 1800. The rise and occasional setbacks of each of these fields is a fascinating story that will be one of the major themes of the ensuing chapters of this volume. A taxonomist, a geneticist, or a physiologist may recognize different periods, and so might a German, a Frenchman, or an Englishman. It is regrettable that history is not more tidy, but this is the way it is. Unfortunately, this makes the task of the historian rather difficult, because he may have to study simultaneously 5 or 6 different contemporary research traditions, as Larry Lawton calls it. As provocative as the problem of intellectual periods is, their recognition is sufficiently new so that no good analysis so far is available for all of biology and for all the world. Each of the numerous biological disciplines, such as embryology, cytology, physiology, or neurology, had periods of stagnation and periods of greatly accelerated advance. The question is sometimes asked whether there was ever any period during which the biological sciences experienced as drastic a reorientation as did the physical sciences during the scientific revolution. The answer must be no. To be sure, there have been particular years during which a new beginning was made in one or the other branch of biology, 1828 for embryology, 1839 for cytology, 1859 for evolutionary biology, and 1900 for genetics. However, each branch of biology had its own cycle, and there was no broad-based general revolution. Even the publication of The Origin of Species in 1859 was virtually without impact on the experimental branches of biology. The replacement of essentialistic by populational thinking, so fundamental in evolutionary biology, hardly touched functional biology until almost 100 years later. The elucidation of DNA, 1953, had a powerful impact on cellular and molecular biology but was irrelevant for much of organismic biology. The closest equivalent to a revolution in the biological sciences can be found from about 1830 to 1860, one of the most exciting periods in the history of biology. See Jacob, 1973, 178. It was then that embryology received a quantum boost through the work of K. E. von Baer, when cytology got its start with the discovery of the nucleus by Brown and the work of Schwann, Schleiden, and Virchow, when the new physiology took form under Helmholtz, Dubois-Raymond, Ludwig, Bernard, when the foundations were laid for organic chemistry by Wohler, Liebig, and others, when invertebrate zoology was placed on a new foundation by Johannes Müller, Lückert, Siebold, and Sars, and finally and most importantly when the new theory of evolution was conceived by Darwin and Wallace. These manifold activities were by no means part of a single unified movement, in fact, they were largely independent. Much of the activity was due to the increasing professionalization of science, the improvement of the microscope, and the rapid development of chemistry. Some of it, however, was the direct result of the inexplicable rise of a particular genius. 127. 128. Biology and philosophy. Among the Greeks there was no separation of science and philosophy. Philosophy was the science of the day, as was particularly true for the Ionian philosophers from Thales on. Some mathematicians engineers, like Archimedes, and some physicians physiologists, like Hippocrates and later Galen, came closest to being genuine scientists, but the outstanding philosophers of the period, like Aristotle, were as much scientists as they were philosophers. The two disciplines began to separate after the end of scholasticism. Anatomists like Vesalius, physicist astronomers like Galileo, botanist anatomists like Caesalpino, and physiologists like Harvey were primarily scientists, even though some of them had a very strong philosophical Aristotelian or anti-Aristotelian commitment. The philosophers, in turn, became increasingly pure philosophers. Descartes was one of the few who was both a scientist and a philosopher, while Berkeley, Hobbes, Locke, and Hume are already pure philosophers. Kant was perhaps the last philosopher also to make distinguished theoretical contributions to science, namely to anthropology and cosmology, contributions that one will find quoted in strictly scientific historiographies. After him it was the scientists and mathematicians who contributed to philosophy: Herschel, Darwin, Helmholtz, Mach, Russell, Einstein, Heisenberg, K. Lorentz, rather than the reverse. Philosophy flowered during the 18th and 19th centuries. The hold of Aristotle had been broken by Descartes, and the hold of Descartes was broken by Locke, Hume, and Kant. Curiously, no matter how different they were in most of their other views, all the philosophers of this period asked most of their questions in the framework of essentialism. The 19th century witnessed various new departures, among which Comte's positivism, a philosophy of science, was most important. A strongly reductionist materialism, represented in Germany by Voigt, Buchner, and Moleschott, Gregory, 1977, was quite influential, if for no other reason than that its exaggerations led to the development of holist, emergentist, or even vitalist movements. Yet by its consistent and never falsified denials of any dualism and supernaturalism, it had a lasting effect. Within biology, these philosophical movements had their greatest impact on physiology and psychobiology, that is, on disciplines of biology dealing with proximate causes. What has not yet been properly analyzed is the exact nature of the relation between these philosophies and physiological research. Some opposing claims notwithstanding, philosophy seems to have played only a minor, if not negligible, role in the process of discovery, but philosophical dogmas or principles played a large role in the framing of explanatory hypotheses. Among the philosophers, Gottfried Wilhelm Leibniz, 1646–1717, in contrast to the physicalist philosophers of his day, had a real concern for understanding nature as a whole. He showed how unsatisfactory it is to explain the workings of the living world strictly with the help of secondary, physical causes. Even though his own answers, a pre-established harmony and a law of sufficient reason, were not the sought-for solutions, he posed problems that deeply puzzled the following generations of philosophers, including Kant. In spite of his mathematical brilliancy, Leibniz saw clearly that there was more to nature than mere quantity and became one of the first to appreciate the importance of quality. In an age dominated by the discontinuity concept of essentialism, he stressed continuity. His interest in the scalzi naturae, static though he conceived it, helped to prepare the ground for evolutionary thinking. He profoundly affected the thinking of Buffon, Maupertuis, Diderot, and others of the philosophers of the Enlightenment, and through them Lamarck. He was perhaps the most important counter-influence to the essentialistic, mechanistic thinking of the Galilei-Newton tradition. The philosophical foundations of evolutionary biology are far less clear than those of functional biology. The concept of a directionality in life, higher and lower, goes back to Aristotle and to the Scala Naturae, Lovejoy, 1936, but population thinking apparently had only very tenuous roots in philosophy, late nominalism. The crucial insight of the importance of history, in contrast with the timelessness of physical laws, did receive a considerable input from philosophy, Vico, Leibniz, Herder. An acceptance of the importance of history almost inevitably led to a recognition of the process of development. Development was important for Schelling, and the Naturphilosophien, Hegel, Kant, Marx, and Spencer. The importance of these thinkers is well stated in Mandelbaum's, 1971, 42, definition of historicism. Historicism is the belief that an adequate understanding of the nature of any phenomenon and an adequate assessment of its value are to be gained through Con. 729. 130. Citing it in terms of the place which it occupied and the role it played within a process of development. It would be tempting to suggest that the theory of evolution originated in this type of thinking, but there is little evidence that this was the case, except for Spencer's evolutionism, which, however, was not seminal for the thinking of Darwin, Wallace, Huxley, or Haeckel. Indeed, and rather unexpectedly, historicism never seems to have had close relations to evolutionary biology, except perhaps in anthropology. However, historicism and logical positivism were two completely incompatible developments. It is only in relatively recent times that the concept of historical narratives has been accepted by some philosophers of science. And yet, it might have been evident soon after 1859 that the concept of law is far less helpful in evolutionary biology, and for that matter in any science dealing with time-dominated processes such as cosmology, meteorology, paleontology, paleoclimatology, or oceanography, than the concept of historical narratives. The opponents of Cartesianism asked questions that never occurred to the mechanists. These questions made it embarrassingly evident how incomplete the explanations of the mechanists were. Not only did they ask questions about time and history, but also why questions were asked increasingly often, that is, ultimate causations were searched for. It was in Germany, toward the end of the 18th and early in the 19th century, that the most determined resistance developed against the mechanistic approach of the followers of Newton, who were satisfied in asking simple questions concerning proximate causations. Even authors outside of biology, like Herder, exerted a powerful influence on this dissent. Unfortunately, no constructive new paradigm emerged from these efforts, in which Goethe and Kant were also involved. Instead, this movement fell into the hands of an Oken, Schelling, and Karras, authors whose fantasies the experts could only meet with ridicule and whose silly constructions the modern reader can only read with embarrassment. Yet some of their basic interests were to be very much the same as those of Darwin. Revolted by the excesses of the Naturphilosophien, the anti-mechanistic naturalists retreated into non-problematic description, a field in which the scope was unlimited but, as the best minds soon pointed out, also intellectually unrewarding. It is still subject to controversy whether or not philosophy has made any contribution to science after 1800. Not surprisingly, philosophers generally tend to answer this question in the affirmative, scientists often in the negative. There is little doubt, however, that the formulation of Darwin's research program was influenced by philosophy. Roos, 1979, Hodge, 1982. In recent generations philosophy rather clearly has retreated into metascience, that is, an analysis of scientific methodology, semantics, linguistics, semiotics, and other subjects at the periphery of science. Biology today. If one wanted to characterize modern biology in a few words, what would one say? Perhaps the most impressive aspect of current biology is its unification. Virtually all the great controversies of former centuries have been resolved. Vitalism in all of its forms has been totally refuted and has had no serious adherency for several generations. The numerous competing evolutionary theories have been abandoned one by one and replaced by a synthetic one, which rejects essentialism, an inheritance of acquired characters, orthogenetic trends, and saltationism. More and more biologists have learned that functional and evolutionary biology are not an either-or situation, but that no biological problem is solved until both proximate and ultimate, equals evolutionary, causations are determined. As a result, many molecular biologists now study evolutionary problems, and many evolutionary biologists deal with molecular problems. There is far more mutual understanding than prevailed even 25 years ago. The last 25 years have also seen the final emancipation of biology from the physical sciences. It is now widely admitted not only that the complexity of biological systems is of a different order of magnitude, but also that the existence of historically evolved programs is unknown in the inanimate world. Teleonomic processes and adapted systems, made possible by these programs, are unknown in physical systems. The process of emergence, the origination of previously unsuspected new qualities or properties at higher levels of integration in complex hierarchical systems, is vastly more important in living than in inanimate systems. This also contributes to the differences between the physical and biological sciences, and to differences in the strategies and explanatory models in these fields. The question of what the major current problems of biology are cannot be answered, for I do not know of a single biological. 131. 132. Discipline that does not have major unsolved problems, this being true even for such classical fields as systematics, biogeography, and comparative anatomy. Still, the most burning and as yet most intractable problems are those that involve complex systems. The simplest of these, currently in the center of interest in molecular biology, is the structure and function of the eukaryote chromosome. To understand this, we must also know what is the specific function and the interaction of the various kinds of DNA, coding for soluble or non-soluble proteins, silent DNA, middle repetitive, high repetitive, and so forth. Although chemically all these DNAs are in principle the same, some produce building materials, some have a regulatory function, and still others are believed by some molecular biologists to have no function at all, to be parasitic. This may be true, but is not very convincing for a dyed-in-the-wool Darwinian like myself. However, I have no doubt that the whole complex DNA system will be understood within a few years. I am less sanguine about the rate of progress in our understanding of the more complex physiological systems such as those that control differentiation and the working of the central nervous system. One cannot solve these problems without dissecting the systems into their components, and yet the destruction of the systems during the analysis makes it very difficult to understand the nature of all the interactions and control mechanisms within the systems. It will require much time and patience before we will fully understand complex biological systems. And it will come only through a combination of reductionist and emergentist approaches. Biology has now become so large and so diversified that it can no longer be dominated entirely by one particular fashion, such as species describing in the age of Linnaeus, the construction of phylogenies in the post-Darwinian period, or Entwicklungsmechanik in the 1920s. To be sure, molecular biology is particularly active at present, but neurobiology is also vigorous and flourishing, and so are ecology and behavioral biology. And even the less active branches of biology have their own journals, including many new ones, organize symposia, and pose new questions all the time. What is most important is that in spite of the seeming fractionation, there is now more of a spirit of unity than in several hundred years. Diversity of life. Hardly any aspect of life is more characteristic than its almost unlimited diversity. No two individuals in sexually reproducing populations are the same, no two populations of the same species, no two species, no two higher taxa, nor any associations, and so ad infinitum. Wherever we look, we find uniqueness, and uniqueness spells diversity. Diversity in the living world exists at every hierarchical level. There are at least 10,000 different kinds of macromolecules in a higher organism, some estimates going even much higher than that. Taking all the different states of repression and repression of all the genes in a nucleus into consideration, there are millions, if not billions, of different cells in a higher organism. There are thousands of different organs, glands, muscles, neurocenters, tissues, and so on. Any two individuals in sexually reproducing species are different not only because they are genetically unique but also because they may differ by age and sex and by having accumulated different types of information in their open memory programs and in their immune systems. This diversity is the basis of ecosystems and the cause of competition and symbiosis. It also makes natural selection possible. Every organism depends for its survival on a knowledge of the diversity of its environment, or at least on an ability to cope with it. Indeed, there is hardly any biological process or phenomenon where diversity is not involved. What is particularly significant is that one can ask very similar questions concerning diversity at each hierarchical level, such as the extent or variance of the diversity, its mean value, its origin, its functional role, and its selective significance. As is characteristic for so much in the biological sciences, the answers to most of these questions are of a qualitative rather than a quantitative nature. Whatever level of diversity one is dealing with, the first step in its study is obviously that of inventory taking. It is the discovery and description of the different kinds of which a particular class consists, whether they be different tissues and organs in anatomy, different normal and abnormal cells and cellular organelles in cytology, different kinds of associations and biota in ecology and biogeography, or different kinds of species and higher taxa in taxonomy. The foundation which description and inventory TAC 134 lays forms the basis on which all further progress in the relevant sciences depends. In the ensuing chapters I shall concentrate on one particular component of the diversity of life, the diversity of kinds or organisms. 1. The discovery of the extent of diversity. Diversity has occupied man's mind ever since there has been man. No matter how ignorant a native tribe might be in other matters biological, invariably it has a considerable vocabulary of names for the various kinds of animals and plants occurring locally. The first creatures to be named are, of course, those of immediate concern to man, whether predators, bears, wolves, sources of food, hares, deer, fish, clams, vegetables, fruits, and so on, sources of clothing, skins, fur, feathers, or possessors of magical qualities. These are still today the predominant kinds in folklore. That this preoccupation with the diversity of nature is worldwide became apparent when European naturalists returned from expeditions and collecting trips. They would invariably report on an amazing knowledge of birds, plants, fishes, or shallow water sea life which they had encountered in every tribe of native peoples they had visited. Such knowledge is handed by word of mouth from generation to generation. Each tribe, not surprisingly, concentrates on the natural history of special interest to its daily life. A coastal tribe may know all about the shellfish in the intertidal zone but hardly anything about the bird life of the adjacent forest. Since the number of kinds of birds in a district is usually quite limited, a tribe may have a separate name for each species. Diamond, 1966. In the case of rich local floras, the emphasis may be on generic names, a tradition continued by the botanist Linnaeus. There is usually a rich vocabulary for cultivated plants and domesticated animals, but members of tribes with a hunting tradition may also have a superb knowledge of wild animals and nad plants. It is a great pity that this knowledge has been neglected by anthropologists for such a long time. Since these traditions are quickly lost under the impact of civilization, it is too late in many areas to study folk taxonomy. Fortunately, some excellent studies have been published in recent years. 2. What is particularly interesting is how often not only species and varieties were recognized but also higher taxa. The early naturalists knew only the limited fauna or flora of their home country. Even Aristotle mentions only about 550 kinds of animals, and the early Renaissance herbals contained between 250 and 600 kinds of plants. That not all parts of the world have the same biota was, however, already known to the ancients from the accounts of travelers as recorded by Herodotus, Pliny, and other authors. They mentioned elephants, giraffes, tigers, and many other animals not found in the Mediterranean, or at least not on the European shores. The existence of such strange creatures greatly excited the European imagination, because of the universal fascination of civilized man with the unknown, whether it be exotic countries, strange people, or bizarre animals and plants. To discover and describe all the marvelous creatures in this wonderful world of ours was the great passion of travelers and compilers from Pliny to Gesner and the disciples of Linnaeus. The ancients, of course, had not the slightest inkling of the extent of the geographical localization of faunas and floras which we now know to exist. This did not happen until travelers penetrated far into Asia, like Marco Polo, 1254–1323, or into Africa. When the Portuguese began their voyages in the 15th century and Columbus discovered the New World, 1492, a whole new dimension was added to the appreciation of the world's biotic diversity. Cook's voyages, which opened up the exploration of Australia and the Pacific Islands, were the capstone in the erection of this edifice. Yet, this was only the beginning, for the early travelers and collectors obtained only small samples of the distant faunas and floras. Even in Europe new species of mammals and butterflies were described as late as the 1940s and 1950s. And as far as less conspicuous groups and less accessible areas are concerned, the treasure chest of undescribed species seems to be inexhaustible. In the tropics even at this date we may not know more than a fifth or tenth of the existing species. The increase in knowledge was accompanied by a noticeable change in attitude. The early travelers were interested in the speck. 735. 136. Tacular. They liked nothing better than to come home with tales of monsters and fabulous creatures of all sorts. Soon this was replaced by a genuine interest in the purely exotic. Private collectors in Britain, France, Holland, and Germany established natural history cabinets, with an attitude that was hardly better than that of stamp or coin collectors. However, true naturalists like Linnaeus and RTD benefited from the enthusiasm of such collector patrons. Markgrave in Brazil and Rumphius in the East Indies were among visitors to the colonies who made important contributions to the natural history of previously almost unknown areas, see Stresemann, 1975. The 18th century was the beginning of the era of great voyages. Bougainville and other French expeditions, as well as Cook and other British ones, brought home wonderful treasures. This activity accelerated in the 19th century, with Russia, Kotzebue, and the United States joining. Travelers went to the corners of the globe, collecting natural history specimens of all descriptions, filling the private museums to the point of bursting, and forcing the building of great national and state museums and herbaria. There never were too many specimens because every collection produced more novelties. In a group as well known as the Birds, a single expedition, Whitney South Sea Expedition, visiting nearly all islands of the South Seas, discovered more than 30 new species as recently as the 1920s and 30s. The work of Humboldt and Bonpland in South America, of Darwin on the Beagle, 1831–1836, of A.R. Wallace in the East Indies, 1854–1862, and of Bates and Spruce in Amazonia is well known, but it is usually forgotten that there were quite literally thousands of other collectors. Linnaeus sent his students to bring back exotic plants, but some of the best succumbed to tropical diseases. Barch, D 1738, Turnstrom, D 1746, Hasselquist, D 1752, Leifling, D 1756, and Forskell, D 1763. The tragedy was even greater in the East Indies, where the flower of European zoology succumbed to tropical diseases or murder during a 30-year period. Cole, D 1821, Van Hasselt, D 1823, Boy, D 1827, Maclot, D 1832, Van Oort, D 1834, Horner, D 1838, Forsten, D 1843, and Schwanner, D 1851. This included the most enthusiastic and gifted naturalists of the period, their dream being to contribute to the knowledge of the animal life of the tropics. Kohl and Boy had been the most brilliant young naturalists of Germany, Stresemann, 1975. The gap caused by their death contributed to the ensuing decline in the quality of German natural history, for there is always only a limited number of first-rate minds at a given period. Unexplored or poorly known countries were only one of the many frontiers rolled back by the students of diversity. Other life forms and exotic environments were studied as well. Parasites, for example, became fit subjects for serious study. Human intestinal parasites were already mentioned in the Papyrus Ebers, 1500 BC, and were discussed by the ancient Greek physicians. When their ubiquity in man and animals was established, it led to the belief that they originated by spontaneous generation. Not until the 19th century was it realized that many, if not most, parasites are restricted to a single host and that a host species may be infested simultaneously by several different kinds of parasites: tapeworms, cestodes, flukes, trematodes, threadworms, nematodes, blood parasites, and cell parasites. Beginning with the work of zoologists like Rudolphi, von Siebold, Kiechenmeister, and Luckert, an ever larger army of parasitologists specialized in this brand of diversity. For owing to the complex life cycles of most parasites, their study requires particular perseverance and ingenuity. Since parasites are among the most serious causes of human diseases, malaria, sleeping sickness, schistosomiasis, rickettsias, and so on, their study was rightly given special attention. Plants likewise are extensively parasitized by gall insects, mites, and a vast array of fungi and viruses. It probably would be no exaggeration to claim that there are more species of plant parasites than of higher plants. Their gradual discovery led to an enormous expansion of the realm of organic diversity. Another frontier of diversity was found in fresh water and the oceans. Aristotle, during his stay on Lesbos, had been fascinated with marine life. Yet, as late as 1758 Linnaeus mentioned ridiculously few marine organisms in the Systema Naturae, except for a few fish, mollusks, and corals. This changed rapidly, owing to the interests of Pallas, St. Muller, and a series of Scandinavian investigators. Soon discovery followed on discovery. But here again, the end of the quest is not yet in sight. Sars was the first to open the gate to the deep-sea fauna, which received the special attention of the British Challenger expedition, 1872–1876. The Scandinavians, Dutch, Rank, and Germans followed with oceanographic expeditions, and specialists are still busy describing their discoveries. Marine life itself provided still another frontier: marine parasites. Marine organisms are in part parasitized by the same higher taxa as terrestrial organisms, such as cestodes and 137. 138. Trematodes, but other parasites are restricted to the oceans, mesozoans, parasitic copepods, rhizocephala, where they have experienced a rich radiation. The microscope opened up still another frontier of diversity, the world of organisms that could not be seen with the naked eye, or at least not well. Nordensk-Schold, 1928. The use of simple lenses to magnify small objects may go back to the ancients. A combination of lenses, that is, a microscope, was apparently first constructed by some Dutch lens makers early in the 17th century. A study of the structure of the bee, based on a five-fold magnification, by the Italian Francisco Stelluti, published in Rome in 1625, was the first work in biological microscopy. All of the microscopical work in the next 200 years was done with exceedingly simple instruments. Much of it was devoted to the study of plant tissues, hook, grew, Malpighi, or of the fine structure of animals, particularly insects, Malpighi, Swammerdam. Swammerdam discovered Daphnia in 1669 but neither described it in detail nor followed it up by studying other plankton organisms, Schierbeck, 1967, Nordensk-Schold, 1928. As important as the role of these investigators was for the history of cytology and of animal and plant morphology, it was van Leeuwenhoek who deserves the principal credit for having employed the microscope to expand the frontiers of diversity, Dobel, 1960. With quite an amazing instrument, a single lens microscope, he was able to achieve magnifications up to, it is said, 270 times. It was he who discovered in 1674, 1675, 1676, and later years, the rich life of protists, protozoans and one-celled algae, and other plankton organisms, rotifers, small crustaceans, and so on, in water, and thus laid the foundation for several of the subsequently most flourishing branches of biology. Indeed, he even discovered and described bacteria. His discovery of the infusoria, one-celled animals and plants, had an enormous impact on the thinking of his period and on the problem of spontaneous generation. But most importantly, van Leeuwenhoek was the first to make biologists aware of the vast realm of microscopic life, which raised entirely new problems for the students of classification. It was not until 1838 that Ehrenberg gave the first comprehensive treatment of the protozoans, but, this being prior to the cell theory, he considered them vollkommene organismen, endowed with the same organs as higher organisms, nerves, muscles, intestines, gonads, and so forth. C. T. von Siebold established the phylum Protozoa in 1848 and demonstrated their single-cell nature. Rapid progress was made in the first half of the 19th century also in the knowledge of all kinds of plankton animals and algae. Every improvement of the microscope added to our knowledge, the invention of the electron microscope in the 1930s even permitting the study of the morphology of viruses. The focus in my story so far has been the opening of the world of animal diversity. This coincided with a similar activity in plant exploration. Here also one can speak of a series of frontiers. Even before the flowering plants, angiosperms, had been reasonably well described, certain botanists had begun to specialize in the cryptogams, ferns, mosses, lichens, algae, and the rich world of fungi, Magdefrau, 1973. Fossils. But this is not the end. The diversity of the living world is more than matched by the life of bygone ages, represented in the fossil state. The highest estimates of the number of living animals and plants is about 10 million species. Considering that life on Earth began about 3.5 billion years ago, also that a rather rich biota has existed for at least 500 million years, and allowing for a reasonable turnover in the species composition of the biota, an estimate of 1 billion extinct species is presumably rather on the low side. In paleontology, the time of the great discoveries, like Archaeopteryx, a link between reptiles and birds, and Ichthyostega, a link between fishes and amphibians, is perhaps nearing an end, but even today an occasional new phylum of fossil invertebrates is still described and there seems to be no end to the new orders, families, and genera. The discovery of fossil faunas and floras has a long history, going back to the ancients, see also Part 2. 6 fossil marine mollusca were mentioned by Herodotus, Strabo, Plutarch, and particularly Xenophanes and were recognized as due to marine regressions. Fossil mammals, reptiles, and amphibians, however, were beginning to get attention only in the 17th century, with an ever-increasing number of discoveries being made in the 18th and 19th centuries. Who is not familiar with the discovery of mastodons, dinosaurs, ichthyosaurs, pterodactyls, moas, and other, often giant, fossil vertebrates? A parallel expansion of our knowledge was experienced by paleobotany, Magdefrau, 1973, 231 to 251. The problems in this field are great owing to the difficulty of matching stems, leaves, flowers, pollen, and fruits, seeds, but the number of known FOS 139 sills has steadily grown, and with it our understanding of their distribution in space and time. The study of fossil pollen has made a particularly important contribution. But there are still many great puzzles, including that of the origin of the angiosperms, Doyle, 1978. Until the 1950s the oldest known fossils, latest Precambrian, were about 625 million years old. Bargorn, Cloud, and Scove have, since then, pushed this frontier back by an order of 5 with their discovery of fossil prokaryotes in rocks that are about 143.5 billion years old, Scove, 1978. The prokaryotes, living or fossil, are now the most challenging frontier of descriptive systematics. A careful study of the biochemistry and physiology of the bacteria has revealed that they are far more diversified than had been previously realized. Woese and collaborators, indeed, have proposed to recognize a separate kingdom, Archaebacteria, for the methanobacteria and relatives, and still another one for those prokaryotes that are believed to have given rise to the symbiotic organelles of the eukaryote cells, mitochondria, plastids, and so on. The study of ribosomal RNA and of other molecules has finally brought considerable light into the previously rather controversial classification of the bacteria, Fox et al., 1980. Amazingly enough, there is always something new, often startlingly new, being discovered in taxonomy, the oldest of the branches of biology, for instance, the rediscovery of Trichoplax, seemingly the most primitive of the metazoans, Grell, 1972. Systematics, the science of diversity. When one reviews the history of the exploration of organic diversity, one cannot help being awed by the overwhelming diversity of nature in space, all continents, in time, from 3.5 billion years ago to the present, in size, from viruses to whales, in habitat, air, land, fresh water, ocean, and in lifestyle, free living versus parasitic. Not surprisingly, man did not ignore the incredible richness of organic life all around him. In fact, he had diverse reasons for studying it. There was, first of all, his ever-present curiosity about his environment, and his wish to know it and to understand it. There was also the purely practical need to know which animals and plants might be useful to him, particularly as food and, in the case of plants, as medicine. When Tinnius was asked what good the study of diversity was, he, as a pious creationist, answered in his dissertation, cui bono, all created things have to serve a purpose. Some plants are for medicine, some organisms are meant for human food, and so on. The all-wise Creator did not do anything in vain but created everything for a special purpose or for the benefit of somebody or something. It is our task to discover these intended uses, and this is the purpose of natural history. The passion of some of 17th and 18th century authors for the study of nature had, however, still another reason. Already the Greeks had extolled the harmony of nature. The whole world forms a cosmos, a word implying for the Greeks beauty and order. Whether nature was considered the perfect product of the Creator or, as interpreted by Seneca and the Pantheists, as being one and the same with God, many devout scientists, such as John Ray, Isaac Newton, and Carl Linnaeus were convinced of the existence of a deep-seated hidden order and harmony in nature which it was their task to unravel and explain. The laws of physics stress universality and uniformity. If only chance and the blind action of physical laws were active in the universe, thus argued the natural scientists of the 17th and early 18th centuries, one should find either a homogeneous or a totally chaotic world of things. Consequently, only the existence of a creator can account for the well-integrated diversity of living beings one actually finds. As Newton phrased it, we know him only by his most wise and excellent contrivances of things, and final causes. We admire him for his perfections, but we reverence and adore him on account of his dominion, for we adore him as his servants, and a God without dominion, providence, and final causes, is nothing else but fate and nature. Blind metaphysical necessity, which is certainly the same always and everywhere, could produce no variety of things. All the diversity of natural things which we find, suited to different times and places, could arise from nothing but the ideas and will of a being necessarily existing. The study of the perfect harmony of nature, and of its diversity, was, thus, the best way to know God. And it became part of the great vogue of natural theology in the 18th and early 19th centuries. Not only adaptation, as evidence for design, was the subject matter of natural theology but diversity itself. No one felt this more keenly than Louis Agassiz, who considered the natural system, as he described it in his essay on classification, as the most decisive proof of the existence of God. 7. The well-nigh inconceivable richness of kinds of organisms. 141. 142. Posed a serious challenge to the human mind, however. The Western world was preoccupied with the search for laws ever since the scientific revolution in mechanics and physics. Yet, no aspect of nature was as unyielding to the discovery of laws as was organic diversity. The only way such laws could be discovered, it was felt, was to order diversity by classifying it. This explains why the naturalists in the 17th, 18th, and 19th centuries were so obsessed with classification. It permitted them to put the bewildering diversity at least into some sort of order. As it happens, classification eventually did lead to the search for law, descent, by modification, from a common ancestor. So important seemed this ordering procedure to the zoologists and botanists in the 18th century that classification was treated almost as synonymous with science. As all other branches of science, taxonomy had gifted as well as rather dull-witted practitioners. Some specialists did nothing throughout their professional lives but describe new species. This seemed acceptable in the era of Linnaeus when taxonomy had enormous prestige. At that period the dominance of systematics resulted in the neglect of all other contemporary biological researches, for instance, those of Cadell-Reuter. But eventually, quite rightly, the question was asked, does such purely descriptive activity qualify as science when it does not include a search for laws nor any endeavor to reach generalizations? The splendid successes of von Baer, Magendie, Claude Bernard, Schleiden, von Helmholtz, and Virchow, from the 1830s to 1850s, in other branches of biology resulted in a rapid decline of the prestige of systematics. However, it took a new lease on life after 1859, when Darwin's theory of the origin of taxa by common descent provided the first non-supernatural explanation for the existence of higher taxa. This new intellectual impulse, however, was soon exhausted, and the exciting advances in functional biology in the last third of the 19th century led to a renewed decline of systematics. Physiologists and experimental embryologists considered it a purely descriptive activity and quite unworthy of the attention of a true scientist. Physical scientists as well as experimental biologists agreed in considering natural history a form of stamp collecting. A leading zoologist, when visiting Cambridge University late in the 19th century, observed, "Natural history is discouraged as much as possible, and regarded as idle trifling, by the thousands and one mathematicians of that venerated university." A well-known historian of the physical sciences stated as recently as 1960, "Taxonomy little tempts the historian of scientific ideas." What these critics failed to see was to what extent the study of diversity was the basis for research in major parts of biology. Mayr, 1974b. They failed to see what it had become in the hands of Aristotle, Cuvier, Weismann, or Lorentz. Natural history is one of the most fertile and original branches of biology. Is it not true that Darwin's Origin of Species was essentially based on natural history research and that the sciences of ethology and ecology developed out of natural history? Biology would be an exceedingly narrow discipline if restricted to experimental laboratory researches, deprived of the contact with the continuing, invigorating input from natural history. Unfortunately, no one has yet written a history of the influence which natural history has exerted on the development of biology, although D. E. Allen's The Naturalist in Britain, 1976, does an excellent job for 19th century England. Stresemann's Ornithology, 1975, covers the same subject as far as birds are concerned. In every group of naturalists there have been keen and inquisitive minds who ask deeper questions. They contributed the most valuable of the writings of natural theology, for example, Ray, Zorn, and Kirby. They founded natural history journals and societies, and they outlined the basic problems which eventually became the subject matter of evolutionary biology, biogeography, ecology, and behavior. Interestingly, all the great pioneers in these areas were amateurs, dedicated and enthusiastic amateurs. Natural history was the last branch of biology to become professionalized. Only in our age is it being appreciated what a great conceptual contribution natural history has made to biology. There is no dearth of so-called histories of taxonomy, but almost without exception they are merely histories of classifications. They record the gradual improvements, as well as occasional backward steps, in the concrete classification of groups of animals or plants proposed by authors from Aristotle, Theophrastus, and Dioscorides to Audonson, Linnaeus, Pallas, Cuvier, Lamarck, de Jussieu, Lindley, Hooker, Engler, Ehrenberg, Leuckart, Haeckel, Huxley, and many others. These historians show that the incessant endeavors to regroup genera, families, and orders have succeeded in establishing more homogeneous groupings, groupings which reflect common descent and degree of evolutionary divergence. It is a fascinating history of trial and error. 8. 143. 144. The focus on classification in this genre of literature fails, however, to come to grips with the history of the changing ideas and concepts of the field. The most important aspect of the history of systematics is that it is, like the history of evolutionary biology, a history of concepts rather than of facts, and that certain competing, if not totally antagonistic, concepts and interpretations have continued to coexist from the beginning of the 18th century to the present time, a period of some 250 years. The heterogeneity of conceptualization in taxonomy is in part due to the fact that a different tradition prevails in the taxonomy of each group of organisms. This is true not only for bacteria, plants, and animals but even for different groups of plants, insects, or vertebrates. The entry of such new concepts as multiple character classifications, polytypic species, sibling species, versus biological races, or biological species into the taxonomy of different higher taxa occurred at very different times. One's first impression is that the history of systematics was a never-ending struggle with the same old problems, such as, what is a species? What is relationship? How are higher taxa best delimited? How does one assemble species into higher taxa? What are the most reliable characters? What principles have to be applied when ranking taxa in higher categories? What is the function of a classification? And so forth. Evidently, the history of systematics does not conform at all to the concept of the progress of science described by Thomas Kuhn in his theory of scientific revolutions. Not even the Darwinian Revolution in 1859 produced as decisive a change in systematics as one might have expected. What the reasons for this state of affairs are will become apparent from the ensuing presentation. Yet, it will also show that there was by no means a total conceptual stasis in the last 300 years. Concepts have changed and have been clarified, as is best demonstrated by the changes in the use and meaning of some frequently employed terms at different periods and in the writings of different authors. 9. How could a truly unified theory of systematics develop as long as the term affinity was used both for mere similarity and for genetic relationship, when the term variety was used for geographically circumscribed populations and for intrapopulation variants, individuals, when the term species was used for morphologically different individuals and for reproductively isolated populations, and the term classification for identification schemes, and for true classifications? The term natural system meant very different things at different periods, and certain terms, like category, were often used by the same author for very different concepts. Most of the authors who employed the same term, for example, category or variety, in very different ways were quite unaware of the ambiguity of their own usage. It is probably legitimate to say that more progress was made in clarifying the concepts of taxonomy during the last 40 years than during the preceding 200 years. The structure of systematics. Uniqueness is the first overwhelming impression one gets when one looks at the elephant, the giraffe, the emperor penguin, the swallowtail butterfly, the oak tree, and the mushroom. If this diversity were really chaotic, it could not be studied. But there are regularities, and more than that, as Darwin and so many others have shown, these regularities can be explained. In addition to a chance element, there are determinable causes in the production of diversity. It is therefore legitimate to recognize a science called systematics, which has diversity as its subject matter. As Simpson, 1961, defined it, systematics is the scientific study of the kinds and diversity of organisms and of any and all relationships among them. As Simpson has furthermore said, systematics is at the same time the most elementary and the most inclusive part of biology, most elementary because organisms cannot be discussed or treated in a scientific way until some taxonomy has been achieved, and most inclusive because systematics in its various branches gathers together, utilizes, summarizes, and implements everything that is known about organisms, whether morphological, physiological, psychological, or ecological. Because systematics covers such an enormous field, endeavors have been made to subdivide it. For instance, it has been stated that the classification of a taxon goes through various stages of maturation. These have sometimes been informally referred to as alpha, beta, and gamma taxonomy. Alpha taxonomy refers to the level at which species are characterized and named, beta taxonomy to the arranging of these species into a natural system of lesser and higher categories, and gamma taxonomy, to evolutionary studies based on taxonomic research, Mayr, Lindsley, and using 1953, 19. Actually, work at the alpha and beta level proceeds simultaneously. They are not stages, and gamma taxonomy is not strictly taxonomy. The histochart of phi field is best understood if two subfields of taxonomy are recognized: 1. Microtaxonomy, which deals with the methods and principles by which kinds, species, of organisms are recognized and delimited, and 2. Macrotaxonomy, which deals with the methods and principles by which kinds of organisms are classified, that is, arranged in the form of classifications. Taxonomy as a whole, then, is defined, somewhat more narrowly than systematics, as the theory and practice of delimiting kinds of organisms and of classifying them. Simpson, 1961, Mayr, 1969. For macrotaxonomy, the science of classifying. Classifications are necessary wherever one has to deal with diversity. Thus one has classifications of languages, of goods in any manufacturing or marketing system, of books in a library, or of animals and plants in nature. In all these cases the process of classifying consists in the grouping of individual objects into categories or classes. There is no argument about this basic procedure, but what has been controversial for centuries is how this is best done, what classifying criteria should be used, and what the ultimate purpose of a classification should be. It is the task of the history of macrotaxonomy to recount and discuss the diverse and frequently changing answers to these questions. Before treating the subject historically, it is necessary to deal critically with a number of concepts which have often, one is tempted to say consistently, been confused in the history of taxonomy. Identification versus classification. Identification schemes are not classifications. The procedure of identification is based on deductive reasoning. Its purpose is to place an investigated individual into one of the classes of an already existing classification. If one succeeds, one has identified the specimen. Identification deals with just a few characters which assign the specimen into one or the other couplet of an identification key. Mayr, 1969, 466, 112 to 115. By contrast, classification, as now conceived, assembles populations and taxa into groups, and these, in turn, into even larger groups, this process making use of large numbers of characters. An understanding of the difference between classification and identification schemes is crucial in the evaluation of so-called special-purpose classifications, such as classifications of medicinal plants on the basis of specific curative properties. Such classifications are actually nothing but identification schemes, or so it seems to the modern taxonomist. When the Greek physician Dios 147, 148 Corides ordered plants according to their curative properties, he wanted to safeguard the use of the right species for its specific medicinal purpose. Since most medicines were derived from plants almost up to modern times, pharmacopoeias served simultaneously as manuals of plant identification. Some special-purpose classifications, however, are not identification keys but actually serve the purpose implied by their name. This is true, for instance, when plants are classified in the ecological literature according to growth form or habitat. The usefulness of such classifications is very limited. Yet, prior to the 16th century virtually all attempts at classification were of this utilitarian type. In the consideration of classifications, it is therefore very important to have a clear understanding of the various possible objectives of a classification. The functions of classifications. Philosophers as well as taxonomists have realized almost from the beginning that classifications serve a dual purpose, a practical and a general, that is, scientific or metaphysical, one. But there has been considerable disagreement as to the nature of these two objectives. The practical purpose that was stressed particularly by the early authors was that of serving as an identification key. In more recent times the practical purpose that is most often stressed is that a classification should serve as an index to an information storage and retrieval system. In order to accomplish this purpose best, a classification should consist of classes of objects that have the greatest number of attributes in common. Such a classification is automatically the key to the information stored in it. Ease of information retrieval is generally the principal or exclusive objective of the classification of items like books in a library and most other inanimate objects that are ordered according to more or less arbitrary criteria. By contrast, the classification of items that are connected by causation, as in a classification of diseases, or by origin, as in biological classification, are subject to considerable constraints but have the valuable capacity to serve as the basis of far-reaching generalizations. As far as the general meaning of biological classification is concerned, there has been much change over time. For Aristotle it reflected the harmony of nature, in particular, as far as it was expressed in the Scala Naturae. For the natural theologians, as was clearly expressed by Louis Agassiz, 1857, the classification demonstrated the plan of creation of the designer of this world. The macrotaxonomy, the science of classifying. Natural system is the expression of this plan. After the proposal of the theory of common descent by Darwin, the metaphysical interpretation of classification was replaced by a scientific one. Since the observations in all comparative branches of biology were organized with the help of the natural system, now evolutionarily defined, it became the primary function of classification to delimit taxa and construct a hierarchy of higher taxa which permitted the greatest number of valid generalizations. This was based on the assumption that members of a taxon, sharing a common heritage as descendants from a common ancestor, will have more characters in common with each other than with species not so related. Evolutionary classifications thus have considerable heuristic value in all comparative studies. They are open to testing either with additional characters or by comparison with other taxa. Warburton, 1967. The existence of these two kinds, practical and general, of objectives of a biological classification has led to controversy. For instance, it has been questioned whether the object of information retrieval is compatible with that of generalization. What is the nature of the embodied generalizations? Can they be considered a theory? This short statement of the problems connected with the various roles of classification may sharpen the attention of the reader when following the historical changes in the attitude toward these problems. Aristotle. The history of taxonomy starts with Aristotle, 384 to 322 BC. Though much seems to have been known about animals and plants before him, the few earlier writings that have come down to us do not contain any classifications. As far as factual information is concerned, Aristotle evidently incorporated in his work anything he was able to obtain from his predecessors, presumably mostly from the school of Hippocrates. Yet, the loving detail with which Aristotle describes various marine animals indicates that much of his information is original, or at least was obtained by him personally from fishermen and similar folklore sources. It is believed that he devoted himself largely to natural history studies during his years at Lesbos. His main work of descriptive zoology is Historia Animalium, but there are numerous statements of systematic. 149. 150. Relevance also in De Partibus, in De Generatione, and in other writings. Aristotle is traditionally celebrated as the father of the science of classification, and yet from the Renaissance to the present there has been great uncertainty and much disagreement as to what really his principles of classification were. In part this seems to be due to the fact that Aristotle advanced different methods in his earlier writings, in which he developed his principles of logic, from those in his later biological works, in part owing to his conviction that the method of definition by logical division was not capable of providing a reasonably comprehensive description and characterization of groups of animals. Aristotle's method of logic is best explained by reference to a well-known parlor game. A person is asked to guess an object which the other members of the party have chosen during his absence. Is it alive? Might be his first question. This separates all conceivable objects into two classes, organic beings and inanimate objects. If the answer is yes, he may ask, does it belong to the animal kingdom, thus dividing the class of living beings into two classes, animals and non-animals. A continuation of this procedure of always splitting the remaining class of objects into two parts, dichotomous division, will sooner or later lead to the correct choice. Expressed in terms of Aristotelian logic, the largest observed class, the summium genus, for instance, plants, is divided by a deductive process into two, or more, subordinated subclasses, which are called species. Each species in turn becomes at the next lower level of division a genus which is again subdivided into species. This process is repeated until the lowest set of species can no longer be divided. The species of the logician need, of course, have nothing to do with the biological species, although the products of the last step in the division of a class of organisms may, in fact, be biological species. Classification by logical division is downward classification. It is as applicable to inanimate objects. Furniture can be divided into chairs, tables, beds, and so on, as it is to organisms. What has confused later writers is that Aristotle, when describing his method of logic, actually used as examples discriminating criteria that applied to animals, such as hairy or not, with blood or bloodless, quadrupedal or not. However, logical division was not the method by which Aristotle classified animals, as is evident from the fact that Aristotle's system of animals is not an macrotaxonomy, the science of classifying. Elaborate hierarchy, too, and even more so from the fact that he quite specifically ridicules dichotomous division as a classifying principle, De Partibus Animalium 642b5 644a11, and goes to considerable lengths to show why it would not work. But in spite of its rejection by Aristotle, logical division in biological classification was the preferred method from the Renaissance, see Zalpino, to Linnaeus, see below. Contrary to what is found in much of the historical literature, it is not legitimate to designate this method of classifying as Aristotelian. How then did Aristotle proceed when classifying the diversity of animals? He did so in a very modern way. He formed groups by inspection. The proper course is to endeavor to take the animals according to their groups, following the lead of the bulk of mankind, who have marked off by many differentia, not by means of dichotomy, 643b9-14. It is by resemblance of the shapes of their parts, or of their whole body, that the groups are marked off from each other, 644b7-9. Only after he had established the groups did Aristotle select some convenient differentiating characters. On this common-sense phonetic approach Aristotle superimposed a system of evaluating the attributes that serve to characterize these groups and rank them in some sort of sequence. This ranking is the aspect of Aristotle's taxonomy that is hardest to understand for the modern. As is well known, Aristotle was greatly impressed by the importance of the four elements fire, water, earth, and air, and thus the attributes hot versus cold, or moist versus dry, were of crucial importance to him. Hot ranked above cold, and moist above dry. Blood, being both hot and moist, became thus a particularly important characteristic. Aristotle, consequently, had a scale of values for different physiological functions, as they seemed to be characteristic for different kinds of animals. Hotter, moister creatures were supposed to be rational, whereas colder, drier creatures had less vital heat and lacked the higher type of soul. This type of speculation particularly appealed to the Renaissance Aristotelians and induced them to propose concrete rank scales of taxonomic characters, based on their assumed physiological importance. This must be remembered, if one wants to understand why Aristotle's classifications were not meant to be identification schemes or purely phonetic schemes. Aristotle recognized certain groups primarily to illustrate his physiological theories and to be able to organize information on reproduction, life cycle, degrees of perfection of the offspring, and habitat, air, land, water. 4. 151. 152. His purposes. It was therefore quite legitimate to separate the aquatic cetaceans from the terrestrial mammals, and the soft, free-swimming cephalopods from the marine and terrestrial hard-shelled mollusks. On the whole, in spite of some incongruous combinations and unclassified residues, Aristotle's higher taxa of animals were distinctly superior to those of Linnaeus, whose primary interest was in plants. When we study Aristotle's zoological works, we are impressed by three findings. First, Aristotle was enormously interested in the diversity of the world. Second, there is no evidence that Aristotle had a particular interest in animal classification per se, he nowhere tabulated the 9 higher taxa recognized by him. Finally, to repeat, whatever classification he had was not the result of logical division. It is remarkable how little of Aristotle's system of logic is reflected in the Historia Animalium. In this work one has far more the impression of an empirical, almost pragmatic approach rather than that of deductive logic. Aristotle simply wanted to tell in the most efficient way what he knew about animals in order that we may first get a clear notion of distinctive characters and common properties, 491-8. The quickest way to achieve this objective was comparison. Indeed, the entire book is built on comparisons, of structure, comparative anatomy, of reproductive biology, and of behavior, animal psychology. To facilitate comparison he grouped the 580 kinds of animals mentioned by him into assemblages like birds and fishes, often making use of groupings that are as old as the Greek language. His classification of all animals into blooded and bloodless was accepted until the groups were renamed by Lamarck vertebrates and invertebrates. Within the blooded animals Aristotle recognized the birds and fishes as separate genera, but ran into some trouble with the remainder. Accepting vivipary versus ovipary as an important characteristic, he separated the hairy ones, now called mammals, from the cold-blooded oviparous ones, reptiles and amphibians. He clearly separated the cetaceans both from the fishes and from the terrestrial mammals. Different kinds of flying animals were separated by him quite widely from each other, the birds having feathered wings, bats leathery wings, and insects membranaceous wings. However, among the invertebrates his testacea, hard-shelled mollusks, included such heterogeneous elements as barnacles, sea urchins, snails, and mussels. Aristotle provided a wealth of observations on structural macrotaxonomy, the science of classifying phalanx of various animal groups with particular reference to the digestive and reproductive systems. Yet he seems to have been at least equally interested in the ecology of animals, their habitat and mode of living, their reproductive biology, and their temperament. Animals differ from one another in their manner of life, in their activities, in their habits, and in their parts, particularly with relation to the elements water, air, and earth, 487 all 12. It is now clear that it was not Aristotle's objective to provide a classification of animals that would be useful in identifying them. What then was Aristotle's importance in the history of systematics? Perhaps his most important contribution was that he, an outstanding philosopher, took such an interest in animals and their properties. This greatly facilitated the revival of zoology in the late Middle Ages and in the Renaissance. Whether in relation to structure, food habits, behavior, or reproduction, everywhere he asks the kind of significant questions that made the study of animals a science. He also laid the groundwork for the eventual organization of biology into morphology, systematics, physiology, embryology, and ethology, and gave instructions on how a researcher should proceed. His formalization of individual kinds, species, and of collective groups, genera, was the point of departure for the more perceptive and elaborate classifications of the later period. Now that Aristotle is no longer considered merely one of the fathers of scholasticism but also a philosophizing biologist, many aspects of his work appear in an entirely new light. A modern analysis of Aristotle's conceptual framework of taxonomy is still wanting, however. 3. As a broad generalization, one can probably say that the level of natural history went steadily downhill after the death of Aristotle. Pliny and Aelian were busy compilers who quite uncritically placed good natural history next to fabulous creatures of various mythologies. For in the ensuing period animals were written about not for the sake of providing knowledge about them but for the sake of moralizing. They became symbols. If one wanted to moralize about diligence, one wrote about the ant, about courage, the lion. With the rise of Christianity, stories about animals were often made part of religious tracts. Animals became symbols for certain ideas in Christian dogma and were introduced in paintings and other art as symbols of these ideas. One might say that the study of animals became a purely spiritual or aesthetic endeavor, almost totally divorced from natural history as such. This was true. 153. 154. Broadly speaking, at least for the more than 1,000-year period from Pliny, d.A.D. 79, to the 15th century, Stannard, 1979. Frederick I's De Arte Venandi, 1250, and the writings of Albertus Magnus, ca 1200 to 1280, were quite exceptional for their period. A rapid change occurred in the ensuing centuries, furthered by a number of developments. One was the rediscovery of the biological writings of Aristotle and their being made available in new translations. Another was a general improvement in the standard of living, with more emphasis on medical art and a corresponding emphasis on medical herbs. Finally, a kind of back-to-nature movement, away from the exclusive emphasis on spiritual life, developed in the late Middle Ages. From Hildegard von Bingen, 1098 to 1179, and Albertus Magnus on, more and more people apparently looked at living plants and animals in nature, and what is more, they wrote about them, and what is even more, when the art of printing came up, they printed books about them. Yet, it was a slow and gradual process. The encyclopedic tradition of that great and uncritical compiler Pliny continued unto the days of Gesner and Aldrovandi. But by then, in the 16th century, the authors of all nature books were physicians. The classification of plants by the ancients and the herbalists. Aristotle also wrote on plants, but his writings are lost. Thus the history of botany starts with the inquiry into plants of his pupil, Theophrastus, 371 to 287 BC. As important as his contributions are to plant morphology and plant biology, Theophrastus adopted no formal system of classification, the form of growth, trees, shrubs, undershrubs, and herbs, constituting the primary criterion of division, Other criteria are the presence or absence of spines, cultivation by man or not, and so on. Theophrastus apparently took many of his groupings from folklore, with the result that some of them are quite natural, oaks, willows, while others are, taxonomically speaking, quite artificial, like Daphne, a conglomerate of plants with evergreen leaves. Far more important for the immediate history of botany was Dioscorides, ca. AD 60. As a Greek physician attached to the Roman army, he had traveled very widely and acquired an enormous treasure of information on plants that were of use to man. His Materia Medica contains descriptions of between 500 macrotaxonomy, the science of classifying, and 600 plants that are either of medicinal use or provide spices, oils, resin, or fruit. The arrangement of the plants in his 5 books is based principally on their practical use, medicinal roots, herbs used as condiments, perfumes, and so on. Nevertheless, he often lists related plants in sequence, for instance most of his 22 species of Labiati or 36 species of Umbelliferae. Indeed, he criticized the alphabetical arrangement adopted by some previous authors on the ground that it separated related plants possessing similar properties. The principal importance of Dioscorides is that his Materia Medica was the chief botany text for 1.5 millennia, Magna Frau, 1973, 4-11. Dioscorides was considered the supreme authority in all matters relating to plants, particularly their medicinal properties. Yet, as in the case of Galen's anatomy, the tradition became more and more book knowledge, more and more divorced from nature and from actual organisms. Beginning with the 13th century, however, a number of herbals were published in which one notices a return to actual observation of nature, a trend which greatly accelerated after the invention of the art of printing. A Latin translation of Dioscorides was published in 1478, and one of Theophrastus in 1483, and many of the handwritten herbals of the preceding several centuries were printed for the first time at that period. 5. The increasing interest in the identification of plants, the discovery of rich floras of local species unknown to Dioscorides, as well as the search for new medical properties in newly discovered plants led to the founding of chairs of botany at European medical schools, the first at Padua, in 1533. A new era started with the work of the German fathers of botany, Brunfels, 1488-1534, Bach, 1489-1554, and Fuchs, 1501-1566. These naturalists represent a return to nature and to personal observation. Their accounts are not a set of compilations and endlessly copied myths and allegories, but are descriptions, based on real, living plants, observed in nature. They also represent attempts to describe and illustrate local floras. The illustrations produced by the excellent draftsmen and woodcarvers they employed reached a level of accuracy and artisanship not surpassed for generations. These played the same role in botany that the illustrations in Vesalius had played in anatomy. The title of Brunfels' work, Herbarum Vivae Icons, 1530, stresses the fact that the plants had been drawn from nature, by Hans Waditz. All 3 herbals describe and illustrate many Central European species that had been entirely unknown to the ancient botanists. 155. Brunfels illustrated 260 plants, Fuchs in his Historia Stirpium, 1542, no less than 500 plants. Hieronymus Bach was the most original of the 3. All of his descriptions, written in precise and picturesque colloquial German, were clearly based on his own observations. Furthermore, he rejected expressly the alphabetical arrangements of other herbals and gave as his method to place together, yet to keep distinct, all plants which are related and connected, or otherwise resemble one another. Not only did he write good descriptions, 156, but he noted the localities and habitats, including properties of soil, of the plants he describes and their flowering seasons and other aspects of their life history. In this way Bach's work was the prototype of all future local floras, and along with other herbals printed in France and England, was among the most popular books of the era. 6. Classification among the herbalists. Perhaps the most conspicuous aspect of the classifications of the herbalists is the absence of any consistent system, their interest being not at all in classification but in the properties of individual species. In the case of Brunfels, 1530, the sequence seems to be quite arbitrary, at least as far as genera are concerned. However, closely related species, for instance Plantago major, P minor, and P. rubia, are placed next to each other. Fuchs, 1542, arranges his plants largely alphabetically, the contents of the first 4 chapters being Absinthium, Abrotinum, Acerum, and Acarum. This sequence is retained in the German edition, 1543, even though the German names for these 4 genera, Wormit, Taubwurz, Hasselwurz, and Drachenwurz, are now in the reverse sequence of the alphabet. Amusingly, Fuchs comments that he has left out of the greatly abbreviated German edition that which the common man does not need to know. 3 classificatory aspects of the herbals are worth singling out. First, there is a vague recognition of kinds, species, and groups, genera. Second, many recognized groups, like grasses, are quite natural but are often expanded by the addition of superficially similar forms. For instance, among the nettles would be classified the true nettles, urtica, as well as labiates with similar leaves, the false nettles. Next to wheat, a grass, one finds buckwheat, a dicotyledon, merely because the word wheat is part of its vernacular name. Such juxtaposition was of considerable value for Iden. Macrotaxonomy, the science of classifying. Tification but was no basis for a sound classification. Finally, there were only limited attempts to establish higher taxa. In his Herbal, 1597, based on Dodoens and Lobel, for instance, Gerard devotes his first chapter to grasses, rushes, corn, flags, bulbous or onion-rooted plants, that is, to largely monocotyledonous plants. His second chapter, however, contains all sorts of herbs for meat, medicine, or sweet-smelling use. Botanically speaking, a complete hodgepodge. The tradition of the herbals reached its climax with the publication of Caspar Bauerhin's Pinax, 1623. It shows the remarkable progress made in the 90 years since the publication of the Icons of Brunfels. Some 6,000 kinds of plants are described in 12 books divided into 72 sections. All kinds are assigned to a genus and a species, although no generic diagnoses are given. Related plants are frequently placed together on the basis of their overall similarity or owing to common properties. The groups thus formed are not given taxa names and no diagnoses of higher taxa are provided. Nevertheless, there is an implicit recognition of the monocotyledons, and the species and genera of some 9 or 10 families and subfamilies of dicotyledons are brought together. Although Bauerhin nowhere explains his method, it is evident that he simultaneously considered a large number of different characters and grouped those genera together which share a large number of characters. Considering that it was the main purpose of the Pinax to provide a convenient catalogue of plant names, Bauerhin's ability to find related genera and to group them together is altogether astonishing. The beginnings of almost every later development of systematic botany can be found in the writings of the herbalists, attempts to group plants on the basis of similarity or shared characteristics, beginnings of a binary nomenclature and even of dichotomous keys, a search for new characteristics, and an endeavor to provide more accurate and more detailed descriptions. Perhaps the most valuable contribution of the herbalists was their empirical attitude. No longer were they satisfied merely to copy the writings of Dioscorides and Theophrastus, they actually studied the plant in nature and described wie in seiner art und geschlecht nach aufwachs wie es blue und besame zia welcher Zeit im Jahr und in welcherlei Trichen jeds am besten zia finden see, how each grows according to its species and genus, how it flowers and sets seed in what season of the year, and on what soil each is best found. Bach, 1539. But each of the herbalists had his own way. 157. of doing things, and all of them were utterly inconsistent in whatever methods they used. Since at that time relatively few plants were known, one could find a species by simply thumbing through an herbal until one encountered something reasonably similar, and only then did one carefully read the description and study the illustration, in order to ensure the identification. This simple method became insufficient, however, when the number of known plants increased during the 16th and 17th centuries at an almost exponent 158 tile rate. Whereas Fuchs, 1542, knew some 500 species, and Boerhaave, 1623, 6,000 species, John Ray in 1682 listed already 18,000. An alphabetical or otherwise arbitrary arrangement was no longer sufficient. To cope with this avalanche of new kinds of plants, a far more careful discrimination of species within the broader kinds, genera, became necessary, and a more serious endeavor was made to recognize groupings of related genera, that is, higher taxa. Some system or method by which one could rather quickly identify a given specimen was also required. Downward classification by logical division. The theory of classification would seem deceptively simple. One orders the to-be classified objects on the basis of their similarity. When one deals with organisms, this at once leads to the question, how does one determine, indeed preferably measure, similarity? The answer is by a careful analysis of characters. The choice and evaluation of characters has therefore occupied the center of attention in recent discussions. However, we shall never understand the contrast between the earlier theories of classification, dominant from Caesalpino to Linnaeus, with those prevalent since Darwin if we start with a consideration of characters. Rather, one must begin by asking what kinds of classifications are possible. Actually, ordering by similarity was not the way classifications were constructed during the Renaissance. The need for identification was preeminent, and the first comprehensive methodology of plant taxonomy was developed to satisfy this demand. The Italian anatomist-physiologist Andrea Caesalpino, 1519–1603, is generally and rightly credited with having been the first to have done this consistently in his great work De Se Plantae, 1583. He considered himself a follower of Theophrastus and, like him, divided plants. Macrotaxonomy, the science of classifying into trees, shrubs, undershrubs, perennials, and herbaceous plants. But for a system of easy identification he turned to Aristotle and borrowed from him the method of logical division, with which everybody was familiar who had attended school between the Middle Ages and the end of the 18th century. See discussion of Aristotle, above. The principles of downward classification by logical division are basically very simple. Yet, in the writings of the classifiers from Caesalpino to Linnaeus they were embedded in such a complex matrix of scholastic dogma and jargon, as indicated by such terms as essence, universal, accidentals, differentia, characters, and so on, that a specialized study is required for their understanding. 7. The method of logical division did not originate with Aristotle. Already Plato was interested in distinguishing general groups from subordinated items, Messon 72, Parmenides 129c, Politicus 26ib, but it reached its full importance only in Aristotle's followers. For example, the tree of porphyry, also called the Ramine tree, Jevons, 1877, 702. The most characteristic feature of this method is the division of a genus into two species, tertium non dat. This is called dichotomous division. This method is ideally suited for the construction of identification keys, but it often leads to highly artificial and unbalanced classifications. Aristotle himself, as pointed out above, ridiculed the idea of basing a classification on dichotomy, but his use of zoological examples in his logical exercises misled his followers. There were several reasons for the great popularity of downward classification between Caesalpino and the 19th century. Its most important practical advantage was that it started with a number of easily recognizable classes, let us say with trees, shrubs, herbs, or, in the case of animals, with birds, butterflies, or beetles, and divided them into subordinate sets of subclasses with the help of appropriate differentiating characters, differentia. No prior knowledge of species was required, only an ability to carry out the procedure of logical division. Any layperson could do this. It would be a mistake, however, to think that the only reason for the popularity of logical division was its practicality. Its popularity was greatest in the centuries when everyone looked for order and logic in the created world. Hence, if the world represents an orderly system, what better way could there be to study and analyze it than with the tools and procedures of logic? A classification could reflect the order of nature adequately only if it was based on the 159. 160. True essences of the organisms. It was the method of logical division which would help in the discovery and definition of these essences. The method thus was a perfect reflection of the dominant essentialistic philosophy of the period. Nothing in the whole method of logical division is more important than the choice of the differentiating characters. The dependence on single characters implicit in this method necessitates a careful weighting of characters. Cisalpino, fully aware of this, devoted a great deal of care and attention to the study of plant morphology. He discovered many useful characters and was one of the first, Gessner preceded him, to recognize the taxonomic value of fructification. Cisalpino was altogether on the wrong track in his theory of weighting characters, however. A true follower of Aristotle, he selected characters on the basis of their physiological importance. The two kinds of attributes he considered to be most important for a plant were those relating to nutrition and to generation. The nutritive aspect, growth, was considered the most important, and this is why his first division was into trees, herbs, and so on. The importance of generation was reflected in the emphasis on fructification, seed, and seedlings, in analogy with Aristotle's emphasis on the animal embryo. Comparison was an important element in his method, but he carried it to ludicrous extremes when he attempted to match the functionally most important structures of animals and plants. Thus, he equated the roots of plants with stomach and intestinal tract in animals, and he included the stem and stalk of plants in their reproductive system because they bear the seeds and fruits. Considering the frequency of convergence, parallelism, the loss of characters, and other irregularities of character evolution, one would expect that the method of logical division based on single characters would lead to absolute chaos. A study of Cisalpino's plant classification shows, however, that the 32 groups of plants recognized by him are, on the whole, remarkably natural. 9. It is quite evident that Cisalpino could not have arrived at his groupings merely by applying logical division. As Stafleau, 1969, 23, correctly remarked, Cisalpino evidently started out with certain natural groups known to him intuitively or by tradition, and added the rather irrelevant and certainly unimportant superstructure of logical division. Cisalpino, thus, followed a two-step procedure. He first sorted his plants by inspection into more or less natural groups and then searched for suitable key characters. Macrotaxonomy, the science of classifying. That would permit him to arrange these groups in accordance with the principles of logical division. Only thus was he able to achieve simultaneously two objectives, to provide a convenient identification key and to group his plants into classes according to their affinity, see below. He was not always successful in compromising between the conflicting demands of the two methods, as when the principles of logical division forced him to separate the herbaceous and the tree-like legumes into two different families. In spite of the evident shortcomings of his system, Cisalpino exerted a powerful influence on botany during the ensuing 200 years. Up to and including Linnaeus, all systems of plant classifications were variations and improvements upon the approach first taken by Cisalpino. They all based their classifications on the method of logical division and on some a priori weighting of characters. Cisalpino had such an impact not because his classification was particularly useful but simply because he was the first author to provide a more or less consistent method of classification. It would have to do until someone came up with a better one. The choice of the characters during the early steps of the division results by necessity in entirely different classifications. This is why the systems of the great botanists of the 17th and 18th centuries, who followed in César Pinot's footsteps, differed so drastically from each other. Only the specialist is interested in the details by which the classifications of Magnol, Tournefort, Rivanus, Vallerien, Ray, and the various lesser figures disagreed with each other. All these botanists differed in their knowledge of plants, and this influenced their choice of the characters for the first division. In the classification of animals, likewise, it led to entirely different classifications whether one chose as the first differentia with blood or without, hairy or hairless, two-footed or four-footed. Another consequence of the method of downward classification is that it cannot be improved gradually and piecemeal. The replacement of one character by a different one will result in an entirely new classification. Under this system, the possible number of different classifications is virtually unlimited. And yet these botanists somehow succeeded in adjusting the choice and sequence of their characters in such a way as not to break up certain well-known natural groups of plants. How clearly the naturalness of certain groups was appreciated is demonstrated by the fact that, as Larson, 1971, 41, points out, many plant families, 161, Coniferae, Cruciferae, Graminaceae, and Umbelliferae, for example, were established in the 16th century, and remained intact throughout the vicissitudes of the struggle over systems. More and more such groupings were recognized, particularly when certain seemingly isolated European genera were discovered to belong to rich tropical families. The botanists of the 17th century differed from each other, however, not only in the weight they gave to different characters but also in whether their major interest was in the genus or 162 the species, and how sacrosanct they held the principle of logical division and the reputedly Aristotelian weighting system of characters. It is in these 2 points in which the two greatest botanists of the late 17th century most strongly differed from each other. Ray and Tournefort. John Ray, 1627–1705, of course, was far more than a botanist. 10 He co-authored the most important zoological treatises of the period and wrote one of the great books in natural theology. But he was also a practical Englishman, whose primary aim was to produce a plant book that would permit the unequivocal identification of plants. Consequently, he was particularly concerned with the nature of the species. In his Historia Plantarum he deals with no less than 18,655 plant species and gives a definition of the species category, see glossary, which was largely adopted for the next 150 years. Almost unique among the early botanists, he was not educated as a physician, and was less touched by the scholastic tradition than his contemporaries, including even Tournefort, who had been educated at a Jesuit college. Consequently, it is not surprising that John Ray from his earliest botanical publications on was far less consistent in his application of dichotomous division than César Pinot or Tournefort. He not only used different sets of subordinate characters in different of his classes, but he did not even hesitate to shift from the fructification to vegetative characters, presence of a stem or of bulbous roots, when this seemed convenient. Tournefort and Rivanus attacked him vigorously for these deviations, but Ray answered the criticism with the pragmatic advice, an acceptable classification is one that joins together those plants which are similar, and agree in primary parts, or in total external aspect, and that separates those which differ in these aspects. Synopsis, 1690, 33. He repeats this guiding prin. Macrotaxonomy, the science of classifying. Sipple in all of his subsequent publications. For instance, the first condition of a natural method must be that it neither splits plant groups between which apparent natural similarities exist nor lumps such with natural distinctions. Sylloge, 1694, 17. César Pinot and other defenders of logical division had, of course, claimed that this is precisely what their method would do. Ray is thus forced to go further. In his De Variis, 1696, he points out that one really has no objective method of determining which characters reflect the essence and which are accidental. In other words, he implicitly rejects the method of a priori weighting. It is important to note that he does not reject the concept of an essence or the difference between essential and accidental characters. From this he concludes that not only flower and fruit but other parts of the plant as well may reflect the essence. He even goes so far as saying that species may differ from each other by their sets of accidentals. Ornithology, 1678. Sloane, 1972, advocated the thesis that it was Ray's study of the writings of Locke which led him to these heretical views. There is much to indicate, however, that Ray had arrived at the unorthodox evaluation of characters by a purely pragmatic approach and had taken up philosophical studies in order to gather ammunition for his reply to Tournefort, April 29, 1696, letter to Robinson. Since it is very doubtful that a single character can reflect the essence of a genus, Ray recommends in his Methodus Plantarum, 1703, 6-7 the best arrangement of plants is that in which all genera, from the highest through the subordinate and lowest, have several common attributes or agree in several parts or accidents. He goes so far as to employ even ecological criteria for groupings, a set of characters strictly forbidden since Cisalpino. Actually Manual. Prodromus, 1689, had already recommended combinations of characters. Ray's contribution to the true classification of plants was rather minor. Like Albertus Magnus, Pina, Lobel, and Boerhaave, he distinguished monocotyledons and dicotyledons without recognizing the fundamental nature of the difference. He still retains Theophrastus' division of plants into trees, shrubs, herbs, and so on, and his classifications of the Caryophyllaceae and Solanaceae, for instance, are quite inferior to those of Boerhaave and other predecessors. The history of botanical classifications indicates that Ray's influence was limited. Nevertheless, it can hardly be doubted that he contributed to a weakening of the hold of the method of logical division. 163. 164. Ray's illustrious contemporary in France, Joseph Pétain de Tournefort, 1656–1708, was perhaps the first botanist fully to realize the wealth of exotic floras. Sloane, 1972, 39–52, Mag de Frau, 1963, 46–48. Purely practical considerations were therefore more important for him than the development of a universal or natural method. His aim was to provide a convenient key to the diversity of plants. To know the plants is to know the exact names one has given to them on the basis of the structure of some of their parts. Tournefort, Institutions, 1694, 1. Since the number of genera was still manageable in his day, he concentrated on this rank. In contrast to most of his predecessors, he used a single word as the generic name. Tournefort's greatest merit consists in the first clear formulation of the genus concept and the judicious delimitation and clear description of 698 genera of plants, most of which, sometimes under different names, were adopted by Linnaeus. As a result, some of the best-known generic names in plants go back to Tournefort. Since flowers and fruits offer the greatest number of easily visible characters, these were the parts of the plant on which he based most of his descriptions, but he occasionally referred to other structures when this seemed helpful. Tournefort was far more willing to make concessions to practical needs than Linnaeus. In the case of plants without fruits and flowers or those in which these structures are too small to be seen with the naked eye, he recommended that for the correct determination of such genera not only all the rest of the parts of the plants should be utilized, but also their accidental characters, means of propagation, and overall character and external appearance, Institutiones, 61. In spite of his careful analysis of characters, his classification of higher taxa was more or less artificial. Of the 22 classes he had established, only 6 correspond to natural groups. For purposes of identification, however, Tournefort's method was more successful than the systems of his contemporaries Ray, Morrison, or Rivinus. It was widely adopted not only in France but also in the Netherlands and eventually in England and Germany. The systems of Mayr have, 1710, Manual, 1729, and Siegesbeck, 1737, were variants of Tournefort's. They differed primarily in the choice of the character which they considered most important. The primary objective of all these systems was identification with the help of logical division. None of them succeeded in achieving a consistent delimitation of natural groups, as is indeed impossible with the method of logical division. Macrotaxonomy, the science of classifying. Downward classification was not a bad strategy at the time of Cisalpino, for everything about classification was uncertain at that period. A realistic species concept had not yet been developed, and the number of newly discovered kinds of organisms was increasing at an exponential rate. At a time when few people knew anything about natural history, correct identification was the greatest need, and divisional classification was very well suited for this objective. In retrospect, it is obvious that it was a suitable, if not inevitable, first step toward a superior method of classification. The botanists of this period were frequently maligned as Aristotelians, implying a deductive approach and a blind reliance on tradition and authority. This is quite unjustified. To be sure, they used the methods of logical division as being the system best suited for successful identification, but their work was not at all based on authority but rather on study in nature, extensive traveling, and careful analysis of specimens. They laid a sound empirical foundation for the improved systems of the post-Linnaean period. Attention must be called here to striking difference in the historical development of natural history and of the physical sciences. The 16th and 17th centuries witnessed the so-called scientific revolution, which, however, was essentially limited to the physical sciences and, to a lesser extent, to some parts of functional biology. Natural history and systematics, however, were almost totally untouched by these sweeping changes in the neighboring sciences. From Cisalpino through Tournefort and Ray, not to mention Jungius or Rivanus, to Linnaeus there continued an unbroken tradition of essentialism and the method of logical division. It has been claimed, not without justification, that natural history, almost up to the time of Darwin, continued to be dominated by the metaphysics of Plato and Aristotle. What should be added, however, is that it was also dominated by a different strand in the skein of Aristotle's thinking, the spirit of the naturalist, the joy of observing nature and the fascination with diversity. That part of the Aristotelian heritage has continued to the present day, while in systematics the Aristotelian metaphysics, already greatly weakened during the transition period between Adanson and 1859, was completely rooted by Darwin. The rapid accumulation of knowledge on plant classification between the early 1500s and Linnaeus would have been impossible without an important technological advance, the invention of 165. 166. The herbarium, Lanu and Stafflau, 1956. The idea to press and dry plants seems to have originated with Lucagini, 1490 to 1556, among whose pupils were Cibo, whose herbarium from 1532 is still extant, Turner, Aldrovandi, and Cisalpino, all of whom made herbaria. Herbaria were quite indispensable for the collecting of exotic plants. Most of Linnaeus' descriptions of non-Swedish plants, for instance, were made from herbarium specimens. Each of the great herbaria of the world has now 3 to 6 million specimens, to which botanists actively refer for description and identification. There are good reasons to believe that the great advances made in the classification of plants during the second half of the 16th century were considerably facilitated by the new technology of herbaria, which permitted a referring back to specimens at all seasons of the year. The second important technological advance, of course, was woodcut making. Lucagini was a great innovator in another way. He established in 1543, or 1544, the first university botanic garden at Pisa. A second one was established in Padova in 1545. At a time when herbaria were few and illustrations poor, the value of botanic gardens for teaching purposes cannot be exaggerated. By the end of the 16th century, public botanic gardens had been established at Florence, Bologna, Paris, and Montpellier. Pre-Linnaean zoologists. Animal classification, by comparison to that of plants, had a considerable head start when science reawakened during the Renaissance. While flowering plants are rather uniform in their structure, there are conspicuous differences between a vertebrate, an insect, or a jellyfish, and even within the vertebrates, between a mammal, a bird, a frog, or a fish. Not surprisingly, therefore, the major groups of animals had been distinguished since before the time of Aristotle. No elaborate theory was needed to recognize them. As a result of such striking differences among well-defined animal taxa, zoologists tended to specialize and to concentrate on one particular group, like mammals, birds, Turner, Bellin, or fishes, Rondelet. But there is an even more important difference between the treatment of plants and animals. Plants are very numerous, but in spite of their seeming similarity, certain species were believed to have very specific curative properties. Correct identification was macrotaxonomy, the science of classifying. Thus the overriding need. Although identification played also some role in the animal books, everybody knew the lion, the fox, the hare, the crow, and it did not seem particularly interesting or important how they were classified. However, there was the tradition of the moralizing animal books like the Physiologus or Conrad von Meyenberg's Buch der Natur, which dwelled on the habits of animals. As a result, from the very beginning the emphasis of the new zoologies was on what we would now call behavior and ecology. To be sure, there was still a tradition of quoting faithfully from the classical authors and of indulging in learned philological analyses of the meaning of animal names. Also there was still considerable credulity in travelers' tales and in the existence of monsters. But the authors showed a genuine interest in the living animal and clear evidence that they had studied their subject matter in nature. Yet they had little interest in classification, and animal taxonomy soon lagged behind that of plants. At the beginning of the 16th century, 5 naturalists born within 22 years of each other were responsible for the revival of zoology after the Middle Ages. 1. William Turner, 1508 to 1568, although an Englishman, spent much of his adult life on the continent, where he published in Cologne in 1544 an avium Histona containing life histories of individual birds, clearly based on his own observations. Turner is also known for botanical publications, but they were not as pioneering as his ornithology. A far more weighty tome is Pierre Bellin's, 1517 to 1564, L'Histoire de la Nature de Oisiaz, 1555. Bellin had acquired considerable fame owing to his travels through the eastern Mediterranean and the countries of the Near East. Using ecological and morphological characters, he classified birds into raptors, waterfowl with webbed feet, marsh birds with webless feet, terrestrial birds, and large and small arboreal birds. Thus, adaptation to the habitat was his major classifying criterion. Yet some of Bellin's groupings survived, particularly in the French ornithological literature, until the latter part of the 19th century. Bellin also published on fishes and other aquatic animals, 1551, 1553, but these works were almost immediately eclipsed by Guillaume Rondelet's, 1507-1566, De Piscibus Libri 18, 1554, which included the description of about 200 species of real fishes as well as cetaceans, cephalopods, crustaceans, hard-shelled mollusks, annelids, echinoderms, coelenterates, and sponges. A number of monsters were also included, as if they were regular inhabitants of the Mediterranean. In 1551 began the publication of Conrad Gessner's Historia. 167. 168. Animalium. This was an immense encyclopedia comprising more than 4,000 pages, where Gessner, 1516 to 1565, had compiled everything he could find in the literature on the various species of animals. Pliny rather than Aristotle was evidently his ideal. Gessner was far too busy to contribute many personal observations on animals, but his numerous correspondents supplied him with original material. In spite of his intense interest in anything and everything he could learn about animals, Gessner was obviously not interested in classification. The species are listed alphabetically in each volume, in order to facilitate the use of the work. In two other works, Leon's, 1553, and Nomenclator, 1560, Gessner grouped the species systematically but did not demonstrate any progress beyond the earlier attempts of Aristotle and Rondelet. His superior botanical work, unfortunately, was not published until long after his death, 1751 to 1771, and thus exerted little influence. Gessner's single volume on birds was expanded by Ulisse Aldrovandi, 1522 to 1605, into 3 large volumes, apparently without adding any original observations except the anatomical findings of some of his friends and their students. It was nothing but a vast compilation, of which Buffon said, by eliminating everything useless or irrelevant to the subject, one could reduce it to a tenth of the original. Aldrovandi's Ornithologia, 1599, 1600, 1603, differed in one respect from Gessner's Historia. The species were not listed alphabetically but grouped into such totally artificial categories as birds with hard beaks, birds that bathe in dust or in dust and water, those that sing well, that are water birds, and so on, quite a caricature of a classification, not even following the principles of logical division. The 100 years after Gessner which saw great advances in plant classification saw none in zoology. Progress was not made until function and habitat as classifying criteria were replaced by structure. This was first done in Francis Willughby's, 1635 to 1672, posthumously published Ornithologia Libri Trace, 1676, where birds were classified on the basis of structural characters, such as the form of the bill and feet and body size. Even though the principles of logical division were used, Willughby had obviously known birds very well, and most of the groups recognized by him are still considered natural by current standards. Stresemann, 1975. We shall never know how much of this classification was contributed by his friend John Ray, the editor of Willughby's manuscripts. At any rate, Ray himself soon published small synopses of mammals and reptiles, 1693, and insects, 1705, and his Macrotaxonomy, the Science of Classifying. Synopses of birds, 1713, and fishes, 1713, were published posthumously. As artificial as much of Ray's method was, the resulting classifications were not only the best up to that time but in certain details superior even to the later ones of Linnaeus. Animal classification became a burning problem when the world of insects was discovered in the 17th century. It was soon realized that the number of insect species far exceeded that of plants, and various naturalists, Swammerdam, Marion, Réaumur, Daguerre, and Roisel, began to devote much or all of their attention to insects and their classification. Among these René Antoine Foucault de Réaumur, 1683 to 1757, was the greatest. His famous 6-volume Natural History of Insects, even though in part patterned after Jan Swammerdam's, 1637 to 1680, work, was pioneering in various ways. His superb observations of the living insects set an example for Buffon's Histoire naturelle, and his emphasis on the higher taxa, rather than the tedious description of species, was followed by Cuvier in his 1795 memoir. Although Réaumur was not particularly interested in classification, he made numerous perceptive observations such as that female glowworms, fireflies, even though lacking the diagnostic character of hard elytra, were nevertheless beetles. He realized that the delimitation of natural groups does not depend on single diagnostic characters. Réaumur's views were clearly indicative of the growing resistance to the method of logical division, and together with the writings of Adamson, pioneered the principles of upward classification, see below. Réaumur's work was continued by C. de Geer, 1720–1778, who made major contributions to insect classification which apparently influenced Linnaeus' system of insects considerably. Tuxen, 1973, Windsor, 1976a. Natural history from the 16th through the 18th centuries was not as strictly divided into zoology and botany as it was in the 19th century. Authors like Turner, Gessner, Ray, Linnaeus, Adamson, Lamarck, and others wrote books on animals and on plants. But even in these centuries most authors specialized either on animals, Bellin, Rondelet, Swammerdam, Réaumur, Buffon, or on plants, see Zalpino, Boerhaave, Morrison, Tournefort. After 1800 no taxonomist was any longer able to cover both the animal and plant kingdoms. Owing to this increasing separation, it is not surprising that rather different traditions developed gradually in the taxonomy of the two kingdoms, in spite of the partial transfer of the botanical methodology from plants to animals by Ray and Linnaeus. 169. 170. While specialization among the zoologists was pronounced from the beginning, the botanists, owing to the structural uniformity of the flowering plants, angiosperms, could readily switch from the study of one family to that of any other, without having to learn any new techniques or terminologies. It was not until rather late in the 19th century that some botanists began to become specialists of certain families, be they orchids, grasses, or palms, a trend which has become pronounced in the last 50 years. Specialization among zoologists increased further when they began to study insects and aquatic animals, though an occasional zoologist has specialized simultaneously in very different taxa, like the French arachnologist Eugene Simon, 1848–1924, who was also a hummingbird specialist. Such specialization on a single higher taxon distracted from a concern with the methods and principles of higher classification. One can hardly deny that up to the end of the 18th century animal taxonomy was trailing behind plant taxonomy. There is another reason for the lag of zoology: plants are much easier to preserve than animals. While herbaria had been popular since the middle of the 16th century, it was not until the end of the 18th century that appropriate methods were invented for the protection of animal collections against the ravages of moths and dermestid beetles. Preservation in alcohol had long been used, but who can study a collection of birds preserved in alcohol? This method is suitable for fishes and certain marine organisms and for specimens to be used for dissection, but not for birds whose color is important. Salt and alum were used for a time to preserve bird and mammal skins, but not until Bicoeur had invented arsenical soap in the 1750s did it become possible to preserve bird skins permanently. Farber, 1977. This single technical advance is responsible for the existence of the vast modern bird and mammal collections. Insects likewise were extremely vulnerable to destruction by dermestid beetles, and it was not possible to have permanent insect collections until naphthalene and tightly fitting collection cases and occasional fumigation were introduced. There also had to be constant supervision by a curatorial staff. Even though the same problems existed in principle for plants, the actual danger was far smaller and the ease of making and maintaining collections correspondingly greater. The rapid ascendancy of animal systematics after 1800 is to be explained in part as a result of new technologies in preservation of animal collections. Macrotaxonomy, the science of classifying. Two other major differences between animals and plants must be pointed out. When the extraordinary diversity of the internal anatomy of invertebrate animals was discovered by Cuvier and Lamarck, see below, it led to a great flourishing of comparative anatomy, and this in turn to a great interest among zoologists in the classification of classes and phyla. The far greater internal uniformity of plants, or perhaps more correctly the greater difficulty of interpreting plant anatomy, precluded a similar development in botany. Finally, the species is a far more complex phenomenon in plants than in animals, at least higher animals, and this has resulted in the fact that zoologists have held a rather different species concept from that of the botanists. See Chapter 6. When writing a history of systematics, it leads to misinterpretations if one lumps indiscriminately the statements of botanists and zoologists. The views of these two kinds of biologists will have to be presented and interpreted in the context not only of their material but also of their conceptual development. But even within one of these branches of taxonomy, different conceptual worlds may coexist. For instance, in plant taxonomy, the Linnaean school was for a long time so dominant that nonconformists were systematically ignored, if not suppressed. This is, in part, the reason for the neglect of botanists like Manuel and Adanson, who, in some ways, were greater scientists than Linnaeus. Even today, the theory of classification and the species concept are usually vastly different, when the views of a specialist of a well-known group of animals, for example, birds, are compared to those of a poorly known one of insects or other invertebrates. Carl Linnaeus. No other naturalist has had as great a fame in his own lifetime as Carl Linnaeus, 1707 to 1778, one too sometimes called the father of taxonomy. Yet 100 years after his death he was widely considered nothing but a narrow-minded pedant. Now, through the researches of Kane, von Hofsten, Stern, Larsen, Staflau, and other Linnaeus scholars, we can paint a more balanced picture. 1-3 This is not an easy task, since Linnaeus was a very complex person, having seemingly incompatible traits. In his methodology he was, indeed, of a pedantic pragmatism, yet he also had great literary powers. He was a numerologist, with a fondness for the numbers 5, 12, 365, and, particularly in later years, quite a bit of a mystic. 171. And yet he was the model of a painstakingly descriptive taxonomist. He spent years in Holland and visited Germany, France, and England, yet he spoke only Swedish and Latin and knew little of any foreign language. By the time he reached Holland, 1735, his method and conceptual framework had already matured to a remarkable degree, but even though his method changed subsequently only little, his later invention of binomialism was not considered by Linnaeus an important modification of his system. His philosophical ideas changed rather decisively. He took a deeper 172 interest in only one aspect of the biology of the individual species, their sexual biology. Ritterbusch, 1964, 109 to 122, but, as his essays show, Amoenitates Academici, Linnaeus was interested in a wide variety of biogeographical and ecological subjects. Linn, 1972. 1-4 Classifying, however, was his primary interest. Indeed, his obsession to classify anything he came in contact with went so far that he proposed an elaborate classification of botanists into phytologists, botanophiles, collectors, methodici, Adonides, orators, aristici, and so on. Philosophia Botanica, para 6-52. In 1753 Linnaeus knew about 6,000 species of plants and believed the total might be about 10,000, and the number of species of animals, he listed 4,000 in 1758, to be about the same. His contemporary Zimmermann, 1778, made the remarkably more realistic estimates of 150,000 species of plants and 7 million species of animals, to be discovered eventually. His entire method, for instance, a botanist must remember the diagnosis of every genus, was based on his assumption of a limited number of taxa, and yet we now know more than 200,000 species of phanerogams alone. Linnaeus knew 236 Swedish species of algae, lichens, and fungi, as compared to about 13,000 species known from Sweden today. He assumed that the tropics of all parts of the world had a rather uniform plant life. But such insufficiencies in his knowledge were not nearly as deleterious for the development of his methodology as his conceptual conflicts. On one hand, as we shall presently see, Linnaeus was a practitioner of scholastic logic and a strict essentialist. On the other hand, he also accepted the principle of plenitude, which stresses continuity. The major aim of his method was the eminently practical one of assuring the correct identification of plants and animals, Yet the procedure by which he tried to achieve this was the highly artificial one of logical division. No wonder his critics were able to discover so many inconsistencies in his writings. Macrotaxonomy, the science of classifying. Still, Linnaeus deserves all the praise he got. His technical innovations, including the invention of binomial nomenclature, his introduction of a rigorous system of telegram-style diagnoses, his development of an elaborate terminology of plant morphology, Bremerkamp, 1953a, his standardization of synonymies, and of every other conceivable aspect of taxonomic research brought consensus and simplicity back into taxonomy and nomenclature where there had been a threat of total chaos. This was the secret of his popularity and success. By his authority Linnaeus had been able to impose his methods on the world of systematics, and this was largely responsible for the unprecedented flowering of taxonomic research on animals and plants during the 18th and early 19th centuries. Nevertheless, various post-Linnaean authors, both botanists and zoologists, deplored the fact that Linnaeus' work had resulted in such an emphasis on classifying and name-giving that it had led to a near obliteration of all other aspects of natural history. In particular, the study of the living animal has been completely suppressed. As a further result, not only varieties, but also juveniles and larvae of known species were described as separate species, see bold, 1854. The neglect of Karl Rutter and the struggles, in both botany and zoology, to attract talent to physiology and embryology deplored by Nageli and Sachs support this evaluation. The reason why modern writers have had so much difficulty in understanding Linnaeus is that many of the terms used by him, like genus, species, name, to know, and natural system, have the very special meanings which these terms have in the system of scholastic logic. In school Linnaeus had excelled in logic, and he was evidently deeply impressed by the precision of this method. From Cisalpino on, every botanist had applied logical division with more or less consistency, and it still dominated Linnaeus. Kane, 1958. 1.5 There is one respect in which Linnaeus differed significantly from his forerunners. In their downward classifications they had applied dichotomy as often as was necessary to reach the looked-for genus or species. By contrast, Linnaeus applied the full rigor of the method only at the level of the genus. He was less interested in categories higher than the genus and was vague and inconsistent with respect to intraspecific variation. 173. 174. Linnaeus and the higher categories. Instead of a system of consistent downward dichotomy, he adopted a system dominated within a kingdom, by a hierarchy of only 4 categorical levels: class, order, genus, and species. Classifying the entire diversity of nature into taxa at these 4 levels gave a clarity and consistency to his system that was altogether absent from the cumbersome dichotomies of most of his forerunners. The modern taxonomist recognizes an elaborate hierarchy of higher categories. The complete series from the species to the kingdom is often called the Linnaean hierarchy. Simpson, 1961, Mayr, 1969, though Linnaeus was not the first author to recognize categories above the genus. As we have seen, Aristotle vaguely indicated a hierarchy in his arrangement of animals. He divided all animals into bloodless animals and those with blood. The latter have subcategories like four-footed, many-footed, or footless ones, and so forth. Most of these groupings are made with the help of single diagnostic characters, and Aristotle's successors have usually interpreted his arrangements as diagnostic keys. Yet, as I mentioned earlier, Aristotle himself made fun of the artificial method of dichotomous keys. He realized that his criterion live-bearing, versus egg-laying, for example, does not produce a natural group. At no time did Aristotle make a terminological distinction between various levels of higher categories. When the Aristotelian tradition was revived during the Renaissance, it included a lack of interest in the higher categories. The herbalists as well as the encyclopedists either recognized no higher categories at all above the genus, or they designated the groups which resulted from their logical division as books, chapters, or some other non-taxonomic term. Res supergeneric groups, likewise, were entirely informal designations. Tournefort was apparently the first botanist to develop a formal classification of categories higher than the genus. He divided plants into 22 classes, these classes in turn he subdivided into 122 sections. The terminology of these higher categories varied at first from author to author. What Tournefort had called sections Manuel and Adanson called families and Linnaeus orders. As the number of genera and species of plants grew, and with it the need for a more elaborate hierarchy, all these alternative terms were incorporated into a single terminology. The family category was rather consistently used by 1800 to designate a level between genus and order. Cuvier is still inconsistent in the application of macrotaxonomy, the science of classifying these terms in succeeding publications. They became completely formalized only in the writings of the entomologist Latreille. Linnaeus was singularly uncommunicative when it came to defining his categories order, class, and kingdom. One has the feeling that he introduced these higher categories not for theoretical but for purely practical reasons. Indeed, he states quite frankly that class and order are less natural than the genus. As he writes in the Philosophia Botanica, Para 160, a class is an agreement of several genera in the parts of their fructifications in accordance with the principles of nature and art. In other words, classes are to some extent artificial, but Linnaeus intimates that they will be replaced by natural classes when all the genera of plants have been discovered and described. The order was for Linnaeus even more of a choice of convenience. An order is a subdivision of classes needed to avoid placing together more genera than the mind can easily follow, Para 161. It is evident that the higher categories were for Linnaeus primarily convenient information retrieval devices. His lack of interest in the higher categories is documented by the fact that the higher taxa of animals recognized by Linnaeus are decidedly inferior, that is, more heterogeneous, than those that had been delimited by Aristotle more than 2,000 years earlier. There are various inconsistencies in Linnaeus' attitude toward the higher categories. The genus represents his essentialist thinking par excellence, and all genera are separated by sharp discontinuities. However, he has a rather nominalist attitude toward classes and orders. For them he adopts Leibniz's motto that nature makes no jumps. The more plants we know, the more gaps between the higher taxa will be filled until the boundaries between orders and classes may finally disappear. His adherence to the principle of plenitude is documented by his statement that all taxa of plants have relationships on all sides as do neighboring countries on a map of the world, PAR 77, for map, see Green, 1959, 135. The genus. The genus is for the modern taxonomist the lowest collective category, an aggregate of species sharing certain joint properties. This was not the concept of the genus among the practitioners of logical division. For them the genus was a class with a definable essence which can be divided into species with the help of differ. 175. 176. NGE. A genus did not designate a fixed rank in a hierarchy of categories, and the generic name was often a polynomial, particularly at the lower levels of division. Originally there was little uniformity in usage, and Aristotle sometimes used the term genus even where we would now speak of species, Baum, Green. The gradual narrowing down of the term genus to the categorical level which we now call genus was a slow process. It began among the herbalists and encyclopedists, among whom Cortis, 1541, and Gessner, 1551, already used the generic name in a remarkably modern way, although the German herbalists used the word Geschlecht, genus, more often in the sense of species than of genus. The rather vague usage of the words genus and species began to acquire biological meaning in the writings of the great 17th-century taxonomists Ray and Tournefort. The genus was for Linnaeus the cornerstone of classification. 1-6 When establishing order in one's environment, one does not classify things but their essences. It was an axiom for Linnaeus that natural genera exist, that these, that is, the essences had been created as such, and that they could be recognized on the basis of their characters of fructification. He admitted as many genera as there are different groups of species which agree in the structure of their fructification. It is not the taxonomist who makes the genus, he only discovers the genera that had been created in the beginning. There is a very close association in Linnaeus' theory of classification between creationist dogma and essentialist logic. In his earliest writings Linnaeus still adhered to the strict code of logic, so that he called the whole plant kingdom the summum genus, the species of which were the classes of plants. He abandoned this usage after 1735, and restricted the term genus to the hierarchical level immediately above the species. In 1764 he listed 1,239 genera of plants. Linnaeus is quite emphatic about his method, which he describes in great detail in his Philosophia Botanica, para 186-209. The definition of a genus is a statement of its essence. The character is the definition of the genus, it is threefold, the factitious, the essential, and the natural. The generic character is the same as the definition of the genus para 186. The essential definition attributes to the genus to which it applies a characteristic which is very particularly restricted to it, and which is special. The essential definition character distinguishes, by means of a unique idea, each genus from its neighbors in the same natural order, para 187. Macrotaxonomy, the science of classifying. One would need only the essential definition if there were a way to determine what the essential characters of a genus are. However, Linnaeus, by implication, concedes to Ray that no such method is known. For this reason one must also present a factitious definition which distinguishes a genus from the other genera in an artificial order, para 188. Finally, the natural definition lists all possible generic characters, and so it includes both essential and factitious definitions, para 189. 17. Although Linnaeus greatly changed his ideas on the sharp delimitation and fixity of species in the course of his scientific life, see chapter 6, he never wavered on the genus. One has the impression that he perceived genera intuitively, by inspection, which prompted his famous motto, "It is not the character, diagnosis, which makes the genus, but the genus which gives the character." Indeed, he often ignored deviations in somewhat aberrant species as long as these still obviously belonged to a given genus. The genus, to him, was the most convenient information retrieval package, because in the limited representation of the animal and plant kingdoms known to him, the genera, on the whole, were separated from each other by clear-cut discontinuities. But more importantly, for reasons of his essentialist philosophy, the genus, with its essence, was the God-given real unit of diversity. In some respects, at least conceptually, the genus of Linnaeus, in its essentialistic, monolithic, independent existence, was a backward step from the genus of Tournefort, which was an aggregate of species, hence a collective category. The genus is a device, Tournefort said, to bring together as in bouquets plants which resemble one another, and to separate them from those which they do not resemble, Elements de Botanique, 1694, 13. The modern genus concept thus traces back to Tournefort rather than to Linnaeus. Staffleu, 1971, 74, is quite correct in pointing out that it was not really Linnaeus who produced for the first time consistently composed definitions, diagnoses, and therefore comparable descriptions of genera. The honor for this goes to the pragmatic empiricist Tournefort. The sexual system of Linnaeus. A classification, for Linnaeus, was a system that permitted the botanist to know the plants, that is, to name them quickly and with certainty. One could devise such a system only by using well-defined, stable characters. The vegetative portions of the plant. 177. 178. Show many adaptations to special conditions and are thus subject to convergent trends, such as between cacti and euphorbes, which misled the early plant taxonomists. The flower, which Linnaeus chose as the major source of his characters, had the great advantage that the numerical differences in stamens and pistils, and several other flower characters, were not ad hoc adaptations but, as we would now say, either an incidental byproduct of the underlying genotype or else adaptations to facilitate pollination, independently of the habitat. Linnaeus, rather misleadingly, called his method the sexual system. This terminology reflected Linnaeus' evaluation of the preeminent importance of reproduction. Reproduction, for him, indicated the secret working plan of the Creator. Actually, of course, differences in the number of stamens and pistils, as practical as they may be for identification, are of little functional significance, if any. But Linnaeus would have considered it bad taste to admit this frankly, and in order to give his system philosophical justification, he called it the sexual system. It was first set out in a key in the Systema Naturae, 1st ed., of 1735. 4 basic criteria were used: number, shape, proportion, and situation. Absolute number, thus, was only one of Linnaeus' character sets. Whether the flowers were visible, later called phanerogams, or not, how many stamens and pistils there are, whether or not they are fused, and whether or not male and female elements occur in the same flower were among the characters which Linnaeus used to distinguish 24 classes, Monandria, Diandria, and so on. The classes, in turn, were divided into orders with the help of additional characters. As artificial as the system was, it was remarkably useful for the practical purposes of identification and for information storage and retrieval. Any botanist using the sexual system would come to the same result as Linnaeus. All he had to do was to learn a rather limited number of names of the parts of the flower and fruit, and then he could identify any plant. No wonder nearly everybody adopted the Linnaean system. When, already in 1739, Bernard de Jussieu, the leader of French botany, pronounced the Linnaean method preferable to that of his compatriot Tournefort, because it was more exact, the victory was complete. In a classification based on common descent, any species, or higher taxon, can be encountered only a single time. It has a unique position in the hierarchy. This constraint does not exist for an artificial identification key. A variable taxon may be n. Macrotaxonomy, the science of classifying. Tiered repeatedly in different couplets. This must be remembered in connection with Linnaeus' classification of hard-shelled invertebrates. He placed types with a shell, mollusks, Cirripedia, certain polychaetes, in the order Testacea, but soft animals, that is, mollusks without a shell, such as slugs and cephalopods, coelenterate, and most polychaetes, in the order Mollusca. But when he listed the genera of Testacea, he gives in each case also a molluscan generic name for the soft animal. For instance, chiton, animal Doris, Cyprea, animal Limax, Nautilus, animal Sepia, Lepus, animal Triton, and so on. The genera Doris, Limax, Sepia, and Triton are again listed as valid genera in the order Mollusca. The overriding concern for Linnaeus was the practical one of identification, and this is what his double-entry system attempted to facilitate. Von Hofsten, 1963. It was clearly a compromise, with the shell serving for identification, while the animal indicated the real position in the system. One might also interpret it as the simultaneous attempt at an artificial and a natural classification. Considering the seeming artificiality of the method of logical division, surprisingly many of the genera recognized by Linnaeus consist of well-characterized groups of species, many still accepted as genera or families today. A close examination of these classifications solves the riddle. It is rather obvious that Linnaeus, like Caesalpino, first recognized such groups by visual inspection and elaborated the definition, essence, only subsequently. This Linnaeus confessed openly in his Philosophia Botanica, para 168, where he says, one must consult the habit secretly, under the table, so to speak, in order to avoid the formation of incorrect genera. When Linnaeus' son was asked what his father's secret was to be able to create so many natural genera, In spite of the artificiality of his method, he answered, it was no other than his experience in knowing plants from their external appearance. Therefore he often departed from his own method by not being disturbed by variation in the number of parts if only the character of the genus could be preserved. As a result, Linnaeus sometimes went even so far as placing in a single genus species which differed in their number of stamens and should have gone into different classes of his sexual system. Also, he often transferred the diagnosis of a genus untouched into later editions of his works, even though subsequently added species had attributes that were in conflict with the old generic diagnosis. He was equally inconsistent in his animal classifications. The sheeptick, a wingless fly, was without hesitation classified among the two-winged insects, Dip. 779. 180. Terra. There are scores of similar cases in Linnaeus' zoological works where pragmatic considerations won out over philosophical principles, see also Windsor, 1976a. Buffon. The 18th century was the great age of natural history. It saw the heroic voyages of Captain Cook, of Bougainville, and of Commerson, Stresemann, 1975, and a new interest in nature was reflected not only in the writings of Rousseau but in those of most of the philosophes of the Enlightenment. It was the century of natural history cabinets and herbaria owned not only by kings and princes but also by wealthy citizens such as George Clifford, 1685-1760, in Holland, Sir Hans Sloane, 1660-1753, and Sir Joseph Banks, 1743-1820, in England, and others in France and other countries on the continent. 181 of the ambitions of these patrons of natural history was the publication of a scientific catalogue of their collections. Books on nature became increasingly popular, but none had the spectacular success of Buffon's Histoire naturelle. Though dealing, like Linnaeus' taxonomic treatises, with the diversity of nature, Buffon's approach was fundamentally different. Identification was the least of his concerns, rather he wanted to paint vivid pictures of different kinds of animals. He rejected the pedantry of the scholastics and humanists and wanted to have nothing to do with their emphasis on logical categories, essences, and discontinuities. He was rather inclined to favor ideas promoted by Leibniz in which plenitude and continuity were emphasized as well as the Aristotelian concept of the scale of perfection. To Buffon this seemed a far superior view of nature than the dry-as-dust compartmentalization of the nomenclateurs, by which term he contemptuously referred to Linnaeus and his disciples. Buffon's studies of Newton led him in the same direction. Did not the law of gravitation and the other laws of physics show that there was a unity in nature effected by general laws? Why dissect and destroy this unity by cutting it up into species, genera, and classes? Nature knows no species, genera, and other categories, it knows only individuals, he declared in the first volume of his Histoire naturelle in 1749, all is continuity, but already in 1749 he excluded species from this sweeping claim. Buffon's first love had been physics and mathematics and, although he had had some previous familiarity macrotaxonomy, the science of classifying with natural history, it was not until he had been appointed director of the Jardin du Roi, now Jardin des Plantes, in 1739 at the age of 32 that he became vitally interested in the diversity of the organic world. Buffon and Linnaeus were both born in 1707, and yet the contrast between the two men could not have been greater, and this was, at first, also true for their followers. The Linnaeans emphasized all those aspects of the taxonomic procedure that would facilitate identification, while Buffon and the French school concentrated on the understanding of natural diversity. The Linnaeans stressed discontinuity, Buffon continuity. Linnaeus adhered to Platonic philosophy and Thomistic logic while Buffon was influenced by Newton, Leibniz, and nominalism. Linnaeus concentrated on essential characters, quite often a single diagnostic one because, as he claimed, attention to descriptive detail would prevent recognition of the essential characters. Buffon, by contrast, insisted that we must make use of all parts of the object which we have under consideration, including internal anatomy, behavior, and distribution. Buffon's approach was well suited for the treatment of mammals and merely a continuation of the tradition of earlier classifiers, for example, Gessner. The number of mammal species was quite limited, and identification was rarely a problem. Only botanists like Ray and Linnaeus had applied the principles of logical division to the classification of animals. When Buffon classified mammals into domestic and wild animals, he justified the division as being the most natural one. For him natural meant practical, not reflecting the essence, as for Linnaeus. Around 1749 Buffon's views began to change, eventually becoming considerably modified under the impact of his growing knowledge of organisms. Roger, 1963, 566. While in 1749 he expressed a radical skepticism of the possibility of any classification of living organisms, by 1755 he admitted that there are related species. In 1758 he still ridiculed the idea of genera, but in 1761 he accepted them to facilitate the difficult enumeration of the smallest objects of nature, and by 1770 the genus is made the basis of his classification of birds, presumably still with the mental reservation of its arbitrary nature. Even though he admits a common descent of genera of domestic animals, they are, of course, only biological species. Also, from 1761 on, he adopted the concept of the family. Yet, it must be remembered that Buffon never attempted to classify the entire animal and plant kingdoms. Indeed, much of his Histoire naturelle is a series of monographs of individual mammalian species. These are superbly done, from the literary as well as the scientific point of view, and had an enormous impact on the education of young zoologists. Yet, they were not the material with which to develop a general theory of systematics, something Buffon simply was not interested in. Although starting at opposite poles, Linnaeus and Buffon got increasingly closer in their ideas as their work progressed. Linnaeus liberalized his ideas on the fixity of species, and Buffon 182 admitted, contrary to the nominalists' views, that species could be non-arbitrarily defined as reproductive communities. Hist. Nat. 1753, 4, 384-386. Buffon, however, never accepted Linnaeus' views on the nature of the genus, that is, the belief that it is the most objective of all categories. Furthermore, his criteria for the recognition of higher taxa were entirely different from those which Linnaeus professed to use, total habitus versus single characters revealing the essence. Toward the end of their lives, let us say in the 1770s, the contrast between the taxonomic methods of Linnaeus and Buffon had been reduced to such an extent that their respective traditions merged in their pupils. Lamarck, a protégé of Buffon, still proclaimed loudly that categories do not exist, only individuals, but once he had recorded this article of faith, he no longer paid much attention to it in his taxonomic works. The same is true for Lespiti. In Cuvier, finally, it is no longer possible to discern the Buffonian nominalist tradition. A new start in animal classification. Little progress was made in animal classification during the 17th and 18th centuries. Indeed, the Linnaean classification of the invertebrates was a backward step from that of Aristotle. All this changed overnight with the publication in 1795 of Georges Cuvier's, 1769-1832, memoir on the classification of the animals named worms. 20. The catch-all taxon recognized by Linnaeus under the name vermes was divided by Cuvier into 6 new classes of equal rank: mollusks, crustaceans, insects, worms, echinoderms, and zoophytes. 17 years later he deprived the vertebrates of their favored position by raising some of the invertebrates to an equal rank, and classified all animals in 4 phyla: embranchiments, vertebrates, mollusks, articulates, and RA. Macrotaxonomy, the science of classifying. Diates, Cuvier, 1812. Within these highest taxa, a number of new classes, orders, and families were recognized which up to then had been confounded with each other or totally overlooked. He consolidated the Linnean mollusca and Testacea into the class Mollusca and removed the jellyfish, Medusa, and sea anemone, Actinia, from the mollusks to the zoophytes. What was most important in Cuvier's contribution to animal classification was his discovery of the great information content of the internal anatomy of the invertebrates. When dissecting numerous marine animals, he found an abundance of new characters and types of organization. This initiated the great tradition of the comparative zoology of the invertebrates. His findings permitted Cuvier to recognize for the first time a number of taxa that are still accepted today. What is rather remarkable about Cuvier's enormous contribution is that even though it is based on a carefully worked out system of concepts and laws, conceptually it represents no advance over the principles of Aristotelian logic. Again, the emphasis is on classification from the top down by a process of division, and there still is a search for the essence, the true nature of each group, and characters are still weighted on the basis of functional importance. Nevertheless, he introduced some innovations. Cuvier and the correlation of characters. Cuvier thought that certain physiological systems were of such importance that they would control the conformation of all other characters. This was a new conceptual departure. Taxonomists prior to Cuvier had acted on the whole as if each character was independent of every other character, and as if an organism with a different character had a different essence. Buffon had been the first to disagree with this atomistic approach. An organism was not an arbitrary jumble of characters, as it appeared from the writings of the Linnaeans, rather the composition of the characters was dictated by their correlation. Cuvier expanded Buffon's rather general ideas into a concrete principle, that of the correlation of parts, see Chapter 8. The various parts of an organism are interdependent to such a degree that if given the tooth of an artiodactyl ungulate, the anatomist can at once make numerous statements about the probable structure of other parts of the anatomy of this animal. All the functions of an organism are mu. 183. 184. Totally dependent on each other to such a degree that they cannot vary independently. It is in this mutual dependence of the functions and the aid which they reciprocally lend one another that are founded the laws which determine the relations of their organs and which possess a necessity equal to that of metaphysical or mathematical laws, since it is evident that the seemly harmony between organs which interact is a necessary condition of existence of the creature to which they belong, and that, if one of these functions were modified in a manner incompatible with the modification of the others, the creature could no longer continue to exist. Lemons de Anatomie Comparée, 1800, I. 51. Ever since Cuvier's proclamation, experienced taxonomists have utilized correlated variation as one of the most important clues in the evaluation of characters. It may reveal both ad hoc specializations in connection with the occupation of special adaptive zones as well as deep-seated genetic integration, as expressed in character constancy in higher taxa. Lamarck was apparently the first to call attention to the importance of such constancy in his Flore Francoise, 1778, soon followed by de Jussieu. But Cuvier went further than merely calling attention to a correlation of parts. He also had an elaborate system of weighting characters, embodied in his principle of the subordination of characters, see below. Where Cuvier differs in his approach from an author like Linnaeus is that he is genuinely interested in classification and its principles, rather than in an identification scheme. In his 1795 memoir, like Réaumur before him, he does not even bother to describe genera or species. What his real aim is, he expressed in these words: in conclusion, I have not presented this essay on division that it may serve as the beginnings of the determination of the name of species. An artificial system would be easier for this, and this is only proper. My aim has been to make known more exactly the nature and true relationships of the Animaux sang blanc invertebrates, by reducing to general principles what is known of their structure and general properties. Lamarck. As different as Jean-Baptiste Lamarck, 1744 to 1829, and Cuvier were from each other philosophically, their contributions to classification were remarkably similar. Burckhardt, 1977. Lamarck also made numerous valuable innovations in the classification of macrotaxonomy, the science of classifying the invertebrates, dealing with such problems as the position of the cirripedes and tunicates and the recognition of the arachnids and annelids as distinct taxa. Indeed, from the protozoans to the mollusks, Lamarck made numerous taxonomic contributions. But when it comes to the theory of classification, his concepts were as conventional as those of Cuvier. Lamarck started out with a belief in a single series of animals beginning with the simplest infusoria and culminating with man. Consequently, he tried to rank each higher taxon according to its degree of perfection. Later on, in part under the impact of Cuvier's replacement of the single series by 4 embranchements, but also in part as a result of his own comparative studies, Lamarck increasingly abandoned the concept of a single series. At first he merely admitted that certain species and genera diverged from the straight line owing to the force of circumstances, but eventually he admitted the branching of masses, higher taxa, and his final presentation of animal relationships, 1815, does not differ in principle from a phylogenetic tree such as one would expect to find in the literature at the end of the 19th century. Lamarck frequently emphasized how important he considered the activity of classifying, since the study of affinities should now be regarded as the chief instrument for the progress of natural science. Taxonomic characters. Classification is the ordering of organisms into taxa on the basis of their similarity and relationship as determined by or inferred from their taxonomic characters. This definition indicates the decisive importance of taxonomic characters for the construction of classifications. Yet, from the beginnings of the history of taxonomy to the present day, there has been much disagreement as to what characters are most useful and, indeed, legitimate in taxonomic analysis. Much of the history of classification is a history of controversy on this point. The Greeks were fully aware of the fact that utilitarian characters, like medicinal properties or the presence of spines, have little to do with other, seemingly more deep-seated, properties of a plant. The essentialists, who classified by logical division, also felt that some characters were more fundamental than others. Even though their terminology of essential and accidental characters was burdened by scholastic dogma, they did sense a truth which was not understood until centuries later. From César Pinot 185 on, it was recognized that such non-morphological characters as relation to man, cultivated versus wild, seasonality, deciduous or evergreen, or habitat were less apt to produce useful classifications than structural characteristics. Consequently, use of structural characters has dominated taxonomy since the 16th century. Taking the entire period from César Pinot to the present, taxonomic characters have provoked 3 major controversies. 1. Should one use only a single key character, Fundamentum DV 186 Cyanese, or multiple, all possible, characters? 2. Should only morphological characters be allowed, or also ecological, physiological, and behavioral characters? 3. Should characters be weighted or not, and if weighted, by what criteria? Already Aristotle stated that some characters are more useful in delimiting groups of animals than others, and very few authors throughout the whole history of taxonomy have disagreed with this conclusion. The numerical phoneticists see below, in some of their earlier publications, Sokol and Sneth, 1963, are among the few exceptions by promoting equal weighting of all characters. The problem thus was not to weight or not, but 2 other problems. What principles should one use to determine the weight of a character? And how should one translate a scale of weights into a classification? It must be remembered that rejecting a particular criterion of weighting of one author by another one does not mean a rejection of the method of weighting as such. Authors like Buffon and Audonson, who favored the use of as many characters as possible, did not in the least propose that they be weighted equally. As long as classifications were basically identification schemes, they required, by necessity, a reliance on single characters. It did not matter if the groups produced by this method were heterogeneous, as long as the goal of identification could be reached. In the case of plants, experienced botanists knew that no other part of a plant provides more and better diagnostic features than the fructification, flowers, fruits, and seeds. A particular advantage of this structural system is that it includes a great number of quantifiable characters, such as the number of flower petals, stamens, and pistils. Flowers had the additional advantage of being comparatively invariant within a species, compared to most aspects of the leafy vegetation, and yet composed of a rich assortment of variable parts displaying species-specific differences. No one was more diligent and successful in pointing out such differ. Macrotaxonomy, the science of classifying. Inces than Linnaeus, even though some contemporaries cursed him for using characters which one could only see with the help of a hand lens. None of the essentialists would have admitted that he used fructification because of its practical advantages. Instead, they constructed an elaborate myth, in which evidently they believed themselves, that certain aspects of a plant in some way were more important than others, and therefore reflected the essence better. Alpino rated nutrition and the results of nutrition, growth, highest, while he ranked reproduction, reflected in fructification, next highest, since providing for the continuation of a plant into the next generation is the next most important clue to the essence. All aspects of fructification, flowers and seeds, are the next most important characters. Linnaeus differed from him by ranking fructification above growth, and stated quite simply, Philosophy Bot, Para 88, that the essence of the plant consists in its fructification. Perhaps the best evidence for the fact that flowers were chosen for their usefulness rather than for philosophical reasons is that even today they are most prominently used in identification keys in spite of the fact that the argument of their functional importance was abandoned 200 years ago. Even though botanists from Gessner, 1567, and Alpino, 1583, to Linnaeus all agreed on the importance of fructification, this still left a great deal of choice owing to the multitude of characters available, all relating to fructification. Different botanists chose different characters on which to base their first division, Tournefort and Rivinus the corolla, Magnol the calyx, Boerhaave the fruit, Sieg-Esbeck the seeds, and Linnaeus the stamens and pistils. It would have been difficult to decide how these components of fructification should be ranked according to their functional significance. As a result, pre-Linnaean botanists largely split on national lines. The British followed Ray, the Germans Rivinus, Bachmann, and the French Tournefort. Since identification was the principal objective, Tournefort's system, which was simpler, more concise, and more easily memorized than the other two, was more and more widely adopted by botanists, until it was replaced by the even more practical sexual system of Linnaeus. When the number of known animals increased rapidly during the 17th and 18th centuries, morphological characters were used ever more frequently, but among the zoologists there was none of that intense interest in methodology that characterized contemporary botanists. Ecological criteria were still 187. Often given preference, particularly for groups other than the vertebrates. Vallisnieri, 1713, for instance, divided the insects into 4 major groups: those that inhabit plants, those that live in the water, including crustaceans, those that dwell in rocks and in the soil, and those that live in or on animals. Even when morphological characters were used, they were often poorly chosen, such as when Linnaeus classed the fish-shaped whales with the fish, or when he combined the majority of the invertebrates into the worms, vermes. 188. Cuvier's principle of the subordination of characters, according to which various parts in an organism differ in taxonomic value, was a system of weighting. In his earlier work, prior to about 1805, the organs of nutrition, and particularly of circulation, are most prominent as the diagnostic characters of Cuvier's higher taxa. By 1807, however, the nervous system had been clearly raised to the top rank, and it now played the most important role in the delimitation and ranking of his 4 embranchements. Coleman, 1964. At the level of the lower categories, Cuvier often assigned the same character different weight in different animal groups. For instance, tooth characters define orders among the mammals, genera among the reptiles, but only species among the fishes. The structure of the feet, to give another example, has the value of an ordinal character for mammals, being their principal means of locomotion, while in birds where the wings are preeminent, the feet have a much lower value as a taxonomic character. Nevertheless, Cuvier thought that certain characters were associated with a certain rank in the hierarchy of categories. Evidently his subordination of characters is nothing more or less than the a priori system of weighting of the botanists, except that in animals, in traditionally Aristotelian manner, sensitivity is ranked highest, hence the primary characters are derived from the nervous system. Even though Cuvier revolutionized the classification of the invertebrates, it was not through the introduction of new concepts but rather by making available a whole new set of characters, those derived from the internal anatomy. A second revolution in the use of animal characters, again not involving any new concepts, was produced by a technological advance, the invention of the microscope. Van Leeuwenhoek's introduction of optical instruments into the study of natural history, about 1673, was an innovation the full impact of which has not yet run its course, as indicated by recent discoveries made with the help of the scanning electron microscope. Even stamens and macrotaxonomy, the science of classifying pistils, the key characters in Linnaeus' system, are best seen with the help of magnification. The study of the sculpture of beetle elytra or of antennae, wing veins, and genital armatures of all insects require at least a hand lens. Most aquatic invertebrates, and of course algae, protozoans and other protists, require a microscope for their study. The extent of microscopical studies greatly accelerated after the 1820s. The careful histological examination of organisms of all sizes led to the discovery of taxonomically important sense organs, glands, accessory structures of the reproductive and digestive systems, and previously unknown details of the nervous system. Entirely novel characters, for example, chromosomal and biochemical differences, were added in due time, also made possible by technological advances. Even though the number of characters available to the taxonomists seemed to mushroom, the new information was not enough to settle important controversies on relationship. The dogma that one particular type of characters is best suited as the basis of classification came under heavy attack already in Linnaeus' lifetime. However, it was not the principle of weighting as such that was attacked but the reasoning on the basis of which weighting was to be done. At first, as was described above, the only weighting criterion that was admitted as determining taxonomic usefulness was that of functional importance. In due time, however, entirely new criteria of weighting were proposed. Lamarck, Cuvier, and de Jussieu stressed the importance of constant characters. De Candolle emphasized growth symmetries which indeed in plants often characterize genera and entire families. Such symmetries can be found in the flowers, in the insertion of the leaves, and in other characteristics of plants. Polythetic taxa. The genus, at any level, is represented for the essentialist by the totality of all species, meaning subordinate taxa, sharing in the same essence, or, as it was later expressed by taxonomists, by all those that had certain characters in common. It was a source of considerable distress, from the earliest period of classification on, that certain individuals or species were found which lacked one or the other character typical, that is, essential, for the taxon. Pedants would separate such species generically, the more experienced taxonomists, for instance Linnaeus, would simply ignore. 189. 190. The discrepancy. Indeed, higher taxa were found that could be reliably defined only by a combination of characters, each of which might occur also outside the given taxon or which might be occasionally absent in a member of the taxon. In such cases no single feature is either necessary for membership in such a taxon or sufficient. Audonson seems to have been the first to have recognized this clearly, although it is already implied in some statements made by Ray. Victiezer, 1786, stated that a group may be perfectly natural, and yet have not a single character common to all the species that compose it. Heinck, 1898, showed that two species of fish, the herring and the sprat, differ from each other in 8 structural characters, but only 10% of the individuals differ from each other in all of these characters. Beckner, 1959, was the first to give formal recognition to this principle by designating taxa based on character combinations as polytypic. However, since the term polytypic was already employed in taxonomy in a different sense, Smith, 1962, introduced the replacement term polythetic. To allow the characterization of higher taxa by polythetic character combinations signaled the final demise of an essentialistic definition. However, long before that the entire concept of relying on particularly important characters, necessitated by the method of logical division, had come under attack and had led in due time to an entirely new concept of classifying. Upward classification by empirical grouping. The dominant method of classifying from Caesalpino to Linnaeus, downward classification by logical division, became more and more unsatisfactory as European botanists and zoologists were inundated by the avalanche of new genera and families from the tropics. The method of classification according to the principle of logical division was expected to achieve two objectives: to reveal the order of nature, the plan of creation, and to provide a convenient identification scheme. When the method was practiced, however, it became apparent that the two objectives were incompatible and that a consistent application of the principles of logical division usually led to absurd results. A retrospective analysis of macrotaxonomy, the science of classifying. This theory of classification shows that it had at least 3 basic weaknesses. 1. When only a small fauna or flora needs to be classified, an identification scheme is sufficient, such as logical division is able to provide. The method is, however, unable to assemble natural groups of species and genera, such as one needs for classifications when one deals with very large faunas and floras. 2. Only a single character can be used at each step. The choice of this character was dictated by its supposed ability to reveal the essence of the genus. However, the claim that certain characters, for instance those of greater functional importance, are better qualified to reveal the essence of a taxon than others is neither theoretically nor practically substantiated. Hence, the whole system of weighting characters according to their presumed functional importance lacks validity. 3. The whole philosophy of essentialism, on which the method of logical division was based, is invalid and therefore unsuitable as a basis for a theory of classification. The drastic revolution in philosophical thinking that had been taking place in the 17th and 18th centuries could not fail to have an effect on the thinking of the classifying naturalists. It has been a fascinating challenge to various historians to infer the relative influence of the scientific revolution and the Enlightenment, of the philosophy of Locke with its emphasis on nominalism and empiricism, of Kant, and of the ideas of Newton and Leibniz with their stress on continuity, on the thinking of Buffon, Linnaeus, and their schools. Buffon's ridiculing of the nomenclateurs, he meant the Linnaeans, was one of the manifestations of these philosophical influences. Yet, when one closely studies the taxonomic work of the 18th century, it is quite evident that purely practical considerations played a major, if not the dominant, role in shaping taxonomic concepts. The practical difficulties encountered by downward classification daily became more apparent. How valid was a method which forced even the great Linnaeus to cheat and to sort his species, so to speak, under the table, because divisional logic was unable to accomplish this? What should his less experienced followers do to avoid coming up with altogether absurd classifications? One will not understand the nature of the fundamental changes in taxonomic theory between 1750 and 1850 unless he pays equal attention to the new demands made by taxonomic practice and to the realization that the philosophical foundations 191, 192 of downward classification were gradually being eroded away. Eventually it became clear that it was futile to attempt to salvage downward divisional classification by modifying it, and that the only way out was to replace it by a completely different method, upward or compositional classification. In this method one starts at the bottom, sorts species into groups of similar ones, and combines these groups into a hierarchy of higher taxa. The method is, at least in principle, a strictly empirical one. In spite of various controversies, see below, it is by and large the method employed by every modern taxonomist, at least in the initial stages of the classifying procedure. The adoption of classification by inspection and by grouping, instead of by division, signified a total methodological revolution. Not only was the direction of the classificatory steps reversed, but reliance on a single character, fundamentum divisionis, was replaced by the utilization and simultaneous consideration of numerous characters, or of all characters, as some of the proponents of upward classification have insisted. In spite of the drastic conceptual difference of the two methods, the replacement of divisional by compositional classification occurred so gradually during the period from the end of the 17th to the 19th century that apparently no one was fully aware that it was taking place. There were several reasons for the gradual nature of the change. First of all, the method of classifying items by inspection was, of course, not at all a new invention. Already Aristotle had delimited his higher taxa by a combination of characters. If one were asked to sort a basket of mixed fruit, one would have little trouble sorting them by inspection into apples, pears, and oranges. Such a preliminary sorting was apparently undertaken by all the early botanists, even by those professing to be practitioners of logical division. It was done quite openly by Bach and Boerhaave, and clandestinely by Cézanne, Tournefort, and Linnaeus. Evidently a certain amount of compositional classification had been incorporated into the divisional method from the very beginning. Conversely, after logical division had been rejected in principle, some elements of it were retained owing to their usefulness in identification. There were several prerequisites for the occurrence of the changeover, but no thorough analysis of its history has so far been undertaken. First, an upward classification is possible only if one understands what one is grouping, that is, species. Thus, a macrotaxonomy, the science of classifying. Requisite of the compositional approach was a knowledge of species, even if essentialistically defined. The early herbalists and other pre-Linnaean authors, who sometimes lumped all species of a genus or treated variants as full species, would have had considerable difficulty with the compositional method. The development of a natural history tradition in the 17th and 18th centuries made here a crucial contribution, see Chapter 6. The second prerequisite was the weakening of the hold of essentialism, as described above. Finally, there developed at this period, in part as a result of the decline of essentialism, an empirical attitude in which a greater interest was displayed in results than in underlying principles. Three botanists in the 1680s pioneered in the method of sorting species on the basis of groups of characters. The British botanist Morrison used a variety of characters, and Ray stated that in order to draw the right inferences on the essence of a genus, there can be no more certain sign or evidence than the possession of several common attributes, de variis, 1696, 13. He repeated this in 1703 by saying, "The best arrangement of plants is that in which all genera from the highest, through the subordinate and lowest, have several common attributes or agree in several parts or accidents." Meth. Plant, 6-7. In France, at about the same time, Magnol, 1689, rejected the reliance on the method of delimiting higher taxa by division. In order to draw inferences on relationship, he used characters from all parts of the plant, not only the fructification. More significantly, he quite specifically stressed the importance of a holistic approach, that is, the grouping of species by inspection. There is even in numerous plants a certain likeness, an affinity that does not consist of the parts as considered separately, but as a whole, an important affinity, but which cannot be expressed. Prodromus, 1689. The special importance of Manuel was that he had a large impact on Adanson, whose ideas he helped to shape. His refusal to classify characters into essential and accidental ones, as demanded by the essentialists, although ignored by Linnaeus, was adopted by Adanson and by the entire empirical school. Buffon, over. Philosophy, 1749, 13, was quite emphatic in backing classification by inspection. It would seem to me that the only way to design an instructive and natural method is to group together things that resemble each other and to separate things that differ from each other. He also stressed that one should take all characters into consideration, and this advice was adopted by 193. 194. Meram, Blumenbach, Pallas, Illiger, Meckel, and other zoologists, Stresemann, 1975, 107. The first author who had the intellectual courage to question openly the validity of the method of logical division was Michel Adanson, 1727–1806. In his LCS Families naturelles de plantes, 1763, he suggested replacing it by an empirical inductive approach because the botanical methods that consider only one part, or only a small number of parts of plants, are arbitrary, hypothetical, and abstract. They cannot be natural. The only natural method in botany is one that takes into consideration all parts of plants. And this is how we find the affinity which brings plants together and which separates them in classes and families. Adanson went further than that and developed an elaborate method of testing taxonomic characters. Adanson and the use of multiple characters. The rejection of the single character divisional method posed new problems. If the delimitation of groups is to be based on several characters, how many characters should be used, and should there be any preference for certain characters? Adanson was the first botanist who investigated these questions quite systematically. In order to find out what effect on the classification the choice of characters would have, Adanson experimentally prepared 65 artificial groupings of plants, each based on a particular character, such as the shape of the corolla, the position of the seeds, or the presence of thorns. These arrangements showed him that it is impossible to arrive at a satisfactory system based either on a single character or a combination of only two. Since Adanson calculated the proportion of natural groupings produced by each of these arrangements, he has sometimes been called a numerical taxonomist, first by Adrien de Jussieu in 1848. This claim is quite misleading, since Adanson did not use this arithmetic approach in the actual delimiting of genera and families. This he did, following Manuel's example, by the visual perception of groups. Although he first worked out the differences between genera and species, it was by the overall view ensemble of these comparative descriptions, that I perceived that plants sort themselves naturally into classes or families. Fampi, 1763, Clay 8. Adanson clearly saw that different characters differed in their taxonomic significance. Giving equal weight to all attributes would have been in logical contradiction to Adanson's inductive method. Such an arbitrary procedure would have meant an a priori eval. Macrotaxonomy, the science of classifying. Uation of the characters, Staffleu, 1963, 201, see also Bird, 1966. What Adanson promoted was the potential consideration of all parts of the plant, not merely of the fructification. He particularly stressed 2 points: 1. That certain characters contribute nothing to the improvement of a classification and should be ignored, and 2. That the characters with the greatest information content are different from family to family. Each family has its own gene. Some of Adanson's opponents criticized him for the peculiar reason that his method required too great a knowledge of plants. This would have been a legitimate criticism if identification were the only object of classification, but, as the history of systematics has proven again and again, satisfactory classifications based upon a critical evaluation of all the evidence can be constructed only by those who do have a thorough knowledge of the group concerned. One can summarize Adamson's attitude toward characters by saying that he did indeed favor the weighting of characters, but not on the basis of any preconceived notion or a priori principles, like physiological importance, but rather by an a posteriori method based on a comparison of groups that had been previously established by inspection. Almost every principle promoted by Adamson has now become part of the taxonomic methodology. Yet, in an age still dominated by Thomistic logic and by a virtually dictatorial Linnean authority, Adamson was almost totally ignored. It is hard to say how much of an impact his family's de Plantes actually had. It was praised by Lamarck, but others who were clearly influenced by it, like A. L. de Jussieu, rather ungenerously failed to mention the source of their ideas. When numerous practicing taxonomists arrived at the same principles in later years and generations, it was independently and empirically rather than by studying Adamson's largely forgotten writings. It was not until almost a century later that Adamson's greatness was rediscovered. Staffleu, 1963. Transition period, 1758 to 1859. The century after the publication of the 10th edition of Linnaeus Systema Naturae, 1758, was an era of unprecedented taxonomic activity, much of it engendered by the enormous prestige which Linnaeus had given to the study of diversity. As more and more organisms were discovered, more and more young people became zoologists and botanists. The search for new species and 195. 196. Their classification threatened to smother all other interests in biology. For instance, the exciting researches in flower biology of Ackal-Rutter or Sprengel were ignored, because they did not produce new species. Nageli, 1865, who was not a taxonomist, deplored the fact that all other branches of botany were being drowned by the stream of systematics. The enormous accumulation of animal and plant specimens in private and public collections resulted in profound changes in the taxonomic profession. Taxonomists became more professional and more specialized. New journals were founded to accommodate the descriptions of the numerous novelties, and amateurs discovered that they could achieve a high level of competence by specializing in a single family. The annual output of taxonomic research climbed steadily. The frontiers of taxonomy expanded into entirely new areas. Up to now, zoology had been dominated by an interest in the vertebrates and botany by the study of the flowering plants. Now in zoology an interest developed in the invertebrates, particularly the marine ones, and eventually, beginning with SARS, even in deep-sea organisms. The botanists, in turn, paid ever greater attention to the cryptogams. It was in the period between the publication of Adamson's family's de Plantes, 1763, and Darwin's Origin of Species, 1859, that downward classification was gradually replaced by upward classification. France, among the European countries perhaps the one least dominated by essentialism, clearly led in introducing the new methods of taxonomy. This is evident not only from the early pioneering efforts of Magnol, Buffon, and Adamson but also from the writings of Lamarck and Cuvier. Lamarck, 1809, 1815, even though still adhering to much obsolete philosophy, classified by grouping rather than by logical division, and Cuvier's principle of the correlation of parts strongly reinforced the trend toward a multiple character conceptualization of taxa and the search for new characters. This ushered in a new pragmatic tradition in zoological classification, in which characters were evaluated by the ability to make a contribution to the formation of seemingly natural groupings, that is, they were evaluated a posteriori. Furthermore, it was recognized that the relative importance of a character, its weight, could change from one higher taxon to another, that is, the taxonomic value of characters is not absolute. This also led to a reconceptualization of the taxonomic categories. No longer were they considered steps in logical division. Macrotaxonomy, the science of classifying. From summum genus down to the lowest species, but rather as ranks in a hierarchy. The genus now became a collective higher category, thus something entirely different, ontologically and epistemologically, from the essentialistic genus of logical division. This change in the meaning and role of the genus was often ignored by taxonomists and philosophers, resulting in misunderstandings and conceptual confusion. There was also a subtle shift in the relative importance of different categories. For Linnaeus, the genus was the center of the universe. As the genera became larger and larger, owing to the continuing discovery of new species, most genera had to be split again and again, and the emphasis shifted to the next higher rank, the family. In many, but by no means all, groups of organisms, the family became the most stable unit of classification. The shift from downward to upward classification, together with the associated methodological and conceptual changes, was slow, gradual, and irregular, as has been true for nearly all scientific revolutions. As I have mentioned, the emphasis on families started with Manuel, 1689, the use of several characters often derived from different organ systems had already been adopted, more or less hesitantly, by Boerhaave, Morrison, Ray, Manuel, and Tournefort. Boerhaave, 1623, was perhaps the first to classify by grouping plants according to their natural affinities. Yet, all of these authors were inconsistent, particularly since they always wanted their classifications also to serve, to a lesser or greater extent, as identification systems. One factor to which Stafleu, 1963, 126, calls attention quite correctly is that not only practical considerations but also Descartes and his principles help to undermine the authority of Aristotelian logical division. Adanson, for instance, modeled his own method very much according to the four basic Cartesian methodical rules: doubt, analysis, synthesis, and enumeration. The Cartesian influence, as well as the Newtonian and Leibnizian influences, through Buffon, were among the reasons why Linnaeus had less impact in France than in any other taxonomically active country. His many practical innovations, binomialism, rules of nomenclature, and so on, were, of course, eventually adopted, but his Aristotelianism was accepted only as a convenient method of identification, and not as a sound philosophical basis for classification. Perhaps the most conspicuous development in post-Linnaean taxonomy was that classifications became more and more clearly hierarchical, see below. 197. 198. Plant taxonomy, which had had such a magnificent flowering in the 200 years between Cisalpino, 1583, and Linnaeus, continued to have steady but unspectacular growth in the post-Linnaean period. Three developments characterized this era. The most important was the endeavor, not yet fully achieved even in our day, to develop a natural system of plants. De Jussere, de Candolle, Endlicher, Lindley, Bentham, and Hooker all contributed more or less successfully to this end. Furthermore, increasing attention was paid among the cryptogams, not only to ferns and mosses but also to fungi, algae, and one-celled aquatic plants, protists. Finally, even though botanists rarely specialized to the extent zoologists did, an age of specialization also arrived in botany, monographs being published dealing with special groups of plants and thus leading to very intensive researches of selected portions of the plant kingdom. One development that is far too little appreciated was the fact that animal taxonomy during this period became a major branch of academic zoology. Naturalists like Siebold, Leuckart, Ehrenberg, Sars, Dujardin, and many others, one might even include Darwin in this category, started out as taxonomists but, by becoming interested in the living animal as a whole, made major contributions to general zoology, such as the clarification of the life cycle of parasites, the alternation of generations, the sequence of larval stages of marine invertebrates, the structure of internal organs and their function, and almost any other aspect of the living animal. Quite often it can be demonstrated unequivocally that such studies arose directly from taxonomic researches, and yet taxonomy has rarely been given credit for its role in initiating new approaches in biology. For instance, it is only within recent years, Gazellin, 1969, that it has been fully realized how important Darwin's monographic work on the cirripedes was for the maturation of his evolutionary theory. The search for a natural system. Most proponents of downward classification were fully aware of the fact that the classifications produced by their methods were artificial. Linnaeus deplored in several of his works that the time had not yet come for a truly natural classification, as he interpreted it. On several occasions he published fragments of a natural classification of plants, Staffleu, 1971, and, no matter how artificial some of his major divisions were, within them he grouped macrotaxonomy, the science of classifying the majority of the genera very much as would a modern evolutionary taxonomist. However, simply replacing downward by upward classification was not sufficient to produce a natural classification. There had to be some organizing principle, some basic concept that would serve as a guideline for the taxonomist. Ever since the Greeks, a conviction had prevailed that the diversity of nature was the reflection of some deeper order or harmony. No other group of philosophers, as far as we can judge from what little of their writing has survived, devoted so much thought to this harmony than the Pythagoreans. Natural theology revived the concept of a harmonious balance of nature and saw signs of it everywhere in the evident design of all adaptations. But diversity at first seemed quite chaotic and did not seem to fit too well with this philosophy. The situation became particularly unsatisfactory in the post-Linnaean period when the number of known species and higher taxa of animals and plants was growing at an almost exponential rate. When viewing the almost chaotic mountains of new species, how could one avoid asking, where is that harmony of nature of which every naturalist is dreaming? What are the laws that control diversity? What plan did the Father of all things have when he designed little creatures and big ones? It was simply inconceivable, in a period so strongly dominated by natural theology, that organic diversity could be totally without rhyme or reason, that it could be simply the result of accident. Consequently, it was the task of the taxonomist to find the laws that regulate diversity or, as others would put it, to discover the plan of creation. The classification which would reflect this divine plan most perfectly would be the natural system, and to achieve it was the ideal of every naturalist. Yet, when one studies what various authors had in mind who used the term natural, one encounters great diversity. A discussion of some of the usages of the term will help us in understanding the thinking of this period. The several meanings are best made clear by giving their respective antonyms. 1. Natural is that which reflects the true nature, that is, essence, as opposed to that which is due to accident. Essentialist classifiers from Cesare Pino to Linnaeus attempted to provide classifications that were natural in this sense, Kane, 1958. In principle this was the ideal of Linnaeus, and this is what he seems to have had in mind when he expressed his dissatisfaction with his artificial sexual system. Natural did not at all signify to Linnaeus what it means to us, because for him the nature of a species, of a 199 genus, or of a higher taxon was its essence. All Linnaeus scholars agree in this point, Staffleu, 1971, Larson, 1971. One must never forget Linnaeus' belief that genera and higher taxa, as God's creations, represented unchangeable essences, and that one would truly know them only after one had fully recognized these essences. As stated by Kane, 1958, 155, it is likely that for Linnaeus a natural system is one that showed the natures of things, and natures meant in practice essences. To realize this helps us to understand his essays on the natural method 200, meaning natural system. His theory of the origin of classes and genera, in an appendix to the Genera Plantarum, 1764, is a strictly creationist one. From all this, it is rather obvious, what Linnaeus really had in mind, when talking about the natural system, a system in which the intuitive definition of higher taxa, based on overall resemblance, is replaced by a determination of the true essence of these taxa. Among Linnaeus' successors, of course, the term natural system gradually acquired an entirely different meaning. 2. As the power of essentialist philosophy weakened, the term natural began to mean that which is rational rather than capricious. This interpretation reflected the widespread 18th century attitude that the order of nature was rational and could be perceived and understood by reasoning. Everything in nature obeys God-given laws and the order of nature conforms to God's plan. The natural system, if it could be found, would reflect the blueprint of creation. Agassiz, 1857. 3. For still others the term natural meant empirical as contrasting with artificial, that is, purely utilitarian. A natural classification under this conception would satisfy John Stuart Mill's demands. The ends of scientific classification are best answered when the objects are formed into groups respecting which a greater number of general propositions can be made, and those propositions more important, than could be made respecting any other groups into which the same things could be distributed. Basically, considerations of this sort had been underlying Adamson's endeavors. It is a tradition, initiated by Bauerhin, half-heartedly supported by Morrison and Ray, but rather definitely advocated by Manuel. 4. Finally, after 1859, the term natural when used to describe a classification system meant of common descent. A natural classification after Darwin is one in which all taxa consist of the descendants of a common ancestor. Macrotaxonomy, the science of classifying. A listing of these various meanings of the term natural does not describe exhaustively the conceptual foundations of the classifications proposed during this period, however. The search for a harmony or plan in nature was influenced by some other concepts which we have already, in part, encountered in other contexts. 3 concepts, in particular, were popular in successive periods. Scala naturae. For centuries the scale of perfection seemed to be the only conceivable scheme to bring order into diversity. 2-1 Blumenbach, 1782, 8-9, was one of many authors who saw in the Scala naturae the sound basis of a natural system which would permit man to order the natural bodies according to their greatest and most manifold affinity, to bring together the similar ones, and to remove from each other the dissimilar ones. Lamarck, particularly in his earlier writings, expressed similar sentiments. Among botanists the idea of the Scala naturae was less popular, since little of a trend toward perfection was discernible among plants, except for the advance from the algae and other cryptogams to the phanerogams. As a result Linnaeus preferred to compare a classification to a map, where each country touches several others. The claim that there is a continuous sequence from the least perfect atom of matter up to the most perfect organism, man, was challenged increasingly often as more was learned about diversity. Lamarck no longer defended any continuity between inorganic and organic, even though he postulated frequent spontaneous generation. The so-called zoophytes, corals, polyps, and so on, were scrutinized with particular care. Were they truly intermediate between plants and animals, and, if not, were they plants or animals? It produced great excitement and no little consternation when Tremblay II discovered in 1740 that the green hydra, Chlorohydra viridissima, was definitely an animal and yet it had chlorophyll and amazing powers of regeneration, a capacity one had hitherto thought was typically restricted to plants. Soon Tremblay demonstrated that corals and bryozoans were also animals, rather than intermediates between plants and animals. The great deal of branching which Lamarck admitted in different lines of animalian affinity was also quite incompatible with a single scale of perfection. It received its final death blow when Cuvier, 1812, asserted emphatically that there are 4 distinct phyla of animals, no more. 201. And no fewer, and that there was absolutely no connection among them. It was still sometimes possible, after Cuvier, to recognize affinity among the members of smaller groupings, but the ordering principle of growing perfection was no longer applicable. Furthermore, it became ever less convincing to postulate connections between dissimilar groups. The unity of the organic world, at one time symbolized by the Scala naturae, seemed to disintegrate the more, the better one knew the world of life. When it was realized that a one-dimensional line or guiding principle was in 202 adequate, the search began for multidimensional schemes. Affinity and analogy. The placing of a group of organisms in the scale of perfection was determined by its affinity to less perfect or more perfect neighbors. A modern biologist has a good deal of difficulty in visualizing what affinity meant in pre-evolutionary discussions. Perhaps it simply meant similarity. Yet, there was a conviction that this similarity reflected some kind of causal relationship, such as represented in the Scala Naturae or as seen by Louis Agassiz in the Blueprint of Creation. Some of the difficulties of the Scala Naturae seem to be due to existence of two kinds of similarity, true affinity, and another one which was designated by Schelling, Oken, and their followers as analogy. Penguins are related to the ducks or auks by true affinity, but to the aquatic mammals, such as whales, by analogy. Hawks show affinity to parrots and pigeons, but are analogous to the carnivores among the mammals. As bizarre as some of the thinking of the Nährphilosophien was, their partitioning of relationship into affinity and analogy proved to be of great importance in the ensuing history of biology. It was on this basis that Richard Owen developed his concepts of homology and analogy, which henceforth dominated comparative anatomy, particularly after the terms had received an evolutionary redefinition. But prior to the proposal of evolution, how could one convert this idea of affinity and analogy into a system? Here the Nährphilosophien borrowed their thoughts from the Pythagoreans. How can law and harmony in nature be better expressed than in numbers? The entomologist W. S. Maclay, 1819, chose the number 5, and although others subsequently experimented with 3 and 4, 5 remained the most popular number, referred to as the quinarian system. 23 Maclay thought that all taxa were arranged on circles, 5 per circle, and that adjacent circles were touching each other. Macrotaxonomy, the science of classifying. Osculating taxa on the same circle showed affinity, relationship to other circles illustrated analogy. One of the tasks of the taxonomist, thus, was to search for such cross-connections. Even though these often quite bizarre schemes were scathingly criticized by the more sober naturalists, one can sympathize with the adherents of quinarianism. They looked for laws that would account for the diversity of nature, and numerical schemes seemed the best available, prior to evolutionism. Even T.H. Huxley was, for a while, enamored with quinarianism and made numerous attempts to arrange the higher taxa of invertebrates in corresponding circles or parallel rows. Windsor, 1976b. Quinarianism was so popular in England in the 1840s and 1850s that even Darwin gave it some thought. For, if organisms were truly arranged in multiples of 5, then this would indicate that they had been designed by a superior author and, thus, diversification by natural selection would be refuted. However, even a superficial study showed to Darwin that the facts of taxonomic diversity were incompatible with any of the numerological schemes. In particular, his barnacle research provided no evidence for quinarianism. Even most of those who rejected quinarianism could not help recognizing that there were several kinds of similarity. Affinity and analogy were always acknowledged, but mere incidental resemblance and other kinds of similarity were sometimes also recognized. Affinity was the most puzzling of these similarities, but there was broad agreement that it was the direct result of those laws of organic life which the Creator has enacted for his own guidance in the act of creation. Strickland, 1846, 356. This is why affinity became for Agassiz one of the most powerful proofs for the existence of the Creator. Pragmatism and hierarchism. The failure of the Scala Naturae, of the grand schemes of the Nährphilosophien, and of the Pythagorean endeavors of the numerologists had a rather sobering effect on taxonomy. In the 50 years before the origin, most taxonomists shunned theorizing altogether and, when adopting the principles of upward classification, they were satisfied with the simple pragmatic activity of grouping seemingly similar species and genera together. There was little conceptual advance in this period. Cuvier, even in his last publication, merely restated the principles he had enunciated 20 years earlier. The situation in botany was no better. A. P. de Candoll's theory element air, 1813, opposing 203. 204. Claims notwithstanding, still adheres to the classical essentialist a priori methods. 24. Yet, virtually unnoticed by the practitioners themselves, the use of single key characters for the establishment of higher taxa was being replaced by the grouping of species, or other lower taxa, into higher taxa on the basis of character combinations. Upward classification was becoming a matter of course. To begin at the bottom greatly stimulated the development of specialists, Lindroth, 1973. The result of the new approach was the discovery that many previously recognized taxa were highly heterogeneous. For instance, Meckel, 1821, and Lückert, 1848, were able to show that Cuvier's radiata, distinguished on the basis of the key character radial versus bilateral symmetry, was an unnatural assemblage of two highly distinct phyla, the echinoderms and the coelenterates. At every level, from the phylum down to the genus, previously recognized higher taxa were re-examined and separated into more homogeneous components if found to be unnatural aggregates. By 1859 a large part of the animal taxa had been redefined and restricted to groups of species that largely agreed in their structural and biological characteristics. The enthusiasm for this theory-free purely pragmatic approach was somewhat dampened when certain phenomena were discovered which undermined too great a trust in phonetic resemblance. Of course, it had long been known that caterpillar and butterfly are the same animal, but with the increased interest in classifying one could no longer avoid asking whether a classification based on caterpillars would be the same as that based on the butterflies into which they metamorphosed. In the first half of the 19th century it was discovered that such a metamorphosis occurs in many invertebrate groups, indeed it is normal for most groups of sessile marine groups. From the beginning of any zoological system the barnacles had been classified among the mollusca or their subdivision, the Testacea. It created a sensation when John von Thomson observed on May 8, 1826, a crustacean larva attached to the bottom of a glass vessel change into a young barnacle, Windsor, 1969. Further studies left no doubt that the barnacles were sessile crustaceans. Thomson and other students of marine life found, furthermore, that many plankton organisms are nothing but the larval stages of well-known invertebrates, and that even the free-living crustaceans may metamorphose through several larval stages, Nauplius, Zoea, Cyprus. Macrotaxonomy, the science of classifying. The comforting idea of types that could be arranged either according to the primacy of function, Cuvier, or by the determination of a discrete Boplan, von Baer and the Natur-Philosophien, was thrown into even more complete disarray by two further discoveries made in the first half of the 19th century. One consisted in the complicated life cycles of cestodes, trematodes, and other internal parasites. The stages in the alternation of generations, for example, Cysticercus and tapeworm, and Cercaria and fluke are so utterly different although produced by the same genotypes as to cast a great deal of doubt on the validity of a purely phonetic approach to classification. Even more startling was the discovery of a regular alternation of generations in salps, tunicates, by Adalbert von Chamisso, 1819, and in coelenterates by Michael Sars, 1838–1846, and J. J. Steenstrup, 1842. The free-swimming and the sessile generations of a single species are so different that up to this discovery they had been placed into entirely different taxa, Windsor, 1976 b, Churchill, 1979. The problem was not unknown to the botanist where, among various groups of cryptogams, the gametophyte and the sporophyte are usually entirely different. Fortunately, these somewhat unsettling discoveries did not lead to another bout of metaphysical speculations but simply inspired the taxonomists to redouble their efforts to bring together natural groups of related organisms. These efforts, almost automatically, resulted in a classification of subordinated categories, nowadays usually referred to as the Linnaean hierarchy. What is the meaning of the term hierarchy in taxonomic theory? Hierarchical classifications. Most classifications, whether of inanimate objects or of organisms, are hierarchical. There are higher and lower categories, there are higher and lower ranks. What is usually overlooked is that the use of the term hierarchy is ambiguous, and that two fundamentally different kinds of arrangements have been designated as hierarchical. A hierarchy can be either exclusive or inclusive. Military ranks from private, corporal, sergeant, lieutenant, captain, up to general are a typical example of an exclusive hierarchy. A lower rank is not a subdivision of a higher rank, thus, lieutenants are not a subdivision of captains. The scala naturae, which so strongly dominated thinking from the 16th to the 18th. 205. 206. Century, is another good illustration of an exclusive hierarchy. Each level of perfection was considered an advance, or degradation, from the next lower, or higher, level in the hierarchy, but did not include it. The hierarchy of functions, as defended from Cézanne to Cuvier, is another example of an exclusive hierarchy. That growth has the highest rank and reproduction the next highest in this hierarchy does not mean that reproduction is a subdivision of growth, such as genera are subdivisions of families. The modern hierarchy of taxonomic categories is a typical example of an inclusive hierarchy. To illustrate this with a concrete example, dog-like species, such as wolf, coyote, and jackal, are grouped in the genus Canis, dogs. The various dog-like and fox-like genera are combined in the family Canidae. These, together with the cats, bears, weasels, and other related families, are combined in the order Carnivora. Class, subphylum, phylum, and kingdom are successive higher ranks in this hierarchy. Each higher taxon contains the taxa of the lower, subordinate, ranks. In theory, inclusive classificatory hierarchies can be produced both by logical division and by compositional classification. However, historically, logical division never led to a well-defined taxonomic hierarchy, because each level was treated separately, since each species, as defined in divisional logic, became a genus at the next lower hierarchical level. And even when both Tournefort and Linnaeus stabilized the genus to a large extent, they recognized only two higher categories and showed little interest in them, see above. Linnaeus was the first author who used the higher categories rationally and, on the whole, consistently. Nevertheless, his thinking was still too much dominated by the principle of logical division to permit him to propose a fully consistent, inclusive hierarchy of all organisms. This development did not truly take place until the 2 decades between 1795 to 1815, Windsor, 1976b, 2-3. The remarkable group of taxonomists at the Paris Muséum d'Histoire Naturelle was largely responsible for this conceptual change. However, different authors adopted the new way of thinking to different degrees. For instance, Lamarck's arrangement of the higher taxa, masses, still represented a strictly exclusive hierarchy even though there were compositional, hence inclusive, elements at the level of the lower categories. Cuvier's four phyla, embranchements, had no hierarchical connection, or if so, a strictly exclusive one. However, within these phyla, at the level of macrotaxonomy, the science of classifying the lower categories, some inclusive hierarchical tendencies can be observed. The method of constructing inclusive hierarchies by a compositional procedure is important for a number of reasons. Obviously, a theory of common descent, such as Darwin proposed in 1859, would not occur to anyone except for the existence of the inclusive hierarchy of taxonomic categories. Of more immediate concern is that the new approach raises both practical and conceptual questions concerning the principles on which the construction of an inclusive hierarchy should be based. This was a particularly burning problem, because the thinking of most taxonomists was still influenced if not dominated by an adherence to the scala naturae, an exclusive hierarchy. The reality of the higher categories and taxa. As far back as the 17th century, and with more or less vigor ever since, there has been an argument as to the reality of the higher categories. Essentialists like Linnaeus insisted dogmatically that at least the genus, characterized by its essence, was a real phenomenon. Taxonomists with nominalist leanings, led by Buffon, 1749, insisted with equal force that only individuals exist and that at least the higher categories, like genus, family, and class, are only arbitrary conventions of the human mind. The fact that no two botanists of the 17th century arrived at the same classification certainly seemed to support the nominalist argument. By making a distinction between the abstract ideal and the concrete real, Buffon laid the foundation for a solution, but the controversy continued for another 200 years. The reason why it lasted so long was primarily a terminological confusion. The term category was used in two entirely different senses. It was not until a new term, the word taxon, had been introduced for one of the two former meanings of the word category that this confusion was eliminated. 25. A taxon is a group of organisms of any taxonomic rank that is sufficiently distinct to be worthy of being named and assigned to a definite category. In terms of logic, a taxon is an individual, and the individual animals or plants of which the taxon is composed are parts of the taxon. Gazellin, 1975, Hull, 1976. A category, in its restricted modern meaning, designates rank or level in a hierarchic classification. It is a class, the members of which are 207. All the taxa to which a given rank is assigned. The difference between taxon and category is best made clear by an example. Robins, thrushes, songbirds, passerine birds, birds, vertebrates, chordates, and animals are groups of real organisms. They are taxa. The rank which is given to the mentioned taxa in the hierarchical classification is indicated by the categories in which they are placed: species, family, suborder, order, class, subphylum, phylum, and kingdom. The question, are the higher categories real? Must thus be 208 dissolved into two separate questions. 1. Are most of the groups, taxa, which we rank in the higher categories well delimited? And, 2. Is it possible to give an objective, non-arbitrary, definition of such higher categories as genus, family, or order? The answer to the first question is clearly yes, but to the second one it is clearly no. Such taxa as the hummingbirds, anthropoid apes, or penguins are exceedingly natural or real, that is, well delimited, and yet the categorical rank given to them is subjective, at least for taxa above the species level. A taxon might be placed in the family category by one author, in a lower category, tribe, by a second author, and in a higher one, superfamily, by a third author. In other words, categorical rank is largely an arbitrary decision. Those who so heatedly argued about the reality or not of categories were simply talking about different things. This was clearly understood by some earlier authors, for instance, Plate, 1914, but the distinction continued to be ignored for lack of a terminological handle. 5. Grouping according to common ancestry. The empirical taxonomists had no causal explanation for the fact that one is able to group species according to relationship or affinity. When Strickland, 1840, defined affinity as the relation which subsists between two or more members of a natural group, or in other words, an agreement in essential characters, he left the key words, natural and essential, undefined. It was Darwin who filled the explanatory gap and showed why there are natural groups and why they share essential characters. It was he who provided the basic theory of biological classification. No one prior to him had stated so unequivocally that the members of a taxon are similar because they are descendants of a common ancestor. To be sure, the idea was not entirely new, and Buffon had played with the possibility that similar species, like horse and ass, or all cats, might have been derived from an ancestral species, and so had Erasmus Darwin and some of the German evolutionists. Linnaeus, in his later years, had suggested that the members of a higher taxon might be the products of hybridization. Yet, neither Buffon nor Linnaeus converted these speculations into either a theory of classification or of evolution. Nor did it have any influence on hierarchical classification when Pallas in 1766 and Lamarck in 1809 and 1815 proposed tree-like diagrams of relationship. Simpson, 1961, 52. That Darwin was the founder of the whole field of evolutionary taxonomy is realized by only few. As Simpson has rightly said, evolutionary taxonomy stems explicitly and almost exclusively from Darwin. By this is meant not only that the theory of common descent accounts automatically for most of the degrees of similarity among organisms, as indeed it does, but also that Darwin developed a well thought out theory with a detailed statement of methods and difficulties. 1. The entire 13th chapter of The Origin, pages 411 to 458 of the first ed., is devoted by him to the development of his theory of classification. It starts with the often quoted sentences, "From the first dawn of life, all organic beings." 209. 210. Are found to resemble each other in descending degrees, so that they can be classed in groups under groups. This classification is evidently not arbitrary like the grouping of the stars and constellations, p. 411. Darwin here implicitly rejects the frequently made claim that the classifications, which by 1859 had reached a considerable level of refinement and elaboration, were an arbitrary and artificial product of the taxonomist. He continues, naturalists try to arrange the species, genera, and families in each class on what is called the natural system. But what is meant by the system? Some authors look at it merely as a scheme for arranging together those living objects which are most alike, and for separating those which are most unlike. But many naturalists think that something more is meant by the natural system. They believe that it reveals the plan of the Creator, but unless it be specified whether in time or space, or what else is meant by the plan of the Creator, it seems to me that nothing is thus added to our knowledge. I believe that something more is included in our classification than mere resemblance, and that propinquity of descent, the only known cause of the similarity of organic beings, is the bond, hidden as it is by various degrees of modification, which is partially revealed to us by our classifications, p. 413, in The Origin, and in his correspondence. Darwin stresses again and again that all true classification is genealogical, p. 420, but genealogy by itself does not give classification. LLD, 2, 247. To be sure, Darwin believed that the arrangement of the groups within each class, in due subordination and relation to the other groups, must be strictly genealogical in order to be natural, but he also realized that this was not the whole story, but that the amount of difference in the several branches or groups, though allied in the same degree in blood to their common progenitor, may differ greatly, being due to the different degrees of modification which they have undergone, and this is expressed by the forms being ranked under different genera, families, sections, or orders. Origin, 420. This is a very important statement, because it focuses on the principal difference between two modern schools of taxonomy, the cladists and the evolutionary taxonomists, as will be discussed below. At this point Darwin refers back to his famous phylogenetic diagram, Origin, 116, in which each of three congeneric Silurian species, A, F, and I, has modern descendants of very different rank. The line derived from species F changed so little that it is still classified in the Silurian genus, while its two sister groups A, grouping according to common ancestry, and I now constitute different families or even orders, p. 125. In his classification of the Cirripedia, Darwin usually applied the principle of determining rank by degree of divergence rather than by proximity to the branching point. Gazellin and Jaffe, 1973, Mayr, 1974 c. Darwin had spent something like 8 years on the classification of the Cirripedia, barnacles, and this had given him great insight into classification, both theoretically and practically. Gazellin, 1969. This allowed him to draw up a set of recommendations to help the taxonomist in finding what resemblances will be most useful in order to determine propinquity of descent. In particular, he emphasized again and again the importance of weighting the taxonomic value, information content, of all characters. It might have been thought, and was in ancient times thought, that those parts of the structure which determine the habits of life, and the general place of being in the economy of nature, would be of very high importance in classification. Nothing can be more false. It may even be given as a general rule, that the less any part of the organization is concerned with special habits, the more important it becomes for classification. P. 414, see also P. 425. In particular, Darwin rejects the idea so widespread among 17th and 18th century botanists, and since Cuvier also among zoologists, that the more important a structure is for the survival and perpetuation of an organism, the more important it will also be for its classification. He quotes case after case, pages 415 to 416, refuting such an assumption, that the merely physiological importance of an organ does not determine its classificatory value is almost shown by the one fact, that in allied groups, in which the same organ has nearly the same physiological value, its classificatory value is widely different. P. 415. He illustrates this by the highly unequal value of the antennae as a taxonomic character in different families of insects. Darwin's advice does not constitute a denial of the importance of natural selection. What Darwin felt is rather that special adaptations may involve only a limited portion of the genetic endowment of a group and thus be less informative than the general habitus. Furthermore, special adaptations may be acquired independently in several unrelated evolutionary lines. In other words, they are subject to convergence. An awareness of these potential shortcomings of special adaptations may help to protect the tax. 211. Onomist from interpreting convergence as evidence for common descent. Other types of characters, sometimes seemingly very slight ones, are more informative. The importance for classification of trifling characters mainly depends on their being correlated with several other characters of more or less importance. The value indeed of an aggregate of characters is very evident in natural history. P. 417. Darwin, thus, was fully aware of the importance of the concordant variation of several characters. After discussing the particular properties of other characters such as embryology 212 cal, rudimentary, and distributional characters, Darwin reaches the following conclusion: all the foregoing rules and aids and difficulties in classification are explained, on the view that the natural system is founded on descent with modification, that the characters which naturalists consider as showing true affinity between any two or more species, are those which have been inherited from a common parent. And, insofar all true classification is genealogical, that community of descent is the hidden bond which naturalists have been unconsciously seeking. P. 420. In the evaluation of characters, Darwin proposes certain rules, some of which we have already mentioned. Like Ray, Lamarck, de Jussieu, Cuvier, de Candolle, and most classifiers of the preceding centuries, he emphasizes the high taxonomic weight of characters that are constant over large groups. Furthermore, he emphasizes the importance of correlated character complexes, provided they are not merely the result of a similar mode of life. He devotes quite a section to spurious similarities caused by convergent evolution, p. 427, and warns the taxonomist not to be misled by such analogical or adaptive resemblances, p. 427. Two theoretical discussions of evolutionary classification in the ensuing century have consisted in little more than footnotes to Darwin. None of Darwin's rules or principles has been refuted and none of any special consequence has since been added. Two of Darwin's recommendations are of particular importance. One is to separate similarities due to descent from spurious similarities due to convergence. For instance, a character like the chorda has high taxonomic weight because it is part of a complex character system which could have hardly originated twice independently. On the other hand, metamerism, segmentation, is not nearly as basic a character because there is a great deal of evidence that it has originated at least twice in the animal kingdom. It is highly grouping according to common ancestry. Unlikely that the metamerism of the vertebrates has any phylogenetic connection with that of the arthropods. Darwin's other recommendation is to weight characters. Such an evaluation is important because some characters have much greater information content than others. Phylogenetic weighting as practiced by Darwin is a process of a posteriori weighting. The weight of a character is given by its correlation with the most securely established, by various methods of testing, parts of classifications. Some taxonomists have found it difficult to distinguish it from a priori weighting, as practiced by Cézanne and Cuvier. However, this can be done by appropriate analysis, and ever since phylogenetic a posteriori weighting has been re-emphasized, Mayr, 1959a, Kane, 1959b, it has been found a useful method, Mayr, 1969, and is now merging with computerized weighting methods. The reason for the highly unequal information content of so-called taxonomic characters has not yet been determined unequivocally, but is believed to be due to the fact that some components of the phenotype are built far more tightly into the genotype than others. The more deep-seated genetically a character or character complex is, the more likely it will be useful in revealing relationship. The work of Schmalhausen, Waddington, and Lerner has shown that its architecture provides the genotype with such a stable integration that certain components of the phenotype may remain unchanged during phyletic divergence. The underlying canalizations and regulatory mechanisms seem occasionally to remain virtually untouched during evolution, and this accounts for the sometimes quite unexpected stability of seemingly trifling components of the phenotype. As far as the methodology of classification is concerned, the Darwinian revolution had only minor impact. It is evident that the real turning point in the history of taxonomy was the abandonment of essentialism and of downward classification, and this had been largely completed well before 1859. The decisive contribution which Darwin made to taxonomy was twofold. By his theory of common descent he provided an explanatory theory for the existence of the Linnaean hierarchy and for the homogeneity of taxa in a natural classification, and he restored, at least in principle, the concept of continuity among groups of organisms, which had been rejected by Cuvier and by the Naturphilosophien in their theory of archetypes. Let us look at some aspects of these contributions more closely. 213. The meaning of affinity. As we saw, the Quinnerians and various other zoologists and botanists between the 1820s and 1840s had clearly recognized that there were two kinds of similarity among organisms. The similarity of a whale and a terrestrial mammal are due to affinity, the similarity of a whale and a fish are due to analogy. The more perceptive of these students, such as Strickland and Owen, appreciated the fact that analogies were due to similarity of function, but they were quite at a loss to explain affinity, except by invoking 214 the plan of creation. Darwin solved this problem by simply stating that affinity is proximity of descent. This led to the postulate that all taxa should be composed of descendants from the nearest common ancestor, or to use Haeckel's terminology, that they should be monophyletic. In order to delimit such taxa, it was necessary to scrutinize carefully all similarities and differences in order to discriminate between characters due to common descent, the only ones useful for classification, and analogical, convergent, characters, like hooked bills in hawks and owls or webbed feet in aquatic birds, that were acquired independently owing to similarity of function. The restoration of continuity. The rejection of the scale of perfection by the comparative anatomists early in the 19th century had resulted in the recognition of as many unconnected units as there were archetypes, biplane. To be sure, there was still a search for what was higher or lower as reflected in the advice which Louis Agassiz gave to his students: any fact that you may bring to show that one order is higher than any other is true scientific research. Darwin's interpretation of the Linnaean hierarchy as being due to common descent not only restored the principle of continuity but represented a powerful research program. No one perceived this more clearly than Haeckel, whose ambition it was to connect all taxa of animals and plants on the basis of their descent, and to represent this in the form of phylogenetic trees, which have graced textbooks of systematics ever since. Haeckel was an artist and presented his phylogenies quite literally as picturesque trees. They were increasingly replaced by tree-like diagrams, so-called dendrograms, an early example of which can be found in The Origin, Voss, 1952. The relation between postulated phylogeny and classification has remained controversial from 1859 on to the present. As early as 1863, Th. Huxley rejected all phylogenetic considerations and, grouping according to common ancestry, demanded that all classifications be based upon purely structural considerations. Such classification acquires its highest importance as a statement of the empirical laws of the correlation of structures. Huxley here clearly differed from Darwin, whose principle it was that one cannot make observations without having a theory. The modern trend has been to apply Darwin's principle by asking about each taxon whether the characteristics of the included species indicate that the taxon is monophyletic, that is, by consistently making phylogenetic postulates and then testing whether they are supported by the taxonomic evidence. For Haeckel there was no doubt that classification had to be based on relationship, and that relationship was known as soon as phylogeny was understood. The principal task in classification thus was to develop methods that would reveal phylogeny. Among these methods, the one that excited Haeckel and his contemporaries the most was the theory of recapitulation, Gould, 1977. It stated, in its most classical form, that the ontogenetic stages recapitulate the adult stages of the ancestors, see Chapter 10. The theory is now known to be invalid, but it was nevertheless a most heuristic theory, having given rise to comparative embryology and having generated many spectacular discoveries. Its greatest triumph was Kowalewski's demonstration of a chorda in the larvae of the sea squirts, tunicates, thus proving that they are chordates and not mollusks, as had been thought previously. The fact that mammalian embryos have gill arches as their fish ancestors, discovered by H. Rathke, 1825, and many similar discoveries of comparative embryology showed that a modified theory of recapitulation is acceptable, which states that embryos frequently recapitulate embryonic stages of their ancestors. The heuristic value of comparative embryology had already been abundantly demonstrated between 1820 and 1859 by the discovery of the typically crustacean larvae of barnacles, Windsor, 1969, by the elucidation of the life cycle of some parasitic crustaceans, and finally by the demonstration that the brittle starfish Comatula is nothing but the head of the crinoid Pentacvenus. Indeed, Louis Agassiz' 1848-49 Lowell Lectures had as their theme the value of comparative embryology as supplementing comparative anatomy. Since 1836, Agassiz had had the idea that there is a threefold parallelism between fossil history, embryological development, and rank in classification, Windsor, 1976b, 108. The ultimate result of researches in comparative anatomy and embryology was that one unnatural class or phylum of animals, 215, after another was made natural by the removal of unrelated elements, such as the removal of barnacles and tunicates from the mollusks and, most importantly, the breaking up of Cuvier's phylum Radiata, Windsor, 1976b. This process of understanding the relationship of the major groups of invertebrates, which owed its original impetus to Cuvier and Lamarck, probably made as much, or more, progress in the 50 years before The Origin as in the 50 years afterwards. Careful morphological analysis contributed more to the recognition and delimitation of natural taxa than 216 phylogenetic theory. Yet, the endeavor to construct phylogenetic trees was the most active preoccupation of zoologists in the second half of the 19th century. 3. The classification of the major taxa of plants was perhaps even less affected by evolutionary theory than that of animals. Unconsciously, the principles of the Scala Naturae, a progression from simple, primitive, to complex, continued for a long time the guiding principle of botanists. The classification of the flowering plants, angiosperms, was handicapped in two different ways. First, it was based almost entirely on flower structure, and it is only in the last 30 or 40 years that wood anatomy and chemical constituents have been seriously added to the repertory of useful characters. The second handicap was a misconception as to what the most primitive flowers were. It was long assumed that the earliest angiosperms had been wind-pollinated and had no petals, and therefore among living families, those like Bitulaceae, Fagaceae, and related families, Amentiferae, that are wind-pollinated were considered to be most primitive. It is now realized that wind pollination and correlated floral reduction is secondary, and that an entirely different group of families, related to the Magnoliaceae and Ranunculaceae, Ranunculales, are most primitive. The connecting links between them and the seed ferns, the inferred ancestors of the angiosperms, have not yet been found in the fossil record. The treatment in the leading textbooks indicates not only the level of activity in this field in recent decades but also the remarkable progress that has been made in delimiting reasonably homogeneous, natural taxa. Perhaps nothing in the 19th century influenced the development of botany as profoundly as Hofmeister's researches on the life cycle and reproduction of the cryptogams and the homologies of their reproductive structures. This not only gave the first clear view of relationships within the cryptogams but it broke down the previously insurmountable barrier between cryptogams and grouping according to common ancestry. Flowering plants. Hofmeister's investigations clearly established that a more or less uniform plan of organization ran through the entire vegetable kingdom. His comparative studies of the cryptogams, 1851, laid a sound foundation for an establishment of a phylogeny of the cryptogams after 1859. Once the characteristics of the various groups had been clearly worked out, it was a relatively easy matter to order them with the help of the principle of common descent. Soon the main attention was directed toward the study of the variation in reproduction in various groups of cryptogams and to relationships within these groups. None of them needed clarification as much as the highly heterogeneous fungi. The great pioneer in these studies was Anton de Bary, 1831–1888, who summarized his numerous detailed analyses of the life cycle of various groups of fungi in 1866 and 1888, laying a sound foundation for the active work of his successors. The importance and uniqueness of the fungi is recognized by various recent investigators by separating them from the plants in a separate kingdom. The decline of macrotaxonomic research. After the 1880s there was a gradual but noticeable decline of interest in macrotaxonomy and in phylogenetic studies. This had numerous reasons, some internal to the field and some external. Most important perhaps was a feeling of disappointment over the difficulty of getting clear-cut results. Similarity is usually a reasonably accurate indicator of relationship where the classification of taxa below the rank of orders is involved. In the classification of the higher taxa, orders, classes, and phyla, similarity is no longer a reliable guide and disappointingly little progress was therefore made. It comes as rather a surprise to most non-taxonomists how uncertain our understanding of degrees of relationship among organisms still is today. For instance, it is still unknown for most orders of birds which other order is a given order's nearest relative. The same is true for many mammalian families and genera, for instance the Lagomorpha, Tubulidentata, Xenarthra, and Tupaea. Yet these uncertainties in the classification of higher vertebrates are very minor compared to those of the invertebrates, the lower plants, and most of all, the prokaryotes and viruses. When 217. One reads recent discussions on the classification of the lower invertebrates, one is struck by the fact that some of the same questions are still controversial that were argued about in the 1870s, 80s, and 90s. There are usually majority opinions, but the mere fact that unorthodox alternatives have vigorous proponents indicates the degree of still prevailing uncertainty. To provide a flavor of the kind of problems that are controversial, I might pose some questions. From what group of protozoans did the metazoans evolve? Do all metazoans have a single protozoan ancestor, or did 218 the sponges evolve separately? Are the mesozoans, the coelenterates, or the turbularians the most primitive metazoans above the sponges? Is the division of the higher invertebrates into protostomia and deuterostomia a natural one? To which of these two groups, if they are recognized, do the tentaculata, lophophoriates, belong? How sound is the archaeoelement theory? Many problems concerning the relationship of the taxa of arthropods are also still unsolved, and likewise the derivation of the arthropods from the annelids. Kirkwood, 1960, quite rightly has called attention to these uncertainties, of which of course no one is better aware than the specialists in the field. This being a history of ideas, it is impossible even to begin giving a history of the sequence of classifications for the various higher taxa of animals and plants that have been proposed in the last 200 years. Yet it is a fascinating story. For in each generation new hopes were raised by new principles, such as recapitulation, or newly discovered characters, but progress has been slow. The futile attempts to establish the relationship of the major phyla of animals induced at least one competent zoologist at the turn of the century to deny common descent. Fleischmann, 1901, called the theory a beautiful myth not substantiated by any factual foundation. Kirkwood, 50 years later, does not draw such an extreme conclusion, but he is almost equally pessimistic about ever achieving an understanding of the relationship of the higher animal taxa. Honesty compels us to admit that our ignorance concerning these relationships is still great, not to say overwhelming. This is a depressing state of affairs considering that more than 100 years have passed since the great post-origin period of phylogeny construction. The morphological and embryological clues are simply not sufficient for the task. A second reason for the post-Darwinian disenchantment with macrotaxonomy was conceptual confusion. When Haeckel and his followers insisted that only those classifications were natural that, grouping according to common ancestry, were based on the phylogeny of the groups concerned, his opponents objected by saying, "How do we know the phylogeny? Is it not true that phylogenies are deduced from the findings made during the establishment of classifications? Hence, how can we base classifications on phylogeny without getting involved in a hopelessly circular argument?" It is only in relatively recent years that the argument was resolved. Neither is phylogeny based on classification, nor classification based on phylogeny. Both are based on a study of natural groups found in nature, groups having character combinations one would expect in the descendants of a common ancestor. Both classification and phylogeny are based on the same comparison of organisms and their characteristics and on a careful evaluation of their similarities and differences. Mayr, 1969. Evolutionary taxonomists are now in agreement that biological classifications must be consistent with the inferred phylogeny. This conceptual clarification has opened the way for a renewed interest in the classification of higher taxa. The other causes for the decline of interest in macrotaxonomy after 1900 were external. Owing to the claim of the Mendelians that mutations make new species, most of the excitement in taxonomy shifted to microtaxonomy, the species problem, eventually culminating in the new systematics. With subspecies widely considered to be incipient species, many specialists, particularly students of birds, mammals, butterflies, and snails, devoted all of their attention to the description of new subspecies. Concentration on the species level also revealed an endless supply of still undescribed species, all of it contributing to a neglect of macrotaxonomy. Perhaps the most important factor in the decline of macrotaxonomy was growing competition from other branches of biology. With the exciting discoveries made in experimental biology, Entwicklungsmechanik, cytology, Mendelian genetics, physiology, biochemistry, most of the brightest young biologists moved into these areas. This resulted in a manpower shortage in taxonomy and in reduced institutional support for this branch of biology. Among 29 papers given at the Symposium Systematics of Today held at Uppsala in commemoration of the 250th anniversary of the birth of Linnaeus in 1957, Hedberg, 1958, only 4 dealt with problems of macrotaxonomy. This illustrates well the dominant interest in the species level, characteristic for most taxonomists in the first half of the 20th century. Nevertheless, a low-level interest in the classification of higher taxa continued. 219. 220. Throughout the period, and a number of significant papers dealing with the problems and concepts of classification were published, such as those of Mayr, 1927, Simpson, 1945, Wrench, 1947, and Huxley, 1958. By the 1960s the task of the new systematics in microtaxonomy was largely completed, at least as far as the development of concepts is concerned, and the time had come for a new preoccupation with macrotaxonomy. The need for a new methodology. The splendid start which Darwin had made in developing a theory and methodology of macrotaxonomy was largely ignored in the post-Darwinian period. The standards by which genera, families, and orders were recognized and combined into still higher taxa were highly uneven in different groups of organisms. In the more poorly known groups, single character classifications or, more correctly, identification schemes were still very much in vogue. Since different authors might choose different key characters, the same kind of controversies developed as had characterized botany in the 17th century. Taxonomists frequently proposed new classifications without adequate justification, except the claim that they were better. For Linnaeus the names of the higher taxa were meant to serve as aids to the memory, but this objective was completely lost sight of by those zoologists and botanists who split genera and families into ever smaller pieces. This went so far that in birds, for instance, certain authors in the 1920s and 30s recognized a separate genus for nearly every species. There were no standards in the application of the higher categories. One distinguished ornithologist placed the families of birds in 25 orders, another equally distinguished author placed them in 48 orders. To anyone looking at macrotaxonomy from the outside, let us say from applied sciences such as medicine, agriculture, or ecology, the situation in taxonomy looked rather chaotic, as, in fact, it was. However, the situation was not all black. There were at least some useful textbooks of the theory and practice of zoological systematics, Ferris, 1928, Ranch, 1934, Mayr, Lindsley, and Usinger, 1953. Scattered through the literature were occasionally incisive discussions of certain aspects of the theory of classification, for instance, by Mayr, 1942, 280-291, on the meaning of the genus, and, more importantly, by Simpson, 1945, on the theory of macrotaxonomy. Perhaps the outstanding constructive grouping according to common ancestry meant of the period was to give an ecological meaning to the higher taxa. It was recognized that higher taxa are composed of species which, in the aggregate, occupy a specific niche or adaptive zone. In other words, the primacy shifted from the morphological character by which a higher taxon is recognized, to its biological meaning in the household of nature. Nevertheless, as far as the average biologist was concerned, classification offered serious problems, to put it mildly. The new systematics, by largely concentrating on the species level, had provided no solution for the needs of macrotaxonomy. Help had to come from somewhere else. Independently, two drastically different solutions were proposed: numerical phonetics and cladistics. Both new methodologies were not proposed as reforms but rather as revolutionary replacements of existing procedures. Numerical phonetics. Part of almost any method of classification is the ordering of items into groups on the basis of similarity. However, the construction of biological classifications by the method of a posteriori weighting as exercised by empirical taxonomists from Adanson on, and theoretically justified by Darwin, requires considerable knowledge and experience. Quite legitimately, the question was therefore occasionally raised whether it should not be possible to develop a method by which even a totally inexperienced person, in fact even a non-biologist, could group species into natural genera and higher taxa. Indeed, the availability of an automatic and objective method would be advantageous even for the experienced taxonomist in cases where two or more authors disagree on the optimal classification. The essential element in such an approach would be the development of methods that permit one to quantize degrees of similarity and to convert a qualitative or subjective taxonomy into an objective, numerical taxonomy. The history of numerical taxonomy has not yet been written. Pioneering endeavors go back to the middle of the 19th century, although most of them deal with intraspecific variation, particularly geographic variation. Attempts to use numerical methods for the classification of species, genera, and still higher taxa are usually buried in the taxonomic literature and are known only to a few specialists. Some references to this literature can be found in Simpson, Rowe, and Lewontin's Quantitative Zoology, 1960. 221. One of the almost forgotten pioneers was the geneticist A. H. Sturtevant, 1939-1942. He took considerable precautions to escape bias and excluded from his calculations any characters known to be adaptation ally or developmentally related. In an analysis of 39 characters in Drosophila, he was able to order the 58 species into a number of groups of relatives and, more importantly, to arrive at several rather broader generalizations that have since been confirmed repeatedly. The first of these is that strictly phonetic methods are most reliable when applied to close relatives, but 10 to 222 give contradictory results when applied to distantly related forms. Furthermore, he was able to arrive at a definition of good characters by constructing a table showing the correlation between the different characters and discovering that those were the best which could serve as useful indicators of the probable nature of other characters, in other words, characters that were covariant with other characters. After the electronic computer had been invented, it occurred independently to three groups of taxonomists: C.D. Michener, and R.R. Sokol, 1957, in Kansas, P.H.A. Sneth, 1957, a bacteriologist in London, and A.J. Kane and G.A. Harrison, 1958, in Oxford, England, to propose computer methods for quantifying similarity and for the grouping of species and higher taxa with the help of such quantitative methods. The most important aspect of their proposals was to replace the integrating capacity of the human brain, which had achieved in classical taxonomy the grouping of taxa simply by inspection or by a tabulation of similarities, by the mechanical operations of the computer. This, they believed, would replace the arbitrary and subjective evaluation customary in the past with an objective and invariably repeatable method. At first all three groups agreed that all characters be given equal weight, but Kane and Harrison, 1960, soon recognized the different information content of different characters and therefore proposed phyletic weighting. Michener soon also distanced himself from his early proposal, but the two remaining pioneers, Sokol and Sneth, joined forces and presented their methodology and philosophy in 1963 in a classical treatise, Principles of Numerical Taxonomy. The label numerical taxonomy was misleading for, as Simpson and others have pointed out, numerical methods had been used in taxonomy for generations, and by the most diverging schools of taxonomy. It has therefore become customary to refer to the taxonomic methodology of Sokol and Sneth as numerical phonetics. Unfortunately, the new methods were promoted. Grouping according to common ancestry. By making sweeping claims that could not be subsequently substantiated. For instance, it was claimed that any two scientists, given the same set of characters but working entirely independently, would arrive at identical estimates of the resemblance of two organisms when using the new phonetic methods. The evident invalidity of these claims evoked considerable hostility among experienced traditional taxonomists. 5. A drastically revised second edition, 1973, of Sokol and Sneth includes many improvements. Other texts in numerical taxonomy are Jardine and Simpson, 1971, and Clifford and Stevenson, 1975. For a somewhat different approach, see also Throckmorton, 1968. As Darwin had already pointed out, different characters have different information content, and rather different classifications will result when different mixes of characters are chosen. Different parts of the body, different stages in the life cycle, and morphological versus biochemical characters all lead to different similarity estimates. In order to demonstrate their objectivity, the numerical phoneticists propose to reject species as the unit of classification and replace them by operational taxonomic units, OTUs, as if this were an improvement. Actually, this led them into the same practical difficulties which had caused the abandonment of the typological species concept. Either the phoneticists had to treat the different sexes, age classes, and morphs as different OTUs and then separate females and males and other strongly varying phenotypes into different taxa, or else they had to analyze biological variants, pheنا, very carefully and combine variants into OTUs which coincide with biological species. Such an evaluation of variation, although far more realistic, required precisely the kind of subjective judgments that were claimed to be excluded by the objective phonetic method. By far the most important difference between traditional taxonomists and numerical phoneticists consists in their attitude toward weighting. There are three and only three possible attitudes toward weighting. According to the first, all characters are equivalent, that is, they have the same importance in classification. Although the phoneticists have referred to this as a non-weighting method, it is of course a method of a priori weighting to give each character equal weight. This is as misleading as the a priori weighting methods of Aristotle, Cisalpino, and Cuvier. Whether or not a marine invertebrate has a chorda or not is of greater taxonomic value than 100 other characters. That some characters contain a great deal of information concerning rela. 225. Shinship while others are merely noise was pointed out already by Adamson more than 200 years ago, Fampi, 1763, I, Kluxi. The second option concerning weighting is that there exists a set of fixed criteria, for instance physiological importance, by which one can determine the relative taxonomic importance of different characters. This was the a priori method of Aristotle and Cuvier. The third option is a posteriori weighting, in which organisms are first ordered into seemingly natural groups, through a considered 224ation of numerous characters and character combinations, and then those characters are given the greatest weight which seem to be correlated with the most natural groups. This was Darwin's approach. He concluded, the importance for classification of trifling characters mainly depends on their being correlated with several other characters of more or less importance. Origin, 417. Throughout the history of taxonomy, virtually all experienced taxonomists have known and frequently emphasized how different the taxonomic value of different characters can be. A classification of anthropoid apes and hominoids based primarily on the structure of the cortex of the brain would be appreciably different from a classification based on the major physiological macromolecules, hemoglobin, and so forth. The younger generation of numerical taxonomists appreciates the striking differences in information content of various characters and is now concentrating on replacing intuition and subjective evaluation by objective methods of a posteriori weighting, through correlation analysis, for example. Phoneticists convert the totality of the similarity values of individual characters into a single phonetic distance or overall similarity value. But, as Simpson, 1964a, has said correctly, a single measure of similarity involves an enormous loss of information, mainly on the character direction and origin of differences. It is fundamentally unsound to quantify similarity in a comparison of entities as highly heterogeneous as the character complexes of different taxa. This is why phonetics has been called a typological method, and why Simpson concluded that phonetics has led to retrogression in taxonomic principle, a conscious revival of pre-evolutionary, 18th century, principles. One might ignore the conceptual weaknesses of the method if it was able to produce practical results. However, to compensate at least in part for mosaic evolution and for the noise introduced by characters without information content, phoneticists need to grouping according to common ancestry. Program very large numbers of characters, preferably more than 100. It is usually possible to find such large numbers of characters in groups as morphologically complex as the arthropods, insects, arachnids, and so on. But there is a serious scarcity of taxonomically useful characters in most other groups of organisms. This alone precludes the use of a method based on the unweighted analysis of characters. Furthermore, even in insects the method is very laborious, and the programming of 100 or more characters of a large number of taxa is exceedingly time-consuming. One of the pioneers of phonetics, C.D. Michener, for this reason went back to traditional methods when classifying a large collection of Australian bees, containing numerous new species. Now, some 25 years after the phonetic philosophy was first pronounced, it is possible to give a tentative verdict on the validity and usefulness of its methods. Clearly, the basic approach in all classification is phonetic, endeavoring to establish groups of similar entities. The success of this endeavor depends on the methods and principles by which the similarity is established. Numerical phonetics has clearly failed in this respect by its insistence on equal weighting and by its decision to ignore all phyletic information. However, the failure of the basic philosophy of numerical phonetics is no reason not to acknowledge the usefulness of many of the numerical and particularly multivariate methods developed and employed by the phoneticists. The methods pioneered by the numerical taxonomists are now widely used in many areas of science and in other fields where the sorting and classifying of data is important. To have advocated and introduced into taxonomy the use of such methods would seem to be the greatest contribution of numerical phonetics. Another one is the emphasis on the principle, traditionally endorsed by the best taxonomists, of using as many different characters and character systems as feasible and as yield new information. Phonetic methods are most useful in the grouping of species in large genera and in the classification of previously confused groups. On the other hand, I do not know of a single substantial contribution made by numerical phonetics to the classification of any mature groups, or to classification at the level of orders, classes, or phyla. The most promising future development of numerical phonetics is presumably the further development of weighting pro. 225. Cetures. These are either based on the correlated variation, covariation, of characters or on various empirical guidelines. The inferred descendants of a common ancestor are almost invariably recognizable by the joint possession of certain characters, and it is nothing but common sense to give greater weight to some characters than to others. Any approach to classification that does not make use of the weighting of characters is clearly inefficient. In the endeavor to be strictly objective, the phonetic schools refrain from taking any evidence from descent into consideration. 226. To do so is the chief characteristic of an opposing school of classification, cladistics. Cladistics. The proposal of the taxonomic school known by the name cladistics, was motivated by the same consideration as phonetics, to eliminate subjectivity and arbitrariness from classifying by developing a virtually automatic method. Its first comprehensive statement was published in 1950 by Willy Hennig in his Theorie der Phylogenetische Systematik. According to him, classifications ought to be based exclusively on genealogy, that is, on the branching pattern of phylogeny. Phylogeny, he asserts, consists of a sequence of dichotomies, each representing the splitting of a parental species into two sister, that is, daughter, species. The ancestral species is assumed to cease to exist at the time of the dichotomy. Sister groups must be given the same categorical rank, and the ancestral species, together with all of its descendants, must be included in a single holophyletic taxon. Hennig's work is written in rather difficult German, some sentences being virtually unintelligible. It nowhere refers to the writings of Huxley, Mayr, Rensch, Simpson, and other authors who had covered in part the same ground in the preceding decades. New terms and definitions are casually introduced, but there is no index that would guide one to the relevant pages. Not surprisingly, the volume was at first rather universally ignored, except by a few German authors. It did not become more widely known until in 1965 and 1966, when English versions of Hennig's methodology were published. By the 1970s a virtual Hennig cult had developed, even though some of his so-called followers have moved rather far from Henig's original principles. Grouping according to common ancestry. Although Henig had designated his method as phylogenetic systematics, it was based only on a single component in phytogeny, the branching of lineages. It was therefore renamed by other authors as cladistics, or cladism, under which name it is now generally known. The crucial aspect of cladistics is the careful analysis of all characters in the comparison of related taxa and in the partitioning of these characters into ancestral, plesiomorph, and uniquely derived, apomorph, characters. Branching points in the phytogeny are determined by the backwards tracing of uniquely derived characters, synapomorphies, because such apomorph characters are believed to be found only among the descendants of the ancestor in which the character first occurred. The method is said to permit the reconstruction of phytogeny without fossil evidence, and this claim has indeed been substantiated to some extent. Ever since Darwin, it has been the objective of the evolutionary taxonomist to recognize only monophyletic taxa, that is, taxa exclusively composed of descendants of a common ancestor. Groups presumed to be monophyletic are constantly tested against ever new characters to determine whether or not the postulate of monophily is substantiated. This method is non-circular, as was shown by Hull, 1967. The careful comparison of species and genera included in a higher taxon and the analysis of all similarities in order to determine whether they are truly homologous had indeed established by 1950 that the majority of the recognized taxa of animals, this was less true for plants, were monophyletic. However, Willi Henig was the first author to articulate explicitly the principle that branching points in the genealogy should be based exclusively on synapomorph characters. It is the joint possession of uniquely derived characters which proves the common ancestry of a given set of species, he said. Cladistic analysis. In principle, the method of cladistic analysis for the delimitation of monophyletic groups is a superb procedure. It spells out objective criteria for the establishment of the community of descent. It forces the careful analysis of all characters, and introduces a new principle of character weighting, that of joint possession of synapomorph characters. Groups sharing the same. 227. Synapomorphies are sister groups. However, a number of objections have been raised against cladistic analysis. The first is a problem of terminology. Henig introduced a considerable number of new technical terms, most of which were unnecessary, though plesiomorph and apomorph are still commonly in use. Also confusing was Henig's attempt to transfer well-established terms to entirely different concepts, for instance, to restrict the term phylogeny to the branching component of phylogeny, to define relationship strictly in terms of 228 proximity to the nearest branching point, and, worst of all, to shift the term monophyletic from its customary use as a designation of a taxon to the process of descent. From Haeckel to 1950, the sequence of operations had always been first to delimit a taxon on the basis of phonetic considerations and then to test whether it was monophyletic. The cladists simply combine all inferred descendants of a given species into a monophyletic taxon, even if they are as different as birds and crocodiles. A second problem is the difficulty of determining synapomorphy. The joint possession by two taxa of a derived character can have either of two causations. Either the character was derived from the nearest common ancestor, genuine or homologous synapomorphy, or it was acquired by convergence, non-homologous or pseudoapomorphy. The reliability of the determination of monophily of a group depends to a large extent on the care that is taken to discriminate between these two classes of similarities. The frequency of non-homologous apomorphies has been underestimated by many cladists. How often a given, even seemingly rather improbable, adaptation can be acquired independently is well illustrated by the evolution of eyes. Photoreceptors originated at least 40 times independently in the animal kingdom, and in another 20 cases it cannot be determined whether the eyes found in related taxa were patristic or convergent developments. Plauen and Mayr, 1977. This and many other cases, see Gingerich, 1979, illustrate how difficult it often is to partition synapomorphies into those that are homologous and those that are not. The independent loss of a character in separate lineages is a particularly frequent form of convergence. Another formidable difficulty in the determination of synapomorphies is the establishment of the direction of evolutionary change, that is, the determination which character state is ancestral and which is derived. For instance, the placement of a petalous grouping according to common ancestry. Genera and families of angiosperms depends on the decision whether the absence of flower petals is considered a primary, ancestral, or derived condition, or, to take a case from the animal kingdom, the tunicates can either be considered as primitive, and the acrania, amphioxus, and the vertebrates as being due to neoteny, reproduction by larvae, or else amphioxus can be considered as the ancestral condition and the tunicates, ascidians, as a specialized, secondarily sessile side branch. The systems of animals and plants are riddled with situations where the arrangement of higher taxa depends entirely on the reading of the direction in which evolution is believed to have occurred. Cases where the evolutionary direction was reversed are particularly troublesome, but far more common than is generally admitted. There are various methods, including a study of the fossil record, by which either one or the other polarity can be made probable, but the fact remains that an unequivocal determination of the ancestral condition is at present often impossible. The results of the cladistic analysis are recorded in a branching diagram designated as a cladogram. It consists of a series of dichotomies depicting the successive splits of the phyletic lines. Two assumptions in the construction of cladograms are strictly arbitrary. The first one is that every existing species is eliminated when a new species originates, and the second one is that every splitting event is a dichotomy. With the realization that most speciation events occur in small, isolated founder populations, it becomes obvious that such speciation is of no influence whatsoever on the genetics and morphology of the parent species, which may continue essentially unchanged for millions of years and may continue to bud off new daughter species at frequent intervals. Strict dichotomy is likewise an unrealistic assumption. A large taxon, having attained a grade-like stage, may produce simultaneously several specialized daughter lines, which although technically sister groups, may go their own separate ways, having no more in common than the derivation from the same parental taxon. In some recently constructed cladograms this is recognized, and certain dichotomies have been replaced by polytomies. Ashlock, 1981. For all these reasons Hull, 1979, has correctly stressed that the claim of many cladists that their method is completely objective and not arbitrary is not substantiated by the facts. This is important to remember in connection with the criticism by the cladists of the weaknesses of competing taxonomic methodologies. 229. Cladistic classification. The various difficulties of the cladistic analysis are also encountered by the traditional taxonomists and are not the major reason for their opposition to cladistics. Rather, it is the relation between cladistic analysis and cladistic classification. For a cladist his task is completed with the cladistic analysis. The reconstructed genealogy, represented in the branching diagram, cladogram, gives him the classification directly. The cladistic classification Re 230 fleets the branching pattern accurately and permits reading off the phylogeny of a group quite directly. If the only information one wants to retrieve from a classification is the sequence of branching points of the phylogeny, then a cladistic classification is the answer. If one wants more of the history of a group reflected in the classification, one will look for a method which does not completely disregard evolutionary divergence and autapomorph characters. 6. The cladist disagrees with Darwin's insight that genealogy by itself does not give classification. He delimits his taxa not by similarity but by the principle of holophily, that is, by uniting all the descendants of a common ancestor into a single taxon. This results in such incongruent combinations as a joint taxon for crocodiles and birds or for chimpanzee and man. Classifications are based entirely on synapomorphies, even in cases, like the evolution of birds from reptiles, where the autapomorph characters vastly outnumber the synapomorphes with their nearest reptilian relatives. In other words, the method ignores the fact that phylogeny has two components, the splitting of evolutionary lines and the subsequent evolutionary changes of the split lines. The reason why this latter component is so important for classification is that the evolutionary history of sister groups is often strikingly different. Among two related groups derived from the nearest common ancestor, one may hardly differ from the ancestral group, while the other one may have entered a new adaptive zone and have evolved there into a drastically novel type. Even though they are sister groups in the terminology of cladistics, taxonomists traditionally have ranked such groups at different categorical levels. Nothing illustrates better the difference between cladistics and traditional taxonomy than Henig's decree that sister groups must be assigned the same rank regardless of how greatly they differ in their divergence since their separation. For Henig, cladistics was phylogenetic classification and it grouping according to common ancestry was his endeavor, even though the methodology was unsuited for this objective, to represent phylogenetic evolution in his classifications. This interest is not shared by some of his followers, who either refrain from any reference to evolution and phylogeny or even deliberately deny that evolution should be reflected in a classification. For more extensive critiques of cladistic classification I must refer to the recent literature. 7. Let me attempt to do justice to the cladistic method in a few final words. The greatest virtue of cladistic analysis is that it is an effective method for testing the naturalness, that is, the monophily, of groups originally delimited by phonetic methods. Since similarity of species and genera may have various reasons, monophily can be confirmed only by a rigorous analysis of the homology of the characters on which the similarity is based. In order to appreciate how fundamental the impact of Henig's methodology has been, one needs only to look at recent taxonomic revisions, particularly those relating to fishes and certain groups of insects. Even many authors, like Michener, who reject the claim that the cladogram can be translated directly into a classification, carefully attempt to use the principle of synapomorphy in the delimitation of taxa. The cladistic analysis has been particularly successful where numerous characters are available and where the existing classifications have been rather immature. The new cladograms it has produced have shown that many previously accepted taxa were polyphyletic. The translation of the detailed analysis into a strictly corresponding classification, as for instance by Rosen, 1973, for the higher teleosteans, leads, however, to a proliferation of new usages of previously existing taxa names and to the coining of many new names, and, even more disturbingly, to the introduction of many new categorical levels. The objection that such a procedure is clearly incompatible with the ideal of a convenient classification is rejected by Bond, 1974, 567, as not being a valid argument against Henig's theory. It certainly is not against cladistic analysis, but very much so against cladistic classification. Perhaps the most important contribution of Henig's method is that it has helped to clarify the relation between phylogeny and classification. Simpson, Mayr, and other taxonomists had equivocated when discussing the relationship between phylogeny and classification. Angiosperm taxonomists, discouraged by the difficulties of reconstructing the phylogeny of the flowering plants, disagreed with the conclusions of the zoologists that taxa should 231 be consistent with the findings of phylogeny and that the higher taxa must be monophyletic units. Mayr, 1942, 277 to 280. Davis and Haywood write in their textbook, Classification, taxonomists claim, should be based on, or reflect, phylogeny. This aim, we believe, is unrealistic in a group with an extremely inadequate fossil record. Indeed, the whole conception of phylogenetic classification is, we believe, a mistake. 1963, 18. What these authors overlooked is that the fossil record is equally inadequate for most groups of animals and that phylogeny must be inferred in 232 all these groups. It is Henig's great merit to have articulated a methodology that permits such inferences and permits their repeated testing. Thus, the absence of fossils does not preclude the establishment of phylogenies. So far as I know, the entire accepted phylogeny of the orders of mammals had originally been based on comparative anatomical research, via homology, and in no case was the previously established phylogeny refuted by later fossil finds. The seemingly eternal argument whether classification should express phylogeny, or should be based on phylogeny, or should be consistent with phylogeny, or should have nothing whatsoever to do with phylogeny is now beginning to become clarified. It is evident that in both classification and phylogeny one proceeds according to the hypothetico-deductive method. This means that one must test a series of propositions: 1. That the members of each taxon are each other's nearest relatives, that is, most similar to each other; 2. That all members of a taxon are descendants of the nearest common ancestor, monophyly sensu stricto; 3. That the Linnaean hierarchy of taxa is consistent with the inferred phylogeny. There are numerous ways of testing each of these propositions, all of them ultimately going back to an analysis of homology. In the study of homology it is most important to distinguish between definition and the evidence available and used to determine whether the definition can be taken as applicable. Simpson, 1975, 17, also 1961, 68-70. After 1859 there has been only one definition of homologous that makes biological sense: a feature, character, structure, and so on is homologous in two or more taxa if it can be traced back to derived from the same a corresponding feature in the presumptive common ancestor of these taxa. Numerous authors have contributed to the assembling of criteria, helping us to decide whether or not the definition is met in grouping according to common ancestry. A particular case. As far as morphological characters are concerned, the best such enumeration of criteria is that of Remine, 1952. Some of his criteria, for example, position in relation to other structures, are not applicable to behavioral or biochemical homologies. In fact, it may be necessary to develop a different set of criteria as evidence for homology for each type of characters. It was therefore unfortunate, and quite inappropriate, that Remini raised the criteria that served as evidence for homology to the definition for homology. 233. The traditional or evolutionary methodology. Both phonetics and cladistics have recruited numerous followers. Nevertheless, the majority of taxonomists, even though adopting one or the other methodological advance from the two new schools, have retained the traditional methodology of classifying. It consists in attempting to represent in the classification not only the branching of phyletic lines but also their subsequent divergence. This can be done by indicating in the ranking of the various taxa whether or not they have become drastically different from their sister groups owing to invasion of a new niche or adaptive zone. This results in the conversion of the cladogram into a phylogram. Mayr, 1969. This school is sometimes referred to as evolutionary taxonomy, because in its philosophy it follows Darwin almost to the letter. It is also sometimes referred to as eclectic taxonomy, because in its methodology it makes use of newly developed methods such as certain numerical methods of phonetics and the ancestral derived partitioning of characters of cladistics. The methods and principles of evolutionary taxonomy are well described in the textbooks of Simpson, 1961, and Mayr, 1969, as well as in a number of essays by Bach, Gazellin, Michener, and Ashlock. 8. The main difference between this method and cladistics is in the considerable weight given to autapomorph characters. These are derived characters acquired by one sister group but not by the other. Since the number of characters which birds have acquired since branching off from the Archosaurian branch is many times as large as the number of characters which distinguish Archosaurians from the other reptiles, birds are recognized as a separate class of vertebrates rather than combined with the crocodilians, only surviving Archosaurians, into the same class or order. Like 234. Wise, fleas are recognized as a separate order or suborder of insects, even though they are clearly derived from one particular subdivision of the dipterans. Lice, anopleurans, are recognized as a separate higher taxon even though clearly derived from one group of malophagans, which in turn are derived from one group of Psychopterans. In these cases, and all others where one sideline, X group, has acquired numerous autapomorphies by becoming drastically modified through special adaptations, a purely cladistic treatment leads to a misleading picture of relationships, as this term is traditionally understood. Kim and Ludwig, 1978. The ranking of a taxon in the evolutionary method, thus, is based on the relative weight of the autapomorphies as compared to the synapomorphies of the sister groups. As Ranch, Huxley, and others have emphasized, the anagenetic component of evolution often leads to the development of definite grades, or levels of evolutionary change, which must receive recognition in classification. The objection raised by the cladists that this would introduce subjectivity into classification has been rejected by the evolutionary taxonomist with two arguments. The first is that the cladistic method likewise is replete with subjectivity owing to decision-making as to the polarity of evolutionary change, owing to mosaic evolution, and owing to decisions concerning evolutionary parallelism. Hull, 1979. The second counterargument is that in most cases it is not too difficult to calculate an approximate ratio between autapomorphies and synapomorphies of two sister groups. Whenever a clade, a phyletic lineage, has entered a new adaptive zone, resulting in a drastic reorganization, the transformation may have to be given greater taxonomic weight than the proximity of joint ancestry. The particular importance of the autapomorphies is that they reflect the occupation of new niches and new adaptive zones, which often are of far greater biological significance than the cladistic synapomorphies. The concept and term grade have a long history. Ray Lancaster, 1909, spoke of protozoa and metazoa as successive grades, and, after separating the sponges as parazoa, he divided the remaining metazoa into two grades, Enterocilla, Coelenterata, and Coelomata. Bather, 1927, made extensive use of the grade concept, and attempted to illustrate how certain phyletic lines passed through several grades in successive geological periods. More recently, Huxley, 1958, showed how useful the grade concept is in illustrating evolutionary developments and serving as grouping according to common ancestry. The basis for the ranking of taxa. Wrench and Simpson have also called attention to the existence of such evolutionary plateaus on which a good deal of speciation, cladogenesis, may occur without any significant ontogenesis. The cladist ignores the existence of grades because this approach condones the recognition of paraphyletic taxa. A monophyletic group is paraphyletic, in the terminology of the cladists, if it is not holophyletic, that is, if it does not include all of the descendants of the common ancestor. The class Reptilia, for instance, as traditionally recognized, is a paraphyletic group, because it does not include the aves and the mammalia, two groups that were separated as having reached a grade level differing from that of the remaining reptilia. The recognition of paraphyletic groups prevents the automatic translation of a classification into a branching pattern but is able to express degrees of divergence, something the cladogram cannot do. New taxonomic characters. The backbone of all three methods of classification, numerical phonetics, cladistics, and evolutionary taxonomy, is the analysis and evaluation of taxonomic characters. An insufficiency of informative characters is the usual reason why disagreements between competing classifications cannot be resolved. Not surprisingly, the most frequent complaint made by a taxonomist is that the group of animals or plants on which he is working does not supply sufficient characters to allow an unequivocal decision on relationship. Two phenomena in particular contribute to this difficulty. One is the well-known fact that the phenotype in certain groups of organisms is remarkably standardized, as in the hundreds of species of Rana or the thousands of species of Drosophila, and thus provides only few morphological clues to relationship. The other is that any deviation from this standard type usually affects only a single functional complex, correlated with some special ad hoc adaptation. A shift to a new source of food or the adoption of a new set of courtship signals may perhaps result in a noticeable morphological reconstruction that can be divided into a considerable number of individual characters. To count these as separate characters would, however, be quite misleading, since, phylogenetically speaking, they are merely replique. 235. Tions of a single functional shift. Darwin, already, warned against too much trust in ad hoc specializations. Origin, 414. A difficulty encountered by the taxonomist even more frequently consists in a conflict between the conclusions based on different structures. The study of the extremities, for instance, may indicate that taxon B is most clearly related to taxon A, while features of the intestinal tract suggest that taxon B is the nearest relative of taxon C. In such a case, an evaluation of additional features of the extremities or the intestinal tract rarely produces a 236 satisfying solution. One encounters numerous such cases in every higher taxon, and taxonomists have, therefore, in recent decades given much attention to the search for new taxonomic characters. Even though a careful morphological analysis continuously reveals new characters, non-morphological characters play an increasingly important role in the establishment of classifications. This includes components of behavior, life history, and annual cycle. Compare Aristotle's live-bearing versus egg-laying, physiology, ecology, for example, niche utilization, parasites, and any other conceivable attribute of an organism. Many of these characters are most useful in the discrimination of species, but some are indicative of the relationship of groups of species. Geographical distribution often provides unexpected clues, as already Darwin intimated. An aberrant Australian genus is far more likely to be related to an indigenous Australian family than to have its nearest relatives in Africa or South America. This principle of searching for the nearest relative in a geographically easily accessible area does not work in the case of some relics and groups with unusually great dispersal facilities, but it does work in remarkably many instances, as has been documented by Simpson for animals and by Thorne for plants. A combination of a cladistic and a biogeographical analysis, as Hennig and his followers have shown, is sometimes particularly revealing. What only a few decades ago was the most recent frontier of taxonomy, the study of biochemical characters, has now become one of its most active and most useful branches. 9. It began, shortly after 1900, with immunological studies, Nuttall, 1904. Immunological methods are still in use today, Leone, 1964, but a large battery of new methods has since been added. More specifically, what is studied is the distribution, variation, and evolution of molecules. Relatively small molecules, like alkaloids and saponins in plants, have often a rather restrictive taxonomic distribution and grouping according to common ancestry. Thus may be indicative of relationship. Hanager, 1962, Hawkes, 1968. In the case of larger molecules, one can study their evolution by various methods, particularly by the determination of changes in the amino acid sequence. Such differences can often be quantized and used to construct dendrograms of phonetic distance. The study of individual macromolecules, such as hemoglobin, lysozyme, or cytochrome C, are expensive in time and equipment, however, and depend, for broader use, on methods of automation. Biochemical methods are most useful where a morphological analysis has failed or at least has only been able to produce ambiguous results. The analysis of alleles of enzyme genes, isozymes, by the method of electrophoresis has been particularly productive. Ayala, 1976. Not only have numerous sibling species been revealed by this method, but the amount of difference between two species has been shown to be roughly correlated with the time at which the evolutionary lines leading to the two species separated. The electrophoresis analysis, if based on a sufficiently large number of gene loci, is therefore most valuable in providing an independent check on the results of morphological analysis. The method of DNA hybridization progresses directly to the genotype. In this method, the compatibilities of a large part of the genomes of two species are measured, and the degree of matching indicates quite directly the nearness of relationship in those cases in which certain technical difficulties have been overcome. Single molecular characters are, of course, as susceptible to convergence as are morphological characters. It is therefore as dangerous to construct molecular single-character classifications as it is to construct morphological single-character classifications. Molecular methods are needed desperately to discover the connecting points of the higher taxa, let us say the orders of birds or the phyla of invertebrates. Here morphological analysis has so far failed, because it has been impossible to find a sufficient number of clearly homologous characters and because the polarity of evolutionary trends is often uncertain. The results of the morphological and the molecular analysis are not always congruent, as a comparison of man and chimpanzee shows. Some authors have, therefore, suggested that it might be necessary to have two classifications, one based on morphological and one on molecular characters. Such a suggestion seems to be ill-advised for a number of reasons. Not only is there the probability that different molecular characters might require different molecular classifications, but the suggestion also implies that 257. We have several phylogenies, which clearly is wrong. Classifications are not classifications of separate characters but classifications of whole organisms. It will be the task of future synthesis to integrate the findings made on morphological, behavioral, and various kinds of molecular characters into a single optimal classification. The epistemology of classification. 238. Philosophers have traditionally shown a considerable interest in the principles of classification. Indeed, classification, though not the classification of organisms per se, was one of Aristotle's central concerns, see Chapter 4. The replacement of downward classification, logical division, by grouping, upward classification, in the post-Linnaean period was a major philosophical advance, and philosophers in the 19th century continued to be very much interested in classification, for instance Mill, Jevons, and the Thomists. Yet somehow philosophers failed to draw the necessary conclusions concerning biological classification which the Darwinian revolution had made possible. Almost unanimously they continued to support essentialism and various other concepts made obsolete by evolutionary thinking. For instance, they tended to confuse identification and classification, and referred to classification as a process involving individual specimens, while actually classification deals with populations, species, while individual organisms are merely assigned to species, that is, are identified. Even today some philosophers, Hempel, 1965, seem to think that classification consists in the dividing of large classes into subsets, downward classification, though in fact evolutionary classifications operate through the grouping of related taxa into higher taxa. By far the most serious deficiency in the approach of most philosophers has been the assumption that the classification of animals and plants is essentially similar in principle to the classification of inanimate objects. Gilmore, 1940, 465. The methodology of phonetics is based on the same assumption. Unfortunately, it is not valid. Artificial or arbitrary classifications are legitimate for objects that are classified strictly on the basis of some quality or characteristic, like books in a library. Definite constraints, however, exist for the classification of items about which explanatory theories exist. Mayr, 1981. This is true, for instance, grouping according to common ancestry. For causal classifications of diseases as well as for the classification of organisms that is based on the theory that the relationship of organisms is due to common descent. Indeed, it is impossible to arrive at meaningful classifications of items that are the product of a developmental history unless the historical processes responsible for their origin are duly taken into consideration. To classify kinds of stars, geological phenomena, components of human culture, or biological diversity on the basis of Gilmore's advice produces similarity classes which in most cases reflect the actual relatedness of the items only incompletely. As a consequence, ever since Darwin it has been agreed among evolutionary taxonomists that natural taxa must be monophyletic, in the classical usage of this word, that is, they must consist of descendants from a common ancestor. This theoretical basis of all biological classification is a powerful constraint and completely refutes the claim that theories of classification are equally applicable to inanimate objects and organisms. Members of the younger generation of philosophers, such as Beckner, Hull, are cognizant of these developments and are in the process of developing a philosophy of biological classification in collaboration with those biologists who have given most thought to the relation between evolutionary theory and classification, such as Simpson, Mayr, and Bach. 1.0. Facilitation of information retrieval. The conclusions on relationship at which the evolutionary taxonomist arrives represented by a phylogram, places equal weight on the exact positioning of branching points and on the degree of divergence, that is, the number of autapomorphies, of each phyletic lineage. It is this phylogram which is used by the evolutionists as the basis of their generalizations. A classification, however, has a second function, to serve as a key to the information stored in the system. In order for the classification to serve as a maximally useful information retrieval system, a number of aspects of a classification must be considered when translating the phylogram into a classification, aspects known under the terms rank, size of taxa, symmetry, and sequence. Some arbitrariness is involved in the determination of each of these aspects and they will therefore presumably be controversial forever. 239. Ranking. Rank in the Linnaean hierarchy is indicated by the category in which a given taxon is placed. Rank determination is one of the most difficult and arbitrary decision processes in classification. For the cladist, rank is automatically given by the nearest branching point of the phylogenetic tree, since sister taxa must have the same rank. The evolutionary taxonomist, by contrast, must decide what number and weight of autapomorphous characters justify a difference in rank between two sister groups. Such a decision B240 comes particularly difficult when the evidence from different kinds of characters is conflicting. A molecular taxonomist, for instance, might place Pan, chimpanzee, and Homo in the same family, owing to the similarity of their macromolecules, while Julian Huxley proposed to raise man to the rank of a separate kingdom, Psychozoa, owing to the unique characteristics of man with respect to his central nervous system and its capacities. There are no firm rules as to how to resolve such conflicts, except to say that one should look for overall balance in the system, and adopt a scale of ranking that will permit the most useful generalizations. Size. There is even more discordance among taxonomists concerning the optimal size of taxa. Some authors consider even relatively minor differences as justifying the recognition of new genera, families, and higher taxa. They are referred to as splitters in the taxonomic jargon. The majority of taxonomists prefer rather large, comprehensive taxa, as being better able to express relationship and reducing the burden on the memory. They are referred to as lumpers. The conflict between lumpers and splitters has been with us since the days of Linnaeus, who himself was a lumper. He was able to cope with organic diversity by using, in addition to the kingdom, only 4 levels in the hierarchy of categories: species, genus, order, and phylum. Today even relatively conservative taxonomists recognize 21 categorical ranks, Simpson, 1945. Where Linnaeus recognized only 312 genera for all animals, the modern zoologist knows more than 100,000, including 2,045 for birds alone. As a general rule, one can say that most taxonomic groups pass through a phase of rather intensive splitting when they are studied more actively, but that the splitting phase is reversed when the knowledge of the group reaches greater maturity. There is broad agreement that the function of a classification to serve as an index to an information retrieval system, grouping according to common ancestry, imposes constraints on the size of the taxa and the number of ranks in the hierarchy. The phoneticists are the only recent taxonomists who have made a serious effort to introduce some uniformity and non-arbitrariness into the ranking of taxa. By using various distance measures, either based on morphological characters, Sokol and Sneth, 1973, or on genetic distance, NEI, 1975, they have proposed absolute degrees of difference which qualify, or do not, a species group for generic separation. When the distance measure has a sufficiently broad basis, such as DNA matching or the isozymes of at least 30 or 40, preferably far more, gene loci, it may reflect rather well the amount of evolutionary divergence of the various species groups. There are indications that standards of generic recognition, based on degree of molecular difference, should be different in different higher taxa, if degrees of morphological divergence are in strong conflict with the molecular divergence. Morphologically exceedingly similar species of frogs and toads may display remarkable molecular divergence, while in groups like birds and mammals pronounced divergence in morphology and color pattern may not reflect any major molecular divergence. If a uniform molecular yardstick were adopted, many long recognized genera of warm-blooded vertebrates would have to be synonymized, while in the anurans and in the gastropods new genera would have to be introduced for morphologically very similar species groups. It is doubtful whether this would be desirable considering the primary function of classifications.